Hi everyone. So in this video we are going to start the marathon of combinational circuits, but before starting that marathon I want to add a few points. So we have covered first two marathon. So here we saw the basics, and in this one we saw number system and implicants, but here we already started the combination circuit. So 1 hour of content is already there in the previous video. So if you are someone who is looking only for combination circuit, then at least this 1 hour of content you should watch. From the previous video you watch this 1 hour of content, then you can proceed with this particular video. Okay then. So combination circuit has already been started. 1 hour has already been covered, and this is just some of my demands. Like I would be expecting this thing from you. By the end of this session, I would be expecting 10k subs and likes as 250. So let's start this marathon and start studying combinational circuits right from the scratch. And the quality you will get here is next to none. Okay, then let's start it. Hi everyone. So let's continue our discussion on combinational circuits. So in the previous video, I told you that we are going to study some standard circuits now, but before standard circuit, let's take one more video where we don't discuss any standard circuit but just some normal circuits. So here as well you do not need to mug up any final expression. So in this video, whatever that we are dealing, you do not mug up any final expression. Okay, so first one is code converter, then we will see 7-segment display, and then we will see parity generator and parity checker. So these three kind of circuits we are going to see, and you do not need to remember the final answer. Okay, so first, this is the first question. You can do it on your own. Design a 4-bit binary to gray code converter. You need to convert binary to gray. So basically you can, if you need to draw the block diagram, where I will draw the block diagram. So let's just say this is my combination circuit. My input is 4-bit binary and my output should be 4-bit binary. I will make in this manner only. My input is 4-bit binary. My output will be gray code. Certainly it will be 4-bit only, because in binary and gray code number of bits would be the same. So if this is my input 0 0 0 0, so with respect to that what is the gray code? 0 0 0 0 only. If this is my input, with respect to that what is the gray code? This is the gray code. For 2, what is the gray code? This is the gray code. How I have written gray code? 8 times 0, 8 times 1. 4 times 0, 4 times 1, 4 times 1, 4 times 0, 2 times 0, 2 times 1, 2 times 1, 2 times 0, 2 times 0, 2 times 1. So I hope you must have built the habit now. Okay. Now for each line, for each this G3, G2, G1 and G0, we just need to denote this G3, G2, G1 and G0 in terms of B3, B2, B1 and B0. So let's talk about G3. In G3 you can directly see that G3 is directly equals to B3. So I do not need to make any K-map. G3 is directly equals to B3, right? What about G2? What are the min terms of G2? Min terms of G2 are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 4, 5, 6, 7, 8, 9, 10, 11. So these are the min terms. So just put them in your what do we say it? K-map. 4, 5, 6, 7, 8, 9, 10, 11. Now what I need to do? I just need to minimize it, and directly I can see this is a quad and this is another quad. So these two are the quads. So this quad is B3 B2 bar plus B3 bar B2, that is equals to B3 XOR B2. So similarly, what did you get? G3 you get is B3 XOR B2. In the same manner, what you will get as G1, you can do it on your own. Try doing it on your own, because we have seen a lot of example. You can do it on your own and you will get it as B2 XOR B1. And what you will get as G0? G0 you will get as B1 XOR B0. You can see. Let's talk about G0. So that would be 0 XOR 0, 0 XOR 1, 1 XOR 0, 1 XOR 1, 0 XOR 0, 0 XOR 1, 1 XOR 0, 1 XOR 0, 1. Yeah. Now let's just say in the examination this question is coming and they are asking you to derive this expression. So will you derive it there, or you already know? You already know it, right? Because we know the conversion. If I am going from binary to gray, BG, if I am BG, I will never look down. So B3 goes as it is. I am never looking down. So this XOR this, B2 XOR B3. Then this XOR this, B1 XOR B2. And then this XOR this, B0 XOR B1. So this is your G3, this is your G2, this is your G1, and this is your G0. So I directly remember it. I am not going to derive it in the examination by making the K maps. If they are asking me the expression, then I will just directly write I am going from B to G. Okay, in that manner I will write that's it. Okay, so this is the final expression. Sorry, this is G2, this is G1. Right? Let's write gray to binary code converter. Gray to binary, GB. If you are ganda bacha, you will look down. So this is G3 will come as it is. Now in the next time what will happen? G3 XOR G2. Next what will happen? G3 XOR G2 XOR G1. And now next what will happen? Next what will happen is that G3 XOR G2 XOR G1 XOR G0. So I could have done it with the I could have done it with the truth table as well, but I am not doing it because I already know the answer. I remember the answer. So simply this will be your B3, this will be your B2, this will be your B1, and this will be your B0. So you can directly write B3 is equals to G3, B2 is equals to G3 XOR G2, B1 is equals to G3 G2 XOR G1, and B0 is equals to all XOR. So in that manner, no matter how many bits are given, I can always write binary to gray code converter and gray to binary code converter because I already know by the trick. If you are BG, that means you will never look down. If you are GB, if you are ganda bacha, that means you will always look down. So looking down, and this bit will always be equal. So G3 looking down, G2. Okay. Let's go to the next question. This is BCD to XS3 converter. So this is a bit interesting topic. So you need to convert BCD to XS3. You can write both of the codes. BCD code would be and 4-bit, only in 4-bit. Okay, 4-bit BCD to 4-bit XS3. We can take any number of bits, 8 bits, 12 bits, 16 bits, but we are taking 4 bits only. So 0 will be in XS3, it will be 3, 1 will be 4, 2 will be 5. Here this is 4, 7, 5, 8, 6, 9, and this is 6, 9, and 7, 10, 8, 11, and this is your 9, 12. What about this bit? 1, 0, 1, 0. Next is 10. If my input is 1, 0, 1, 0, what would be my output? Don't care. Say yes or no. Why don't care? Why it is don't care? Because 1, 0, 1, 0 is never occur. 1, 0, 1, 0 will never occur. At the input 1, 0, 1, 0 till 1, 1, 1, 1 will never occur. Why it will never occur? Because I told you these are unused bits in BCD. Unused bits in BCD. So these are unused bits. Are you getting this point? So all these are don't care. So if I write the expression of x3, then what is this min term? This is 5. So 5, 6, 7, 8, 9. Now all these are don't care. 10, 11, 12, 13, 14, 15. Because how can you write 14 in BCD? In BCD you will write 14 as this. And 4. 4 is 0, 1, 0. So you cannot write 14 in 4 bits. So these will go as don't care. So 14 cannot be written in BCD code using 4 bits only. It would require 8 bits. So it will not come in this part. So all these goes as don't care. So what do I see here? If I this octet I can see, then any octet? No. This quad and another quad. Okay. If I write here, this is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So in this quad, all these are changing. Only one thing is constant, that is B3 plus. This was about octet. In quad, what is constant? B3 bar into B0 plus. In this one, what is constant? B2 into B1. Here what is constant? B2 is constant into, in this one, B1 is constant. So this is the expression of x3. I used the don't care so that I could make a quad. If you hadn't tried these don't care, then it would be a problem for you, right? Because you would be making this pair there, and it would give more, it would give the expression with more literal count, but we need the minimized expression. Then we know that rest of the part will go to don't care. So that's why we are putting don't care here, and this is the expression of x3. Try deriving x2, x1 and x0 on your own. Okay, do it on your own. So I will only do for x2, then you can do for x0 is directly you can see x0 is b0 bar. X0 is b0 bar, you can directly see here. For x1 you can do it on your own. For x2 I will do it. So what all are the minterms for x2? For x2 what all are the minterms? 1, 2, 3, 4. 1, 2, 3, 4. 5, 6, 7, 8, 9. And plus don't cares are also there. Don't cares are there. 10, 11, 12, 13, 14, 15. Okay. So 1, 2, 3, 4, 9. 1, 2, 3, 4, 9. Don't get starting from 10. 10, 11, 12, 13, 14 and 15. Okay. This looks interesting now. Can we get anything out of it? Let's write 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So I guess this can be a pair only, but I can get two quads here. What all are those two quads? This quad I can see, right? I cannot make any octet. This quad I can see, and another quad I can see. There you go. Okay. So if I write the expression for this one, so here which all are constant? B1 bar, B0 bar, B2. B1 bar, B0 bar, B2. If I talk about this one, then B2 bar is constant and B0 is constant. B2 bar, B0. And what about this one? Here B1 is constant, and what about this row? So B1 is constant, and what about these? B1 is constant and B2 bar is constant. B1, B2 bar. So that's the expression we are getting for x2. Similarly, x3, x0 we can directly see. This you can do on your own. So on your own. Okay. Do the practice on your own. You will get this expression, right? Which is actually an XOR gate. So this will look very simple. Okay, then let's move to the next one. Now, like some people would be thinking, sir, that how they will ask these kind of question in the examination. This would take a lot of time. So they can ask the output expression of a particular bit. That what will be the output expression of x2. So in this way they can ask the question. The way I have expression, the way I have asked here. So a 4-bit binary code B2, B1, B0, B2, sorry, B3, B2, B1, B0 has been converted into BCD code. So BCD code is of 8 bits. Why is that so? Because in binary you can represent 10 in how many bits? In binary you can represent 10 in 4 bits only, like 1 0 1 0. But for BCD you would require 8 bits. That would be 0 0 0 1, and for 0 it would be 0 0 0 0. 11 you can easily denote, right? 8 to 11. But here you would require 2 bits. That would be 11. That this would also be 1. So this is 1 and this is 1. So that's the thing. That's why they have given 8 bits. So make the truth table on your own and tell me the expression of C2. Now let's see the solution. So in the examination, if I need to talk about only C2, so I will write down the truth table of C2 only. Like this is my 0, so 0 0 will be converted to 0. This is my 1. How 1 will be converted? Let's write one more. So 1 will be, these bits will be 0 only, and 1 will be, this is 1, because 1 can be written as 0 1. So this is 0 and this is 1. What about 2? So 2 will be written as this, rest all bits are 0. But I need to talk about C2 only, so I will think about C2 only. What about 3? In 3 as well C2 will be 0 because this will be 3. What about 4? In 4 this will be 1, rest all will be 0. These all also will be 0. What about 5? 1 0 1. What about 6? 1 1 0. What about 7? 1 1 1. What about 8? What about 8? So this would be 1 there and this would be 0. In 8 this would be 1, right? 8421 code it is, 8421. This also has the value of 8421. Okay, so this will be 8. What about 9? In 9 as well this will be 0. In 9 as well this will be 0. Let's write down in the same manner only. This is your 9. So in 9 as well this will be 0. What about 10? 10. 10 means this is 10. So 10 means this would be 1 and this would also be, this would be 0. What about 11? 11 means this would be 1 and this would be also 1. What about 12? So this would be 1 and this would be 2. In 2 what do you write? In this manner you write. So this is 1 and this is 2. Here 13, this is 1 and this would be 3. 14, this would be 1 and this would be 4. And what about 15? This would be 1 and this would be 5. So that's all are the minterms. So what are the minterms of C2? So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So these are the minterms of C2. 4 5, or in the examination, like I would think, okay, what would be 0 0 0? So I can directly write down the minterms, no, in the examination. I will not make this table. If I need to only think about C2, so in the examination what I would be doing, that I will write A3 A2. In the rough work I will write this thing first, C3 C2 C1 and C0. Then I would know that I need to think about this. So I will start from 0. If 0 0 0 is there, this will be 0. If 1 is there, this will also be 0. If 2 is there, this will also be 0. If 3 is there, this will also be 0. If 4 is there, this bit will be 1. So I will write 4. Then if 5 is there, this bit will be 1. If 6 is there, this bit will be 1. If 7 is there, this bit is 1. If 8 is there, this bit will be 0. 9 is there, this bit will be 0. 10 is there, this bit will again be 0. 11 is there, again 0. 12 is there, again 0. Then 13 is there, again 0. Then 14, 15, it would be there. So directly in the examination, I can write down this expression. In the mind only I can think. I do not need to make all these 0 0 0 0 and 0. I can directly write down my minterms. So these minterms, if I know, then I can directly make my K-map. So that's how you will be solving in the examination, and these kind of questions can be asked because people will spend a lot of time in making all these kind of things. But we need to think there intelligently. Okay. So 4, 5, 6, 7, 14, 15. 4, 5, 6, 7, 14, 15. Right? Yeah. So very easily we can see this is a quad here. I can use a different color. This is a quad here and this is a quad here. So 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. C2 is what? B3 bar B2 plus. What about this one? So here B1 is constant, right? And what is constant? B1. And what about this? Here B2 is constant. So that's the final expression. And this one B2 is constant, here B1 is constant. So B1, B2, and what about this? Here B3 bar B2 is constant. So that's the final expression of C2. So in that manner only they can ask the expression of C1 as well, C0 as well, C3 as well, anything they can ask in the examination. Okay, and I hope you would be comfortable. There will be nothing like don't cares, because they are giving 8 bits now. If they have given 4 bits, then there would be don't cares, but here they have given 8 bits, so now I can represent all the numbers in 8 bits. Okay, now let's study about 7 segment display. So code converters, you should be comfortable now, like very easy problems. Just whatever that is given, just convert that to the another code and write down the final expression. Okay, I hope code converters you are comfortable. Let's see 7 segment display, very easy topic. So you might have seen this display in calculator. You see this display. Let's just say you write down 7, not in scientific calculator, in a normal calculator that commerce guy uses. So if you write down 7, so how it will be written? In this manner, right? If you write down 1, if you click on 1, this will be written. If you click on 2, this is how it will be written. Oh, sorry. Actually, this will be 1 only. These will be 1. Okay. I mean, all this is how it will be written. This is how it will be written. If you write down 5, this is how it would be written. This would be 5. So why it is called 7 segment display? Because there are 7 segments. 1, 2, 3, 4, 5, 6 and 7. So there are 7 segments. So let's just see some examples. These are the examples only. Again, let's see it. How will 0 be written? 0 will be written in this manner. How will 1 be written? In this manner. How will 2 be written? 3 will be written in this manner. 4 in this manner. 5, right? You can make it on your own. 6, 7, 8, 9, right? So these all are the numbers. Now let's see the question on this, because like there is no concept, a simple problem, and only one question has been asked in GATE examination, so that you will solve on your own, or I can see that in assignment. Okay, because I do not want you to show, like there is only one question available. So this question I took from my side, and one question will be there from GATE PYQ, so that I will pick in the assignment. Okay, we will see that in assignments. That would be very easy. You can solve it on your own as well. So let's just see this problem. Design a circuit that detects the number that uses lower left segment in 7 segment display for a 4-bit BCD code input. So our input is BCD code. So always in combination circuit, always we need to see, first thing is what is our input. So input is our BCD code. So it can go from 0 to 9. This is our input BCD code, B3, or I have written ABCD. Okay, ABCD I have written. So I will write down by ABCD. ABCD. Now let's just say there is some random input. This is our combination circuit. Okay, and it will give a single bit output. That is our Y. Okay, yeah, Y. So let's just say my input is 0, 0, 0, 1. What is the decimal equivalent of that? 1. So what will happen? 1 can be written in this form. So is it using lower left segment? No, this is using D and E only. What is lower left segment? This is lower left segment. So lower left segment is C. So if you are making 1, is it using C? No. So the output will be 0. Now let's just say this is my input. This is my input. So what is the decimal equivalent of this? 3. If you are making 3, this is how you will make 3. So is it using your lower left? Again it is not using. Output will again be 0. If this is your input, then what is the decimal equivalent? 2. So are you using lower left one? Yes, then output will be 1. This is what you need to design. That's it. Input is a BCD code. You convert that to decimal. It will detect that number only which uses the lower left segment of the display. Okay. So what is my input? It could be 0, 0, 0, 0, right? If it is 0, 0, 0, 0, that means decimal equivalent is, you should do it on your own first. Decimal equivalent is 0. Is it using? No. If my input is 0, 0, 0, 1, oh sorry, it is using, it is using lower segment, it is using, so it would be 1. For if my input is 0, 0, 0, 1, that means this is the scene, not using. For 2 it will use, for 3 it will not use, for 4 it will also not use, For 5, you can think on your own, it will not use. For 6, yes, it will use. For 7, it will not use. For 8, it will use. For 9, it will not use. Now what about these? They don't care, right? Look, these are the possible combinations known, like ABCD can be 1010 as well. But what will BCD say? That these are don't care for me, right? Because these are unused bits. These are unused combinations. Here we write all the possible combination of ABCD, which are all these 16 combination. But these combination are unused for me. If these are unused for me, BCD will say these are unused for me, then I will give my output as don't care. Because I don't care, whatever the input is there, output will be don't care, right? So now let's check back again that if I have written it correct. 0 it will use, 2 it will not use, 3 sorry 0 1 2 it will use, 3 it will not use, 4 it will not use, 5 it will not use, 6 it will use, 7 not use, 8 use, 9 not used, and then all these are don't care. It's not that you will write 10. Now 4-bit input is there, so all these are don't care. 4-bit BCD. Okay, so what all are the minterms? Minterms are 0 1 2 3 4 5 6 7 7 wouldn't be there, 8 wouldn't be there, 9 will also not be there, right? And don't cares are 10 11 till 15. So in the examination directly I can write down these minterms, right? So first I will think 0 will not use, 1 will not use, 0 will use, 1 will not use, 2 will use, 3 will not use, 4 will not use, 5 will not use, 6 will use, so 6 I will return, 7 will not use, 8 will use, so 8 I will write, 9 will not use, so 9 I will not write, so 0 2 6 8. So directly I can write down the minterms, right? And rest all are the don't care. So 0 2 6 8 9 10 11 12 13 14 and 15. So what do I see here? All look, without using don't care I can see a quad here, 1 2 3 and 4, and then directly this. Look, in temptation what would be the first step? That let's make a octet, but that is of no use. I can directly pick this one. This one is already taken, so directly I can see. If I make this one, no, then what is the scene? What would be the scene? If I take this, then there would be three terms. If I, let's just say if I had taken this and then this quad and then this, I would have taken, because this one will not be used. So I have to use this one. So I would have to take 1, 2 and these 3, but this is not required at all. This is not required at all. So directly a 4 and then a quad, right? Basically this octet is redundant. There is no use of this. This octet is redundant. All these ones are being in the box. These are in the box only. So all the ones are in the box. So 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So you will get the expression C bar D bar plus B bar D bar. So that's the final answer. Okay, we can check here as well. Why I have written B3 B2 B1 A B C D. We always start from here, A B C D. So in this one what do you see? Only D bar is constant, so D bar into B bar, and in this one C D bar, so C D bar plus B bar into D bar. So that should be the final answer, and I hope you are able to do it on your own. So that's it about our this 7 segment display. One more problem will be there, which will be in the assignment, not in this particular class. Okay, let's see the next one. Parity generator and parity checker. So it is used in DigiCom. Okay, in digital communication we will again study about it. It is used in digital communication. Okay, we will certainly study about it again in digital communication. So what do? Look, at the receiver I sent this data line. The data line is 1011. If you remember what is data line, in our first lecture we have studied it. What is data line? So 1011 I have sent. At the receiver I should have expected 1011 only, but because of the addition of noise you are receiving 1111. So there is an error. There is certainly an error. So now what will parity bit do? Parity bit will only tell that there is an error. Where there is an error, that it will not tell that there is an error in this bit or in this bit. Parity bit will only tell that there is an error. So what parity defines? So parity simply defines the number of ones. Parity simply defines number of ones. You just need to remember this line. Parity simply defines number of ones. It has nothing to do with the number of zeros. A lot of time people get confused that it will tell something about number of zeros. It has nothing to do with the number of zeros. Parity is an extra bit with the transmitted signal that tells about the number of ones. Okay, so it will only tell about the number of ones. So what we will do actually in our circuit? So this is what we will do in our circuit actually, but let's see the two definition, then we will see what we will actually do, how do we transmit the data. So what do you mean by even parity? Even parity means it will make the number of ones equal to even. So if this is my data line, so what parity I will send? I want to make number of ones equals to even, so I will send 1 because I need number of ones to be even. So here there are odd number of ones, so parity bit would be 1. Here what would be the parity bit? I need total number of ones to be even, so parity bit would be 0. So already these are even, so parity would be 0. Odd parity, it will make the number of ones odd. It will make number of ones odd. Here there are even number of ones, so to make odd number of ones I will put one more 1 here, and here there are odd number of ones already, so parity bit will be 0. So what we will be doing? So this is a parity generator. Okay, this is a parity generator. Let's just say this is a even parity generator, and first we will see here, let's just say this is my input, this is my input, and this is even parity generator I have checked. That means I want to send even number of ones to the parity checker. I want to send even number of, this is at the transmitter side, this is at the transmitter side, and parity checker will be at receiver side. Okay, this will be at receiver side, this will be there at receiver side. This is the transmitter side, this is the receiver side. So this is a even parity generator. That means it will make sure that this parity generator will make sure that at the parity checker you have even number of bits. So if this is my input, then what will be this value? That would be 1. So this is even parity generator, so it would be 1 0 1 0 0. This is my input. Now what is this? This is even parity checker. So what it will check? That the number of ones should be even. At the input side, this is the even parity checker. This was the generator, this is the checker. So what it will do? It will check if the number of ones are even. Yes, if the number of ones are even, it will give error 0. That there is no error. Are you getting this point? What we are doing in parity generator and checker? So first we will see the data line. If we want to generate even number of ones at the receiver, we want to get even number of ones. That means we will generate a parity which will check if the number of ones are even. If it is not even, it will make itself 1, and this will be transmitted to the receiver. At the receiver we will have even parity checker. That means it will make sure that number of inputs should be even. If the number of inputs are even, then it will give error equals to 0. And let's just say if this was odd parity checker, if it was odd parity checker, so what it will see? The number of ones should be odd. If it is odd parity checker, the number of ones should be odd. So if what it will see? The number of ones are even, that means there is an error. So it will throw an error. Are you getting this point? And now let's assume if this was odd parity generator, if this was odd parity generator and this was the input only, if it was odd parity generator, that means it needs number of ones to be equals to odd. So number of ones here are odd only, so parity will be 0. Parity will be 0. And now if this is odd parity checker only, so it will make sure that at my input number of ones should be even. Sorry, number of ones should be odd because it is odd parity checker. So here number of ones are odd only, and if these are odd, it will throw an error equals to 0. And if this was even parity checker, that means it will make sure that at my input number of ones should be even, and if it sees number of ones are odd, then it will throw the error as 1. So this is what we do in transmitter and receiver. I hope this is crystal clear to you. If it is not clear, then you can again watch it, because a lot of people get confused in parity generator and checker. So simple thing is, whatever the generator and checker are there, their task is to make sure that number of ones are even for even parity generator and even parity checker, and it should be odd for odd parity generator and odd parity checker. That's it. This is their task. Okay, in that manner only we will study. So let's see 2-bit even parity generator. So this is my input, this is my even parity generator. What would be your parity? Even parity generator. So the task is number of ones should be even. Here what is the number of ones? Number of ones. I am writing one more thing. Number of ones. Here number of ones are 0. That means it is an even number only. So parity will be 0. Here number of ones are 1. This is even number. This is an odd number. So you see the data line 0 and 1. You got to know that there are number of ones are odd. So I will be 1 so that the number of ones become even. Parity bit will become 1 so that number of ones become even. Here also you will see that number of ones are odd. And in the next one number of ones are even. So in this one what will parity bit do? That parity bit will see that the number of ones are already even, so I will be 0 only. And here it will see that the number of ones are odd, so I will be 1. So what is P? P is D0 XOR D1. Now tell me one thing, in the examination do you actually need to write this truth table? Can you think intuitively? Without writing the truth table, can you think intuitively? What you need to think, that I have an even parity generator and my input are D0 and D1. My parity bit will be 1 if the number of inputs are odd. What I would say, parity bit P will be 1. Listen to this line very carefully. If number of ones are odd, because if odd number of ones are there, then it would be 1, right? Because if odd number of ones are there, it would make it even, so it would be 1, right? That means it is a odd number of ones detector. Odd number of ones detector. And what is odd number of ones detector? XOR gate. So it has nothing to do with the zeros. So if you remember, what was XOR gate? Odd number of ones detector. Odd number of ones detector. And what was XNOR gate? XNOR gate was even number of zeros detector. Even number of zeros detector. But your parity bit has nothing to do with the 0, right? Your parity bit has nothing to do with the 0. So when I am thinking about parity generator or checker, I will never think about XNOR gate. I will always think about XOR gate. Say yes or no? Because your parity bit has nothing to do with the number of zeros. It has everything to do with the number of ones. So I will always think in the manner of 1. And if I am thinking in the manner of 1, that means I will be thinking of XOR gate. Say yes or no? Right? So what else you can write? If odd number of ones detector, that means if number of ones are odd, then output will be 1. If number of ones are even, then output will be 0. If number of ones are even, let's just say if number of ones are even, then what will be the output? 1 XOR 1 0, 0 XOR 1 1, 1 XOR 1 0. So output will be 0. And if number of ones are odd, then output will be 1. So this is what we mean, right? Why did I remove it? Yeah. What about this odd parity generator? Odd parity generator. Number of ones should be odd. Number of ones should be odd. So here number of ones are 0, here 1, and here 2. So here number of ones are even. Here these are odd. These are odd. And this is an even number. So this will be 1, this will be 0 because already these are odd, and this will also be 1 because here number of ones are even, so it makes sure that it would be odd. Here number of ones are odd only, so it makes sure that it would be odd only. Here number of ones are even, so it makes sure that it becomes odd. Okay, so what is P now? P is denote XOR D1 bar, which can be written as denote XNOR D1. Okay, so this is your P. How you will think in the examination? This is my odd parity generator. First you will say, okay, this is a odd parity generator. That means I need to make sure that the number of ones should be odd. So if number of ones at the input is odd, then parity bit will be 0. Number of ones is odd, that means parity bit will be 0. So it is the bar of XOR gate. Because what is XOR gate? You never need to think in terms of XNOR. I told you this thing. Never think in terms of XNOR. Always you need to think in terms of XOR. So what you will think? That I need to make sure that my number of ones are odd. If my number of ones are odd, that means output will be 0. So it is the negation of odd number of ones detector. Say yes or no. Negation of odd number of ones detector. So you will write XOR gate and put negation there. In the end, I will tell you very simple trick. You will be able to write down all the expression. But till now, we are building our concept. So let's go and do the same thing for 2-bit even parity checker. Okay, yeah, this is even parity checker now. So this will be called 2-bit even parity checker only, where 2 bits are data bits and 1 is the parity bit. So you will not say that, sir, this is 3-bit parity checker. No, 2 data bit and 1 parity bit. So what is this? Even parity checker. Even parity checker. So it will see if the number of ones are even, then I will be 0. So here number of ones are 0 only. Here number of ones are 1. Here also number of ones are 1. Here number of ones are 2. Here 1. Here 2. Here 2 and here 3. This is number of ones. So here number of ones are even. So error will be 0. Here number of ones are odd. So error will be 1. Error will be 1. Error will be 0. Error will be 1. Error will be 0. 0. Here number of ones are. So that's the thing. Now what do you think? What is the truth table for this? This is also XOR gate only. Right? You can see 1 is there, 0 XOR 0 XOR 1. 0 XOR 1 XOR 0. 0 XOR 1 XOR 1 is equal to 0. So this is also XOR gate. Now why it is XOR gate? So how you will think? Even parity checker. In the examination, how will you think? If there is even parity checker, that means if the number of ones are odd, then error bit will be 1. If number of ones are odd, then error bit will be 1, because the job of this is to generate even parity. That means it needs to make sure that the number of inputs, the number of ones input should be even. But if the number of inputs are odd, then error will be 1. So this is odd number of ones detector, which is XOR gate only. So even parity checker is a XOR gate only, right? So let's do the same thing for 2-bit odd parity checker. In the examination, how will you think? So if the number of ones are odd, then my error will be 0. If number of ones are odd, then error will be 0. This is odd parity checker. So if number of ones are odd, error will be 0. That means it is the negation of odd number of ones detector. That means it is the negation of this. Can I write down this as this? No, absolutely not. Why so? Because for 3 bits, XOR and XNOR are equal. So I can write down it in this manner. And then there is whole bar. And another expression, more expressions are there, which I have already told you. Camera ko kya ho gaya yaar? Yeah. So more expressions are there. I told you, if one plus sign needs to be converted to dot, then what will happen? 1 bar will go. So if 1 bar goes, then it would be denote D1. More expression could be there, which we have already seen in our basic logic gate course, right? And what about this? This is equals to our P dot denote dot D1. Okay, so these are equal. Now odd parity checker it is. So number of ones are even, so it would be 1. Number of ones are odd, 0. Number of ones are odd, number of ones are even. Number of ones are odd, number of ones are even. Number of, so basically opposite of that, right? Number of ones are even, so 1, and number of ones are odd, so 0. So this is the truth table, but we will not derive that table in the examination. We will think smartly. So 3-bit even parity generator. Write down the final expression of the parity. 3-bit even parity generator. How will you think in the examination? 3-bit even parity generator. That the number of ones should be even. Number of ones. If number of ones, let's think in the form of odd. If number of ones are odd, that means output should be 1. If number of ones are odd, output will be 1 because this is an even parity generator. If let's just say there are 3 1, then output will be 1. So number of ones are odd, output will be 1. That means this is odd number of ones detector. So what is that? XOR gate. So what will be your parity bit? That would be A XOR B XOR C. What about this? 3-bit odd parity generator. If number of ones are odd, if number of ones are odd, that means output will be 0. What does that mean? Negation of XOR gate, right? Negation of XOR gate. So negation of XOR gate, which can be written as this, or there are other expression as well, which is this or this. Anything can be asked in the examination. Or so this traveled here, this traveled here. Yeah, more expression that basically this dot can travel anywhere. Okay, 3-bit even parity checker. If the number of ones at the input side are odd, if the number of ones are odd, then error will be 1. Then that means it is odd number of ones detector. If number of inputs are 1, then error will be 1. If number of ones are odd, then error will be 1 because it is even parity checker. It needs the number of inputs should be even, but if the number of inputs are odd, that means it will give output as 1. So this is again XOR gate, which is equals to, again we can write this is equals to this as well, and this is equals to this. And what about this 3-bit odd parity checker? You can do it on your own. It will be just the negation of the previous one. So you can see here, for even parity generator and checker, always XOR gate is used, and for odd parity generator and checker, always the negation of XOR gate is used. So I will not say XNOR gate is used, negation of XOR gate, because sometimes these two can be equal as well, XNOR and XOR. So I will say negation of XOR is used, right? So for n bit we can write it down, A XOR B XOR C XOR D. In that manner it will keep on going. And for odd parity generator, I will not write dot here, I will write in this manner, okay, and then I will take a bar. What about this? And here for odd it will be the bar. So I will say, do not mug up, but understand the concept. Okay, you should know the concept as well. Now in the examination any kind of questions can be asked, and in that manner you will be able to solve. What is the job of even parity generator? That number of ones should be even. So if at the input side number of ones are odd, even parity generator will be 1. What is the job of odd parity generator? That number of ones at the in the data line should be odd. If the number of ones are even, or you can say if the number of ones are odd, then output will be 0. That means it is the negation of XOR gate. What is the job of even parity checker? So at the input side along with the parity bit, so here I should have written parity bit as well, because there will be parity bit. Even parity checker, that means basically 3-bit even parity checker is there. So wait a second, this is a blunder from my side. Even parity checker it is. So there will be 3 bits and a parity bit, no? 3 bit and a parity bit. So here you take like this, and this can be written as A XNOR B XNOR. This is actually even parity. I will again explain it. This was even parity checker. So at the input side there will be 4 bits, no? 3 is the data line bit and 1 is the parity bit. And now combining all those 4 bits, if the number of ones are even, then output will be 0. And if the number of ones are odd, then output will be 1 for parity checker. If the number of ones are odd, that means there is an error, so output will be 1. Got this point? So there will be four kind of input. And here there will be an input, and this also I should write. So n bit even parity checker, no matter how many bits are there, it doesn't actually matter that how many bits are there. The job is just to make sure that number of ones should be even or odd. So what is the job of n bit even parity checker? No matter how many bits of input are there, the only job is at the input side the number of ones should be even. If the number of ones are odd, error will be 1. So if the number of ones are odd, error will be 1, that means it is an XOR gate, and the next one is simply the complement of that. So that's it about our parity checker and generator. If there is any problem on that, no, there is no problem, there is no issue about this particular lecture. So we have covered everything in a very detailed and short manner, so that we could do all the questions correct if these kind of questions are asked. Okay, so these kind of code converter, 7-segment display, and these kind of this, what do we say, parity generator and checker, we have studied it, right? In the next video we will study about magnitude comparator, which is also a very easy topic. And if that video is not that large, let's just say that video is of roughly around 30-40 minutes, then I will try to add up that video in this video only, because this is also not a very large topic. Magnitude comparator is also a very small topic only. So let's see it in the next video. Okay, thank you very much. Hi everyone, so now we are going to study about magnitude comparator. So this is also in combination circuits. So what it will do, it will compare the magnitude of 2 binary numbers. So there will be 2 binary numbers. It could be of 1 bit, it could be of 2 bit, it could be of 3 bit, 4 bit, 5 bit. So 2 binary numbers will be compared. So this is the job of magnitude comparator. Okay, now very basic thing we know, 1 is greater than 0. What is the magnitude of 1, 1? That is 3. 3 is greater than 2, is greater than 1, is greater than 0. 7 is greater than 6, is greater than 5, greater than 4, 3, 2, 1 and 0, right? But let's observe something very interesting. Let's see these two numbers. Which is the MSB bit? This is the MSB bit. Here, this is the MSB bit. Now, if I look at only MSB bit, then if your MSB bit is greater, that means your number will be greater. Because here 1 is greater than 0. Although 0, 0 is less than 1, 1. But if my MSB bit is greater, then my number will be certainly greater. Say yes or no. Let's see other example now. If your MSB bit, let's see these two examples. Here MSB bit is same. This is your MSB bit. This is also your MSB bit. Both are same. Now where we will go? We will go to the second bit. This is the second bit. Here this is the second bit. Here if second bit is greater, that means the number is greater. Although this bit is lesser than this one. 0 is lesser than 1. But if second bit is greater, then certainly the number is greater. Now if second bit is also equal, let's go to these two examples. Here 0, 0 is also equal, 0, 0 is also equal. Then we will see the third bit. If third bit is greater, that means the number will be greater. So how we need to start? We need to start from the beginning. If that bit is greater, then certainly the number is greater. If these two bits are equal, let's check here. This bit and this bit is equal, this bit and this bit is equal, but this bit is greater than 0. So certainly this number is greater. Now let's check these two numbers. This bit and this bit is equal. Now 1 is greater than 0, so certainly this number is greater. Now let's go to this number. 1 is equal, 0 is equal, but 1 is greater than 0, so this number is greater. So we need to check in this manner. First check the first bit, MSB bit, then go to the next. If that is greater, that means certainly the number is greater. Then go to the next, then certainly the number is greater. Right? So this intuition I will be using in our analysis. Okay. So we are not going to solve it using K maps, but with our intuition only we are able to write down the final expression, and that we will see in our lecture. So now we will see 1 bit magnitude comparator. So we will compare 1 bit. So this is your 1 bit magnitude comparator. If it is a comparator, that means there will be 2 input, no? This input is A, this input is B. Now A is of 1 bit, B is of 1 bit. This is what they mean. 2 inputs are there, A is of 1 bit and B is of 1 bit. So they will say 1 bit magnitude comparator, but input will be 2 bits. 1 bit is of A, 1 bit is of B, right? And there will be 3 outputs. First one would be greater. Now greater can be defined as A greater than B as well and B greater than A as well, but I am defining greater as A greater than B. Okay. Second one will be equal, that I am defining as A is equals to B, and third one is lesser, that I am defining as A is lesser than B. It could be other way around as well, that greater could be B greater than A and lesser could be B less than A, but here I am defining in this manner, that greater is A greater than B, equal is equals to A equals to B, that would be 1 only, and less is A less than B. Okay. Now here let's check. A naught is 0, B naught is 0, both are equal, so this would be 1, these two will be 0. Here A naught is 0, B naught is 1, that means this will be 1 and these two will be 0, because B naught is greater here. Here B naught is greater. What about this? Here A naught is 1, B naught is 0, so A naught is greater here and these two will be 0. What about this? A naught is 1, B naught is 1, both are equal, right? So what you can write, this is your greater, this is your equal, and this is your lesser. So what is the expression of greater? That is A naught, B naught bar. What is the expression of equal? This is simply XNOR gate, right? XNOR gate. You can see it is XNOR gate. And what is the expression of lesser? That is A naught bar, B naught. So these are the expressions we are getting. This we can easily make from our from logic gates. How will you make it? For greater, this is how you can make it. Inverter, and then there is a gate, and for these simply you can use an XNOR gate, and for this you can use another NAND gate. So basically A, B, A, B, A, B. Here you will get greater, here you will get equal, here you will get lesser. So just you pick that in a box and that would be your gate. Okay, that would be your combination circuit. But let's write down these expressions again with a very good intuition. So what I need to compare? A naught and B naught. I am writing greater. Greater, that means my A naught should be greater than B naught. If my A naught is greater than B naught, that means A has to be 1 and B has to be 0. Is there any other condition? If I want my A naught to be greater than B naught, that means A has to be 1 and B has to be 0. There is no other condition where A naught can be greater than B naught. So this is the only condition. So what I will write? A naught, B naught bar. If I need to write lesser, that means I want my B naught to be greater. If I want my B naught to be greater, that means B naught should be 1 and A naught should be 0. I want B naught to be 1 and A naught to be 0. I am writing SOP form, so A naught will be written in bar and B naught will be written in bar. Now if I write equal, for writing equal, when it can be equal? If A naught is 1 and B naught is 1, so A naught is 1 and B naught is 1, or if A naught is 0 and B naught is 0. A naught is 0 and B naught is 0. Let me tell it again. They can be equal when A naught is 1 and B naught is 1, or A naught is 0 and B naught is 0. Are you getting this point? Or and. So what is this? A naught XOR B naught. So in that manner you should also write down the values, okay, or the final expression. So in that manner also you should be comfortable writing your final expression. Let's see it for 2-bit magnitude comparator. So it is a 2-bit magnitude comparator. That means input will be 2 inputs only, but that input will be of 2 bits. So this is your input A, this is your input B, but A is of 2 bits. Basically your A is A1 A0 and your B is B1 B0. You can take an example, that is 1 0, it could be 1 1, right? So this is the scene. 2-bit magnitude comparator. So input will be always 2, input will be always 2, but this input is of 2 bits, 2 bits input is there. Okay, so again greater, equal and lesser. So again I am defining greater as A greater than B, equal as A is equals to B, and less as A less than B. Okay, you can make the truth table. If you make the truth table, how will you write the truth table? You will write in this manner: A1 A0, B1 B0, and then these answers G E L, right? So let's write down the truth table, but we are not going to solve it using K-maps. So for greater A greater than B, A0 A1, B0 B1. So this is also 0, this is also 0. That means it is equal. What about this one? This is also 0, this is 0, this is 1. So A is greater than B, that means A is less than B. This is 0, this is 2, A is less than B. This is 0, this is 3, A is less than B. This is 1, this is 0, A greater than B. This is 1, this is also 1, both equal. This is 1, this is 2, A is less than B. This is 1, this is 3, A is less than B. Now this is 2, this is 0, greater. This is 2, this is 1, greater. This is 2 and this is also 2, equal. This is 2, this is 3, greater, sorry, lesser. 3, 0, greater. 3, 1, greater. 3, 2, greater. 3, 3, equal. So these are the truth table. Now you can write down the final answer, make the K-map and write down the final answer on your own. You can do it, but we are not going to solve it using K-map. So how we will solve it, that we will see. But before that, let's see an interesting observation. So if I am saying that I have 2-bit magnitude comparator, 2-bit magnitude comparator. If I have 2-bit magnitude comparator, then inputs will be 2, but each input will be of 2 bits. Each input will be of 2 bits. Magnitude comparator will always have 2 inputs. Let's take an example of 3-bit magnitude comparator, because 2-bit you can directly see. 3-bit magnitude comparator. So input will be 2 only, A and B, but this will be of 3 bits and this will also be of 3 bits. So how many bits are coming at the input? 6 bits are coming, right? So if I am writing n-bit magnitude comparator, that means how many bits are coming at the input? N-bit magnitude comparator. So each number A, let's just say A, it will be of n bit and B will also be of n bit. So 2n bit will be coming at the input. 2n bit at input. If 2n bits are coming at the input, then how much total combination will be there? If 4 bits are there, the total combination are 2 to the power 4, right? If 5 bits are there, combination are 2 to the power 5. If 2n bits are there, 2 to the power 2n total combination. Say yes or no? At the input side, you are having n plus n 2n bits. If you are having 2n bits, so these kind of total combination you can write 2 to the power 2n, right? Now out of these, 2 to the power n times you will get equal. 2 to the power n times you will get equal. And rest of the times, 2 to the power 2n minus 2 to the power n. So how much is left? 2 to the power 2n minus 2 to the power n. Half of this will be greater and half of this will be, I will explain it, no need to worry, and half of this will be lesser. Okay, how I am saying so? How many bits? Let's just say there is 2-bit magnitude comparator only. 2-bit magnitude comparator. So this is having 2 bits, A0 A1, and this is having 2 bits, which is B0 B1. When they will be equal? When both the bits are equal. That means A is 0 0, this is also 0 0. A0 is 0 1, this is also 0 1. 1 0 1 0, 1 1 1 1. So basically we are taking total combination of A0 and A1. Say yes or no. What all are the possible combination of A0 and A1? At those times it will be equal. You can see here A0 0 0 is equals to 0 0 1 here, 0 1 is equals to 0 1 1 here, 1 0 is equals to 1 0 1 here, 1 1 is equals to 1 1. So total 4 times it is equal, and it was 2-bit magnitude comparator. So 2 to the power 2, total 4 times it was equal. It was 2-bit magnitude comparator. So if you put here 2, you will get 4. So 4 times you are getting equal. And what all are the total possible combination? That would be 2 to the power 4. That would be 16. So 16 minus 4 is 12. So 12 times you will get greater and equal. Sorry, 12 times you will get greater and lesser. So half of that will be greater and half of that will be lesser. Are you understanding this point or not? Look, I could have directly written the expressions, but reasoning I am giving. n-bit comparator is there. So total 2n bit will be there at the input side. If 2n bit are there at the input side, that means total possible combination of input will be 2 to the power 2n. Now in this 2 to the power 2n, 2 to the power n times you will get equal. 2 to the power n times you will get equal. Why you are getting 2 to the power n times equal? Because this will have n bits, and in n bits what are the total possible combination? 2 to the power n. From n bits total possible combination are 2 to the power n, and 2 to the power n combination could be 0 0 0 1 1 0 1 1. In 3 bits it would be 0 0 0 0 0 1 0 1 0 in that manner. So those combination, the same will happen in B0 B1 as well. The same thing will happen in B0 B1 as well. So at that time both will be equal, right? So 2 to the power n times it will be equal. Now whatever is left, what is left? These 2 to the power 2n was a total combination. Out of this 2 to the power n are equal. So this much is left. Half will be greater and half will be lesser. That means in half times A will be greater and in half times B will be greater. That's it. So greater and lesser. That's it. Very easy. Very easy. So total possible combination we have written. Right? I hope you have understood the concept here. Okay, so you can just remember this thing. Like no need to remember. I hope you will be understanding it, and in the examination you can directly write it down. Take an example of 2-bit magnitude comparator or 3-bit magnitude comparator. 3-bit magnitude comparator. So in 3-bit magnitude comparator, input will be 6. So total combination will be 2 to the power 6. What that is? 64. 64 combination. Right? Out of these, 2 to the power 3 are equal. 2 to the power 3 means 8 equal. And 64 minus 8. What that would be? 56 by 2. That is 28 greater and 28 lesser. That's the thing. Okay, well and good, very easy. If these kind of questions are asked in the examination, you can tell it. You can tell the final. You can tell these combinations, like how many times it would be greater, how many times it would be lesser. Now, how to write down the final expression? So that we will see now. Let's write down the final expression for A greater than B. But before that, let's check the conditions when A can be greater than B. So when A can be greater than B. First condition is this, that if your A1 is greater than B1. If A1 is greater than B1, do you need to look at A0 and B0? No. If A1 is greater than B1, then certainly your A will be greater than B. Or what could be the second condition? That if A1 is equals to B1, if A1 is equals to B1 and A0 is greater than B0, then also A will be greater than B. Like if first bit are equal, then this bit should be greater than this bit. A1 is equals to B1, then A and A0 is greater than B0. So if these two are equal, then certainly, if these two are equal, then if A0 is greater than B0, then certainly A will be greater than B. So these two conditions are there, right? And when A can be equals to B, when A can be equals to B, which is A1 is greater than A0, A1 is equals to B1 and A naught is equals to B naught. Both conditions should be satisfied. That's why AND is there. Here there is OR. Here there is AND. Here AND will be there. Why so? Because A1 has to be equals to B1 and A naught also has to be equals to B naught. Then only both numbers will be equal. Right? You have understood it? Let's write down the expression. So greater expression I need to write. So for greater expression, here I can write down the bits A1, A naught, B1, B naught. That means A1, if A1 is greater than B1, so A1 is greater than B1. That means A1 has to be 1 and B1 has to be 0. Then only A1 can be greater than B1, no? So A1 is greater than B1. So A1 is 1 and B1 is 0. Or if A1 is equals to B1, if A1 is equals to B1, now when A1 can be equals to B1, when A1 can be equals to B1, that A1 is 0 and B1 is 0, or A1 is 1 and B1 is 1. This I have written A1 is equals to B1. This I have written A1 is equals to B1. Here also you can see what was your A naught equals to B naught, that was XOR gate. What would be your A1 equals to B1, that would be your XOR gate. So this I have written A1 is equals to B1. So let's write down this is what I am writing. A1 is greater than B1 or A greater than B and A naught greater than B naught. So A naught is 1 and B naught is 0. So that would be the final answer. Let me explain it again. So what all are the conditions of greater? So first we will start with the MSB bit greater. So if A1 is 1 and B1 is 0, if A1 is 1 and B1 is 0, or if A1 is equals to B1, so if A1 is equals to B1, when it can be equal? A1 is not there and B1 is not there. Not there means 0. A1 is 0 and B1 is 0, or A1 is 1 and B1 is 1. So in both of the conditions, let's just say this 1, this 0, this 0. In both of the condition, A1 and B1 would be equal. A1 and B1 would be equal in both of the condition. In this condition as well, in this condition as well. Then what is the other condition? To be greater. So this is if they are equal and A naught is greater than B naught. A naught is greater than B naught. That means A naught is 1 and B naught is 0. Are you getting this point or not? I hope you are understanding it. Let me explain it once again. We are writing for greater. So that means MSB bit should be greater. This is the first condition. If that is happening, then it is fine. There could be other condition as well. So first I will write down the first condition, that if A1 is greater than B1. So if A1 is 1, dot B1 is 0. A1 is 1, A1 is there, dot B1 is not there. Or what could be the condition? That if A1 and B1 are equal. So what is the condition for A1 and B1? A1 XOR B1, A1 XOR B1. So if A1 and B1 are equal, that means A1 is not there and B1 is not there, or A1 is not there and B1 is not there. This is the condition for A1 is equals to B1. Now what could be what we require? So if A1 is equals to B1 and A naught should be greater than B naught. So A naught has to be there and B naught should not be there. I hope you are understanding it. I am taking the examples as well. Can you write down this one? Here B is greater than A. So how will you write down? B is greater than A. First condition could be that B1 is there and A1 is not there. B1 is there and A1 is not there. What could be the next condition? That if A1 is equals to B1, A1 is equals to B1. So A1 is equals to B1 could be if A1 is 1 and B1 is 1, B1 is 1 and A1 is 1, or B1 is 0 and A1 is 0. So if A1 is equals to B1 and B naught is greater than A naught. So that's it. This is the final answer. This could be written as B1 A1 bar, B1 XOR A1, B naught A naught bar. So I hope I have explained it clearly to you. Let's write down for the equal one. Here as well you can write A1 is there, B1 is not there. A1 and B1 are equal, that means A1 XOR B1. A1 is equals to B1, that means A1 XOR B1. A0 is there and B0 is not there. Let's write down for equal. When they will be equal? A1 is equals to B1. So what do we write for A1 equals to B1? A1 is equals to B1 and means dot A0 is equals to B0. Equal means dot. That's equal means XNOR gate. For 3-bit magnitude comparator, try writing down the final answer. For 3-bit magnitude comparator, what would be the first condition? That A2 is there and B2 is not there. A2 is there and B2 is not there. Or if A2 and B2 are equal, then A1 is there but B1 is not there. Or if A2 and B2 are equal, A2 and B2 are equal and A1 and B1 are equal, then A0 is there but B0 is not there. That is the final expression. Are you getting this point? A2 is greater than B2. So A2 is there, B2 is not there. Or A2, B2 are equal, but A1 is greater than B1. So A1 is there, B1 is not there. Or A2, B2 is equal and A1, B1 also equal. And A0 is greater than B0. That's it. What it would be for equal? For equal it would be A2 and B2 is equal and A1, B1 equal and A0, B0 equal. For equal, XNOR gate. Equal means XNOR gate, that's it. What about B greater than A? So if B3 is there, and A3 is not there, if B3, A3 are equal, that means B2 is there but A2 is not there. If B3, A3 equal and B2, A2 equal as well, then B1 is there and A1 is not there. So this is the condition, right? So that's how we write down the final answer. Let me explain it one last time. Here I will explain again, okay? That A1 is there, B1 is not there. Or A1 is equals to B1. A1 is equals to B1, then we will compare A0 and B0. So if A1 is equals to B1, A1 is equals to B1, how it can be written in XNOR gate? A1 XNOR B1. How I can write A1 equals to B1? A1 equals to B1 would be when A1 is there and B1 is there, or A1 is not there and B1 is not there. So A1 XOR B1. And A0 should be greater than B0. That means A0 is 1 and B0 is 0. So A will be greater than B if A1 is greater than B1, or if A1 is equals to B1, A0 is greater than B0. That's it. If A1 is equals to B1 and A0 is greater than B0. So this is how you can say. For 3-bit, how you can say that A2 will be greater than B2, or A2 is equals to B2 and A1 is greater than B1, or A2 is equals to B2, A1 is equals to B1 and A0 is greater than B0. So in that manner you can proceed. So you can write down the final expression of any bit comparator, right? So they can ask these kind of questions in the examination. So there you will not be doing this analysis. This analysis was just to tell you that number of possible combinations. So n bit comparator is there, 2n bit will be at input, 2 to the power 2n will be total combination, 2 to the power n would be equal, 2 to the power 2n minus 2n by 2 would be greater, and 2 to the power minus 2n by 2 will be lesser, right? Proper reasoning also I have given. Why is that happening, right? Now you need to make a 2-bit comparator from 1-bit comparator. So try doing it on your own. Think about it. You need to make 2-bit comparator with the 1-bit comparator. So these outputs you are already having. Think now. So what I need to make, let's write down the final answer. This is what I need to make. Final answer would be better I should show it here. So this would be my final answer, that 2 bits A and B, sorry, not 2 bits, 2 values will be there, and final you will get greater, equal and lesser. So A will be there, which is a string of A0 and A1. B will be there, which is a string of B1 and B0. This is your 2-bit magnitude comparator. And greater you need to find, equal you need to find, and lesser you need to find. So greater, that is A greater than B. How I can write? How I can write? What this shows? This shows that A1 is greater than B1. What this shows? That A1 is equals to B1. And this shows that A1 is less than B1. What this shows? That A0 is greater than B0. This shows what does this show? A0 is equals to B0, and this shows A0 is lesser than B0. And what is my input? Input is A1 A0 and B1 B0. So if I need to write greater, that is A greater than B, how will I write it? How will I write it? That if I get G1, that means A1 is greater than B1. It's all over. If A1 is greater than B1, then certainly A is greater than B. Or if A is equals to B, A1 is equals to B1. If A1 is equals to B1, then A0 should be greater than B0. So this is GA greater than B. Are you getting this point or not? Did you understand what did I do here? A1 is greater than B1. So this output will say that your A1 is greater than B1. So if this output I can take, or if both are equal, if A1 is equals to B1, then at least A0 should be greater than B0. That means this G0 I need to pick. So that would be your final G. Is there any other condition? If I take this one, that I am having L1 first, that means A1 is less than B1. So certainly that if A1 is less than B1, that means certainly B will be greater than A. There is no chance, we cannot think of anything. If MSB bit is greater, that means certainly the number will be greater. So that is the condition for GA greater than B. So better I should write here. I will again write it here. GA greater than B. What is that? That first you can get A1 is greater than B1, or if A1 is equals to B1 and A0 is greater than B0. What about GA equals to B? What would be that condition? A1 should be equals to B1 and A0 should be equals to B0. What about GA less than B? So B1 should be greater than A1, or if B1 is greater than A1, all over. Or what could be the condition? That if A1 is equals to B1, then at least B0 should be greater than A0. B0 should be greater than A0. So that's the final expressions. So these are the final expressions, right? I am assuming that this is my MSB and these are my LSB. This is the assumption we have made. So now if I need to implement it, so how will I implement it? Eventually I need a XOR gate. In that XOR gate, this input is going E1 dot G0, E1 dot G0. E1 dot G0. What about this? This is G1. So what you will get here? You will get this G, that is G1 plus E1 G0. For equal, what you will do? For equal, E1 dot E2. even dot e2. This will be your equal. For lesser as well you can make the same thing, you can make for lesser as well. Okay, so that I am keeping for you. So this is, you are making 2-bit comparator from 1-bit comparator. Let's try make. Now let's make 3-bit magnitude comparator from 1-bit magnitude comparator. So this you should do on your own. So what you need to find, this is your A, which is A2, A1, A0. So for A2, B2 bit and B is B2, B1, B0. So for A2, B2 bit you have made 1-bit comparator, 1-bit comparator, 1-bit comparator. A2, B2, A1, B0, sorry, A1, B1 and A0, B0. First, let's find greater. Greater means A is greater than B. So when A can be greater than B, if initially only you get A1 is greater than B1, sorry, A2 is greater than B2. If initially only you get A2 is greater than B2, or if both are equal, A2 is equals to B2. If both are equal, first bit is equal, MSB bit is equal, and A1 is greater than B1. First bit is equal, but the second one is greater. So into G1. If MSB and the next bit is also equal, that means this bit and this bit is also equal, then this should be greater. I mean, A0 should be greater than B0. So this is the condition of greater. What about the condition of equal? Equal condition would be A2 is equals to B2 and A1 is equals to B1 and A0 is equals to B0. What would be the condition for A less than B? A less than B means B should be greater. So what does this shows? That your B is greater. So if I am getting L2 all over, or what could be the condition? If A2 is equals to B2, but A2 is equals to B2 and A1 is less than B1, or you can say B1 is greater than A1. Or if both are equal, A2 B2 is also equal, A1 B1 is also equal, then at least this was showing equal, then at least this bit, the final bit, the LSB bit should be greater. So B0 should be greater than A0. So these are the conditions, and this is how you can make it. So G2 you will pick, E2 you will pick, G1 you will pick, make an AND gate and then another AND gate, and in that manner then you will connect OR gate. So in that manner you can get 3-bit magnitude comparator from 1-bit magnitude comparator. So these kind of questions can be asked in interview, and even in the gate examination they can directly ask the expression that your 1-bit magnitude comparator is there whose outputs are G2 G1 G2 E2 L2 and G1 E1 L1 and G0 E0 N0. If you are making 3-bit magnitude comparator from 1-bit magnitude comparator, what would be the expression for G? So that would be the expression. So this is how you need to write in the gate examination, and I have given enough intuition to do it quickly. I hope you are understanding it in a better manner now. Okay, is there anything else? Yeah, 3-bit magnitude comparator from 2-bit magnitude comparator and 1-bit magnitude comparator. Okay, so what you need to find? G. Here what this is showing? This is showing that A2 A1 is greater than B2 B1. This is showing that A2 A1 is equals to B2 B1. This is showing that A2 A1 is less than B2 B1. Now we do not know how they are greater, how they are lesser, but we just know that these two bits are greater than this bit. So if I need to write A greater than B, then if I am only getting G2 all over, if I am only getting G2, then it's all over. Why it is all over? Because two bits are greater. Combination of two bit is greater than the next one. It could be this condition as well, or it could be this condition, or it could be this condition. But combination of first two bit is greater than this bit, which is your A0 B0. So here it is A0 greater than B0. Here it is A0 is equals to B0, and here it is A0 is less than B0. It's all over. If initial two bits are equal, that means it is 0 0 0 0. If these two are equal, then at least this should be greater. So if this is 1, this is 0, so at least this should be greater. That's it. What about A equals to B? Initial two bits should be equal. and these two bits should also be equal. What about A less than B? A less than B. That A less than B, that means B should be greater. So this should be greater. If this is greater, all over. Or if these are equal, then at least B naught should be greater. This is how you will write down the final expression. So without even writing down these outputs, that A2 A1 B1 B2 B1 A1 A2 A1 B2 B1 or A naught B naught, without writing down these expressions, you should be able to write down this final expression, that if G2 is there, then all over. Or if E2 is there, then G1 should be there. For equal, E2 and even both should be there. For lesser, if L2 is there, all over. Or if E2 is there, then L1 should be there. This is how you will write down the final expression. And now I hope till this point everything is clear in magnitude comparator. A lot of times I have seen people writing down the final expression using this K-map, but we are not going to use the K-map. K-map here we have never drawn, and this combination also I have drawn just to make you understand that there will be n bit comparator, then there would be 2n bit input, and 2 to the power 2n will be the total combination. Out of these, 2 to the power n will be equal and rest will be unequal, greater or lesser. So half of them will be greater, half of them will be lesser. Okay, let's take example of 3-bit magnitude comparator. That means 3-bit means there will be 6 input. If 6 input are, that means there are total 64 combination. Out of those 64 combination, 2 to the power 3, 2 to the power 3 means 8. 8 will be equal. Now 64 minus 8 will be 56. So 56 will be greater or lesser. So 56 by 2, that would be 28. So 28 will be greater and 28 will be lesser. So this was the important point. And what was the other point? You just need to write down the output. When it will be greater, A1 is greater than B1 all over, or A1 is equals to B1 and A naught is greater than B naught. So A naught in dot B naught bar. And when they will be equal, all bits are A1 A naught, A1 B1 should be equal and A naught B naught should be equal. So A1 is equals to B1, A naught is equals to B naught. Okay, and in that manner we have written the final output. So I guess, yeah, that's it about this whole video, and I hope this concept is crystal clear to you. In the next video, we are going to study about multiplexer. So let's start studying about multiplexer now. Yeah, hi everyone. So just a small correction. I did a blunder here, that this I did not notice actually. A1 is the MSB bit, no, and B1 is the MSB bit. So those should be the MSB bits. A1 and A naught and B1 B naught. This is how it should be written, because your A was A1 A naught and your B was B1 B naught, and in that manner only we have wrote these expressions. A1 A naught greater than B1 B naught, A1 A naught equals to B1 B naught. In that manner only we have written that A1 is greater than B1. So that was a blunder from my side, I just noticed it. Okay, yeah. Hi everyone, so now we are going to start studying about multiplexers. So very interesting topic and very important as well. A lot of times questions will be asked from this particular topic in the interviews as well and in the gate examination as well. So what is a mux? Mux is a many to one selector. That means there will be a lot of inputs but only one output. There would be a lot of inputs, only one output, and there will be select lines as well. So based on these select lines, one of the inputs will be selected and will be given to the output. Based on these select lines, one of the input will be selected and given to the output. Let's see how it will work. But before that, if the mux will be always in 2 to the power n into 1 form. Like it could be 2 into 1 mux, it could be 4 into 1 mux, it could be 8 into 1 mux. What does this show? This is the number of input line and this is output. Number of input lines, output. So number of input lines are 2 to the power n. Number of input lines are 2 to the power n. And this n is the select line. N select lines will be there. So number of inputs are 2 to the power n and output will be 1 and n select lines will be there. Okay. So let's write it down. If your mux is 2 to the power n into 1. So this shows number of inputs, this shows number of output, which will always be 1 only, and this n shows number of select lines, which you don't need to mug up, eventually you will remember it. Okay, let's study about 2 cross 1 mux. So there will be 2 input, 1 output, and 2 to the power 1 is there, so 1 select line will be there. Okay, what this select line will do? Now this select line can vary. It can take 0 value as well, it can take 1 value as well. So if select line is 0, then I naught will be taken out. and if select line is 1, then I1 will be taken out. Here 0 is written, no? So 0, I0 is taken out. If select line is 1, then I1 is taken out. So select line can vary. Select line can vary its value. S is 0, then I0 will be taken out at output, and if S is 1, I1 will be taken out. So how I can write my Y expression? If S is not there, then my output is I0, and if S is there, my output is I1. Do you remember in min terms and max term, when we were studying SOP and POS, we saw this kind of truth table where output was 0 1 0 1 0, and in there somewhere I mentioned output is C. So how did we write? If A bar is not there, B bar is not there, then output is C. So similarly, if S is not there, then output will be I0, and if S is there, output will be I1. So can you design it? Very easily I can design it. How will I design it? S, and then I0 is there. This is S, this is I0. This is again S only, and this is I1. Both will be taken out and will be fed to the OR gate, and this will be the output Y. So this is your combination circuit, which is not that important. Wait a second. Yeah, so I was saying which is not that important. We will solve a problem regarding this, but later on we will solve it. On a block level it is important. So we will solve mux problem on the block level only, not on the circuit level, on the block level. That if S is 0, then I0 will come. If S is 1, then I1 will come. What about 4 cross 1 mux? What do you think? What about 4 cross 1 mux? It will have 2 select line, because this is 4 cross 1 mux. 4 will be input, 1 will be output, and select lines will be 2, because they is 2 to the power 2. So these can also vary. These can be 0 0, these can be 0 1, these can be 1 0, and these can be 1 1. If these two are 0 0, then output will be I0. If these two are 0 1, that means decimal equivalent is 1, so output will be I1. If these two are 1 0, that means decimal equivalent is 2. Decimal equivalent is 2, so output will be I2. And if decimal equivalent is 3, so output will be I3. So generally, if S1 S0 is written and nothing is mentioned, they are not mentioning whether it is MSB or this is LSB. So S1 will be taken as MSB and S0 will be taken as LSB. Although they should mention it, but if nothing is mentioned, then S1 will be taken as MSB and S0 will be taken as LSB, because it is having 1. So let's take it as MSB and S0 as LSB. Okay, and these are I0, I1, I2, I3. By default, you would know that I0 means 0 0, I1 means 0 1, I2 means 1 0, and I3 means 1 1. And these can interchange, like I3 can be written anywhere, I0 can be written anywhere. These are the inputs, so it can be written anywhere. I3 can be written here, I1 can be written down, I2 can be written up, I0 can be somewhere in middle. So these can be written anywhere. Just you need to know that if my select line input is 0 0, I will take I0. If my select line input is 0 1, I will take I1. If my select line input is 1 0, I will take I2. If my select line input is 1 1, I will take I3. So if S1 is not there and S0 is not there, my output will be I0. If S1 is not there and S0 is there, my output is I1. If S1 is there, S0 is not there, my output is I2. If S1 is there, S0 is there, my output is I3. So this is the final expression of Y. Okay. Do the same for 8 cross 1 mux. So 8 input will be there, 1 output will be there, and select lines will be 3. So if all 3 are 0, my output will be I0. This will be taken as MSB and this will be taken as LSB. What will be the decimal equivalent of this? That would be 1. So it would be I1, it would be I2, it would be I3, it would be I4, it would be I5, this will give I6 and this will give I7. You can write down the Y expression. So if S2 bar, S1 bar and S0 bar, then I0 will be my output. If S2 bar, S1 bar, S0, then I1, and in that manner it will keep on going. You can write it down. If S2 is there, S1 is there, S0 is there, my output will be I7. Okay. Now tell me one thing. If I am saying that I have a function f, I have a function f which has the variable s1 and s2. I have a function f which has the variable s1 and s0. This is some function. I am naming this function as x. Okay, I am naming this function as x. So this is my function. So can I write down it in this manner, that y is equals to m0 I0 plus m1 I1 plus m2 I2 plus m3 I3, where m0, m1, m3, m2 and m3 are the minterms of x. Look, my function x is there which has two variables s1, s0. If s1, s0 both are 0, that means it is minterm m0. If it is 0, 1, or you can, if it is 0, 1, then it is minterm m1. If it is 1, 0, it is minterm m2. And if it is 1, 1, it is minterm m3. The condition is my function x should have only two variables which are s1, s0. Now if I am saying that my function x is having s1, s0 and some other variable, let's just say, which is I2. I am telling some other variable is also there. This is my function f. Then I cannot write this is my m0. Then I cannot write this is my m0, because my m0 will be 0, 0, 0. And it's not necessary that your I2 is 0. Are you getting this point? Like, it will depend on s1, s0 and I2. But if it is only depending on s1 and s0, then I certainly know that these two will be 0, 0 and that will belong to m0. 0, 1 will belong to m1. 1, 0 will belong to m2. And 1, 1 will belong to m3. If my function is the function of, if my Boolean expression is the function of s1 and s0, so then only I can write it down. So this is a very important point which I mentioned, that my function is of s1 and s0, then only I can write it down. Okay, we will use it later on. As of now we will not use it, but later on this expression will be used. Similarly here as well I can write down y in this manner, m0 I0 plus m1 I1 plus m2 I2 in that manner till m7 I7, right? Okay, we will use it later on. Let's see some questions now, because this is a very easy topic. The typical part will come, but probably in the next video. Okay, here easy part will be coming. So all these are easy questions. Just write down the minterms of y. So how will you write down? So if b is not there and c is not there, that means both are 0, then a will be coming out. If b is there and if b is not there, if this is 0 and this is 1, then what is the decimal equivalent? 1. So I1 will be coming out, that is 0. Plus, if b is there and c is not there, that means what is the decimal equivalent? Decimal equivalent is 2. Then a bar will be coming out. Plus, if b and c both are there, then it would be a1 will be coming out. So the expression is b bar c bar a plus b c bar a bar plus b c. Okay, this is the expression. Now let's write it in the better manner. That is bc plus a b bar c bar plus a bar b c bar. So y would be equals to, we need to find the minterms. So I need to introduce a here as well. How will I introduce? ABC plus a bar bc. I hope you remember it. A b bar c bar plus a bar b c bar. Okay, so this minterm is m7, this minterm is 0 1 1 m3, this minterm is 1 0 0, this is m4, plus this minterm is 0 1 0, this is m2. 7 3 4 1 and 2. Yeah, so the minterms are 2 3 4 7. So you couldn't solve this question as m0 I0 m1 I1 plus m2 I2 plus m3 I3. If you have solved in this manner, then what will be your m0? That would be b bar c bar, and what is your I0? That is a, plus b bar c 0 plus b c bar a bar plus b c 1. So now you cannot say that, sir, this is my minterm m2. No. Now m1, m2, m3, m4, m5, m6, m7 and m0 will be defined as per this, because this is your final output, which is having the variable of a, b and c. your final output is not having the variable BC only. If it was having variable BC only, then you could have said these will be my minterms. But your final minterms will be different. Are you getting this point? Now let's just say I will copy this question. Okay. Yeah, it has been copied. So let's remove it. Let's remove everything. Now this is the new question, and output will not have now A because A is gone. So output will be function of B and C only. Now you need to write down them in terms of output. So let's write down by conventional method. That would be simply, if B is not there and C is not there, then 1 is coming. Plus, if then 1 is coming, so I will multiply 1 as well. Plus, if B is not there and C is there, then 0 will come. Plus, if B is there and C is not there, that means 2, 0 will come. Plus, if B is there and C is there, 1 will come. So output will be B bar C bar plus BC. So this will, what this will be? This will be M0 and this will be M3. So your Y is having 0 and 3. You can directly see I0 is coming and I3 is coming. Why it is so? Because Y can be equals to M0 I0 plus M1 I1 plus M2 I2 plus M3 I3. So this is 0. This is also 0. So in the answer only I0 will come and I3 will come. So in the answer M0 plus M3 will come. In the next lecture we will use it. Somewhere we are going to use it. Okay, that's why I am writing it. But make sure that all the variables are used as the select line. All the variables are used as the select line. Here I am writing it. All the variables used as select lines. So this is the thing. All the output variables are used as a select line. So then only you can apply this method. Okay. Let's go to the next one. Minimize expression. So just write down the expression by your conventional method. So what will be the select line? Select line will be BC. B into C, BC. So what will be your output Y? If B and C are not there, if BC is not there, basically, I can assume this as X, right? If X is not there, my output will be A. Oh, sorry. If look at it. If X is not there, my output will be what? I0, which is 1. If X is there, my output will be A. Or I can write BC bar into 1 plus BC into A. So X bar plus XA could be written as X bar plus A. So that is the minimized expression of Y. Or it could be written as A plus B bar plus C bar. Are you getting this point? I hope you must have understood that BC bar is not there, then BC is not there, that means BC bar, then 1 would come. If BC is there, then A would come. So X bar plus XA can be written as X bar plus A. So that would be the answer, which is BC bar plus A, or it could be written as A plus B bar plus C bar. So that is the final answer. Let's move to the next one. What would be the minimized expression of output? So here S0 is fixed at 0. Say yes or no. If S0 is fixed at 0, A can have the value of 0 and 1. So how will you write output Y? Output Y. That would be written as, if A is not coming. If A is not coming, then what is the input? 0, 0. If A is not there, that means input is 0, 0. You will pick B. And if A is coming, so what is the input? Input is 1, 0, because this is S1. You notice here, this is S1. So if A is 1 and S0 is fixed at 0, so this decimal equivalent of this is 2. So you will pick I2, that is 1. That's it, this is the answer. And A plus A bar B can be written as A plus, this is A plus A bar B. So output will be A plus B. This is your Y. Did you understand this point? What I did here? S0 is fixed at 0. You cannot change S0. A can change. A can have 0 value. A can have 1 value as well. What is the decimal equivalent of this? 0. What is the decimal equivalent of this? 2. So if A is not there, as in A bar is there, then B would come. If A is there, then I2 will come, that is 1. So A into 1. So A plus A bar B, that is A plus B. Okay. So write down the minimized expression of this. This would be AB. This would be B XOR C. VCC means 1. Okay. And this is ground. This would be D only. Right. Minterms of Y you need to find. So it would be a lengthy problem, but it would be easy only. If D and C are not there, then AB would come. If D is not there and C is there, that is 0 1. 0 1 means this will come, that is B XOR C. Plus if D is there and C is not there, then 1 would come, 1. And if both are there, D and C both are there, then 0 will come. So this is the final expression. It can be written as A B C bar D bar plus D bar C. It can be written as B bar C plus B C bar plus C bar D, and this DC is 0 only. So now I can write it as AB C bar D bar plus this would be B bar C D bar, right? B bar C D bar, because C into C will be C only, and here C and C bar will be multiplied, which will be becoming 0. What I am saying, C bar and C will be multiplied. D bar C into B C bar, C and C bar will be multiplied. It will become 0, and it will be C bar D. So I need to write down them in terms. So how will I write down them in terms? 1 1 0 0. What this will have? This is 0 1 0, right? 0 1 0. A can have value 0 as well. A can have the value 1 as well. What about this? This is 0 1. So 0 1 0 1 0 1. AB can have a value 0 0 0 1 1 0 1 1. This is how we write down the minterms. What is being repeated? 1 1 0 0 1 1 0 1. I guess nothing is being repeated. So this is 12. From here what we are getting? 1 2 1 2 4 8 10. What about this? This is 1. What about this? This is 5. What about this? This is 1 2 4 8 9, and this is 12 and 13, right? So what all are the minterms? 1 2 1 2 5 9 12 5 9 10 12 13. So 4 here, 2 here, 6 7, 4 3 6 7. Okay. So I hope you must have understood. Let's see it again. D bar C bar AB, D bar C B XOR C, D C bar 1, and DC both are coming, then 0. Then this would be the expression B bar C D bar, and this will become 0, and this would be C bar D. A B C bar D bar. 1 1 0 0 0 0 1 0 1 0 1 0. What about this? 0 0 0 1. Okay. Yeah, same. Yeah, it is fine. 0 1 0 1 1 0 0 1 1 1 0 1. This would become 13. This would become 9. This would become 5. This would become 1. This is 2. This is 10, and this is 12. So that's how we write down the minterms. Let's go to the next one. So before moving on to the next topic, I will tell something very interesting. In any combinational circuits you see, no, in any combinational circuit, not just talking about this mux, any combinational circuits. So there will be some input bits, there will be some output bits, right? I know there will be some inputs, there will be some output bits as well. There could be select lines as well. Here there was select lines, there could be select lines as well. But something 3 are constant. What is that? There will be a supply, there will be ground, and there will be a enable button. You know what is supply? Plus 5. Ground is 0. What is this enable button? So if direct enable is written, direct EN is written, that means it is active high enable. What do you mean by active high enable? That if EN is equals to 1, then your IC is working. IC means this is your combination circuit. So combination circuit is working perfectly, working the way it was working. If EN is 1, it is working perfectly. If EN is 0, this is not working. That's it. combination circuit is not working. Basically your output is 0 or 1. Your output is fixed. It could be 0, it could be 1. Based on your combination circuit, it could be a fixed output. It could be 0 as well, it could be 1 as well. But if enable bit is 0, then your combination circuit is not working. If your enable bit is 1, that means combination circuit is working. What about active low enable? That means if your enable circuit is 0, if your enable button is 0, then your combination circuit is working, and if your enable button is 1, then your combination circuit is not working. Active low enable, that means you need to give low at the input. Now this seems like okay, that en is 0, then my circuit is working. If en is 1, then my circuit is not working, and here en bar is written. So basically if en bar is 1, or you can say en bar is 1, or you can wait a second. Basically in place of en bar, if you apply 0, in place of en bar if you apply 0, then it is working, and in place of en bar if you apply 1, then it is not working. It is written, it is active low enable. So now people get confused that sir, here bar is there and here one more bubble is there, so I can cancel out both of them. No, you do not cancel out actually. This is a way of representing. If one of them is having bar, or there is a bubble, or like simply en bar is written, or both of them could also be there. Are you getting this point? They could write en and only a bar, only a bubble. They could write only bar. You could get to know that, you have to get to know that it is active low enable, and they could have written en bar and bubble both together. Then also you need to get to know that it is active low enable only. That means if en bar is equals to 0, then it is working, and if en bar is equals to 1, then it is not working. Okay, let's see a problem, it will be more clear to you. So here en is written, okay, that means this is a enable button, active low enable, sorry, active high enable, this is active high enable. So what will be your output? Let's make a truth table first. So here there is a as well, an as well, and y. So if a is 0, forget about en. If a is 0, what you should expect as output? I naught. And if a is 1, what you should expect as output? I1. But this will work only if en is 1. If en is 0, no matter whatever that is there at the input, output will be 0. There will be no output. If en is 0, no matter whatever that is there at the input, output will always be 0. It will not look at select line, it will not look at select line, it will not look at this I0 I1 input. If en is 0, en means en is equals to c. If your c is 0, better I should write c here. If c is 0, then this circuit is not working. So how you can write down the output? If a is not there, then answer will be 1. Plus if a is there, then answer will be b, with the condition that your c should be 1. This should be 1. Then only this will be the output. Dot c. So this is the final expression. So your final expression will be, this can be expressed a bar plus ab. A bar plus ab can be written as a bar plus b dot c. So your final expression becomes a bar c plus bc. Are you getting this point? If c is 1, then only this circuit will work. So if c you are putting 1, then only this will be your output. If you are putting c equals to 0, then output will be 0, because c is 0. So 0 multiplied with anything will be 0 only. So you need to put c equals to 1. And we are expressing it in terms of SOP. This is product term, right? So if this is product term, then c is the normal form and c bar would be the complemented form. Now what do you understand by this? Here en bar is written. What they could have done? They could have put a bubble here as well. So again we need to understand this is active low enable. This is what? Active low enable. So if c is equals to 0, then it is perfectly working. If c is equals to 1, then it is not working. We will see this one first. We will see this symbol. Or they could have written bubble here, or they could have only put a bubble. Mostly this will be written. There is very high chance that this will be written. They can put a bubble here as well. They can frame this thing. That bubble here is there and En is there. Or they can only frame the En bar and no bubble. En bar plus bubble, En bar plus bubble, and En plus bubble. These three conditions can be there. So whenever you see bubble, that means it is active low, and whenever you see bar, that means it is active low. If both are together, then also it is active low. Like people can think that sir, En bar is there plus bubble is also there, so bar and bubble can get cancel out, so it is active high. No. In GATE examination, 2 to 3 times the question has come. Even in GATE 2024 as well, the question came, and people were saying that En bar is there and 0 is there. So both should cancel each other and it should work as enable button. No, it doesn't happen like that. En bar is there plus bubble is there, still it is considered as En bar only. So you need to take care of this. Okay. That means this is our active low input. So if C is 0, then our output will be working, and if C is 1, then output will not be working. Okay. So without making the truth table, let's write down the final answer. What that would be? If A is not coming, if A is 0, then output will be 1, and if A is 1, then output will be B. A bar into 1 plus A into B, with the condition that your C should be 0. C should be 0. So if C should be 0, that means I will write C bar here, because if C is 0, then C bar would become 1, and C bar would become 1, and 1 is multiplied with this expression. That means this will be the output. If C is 0, then your circuit is working. If C is 0, then your circuit is working. So C0 in min terms, how will you write it? C bar. So A bar plus AB dot C bar. And here also you can put, if you put C equals to 0, what you will get? A bar plus AB, C equals to 0, so C bar will be 1. So this is what you get, and this is what you want. If C is 0, your circuit should be working. So here you will write C bar. Okay, and how it can be reduced? A bar plus B dot C bar. So it would be A bar C bar plus B C bar. Okay, so that's the final expression. Okay, so that is the meaning of enable button. We will use it again and again. So here I have explained it. So active high enable, active low enable. Okay, let's use mux as a universal gate. So using the mux, you can make all the basic gates, universal gates, and arithmetic gates. So let's try making NOT gate. What you need to make? NOT gate. Y is equals to A bar you need to make. How will you make it? Y is equals to A bar. That means with A bar you need 1, and with A you need 0. If A bar is coming, then what you will pick? I naught. Basically, you write your output Y as A bar. If A bar is coming, I will pick I naught. If A is coming, I will pick I1. So if A is coming, you will pick I1. That's it. This is your inverter. If you need to make buffer, how will you make it? Buffer. Let's write down buffer gate. Try making it on your own. I will directly write down the answer, because here you just need to use your brain. If you are not using your brain, then digital electronics will not come to you, because digital electronics is the aptitude of electronics engineering. This is all about aptitude. Okay, what do you think? What should be the value of I0 and I1? I0 should be 0 and I1 should be 1. Because why? If A bar is not coming, if A bar is coming, that means if A is not coming, so I can say if A bar is there, I will pick 0. If A is there, I will pick 1. So Y is equals to A. So this is your buffer gate. So can you just remember that in inverter, I0 will be 1 and I1 will be 0. Basically 0 is 1 and 1 is 0. So opposite is there, no? So it is inverter. And here 0 is 0 and 1 is 1. So same is there, so it is a buffer. So kind of you can remember it, or it will take 2 seconds to get to know it is a inverter, right? Because if A is 0, A bar into 1. So basically it is inverter only. A into 0 sorry, a bar into 0 plus a into 1. So this is a buffer. Or you can just see, okay, 1 is there or 0 is there, that means this is an inverter, this is a buffer. AND gate you need to make, y is equals to ab. So if a is coming, I need b, and if a bar is coming, I need nothing. If a is coming, I need b. If a bar is coming, I do not need anything. So y is equals to ab, right? What about y is equals to a plus b? So if a is coming, I need 1. But if a bar is coming, what do I need? I don't know that, because there is b as well. So somehow in the expression, that is y is equals to a plus b, I need to introduce a bar. How I can introduce it? I can write b into a plus a bar, because a plus a bar is 1. So here there is b into 1 only. So a plus a bar, because I want to introduce a bar. So a plus ab plus a bar b. So from here you are getting a into 1 plus b, that would be a only. So a plus a bar b. So a plus a bar b is a plus b only. So now you get to know that if a is coming, I need 1, and if a bar is coming, I need b. That's it. So this is your OR gate. Similarly, what about this? What is this? AB bar. So it can be written as a bar plus b bar. You know about a bar, but you do not know about a. So I need to introduce a somehow. So there I have introduced a. So this is a bar plus a b bar plus a bar b bar. So a bar you can take common from these two. A bar you can take common from these two. So you will get a bar plus a b bar. So if a bar is coming, you need 1, and if a is coming, you need b bar, right? Let's think about NOR gate. Later on I will have to copy it, so just keep it copied. So yeah, let's talk about NOR gate. So NOR gate can be written as a bar dot b bar. I will always try to write it in SOP form. When I am solving the problem of Muxes, I will write it in SOP form. Why so? Because answer are in SOP form only, no? A bar dot I naught, A dot I1. Answer are in SOP form. So I will write it in SOP form only. So if a bar is coming, that means I need b bar, and if a is coming, I need 0. Okay. So in the same manner we are proceeding. Nothing different we are doing. What about XOR gate? So for XOR gate, directly we can see here. If a is coming, I need b bar, and if a bar is coming, I need b. If a bar is coming, I need b, and if a is coming, I need b bar. So this is your XOR gate. What about XNOR gate? This is your XNOR gate. So if a is not coming, I would need b bar, and if a is coming, I would need b. Okay, if a is coming, I would need b. So here the answer is a bar, b bar plus ab. But one thing is there, like we have mentioned b bar here, in this as well we have mentioned b bar, right? Here we did not mention, here we mentioned b bar. So how will you get this b bar? So for b bar as well you can use a mux. Like the user can say that I have only the literals, that is a and b. I only have a and b literals, I do not have their bar. So you can make bar as well, no? Simply use the mux as an inverter. How do you use mux as an inverter? I naught I1. This is your I naught, this is your I1. So I naught should be 1 and I naught should be 0, and this is your b. What you will get from here? B bar. So you get this b bar and then you connect it here and this will work. Okay. The similar thing you can do here. So making NOR gate will take 2 cross 1 mux. Making NAND gate will take 2 cross 1 mux. Like in the examination or in the interview, if they are asking make NAND gate using 2 cross 1 mux. So first you will make this b bar and then you will connect this b bar here, and then you can say, sir, this is my final design. Like you will make it more beautiful. Basically you will pick this one here and you get the output b bar, directly you will connect it here, and then you can say, sir, this is my final expression. Okay. Now implement the following function using only mux, and mux you need to use, that is 2 cross 1 mux. Okay. And the expression is, 2 expressions are there. This is first question and this is second question. In those questions there are 2 more questions, that is first you need to take a as a select line and then you need to take b as a select line. In these questions as well, it could be given that take b as a select line and make all these gates. Like you need to take B as a select line. Let's just say this question is there and you need to take B as a select line. How will you solve it? Select line should be B. Here directly I took select line to be A. Anything I would have taken it. So if my select line is B, so that's my question now, and this is I0, this is I1, and this will be my output Y. This will be my output Y. So if B bar is coming, I would need A bar, and if B is coming, I would need 0. So that would be my answer. That's it. Select line could be anything. Here also I could have make it, right? If B is coming, I would need A bar. So here I would, sorry, if B bar is coming, I would need A bar. If B bar is coming, I would need A. So here I would have picked A. Here I would have put A bar, and this A would be replaced with B. Okay, very easy. Now this is the question. What you need to implement? A bar B. So I am implementing A bar B. A bar B using A as a select line. And now I only need to use mux only. I only need to use mux because they are saying using only mux. I don't have any inverter or anything like that. So if this is I0, this is I1, what I need to make? A bar B. So if A bar is coming, I would need B, and if A is coming, I would need 0. So this is my output, A bar B, right? Now let's implement the same thing using select line as B. Select line as B. So select line is B now. This is I0 and this is I1. So if B is coming, I need A bar. If B is coming, I need A bar, and if B bar is coming, I would need A. So is that the correct answer? No. Here did you use any inverter here? No. You had A available, you had B available, certainly 0 will be available. But here you have B available, here you do not have A bar available. So you need to make A bar. How will you make A bar? Very simple. Because I have A available with me. I have A available with me. This I will pick I0, this I will pick I1, this I will pick 1, this I will pick 0. So if A bar is there, I will get 1. If A is there, I will get 0. So A will not come, only A bar will come. So this is the A bar. From here you get A bar, and from here B bar is coming, you get 0, and B is coming, then you get A bar. So this is the answer, B A bar, or you can say A bar B. So only using our what do we say, mux only we have designed it. But here I had to use A as a select line. This I had to use. Okay, there was no other option left. I had to use A as a select line. So if I need to make A bar B, then what is a better design for me? This is the better design for me, because here I have to use 2 muxes. And how do I decide which is the better design for me? I need A bar. In my design I need A bar. So which select line I should use, A or B? Select line I should use as A. Why so? Because select line has the capability of giving bar as well and the simple form as well. Are you getting my question? What I am saying? So your manager is asking you, go design A bar B, go design a function A bar B, and try to use minimum number of mux, because if mux are more, then cost will be more and power consumption will also be more. So try to use minimum number of mux, and what you need to design? You need to design A bar B. So what should be your select line, A or B? You will pick select line as A, because the select line has the capability that first it will give you A bar with I0, and then it will give you A with I1. If I had picked B, so it would give me B bar and B. But I do not need B bar. What I need? I need A bar. If I do B bar and B, I am only left with A. I am not having A bar. But actually I need A bar. So from here directly I am getting, no, so only one mux, using only one mux I have implemented it, but here I need to use 2 muxes. Okay, so these kind of important points will come in next lecture. There we will see it broadly, but here I am giving you a feel. The target is to solve the problems here, but just a kind of feel I am giving so that you could connect the next lecture. So that is very important actually. The next lecture is very important for your interview perspective as well, and for your this gate examination perspective as well. Next, what you need to implement? A plus B bar. So you need to implement A plus B bar. So let's use A as a select line. If I use A as a select line, I have the problem. Why I have the problem if I am using A as a select line? Because I know what will come with A, but I do not know what will come with B bar. So I have to solve it. A plus B bar, what I can add? A plus A bar. So A plus AB bar plus A bar B bar. This is A plus A bar B bar. So now I know with A what will come? 1 will come. This is I know, this is I1. So with A 1 will come, and with A bar B bar will come. B bar will come. So now you have to make B bar. So what we can do, we can put this analysis somewhere here for now, and now I need to make B bar. So B bar should be made. So I will use B here, right? This is your I naught, this is your I1. I will put opposite, one I naught as 1 and I1 as 0. So what I will get? B bar and then this. Okay. And if I had to use B as a select line initially, so A plus B bar only I am making. So y is equals to A plus B bar. I know what should come with B bar, but I do not know what should come with B. So this I had to do, right? So it would be AB plus B bar, right? Very easy. So if B is there, this is I naught I1. So if B bar is there, this should be 1. If B is there, this should be A. So that's it. B bar into 1, B into A. This is your output Y. So that's the final expression. This is the final design. So in this one, you only need to use 1 mux, and here you need to use 2 mux. Why is that so? Because here you needed B bar, which mux has the capability if you use it as a select line. If you use B as a select line, mux has the capability of giving you B bar. So that's why here you use here you choose only 1 mux, but here you need to use 2 muxes, right? Let's solve this question. Now you will say that, sir, you said that only 1 output can be there for mux, but here there are 2 outputs. There is only 1 output. This output is just simply complemented. Nothing else is there. Output is F1 only, but this is just a complemented output. Okay. So what would be your F1? What do you think? F1 will be C will go here and C will also go here. So if C is not there, you will get 0. F1, let's write down F1. If C is not there, you will get 0. And if C is there, you will get D. If C is there, you will get D. So F1 is CD. So what this would be? CD bar. Very easy. This would be CD bar, and that is going here. This would be CD bar. This is your CD. What about this one? What about F2? F2. If C is not there, you will get D bar. And if C is there, you will get 0. So what is your F2? If C is not there, in the examination you will write it very quickly. You will not do this thing. If C is not there, you will get D bar. So this is your, actually this is going here. So this is your C bar, D bar. And what about F2 bar? F2 bar, or this can be written as C plus D bar whole bar, right? C plus D whole bar. So F2 bar would be C plus D only. F2 is C plus D whole bar. So F2 bar would be C plus D, right? Now what about output Y? If A is not there and B is not there, then CD. If this is your MSB, right? So if A is not there and B is there, that means it is 0, 1. So it will take C bar, D bar. Sorry, CD bar, it is CD bar. Plus, if A is there and B is not there, basically it is 1, 0. So it will pick C bar, D bar. And plus, if AB both are there, then it will pick C plus D. Okay. So better let's write down the output somewhat above. This is CD whole bar. So I can write it as C bar plus D bar, right? This is CD whole bar. It can be written as C bar plus D bar. This is CD whole bar. It can be written as C bar plus D bar, right? So Y would be equals to A bar B bar CD plus A A bar B, A bar B, C bar plus A bar B, D bar plus A B bar, C bar, D bar plus A B C plus A B D. Okay. So minterms would be 0 0 1 1 because A is MSB. 0 1 0 0 0 1 0 1 0 1 and D bar is 0. 0 1 D bar is 0. So this should be 0, this could be 1 as well. Because here C is not there, so C can take both of the values. Here D was not there, D can take both of the values. What about the next one? That is G1, sorry, it would be 1 0 0 0. What about this ABC? ABC is 1 1 1. D can have value 0, D can have value 1 as well. What about ABD? Out ABD. So 1 1 0 1 and 1 1 1 1, right? ABD 1 1 0 1 1 1 1 1. So this got cancelled. And what about others? Anything is getting cancelled? No, let's check out. This is 3, this is 4, this is 5, this 4 4 are being repeated, this is 6, this is what, 13, right? This is what, 8, this is 14 and this is 15. So what are the minterms you are having? 3 4 5 6, 3 4 5 6, 8, 13, 14 and 15. So these are the minterms you are having, right? Okay, well and good. Let's see some delay based problem. Okay, now we are going to see delay based problem. So Mux has a switching delay of 1 microsecond. Switching delay of 1 microsecond. Comment on V naught. Although 4 option will be mentioned, but here why should we mention the option? We should have the concept. What is the select line here? Select line is directly connected to the output. So this is your V naught. So let's try writing V naught. What will be V naught? V naught will be, if V naught is not there, then it would take 1, and if V naught is there, it would take 0. So your V naught is equals to V naught bar. Do you see anything here? What is that? Remember chapter 1? Output is connected back to the input. This is your V naught. I should not extend it. There is no meaning of that. So V naught goes in, you get V naught bar. Then V naught bar goes in, you get V naught. So what is this? This is A stable multi vibrator. Multi vibrator. Only one inverter is there. 1, 3, 5, 7, 9. These number of inverter could be there, right? A stable multi vibrator. What else you can call it? Ring oscillator. What else you can call it? Pulse wave generator also you can call it. Pulse wave generator. So initial value of V naught I don't know. Let's just say if initial value of V naught was 0. So next value would be 1. Next value would be 0. Next value would be 1, 0. So this is a pulse wave generator. Okay. And if we started from here, this has the delay of 1 microsecond. So for 1 microsecond it would be 0. Then for 1 microsecond it would be 1. Basically you will start from here. You are starting from here. Okay. So this was 0. This 0 will come here. This 0 will come here. It will give you 1 after 1 microsecond. So this will take 1 microsecond. Now this 1 will come here. It will give you 0 after 1 microsecond. So this will take 1 microsecond. 1 microsecond. So all these windows are 1 microsecond. So what is the time period? What is the time period? Time period is 1 by 2 into total delay. What is the total delay? That is 1 micro. So that is, sorry, time period. Time period. Why I am putting 1 by? Time period is 2 microsecond. 2 into total delay. 2 into total delay is 1 microsecond. If you remember this, we have already studied in chapter 1. That's why I am dealing it quickly. So answer is 2 microseconds. So what is the frequency? That is 1 by 2 megahertz. So 0.5 megahertz. This is frequency of oscillations. So if someone is asking you, this particular question is given and find the frequency of oscillation, answer would be 0.5 megahertz. Let's solve this question. This is your output y. Y is going here. What you will get? If y is 1, if y is coming, then 1 would be there. If y is not there, then 0 would be there. So output will be y only. Select line is y, output will be y only. So what do you think? What is this? Buffer. What about this? This y is going here. If y is not coming, that means if y bar is there, then 1 will be multiplied. If y is there, then 0 will be multiplied. So this will be your y bar. So with y select line you are getting y bar. What is this? This is a NOT gate or inverter, I should write. This is an inverter, right? What about this? This y bar is there. You can see I1 is connected to 1, I0 is connected to 0. So 0 is connected to 0, 1 is connected to 1. So rightly I can say this is buffer. Here I could have said 1 is connected to 0, 0 is connected to 1, inverter. 1 is connected to 1, 0 is connected to 0, buffer. So what is this circuit? This circuit is simply, first there is a buffer, then there is an inverter, then there is a buffer. So odd number of inverters are there in the loop. In the loop there are odd numbers of inverter. If there are odd numbers of inverter, what does it mean? That is, it is a stable multivibrator or ring oscillator, you can say stable multivibrator. And what all are the delay? 5, 7 and 8. So what would be your answer? What do you think? What will be the frequency of oscillations? Frequency of oscillation will be 1 by 2 into total delay. Total delay is, never forget this 2. A lot of time people forget this 2. They will just add up the delay 1 by that delay. That they will do. But you need to remember 0 will come for that much time, 1 will come for that much time. Then again 0 will come for that much time, 1 will come for that much time. Okay, so that you need to remember. So 12 1 by this total delay is 20 nano, right? 20 nano. Yeah, 20 nano. So answer would be 1 by 40 nano. 1 by 40 nano can be written as 1000 mega by 40. 10 to the power 9 would go upward, so 10 to the power 3. So it would be 25 megahertz, right? It would be 25 megahertz. So that is the correct answer. So these kind of questions can come in your examination. This has come in GATE examination. Okay, this has also come in GATE examination only. This has also come in GATE examination. Comment on y. Tell the frequency of oscillations. Tell whether it is a stable multivibrator or not. So comment on y. So let's start commenting. Y will come directly here. Y will come here. This is your y. Output is connected here, and this is your y bar, right? And S is fixed at 1. S is fixed at 1. So what will be your output y? S is fixed at 1, so you only need to care about y bar. So 1 into y bar. So y is equals to y bar. But how much time it will take to give the output? First, this comes at t equals to 0. Let's just say y is equals to 0 at t equals to 0. So after 5 nanoseconds, this will be 1. After 5 nanoseconds, this will be 1. And after 20 more nanoseconds, it will become bar of that. That means it will become, yeah, directly it will come, sorry. Basically, at t equals to 0, y is equals to 0. At t equals to 0, y is equals to 0. After 5 nanoseconds, this has become 1. After 20 more nanoseconds, this 1 will come out. Basically, whatever that is there, y is equals to I1. The thing is, y is equals to I1. Y is equals to I1. And I1 is y bar. So if y is equals to 0, after 5 nanoseconds, this will be 1. And after 20 more nanoseconds, this 1 will come out. Now this 1 is there at 25 nanoseconds. Now at 30 nanoseconds, this will become 0. At 30 nanoseconds, because 25 plus 5, 30 nanoseconds, this will become 0. And after 20 more nanoseconds, this 0 will come out. So basically it would be 15 nanoseconds. So for 15 nanoseconds, there is 0. And for 25 nanoseconds, there is 0. and for 25 nanoseconds there is 1. Then again this cycle will keep on being repeated. So basically you need to calculate the total delay in reaching at the output. 5 nanosecond plus 20 nanosecond, that would be 25 nanosecond. From here you are going, let's remove it off. So 5 nanosecond this will take and 20 nanosecond this will take. So this is 25 nanosecond. And this is 25 nanosecond. So this is a pulse wave generator. What is the frequency of oscillation? That would be 1 by 50 nanosecond. And it can be written as 1000 mega by 50. That would be 20 megahertz. Now let's copy this question again. I can frame one more question from here. Yeah, so if I change the question in this manner, I have changed this question in this manner. This particular circuitry is given. You need to comment on y again. So what will be your y? S is equals to 1. S is fixed. S is fixed. So it will look at only I1, right? And what is I1? I1 is y only. So y is equals to y. Basically this is a buffer, right? Y is equals to y. This is a buffer. This is your y. And the same way it will keep on going. So this is a buffer. So what kind of multivibrator is that? There is no oscillations, right? Because always y will be equals to y only. Always y will be equals to y only. So no oscillations is there. So it cannot be a stable multivibrator. Because like I am asking you this question because I know a lot of people would have forgot what is astable, what is monostable and what is bistable. Because people forget it. That's why I give the analogy there. If you remember by analogy, you will remember it for a longer time. Otherwise, you will forget it. So it is not a stable multivibrator. In a stable multivibrator, there is no stable state 10 10 10. So what is that? Monostable or bistable? What is monostable? Monostable means there is only one stable state. So if it is 1, for a momentary time it can be 0, then again it will be 1. And what is bistable? If it is 1, there will be 2 stable states. Bistable means 2 stable states. If it is 1, it will be 1 only. But if you apply some trigger and if you make it 0, it will always be 0. So let us say if my y was initially 1, so it will always be 1. But if I apply some trigger here, and make it 0, then it will always be 0. And again if I apply some trigger, let us say I break it and put 0 here, so it will be 0, always 0. And if I again apply the trigger, it will be again 1. So if you have forgot the concept, then I would recommend you to go and study astable multivibrator again, multivibrators again. So this is your bistable multivibrator. There are 2 stable states. So y is bistable multivibrator. So you will be getting confused in monostable and bistable. So in digital electronics, you will never see monostable multivibrator. For momentary time, there is no unstable state. Whether it is 1, then it will be 0. Then if you give a trigger, it can be 1. Okay, so this is a bistable multivibrator. Okay. Let's see the next question. Next question is also very interesting. Propagation delay question is there. 2 questions we will solve. So propagation delay of XOR gate, AND gate and multiplexer in the circuit shown are 4 nanosecond, 2 nanosecond and 1 nanosecond. So XOR gate 4 nanosecond. Okay. AND gate 2 nanosecond. 2 nano, 2 nano, 2 nano and mux is 1 nano. Mux is 1 nano. All inputs PQ RST are available simultaneously. That means all the inputs are available at given time, that is t equals to 0. All the inputs are available at t equals to 0 and held constant. The maximum propagation delay of the circuit is. So what is the select line? How to solve these kind of problems? Select line is t. Select line is t. So now t could be 0 as well and t could be 1 as well. If t was 0, if t was 0, it would have taken this value. And to get, and if t was 0, it would have taken this value and this value. Now this value will take here, it will take 4 nanosecond. So t has to wait 4 nanosecond to get this output, at least 4 nanosecond. Are you getting this point? Look, t is 0. So now after 4 nanosecond something will come here. Before that there is nothing. So after 4 nanosecond Q and R will be XOR and will give you something here. So 4 nanosecond, and mux will take time of 1 nanosecond to give the output. So after 5 nanosecond you will receive some output here, and after 7 nanosecond you will receive something here. But you do not need to look this one, you need to look here. So here you can see that if t is 0, if my t is 0, then this input will be available after 2 nanosecond only. If my t is 0, this input will be available after 2 nanosecond, because from here p will come, here q will come, and after 2 nanosecond it will be available. So just as it sees the input, it will give that to the output. So 2 nanosecond plus 1 nanosecond, it will take 3 nanosecond. Are you understanding this point or not? First put t equals to 0. If I am putting t equals to 0, then if I look at this mux and then I need to look at this mux. So always look at the final mux. So this final mux, what this final mux is saying, that if your t is equals to 0, then I need to look at this, and when this will be stable, this input is stable after 2 nanosecond. So if this input is stable after 2 nanosecond, so after 2 nanosecond this mux has the capability of giving the output. So 2 nanosecond and mux will take 1 nanosecond to give the output. So answer will be taken out at 3 nanosecond only. Although this bit will become stable after 7 nanosecond, but answer I can take after 3 nanosecond only, because if t is equals to 0, t will not look at this, t will only look at this. So if t is equals to 0, your delay is coming out to be 3 nanosecond. So is this should be the answer? No, wait a second, because you do not take the condition of t is equals to 1. Let's take the condition of t is equals to 1 now. This was 1 nanosecond and this was 2 nanosecond. Okay, so if t is equals to 1, t is equals to 1, so I will always look at the final mux. So this will wait for this one, t is equals to 1, so it has to wait for this input to come. Now after how much time this input will come? Here t is equals to 1, right? Here t is equals to 1, so it will look at this. So after 2 nanosecond this will become, and after 3 nanosecond this will be the output. Look, if t is equals to 1, it will look at this. So after 2 nanosecond this input will be stable, and after 2 nanosecond mux has the capability of giving the output, but it will take 1 nanosecond more to give the output. So 2 nanosecond plus 1 nanosecond, so this will be 3 nanosecond. And what about this input? Because you need to look at AND gate now. This is your AND gate. So this input is available at 3 nanosecond, and this input is available at 2 nanosecond only. This input is available at 2 nanosecond only. So when the gate will give the output, when this AND gate will give the output, after 3 nanosecond or 2 nanosecond? Basically this gate was there, this input was available at 2 nanosecond, and this input came after 3 nanosecond. So output will depend on both of the inputs, no? So it will give output after 3 nanosecond. So this AND gate has the capability of giving output after 3 nanosecond, but it will take 2 more nanosecond. So this has also had the delay of 2 nanosecond. So after 3 nanosecond this input is stable plus 2 more nanoseconds. So this output will be stable at 5 nanosecond. Now at 5 nanosecond this mux has the capability of giving the output. At 5 nanosecond this mux has the capability of giving the output. So how much time it will take? 1 nanosecond more it will take. So output will be stable at 6 nanosecond. So for t is equals to 0 and t is equals to 1, both you need to check. So you just need to make the path, that's it. For t is equals to 1, delay will be 6 nanosecond. Now if you go to some user and you tell him that, sir, the delay of my circuit is 3 nanosecond. You go to the user and tell him that, sir, delay of the circuit I have designed, that is 3 nanosecond, and he put t equals to 1. So how much delay he will get? 6 nanosecond. Then he will fire you, right? Your job will be lost. So delay is defined always as the maximum delay. That, sir, maximum delay could be 6 nanosecond. Now delay you can get 3 nanosecond as well or 6 nanosecond, but maximum is 6 nanosecond. So if they are asking what is the delay of the circuit, then you need to pick the maximum one. So delay of the circuit is 6 nanosecond. Now you can go to the user and you can tell him that, sir, the delay of my circuit is 6 nanosecond. So he will apply the input 0. He can get the output in 3 nanosecond only. So he will be happy because delay is 6 nanosecond that he don't want, but still some delay is there, and you give him the specification that 6 nanosecond is delay, and he is getting output in 3 nanosecond only. So he is happy, and now he applies the input 1. He gets the output after 6 nanosecond. Then he is also happy because you said that the delay is 6 nanosecond. Okay. So when delay is there, you always need to pick the maximum one. So what is the maximum one? Maximum one is 6 nanosecond. So answer would be 6 nanosecond. Okay. Let's remove these off which are not required. So in that manner you need to solve t equals to 0 and t equals to 1. Let's see the next question which you need to solve on your own. Okay. So now let's solve this question. So these data are given, delay of all the gates are mentioned, and mux delay is also mentioned. The same question is there, you need to find the maximum delay at the output. So the same way I will approach. First I will put t equals to 0. So if I put t equals to 0, so if I put t equals to 0 here, what I will get here? 1 I will get. After 1 nanosecond, this input 1 will be stable after 1 nanosecond, right? And this will be stable at t equals to 0 only. So this 0 will look for this one, like, but this 1 will look for this. Now you need to look at this and this. So this 0, this is t equals to 0, is looking for this. This will be stable after 2 nanosecond and this will be stable after 3.5 nanosecond. And since this is looking for this only, so it has to wait for 3.5 nanosecond, because after 3.5 nanosecond only this will be stable. So before that mux doesn't have the capability of giving the output. So 3.5 nanosecond plus 1.5 nanosecond. So delay for this is 5 nanosecond. Are you getting this point? This input is stable at 1 nanosecond, right? So from 1 nanosecond it is waiting that when this input becomes stable. After 1 nanosecond, this is there, this guy is standing there and he is waiting. Just as it becomes stable, my mux will have the capability of giving the output. So it is becoming stable after 3.5 nanosecond. So it has become stable now. Now mux has the capability of giving the output, so it will take 1.5 nanosecond more. So 3.5 nano plus 1.5, 5 nanosecond is the total delay. For t is equals to 0. Let's check for t equals to 1. And before going there, let's just say if this delay was 4 nanosecond, if this delay was 4 nanosecond, then tell me what will be the delay at the output. If this delay was 4 nanosecond, then what will be the delay at the output for condition t equals to 0? What would be the answer? 5.5 nanosecond, right? Because this input will become stable after 4 nanosecond. So this input has already become stable, but mux will say that I do not even know whether I want to give this as output or this as output. So after 4 nanosecond, the mux will get to know that my S naught is 1. That means I need to give this output. So after 4 nanosecond, mux has the capability of giving the output. Now mux can make a decision that I need to give this output. So after how many seconds? 4 nanoseconds. So 4 nanosecond plus 1.5 nanosecond, that would be 5.5 nanosecond. If this delay was 4 nanosecond, but here this question is easy. The delay is 1 nanosecond only. Okay. So delay kind of problems are basic aptitude problem only. You just need to think that when the device has the capability of giving the output. That's it. Okay. Let's check the other case. 2, 2, 2, 1. These were given. Okay. Now t is equals to 1. Now if t is equals to 1, so this input 1 will become stable at t equals to 0 only, right? And this will become 0 at t equals to 1 nanosecond. At t equals to 1 nanosecond. So this has to look here. I will look at the final one. This has to look here. Now after how much time this will become stable? That we need to know. So p will come here as it is. Now can I say that this what is this gate? This NOR gate has the capability of giving the output after 2 nanosecond. Can I say this thing? No, I cannot say, because the output of this NOR gate will depend on this input as well. So when this input becomes stable, that I get to know, that I need to know now. So if this is 1, that means it will look here. So this becomes stable after 1 nanosecond. So after 1 nanosecond, mux has the capability of giving the output. Now mux will take 1.5 nanosecond more. So after 2.5 nanosecond, this will be stable. So now after 2.5 nanosecond, this NOR gate has the capability of giving the output. So 2.5 plus 2. So this will be 4.5 nanosecond. Right? This will be 4.5 nanosecond. So after 4.5, this point is 2.5 plus 2, 4.5 nanosecond. So now this will look at this input only. So after 4.5 nanosecond, this has the capability of giving the output. After 4.5 nanosecond, this mux has the capability of giving the output. So that will be 4.5 plus 1.5. So t is equals to 1. So delay would be 4.5 plus 1.5. That would be 6 nanosecond. So what will be the answer? This would be the answer. That's it. Okay. So now our this part is completed, and in the next lecture onwards we will move towards this implementing lower level mux from higher level mux, or implementing higher level mux from low level mux. So that we are going to see in the next video. So that will be a very interesting video as well, and very important as well. Okay. So in mux everything is important. These kind of questions are also important. So let's meet you in the next video. There we see about implementing more mux from some mux only. Okay. Hi everyone. So let's see this topic now. Now we will implement muxes from muxes. Okay. So first we will implement lower level mux from a higher level mux. So usually this topic is not taught, even in the textbook you will not find it, but just sometimes interviewer can ask these kind of things just to puzzle you. So it is a very simple thing that you need to make 2 cross 1 mux from 4 cross 1. So this is given. The question is, it's not that you need to make 4 cross 1 from 2 cross 1. You need to make 2 cross 1 from 4 cross 1. So you have 4 cross 1 and you need to go to 2 cross 1. This is the question. Okay. So what is the scene in 2 cross 1? In 2 cross 1 there are number of inputs are 2. In 2 cross 1 number of inputs are 2. So you need only I0 and I1 input. And select line is only one, which is S, and this will be your output. So this select line I want, and I0 I1, and this will be Y, and this is your 2:1 mux. So this is what I want. So what I would do, I will keep this as ground, right? I will keep this as ground. Why do I keep it this ground? Because now S can take 0 value. If S takes 0 value, S1 is already 0. S takes 0 value. Look, S1 I have kept a ground. This is always 0. Now S can take 0 value. If S takes 0 value, what will be the output? I0 will be the output. So what will be your Y? Y will be S0. If S0 is not there and S1 is already 0. If S0 is not there, you will simply get I0. If S0 is not there, you will simply get I0 because S1 is already 0. Plus, if your S0 is there, you will get I1. Basically, if this is 1, then you will get I1. That's it. There is no use of I2 and I3. I2 and I3 I don't care here, and this will be the output. Y is equals to S0 bar I0 plus S0 into I1, and this is what you get in this one. So you have directly implemented 2 cross 1 from 4 cross 1. Very straightforward concept, right? And you need to make 2 cross 1 from 8 cross 1. What you will do? That's it. Now all these are 0. S2, S1, S0. These are 0, 0. Now just this will change the values. So it can take, this will be decimal value 0, this will be decimal value 1. That means it can take only I0 and I1. So what will be your Y? So if S0 is not there, then I0 will be there. And if S0 is there, then I1 will be there. That will be your Y. So using only one mux, you can create any lower level mux from higher level mux easily. Using only one mux. If you are having 8 cross 1, you can make 2 cross 1 and 4 cross 1 as well. 4 cross 1 also you will be easily able to make. How will you make 4 cross 1? You will keep S2 equals to 0. If you keep S2 equals to 0 and you keep varying S1 and S0. So very easy thing. Okay, sometimes like you might get puzzled. Okay, what they are asking. Now what is usually asked, this is that you need to implement higher level mux from a lower. So now let's start studying about implementing higher level mux from the lower level mux. Now this is an important topic. You need to implement higher level mux from a lower level mux. That means you are given 2 cross 1 mux, you need to make 4:1 mux. So you are having 2:1 mux, and this is what you need to make. So for 4 cross 1 mux will have 4 input line, right? They will have 4 input line. 4 inputs line. 1, 2, 3, 4. They will have 4 input line. Now what do you have? You have 2 cross 1 mux only. So 2 cross 1 mux can take only 2 inputs line, right? So for 4 input line, you require 2 cross 1 mux. This will have its own select line, and this will also have its own select line. Now what do? They will generate 2 outputs. Each one will generate one output. So total 2 output will be there. Total 2 outputs are there. So 2 outputs are there. Which will be fed to another 2 cross 1 mux, because 2 cross 1 mux can take 2 inputs. You wanted only one output, no? So finally this will give you one output. So this is how you implement 2 cross 1, 2 cross 1 and another 2 cross 1, right? So this will all will have their own select line. So this is this complete diagram, if we say this complete diagram with the select lines, basically you can extend these select lines. नहीं होगी भाई. So if I extend these select lines, so with this complete diagram is your 4 cross 1 mux, right? This is your complete 4 cross 1 mux. So there are two select lines, S0 and S1. Which one will be S1? Which one will be S0? Okay, you tell me. Which one will be S1? Which one will be S0? This one will be S1 and these two ones will be S0. Why is that so? Look, I am considering this is your I0 and basically there are 4 inputs line, no? I0, I1, I2, I3. So if this is 0, this will be taken. And if this is 1, this will be taken. This is what I am considering. This is how I have written it. Okay, and basically this is your I0 dash and this is your I1 dash. So let's just say this is my input S0, S1. This is my input. So if I put 0 0, I should expect I0. Let's see if I am getting. If S1 is 0, then it will look at this. If S1 is 0, this will look at this. So this will look at the output of this mux. So if S0 is 0, what you will get here? I0. So at output you will I0 only get. Basically S0 is 0, so this will give I0, this will give I2, but what S1 will look? S1 will look at I0 dash only, so output will be I0. If S1 is 1 and S0 is 0, sorry, if S0 is 1 and S1 is 0, if S1 is 0, again it will look here only. And what is S0? S0 is 1, so if S0 is 1, I1 will come here and that will be that will be your output. If S1 is 1, S0 is 0. If S1 is 1, it will look here. And S0 is 0. If S0 is 0, that means I2 will come here and that will be fed to the output. S0 is 0, that means I2 will come here, and S1 is 1, so it will look here only. So I2 will be fed to the output. Are you getting this point? So here you are getting I2, here you are getting I1. In the last case, you will get I3 only. So if S1 is 1 and this is also 1, so I3 will come and will be fed to the output. So always keep this MSB bit of select line near to the output. MSB bit of select line near to the output. Bit of select line near to the output. Okay. Now, so how many muxes were required? 3 2 cross 1 muxes were required. Now there is another way of finding it. How will you do it? You need to find 4 cross 1 from 2 cross 1, right? So what you will do? 4 divided by 2. 4 divided by 2. What you are getting? 2. Now this 2 again can be divided by 2. 4 divided by 2, what do you get? 4 divided by 2, what do you get? 2 to the 4. So 2 you are getting. Now this 2 can again be divided by 2. What you will get? 1. 1 cannot be divided by 2. So forget about this one. Okay. So just as you are getting 1 in your answer, you need to stop there. So 1 you will not write. If you are getting 1 in your answer, you will stop there. Basically 2 by 2 is 1. So stop there. So 4 by 2 is 2 plus 2 by 2 is 1. That's it. 3 muxes are required. What did we do? We saw this number, we saw this number. 4 by 2. If we do 4 by 2, we get 2. So plus 2. Again divide by 2. What we get? 1. Again divide by 2. But just as we are getting 1, we are not going to look at this. This 1 we are going to ignore. So 2 plus 1, that is 3 mux required. So in that manner you can find. Let's see this question. For this question, how many mux will be required? What do you think? 8 by 2. What do you get 8 by 2? 8 by 2 is 4. So 4 is again divisible by 2. 4 by 2. 4 by 2, what that will be? 2. So 2 is again divisible by 2. Basically here I am not calculating anything, not writing down anything. Just writing 8 is divided by 2. What do we get? Plus 4 we get. 4 is divided by 2. What do we get? 2 we get. 2 is divided by 2. What do we get? 1. 1 we are not going to write. So here 4 plus 2 plus 1. Basically, how many are there? 7. So what does it tell actually? In 8 cross 1 mux, there will be 8 inputs. So to take 8 inputs, you require 4 2 cross 1 mux. To take 8 inputs, you require 4 2 cross 1 mux. To take the 8 input. So 1, 0, 1, 2, 3, 4, 5, 6, 7. Basically 0 to 7. So I0, I1, I2, I3, I4, I5, I6, I7. Okay, this bit we will see which bit will be what. So how many outputs are there? 4 outputs are there. Now to take 4 outputs, you need another 2 cross 1. Basically there are 4 outputs. No, there are 4 outputs. There are 4 outputs. 1, 2, 3, 4. So 1 can take only 2. So you need another 2. So this is what it shows. So I need another 2 now. So here I am getting another 2. Okay. So now these two will generate 2 outputs. Right. Now what do I need? To take these 2 outputs, I need another 2 cross 1 mux. So this is that one. So this is how 7 are required. Okay. Now these will have the select line, all will have the same select line, and these will also have the select lines, and these will also have the select line, and finally you are having output. Now which one will be what? There are 3 select lines, right? S0, S1, S2. S2 will always be near to the output. So this will be S2, this will be S1, and these will be S0. Why is that so? Let's look at this. Let's put sorry, it should be the other order, like S2 is the MSB, S1 and then S0. If I take 0 0 0, so if S2 is 0, it will look at this, right? If S1 is 0, it will look at this, and if S0 is 0, it will look at this. So I0 will travel here and go there. Let's take a random example. 1 0 1. What do you expect? 1 0 1. What do you expect? I5, right? I5 you will expect. In 8 cross 1, if 1 0 1 is there, what you will expect from here? I5, no? 1 2 4. Yeah, I5 you will expect. So let's see if we are getting it or not. So what is the value of S2? S2 is 1. Let's remove it off. S2 is 1. So if S2 is 1, it will look at this. What is the value of S1? S1 is 0. If S1 is 0, it will look at this. Here also something will come, but output of this is being fed here, but this is of no use. What we need to see, if S1 is 1, it will look at this output, and this output will be coming from this mux. So I am looking at only this mux only. So if S1 is 0, you will get this output. Now this output will come from this mux, so I will look at this mux only. Now S0 is 1. If S0 is 1, what you will get? This I5. So I5 will travel to the output. So our this value is correct. Let's take another example, 0 1 1. So if S0 S2 is 0, 0 1 1. If S2 is 0, it will look at this. Now I will look at this one, this mux only, because output I am not getting from this mux, I am getting from this mux. So that's why I will look at here only. Now if S1 is 1, if S1 is 1, this will come. And if S0 is 1, if S0 is 1, then I3 will come. So I3 will travel in that manner, and this is I3 only. So always this will be near to the output. Okay. how many muxes will be required? 2 cross 1 to make 16 cross 1. So 16 is there and 2 is there. 16 by 2. What you will get? 16 by 2, 8. 8 by 2. What you will get? 4. 4 by 2. What you will get? 2. 2 by 2. What you will get? 1. 1 we are not going to write. So this is 8 plus 4 plus 2 plus 1. What that would be? 15. So basically for 16 is to 1 mux. For 16 is to 1, 2 is to 1 required were 15. For 8 is to 1, 2 is to 1 required were 7. You can see it. 7. And 4 is to 1, 2 is to 1 required were 3. Right? 3. So for 2 to the power n is to 1, how many 2 is to 1 will be required? 2 to the power n minus 1. Let's take an example. You need to make, you can see it, no? 15, 7, 3, 2 to the power n minus 1. You need to make 256 cross 1 from 2 cross 1. From 2 cross 1. So how many numbers will be there? One thing you can do is that 256 divided by 2, what you will get? 128 divided by 2, 64. 64 can also be divisible by 2. 32. 32 again divisible by 2. 16 again divisible by 2. 8 again divisible by 2. 4 again divisible by 2. 2 divisible by 2, but you will get 1. So that's it. This is how you can calculate what this number will be. Can you tell me? It will be 255. Basically 1 less of this number. That's it. 1 less of this number. So this number will be 255. Very easy. Right? No issue about this. 2 to the power n minus 1. Just this number is there, minus 1. This number was 8 minus 1. This number was 4 minus 1. So there will be 255 will be required. Okay. And if I directly need to write, this was example 1. If I take another example, 1224 is to 1 from 2 cross 1. How many would be required? 1023. Okay. So in that manner, I will be able to write down. Now you need to implement 16 is to 1 from 4 is to 1. So how many those will be required? So the same thing you can do. 16 divided by 4. What you will get? 4. 4 is divided by 4. So 4 by 4 is 1. So next rest you are not going to do. So 16 divided by 4 is 4. Plus 4 divided by 4 is 1. So answer is 5. You can see it. How? 16 is to 1 will have 16 input line. And 4 is to 1 will have 4 inputs line. So it can take 4. It can also take 4. It can take 4. And it can also take 4. So 4, 4, 4, 4 they can take. So all can take 4, 4, 4, 4. Now how many outputs line were there? Will be there. Output lines will be there, will be 4 only. So only 4 outputs line will be there. And all these 4 can be taken by a 4 cross 1 mux. Because 4 cross 1 mux has the capability of taking 4 inputs line. And then this will be the output. So this is 4 is to 1, 4 is to 1. Now this is 4 is to 1, it will have 2 select lines. And they will also have 2 select lines. Right? All select lines will be same only. Basically select lines are S3, S2, S1 and S0. So which one will go where? MSB ones. S3 S2 will go here, S3 S2, and LSB1 S1 S0 will be here, S1 S0 will be here. These two are the MSB ones. So MSB and near to MSB, S3 S2 will go here, and you can take an example. Okay, let's start taking example. Let's take a random example. 1 0 1 0. What do you expect? I10. Where will be I10? 0 1 2 3 4 5 6 7 8 9 10. This we will be expecting. Let's check that out. So if S3 S2 is 1 0, S3 S2 is 1 0, S3 S2 is 1 0, 1 0, 1 0 means 2. So they will be 1 0 means I0, I1, I2. So they will be looking at this, and S1 S0 is 1 0, S1 S0 is 1 0, S1 S0 is 1 0. That means this is also equals to 2. So I0, I1, I2, they will be looking at this. So this will travel down to this one. So correct answer you are getting. Let's take another example. 0 1 1 1. So S3 S2 is 0 1, S3 S2 is 0 1. That means they will be looking at 1. Where is 1? This is 1. 1 1. If S1 S0 is 1 1, that means they will be looking at this. So this will be traveled. So this you will get as the output. At output you will get this. And what is this? I0, I1, I2, I3, I4, I5, I6, I7. So this is I7. Was the 7 only? Yes. So you are getting the correct answer. Okay, so MSB bit will always be near to the output, right? Just like this, I0, I1 in that manner, I2, I3, I4, I5, I6, I7, I8, I9, I10, I11, I12, I13, I14, I15. Okay, so in that manner you are writing the output. So this is your complete 16:1 mux. This was your 4:1, and this was your output. Okay, let's see the next one. Make 8:1 mux using minimum number of lower level mux. If I make 8:1 mux from 2:1 mux, so how many will be required? 7. So 7 will be required. This number is 7. But what they are saying, using minimum number of lower level mux. So I will try to make it from 4:1, right? 8:1 mux from 4:1 mux. So what I will do? 8 divided by 4. Now 8 is divisible by 4. 2 is coming. What does that mean? That basically there will be 8 divided by 4. 8 is divisible by 4. So what is left? 2 is left. So it will have 8 inputs. So one 4 cross 1 can take 4 inputs, and it will generate 2 outputs. It will generate 2 outputs, and these 2 outputs can be taken as an input by 2 cross 1 mux. This is 4 cross 1. This is 4 cross 1. So 2 4 cross 1 will be required. 2 4 cross 1 will be required to take 8 inputs. Now they will generate 2 outputs, which can be taken by 1 2 cross 1. So 8 divided by 4, what do you get? 2. You know that this can be divisible by 2. That means 2 4 cross 1 mux are required, plus 1 2 cross 1 mux is required. Now tell me one thing, if in the examination it is written that 8 cross 1 mux can be made by 2 4 cross 1 mux and 1 2 cross 1 mux. Is that statement correct? Yes, it is correct. Now if in the examination it is written like that 8:1 mux can be made from 3 4:1 mux. Is that statement correct? In the exam they are asking how many 4:1 4 cross 1 mux you require to make 8 cross 1 mux. So what you will do? 8 divided by 4. What we are getting? 2. Now you know this 2 can be implemented using 2 cross 1 mux, right? But certainly it can be implemented using 4 cross 1 mux as well. If some function is being implemented using 2 cross 1 mux, then certainly it can be implemented using 4 cross 1 mux as well. No, like there are two outputs line are there. So I will keep these as it is. I will keep this as grounded. and I will use only these two. This thing I told you here, no? So that's why I told this thing here. Now you are getting the point that you can make 2 cross 1 from 4 cross 1 any day. So if this here you can get your work done using 2 cross 1 mux only, then certainly 4 cross 1 mux will do the job. So this statement is also correct, right? Because 2 cross 1 mux can certainly be made from 4 cross 1 mux. So this statement is also correct. They were asking minimum number of lower level mux. So two possible answers are there: 2 4 cross 1 and 1 2 cross 1 mux, or 3 4 cross 1 mux. So here also you are using 3 mux only, 2 plus 1, and here you are using 3 mux only. So two possible answer would be there. Okay, I hope you must have understood it. So like this is the best case, but sometimes in the question paper this can also be written that first you will do 8 by 4, then you will get to know that there are two lines. So using 4 cross 1 mux also I can make, using 8 cross 1 mux also I can make, using 60:1 mux also I can make it, right? Make 13:1 mux from 8:1 and 4:1 mux such that the MSB bit of select line should go to 8:1 mux. MSB bit of select line should go to 8:1 mux. What do you think? How we should start? Look, if I start like this, 32 by 8, that means first I am making 8. First I am making 8 cross 1 mux. Those will required will be 4, because 8 here, 8 here, 8 here, 8 here. Total 32 inputs. So total 32 inputs it can take. So this is what I am doing. Then what I will be left with? 4 outputs. And these 4 outputs can go to 1 4:1 mux. 1 4:1 mux. So MSB bit will be here, and it will be fed to the 4 cross 1 mux. MSB bit is here and it will be fed to the 4 cross 1 mux. But what do you want? That MSB bit should be fed to the 8 cross 1 mux. So this design you do not want. So what you want? Initially there should be 4 cross 1 mux should be there. So you will require 8. You will require 8 of such kind, right? If there are 8 like this, so this will take 4, 4, 4, 4, 4 into 8, 32 input will be taken, and all will generate outputs. So how many outputs will be generated? Since they are 8, so 8 outputs will be generated. So 8 outputs will be generated. Now it can be taken by 8 cross 1 mux. Here you can see 32 by 4. What you will get? 8. 8 is simply divisible by 8 only. You can make it from 4 4 as well. Like 4 you use here, 4 you use here. This is also you can do. But final stage I want 8 cross 1 mux only. So final stage I want 8 cross 1 mux only. So basically there are 8 4 cross 1 mux. So what I can write? 8 4 cross 1 mux and 1 8 cross 1 mux. And let's write down the final design in some good manner. 1 I will make, 2 I will make, and directly 8th I will show. And then 8 input lines are there. So this is 4 cross 1 only. So total 8 are there. And this is your 8:1. So only 1 is there. Now all will be fed to the input here. So 8 input lines will be there. Right? This will be I0, I1, and finally it will be I7. Now these will have 3 select lines, and these will have 2 select lines. Now what all select lines will be there? S5, S4, S3, S2, and S1. So these 3, maximum 1 will be fed to this S5, S4, S3. And what about these 2? S2, S1. Shall we take any random example? Yes, we can take any random example. 1, 0, 1, 1, 0. So what that would be? 1, 2, 4, 8, 16. So you will be expecting 16 plus 4, 22. At the output you will be expecting 22. Okay. So what is written? 101. 101 means this is your 101. 101 means I5. So it will be looking at I5. 5. From here it will be looking at 5. Okay, like it will be very tough to show here because another one 4x1 mux I will have to show here, right? And then this is your 1 0. 1 0 means it will be looking at 2. So this bit will be coming. In fifth block, third bit will be coming. Fifth block, third bit. So 4 here, 4 here. In fifth block, third bit. So that means 23rd bit is coming. And what is 23rd bit? I22 only. And that is correct. If you are able to understand it, if you are able to visualize it, I am interested in I5. So that means I am interested in fifth block of 4x1. Fifth block, third bit, because here it is 1 0. 1 0 means 2. So 0, 1, 2. So fifth block, third bit. Fifth block, third bit. What that would be? 22 only. Right? Because each are having 4 4 input. So it will end at 3, then 7, then 11, and then 15, and then next will end at 19, and next will end at 23. So 23 is the last bit. I3 it is. So I want I2. That means I want 22. So 22 will be fed. And this design is absolutely correct. No issue about that. Okay. So in that manner you can make your design. Yeah. So one more question is there. Yeah. This is a question, you should try it on your own. Cost of a 2 to the power n cross 1 mux is 3 to the power n rupees. Basically 2 cross 1 mux will cost you 3 rupees. This question I made on my own only, not copied from anywhere. And 4 cross 1, which is 4 cross 1 mux, will take you 3 square rupees. That means it would be of rupees 9. 4 cross 1 mux will be of rupees 9. This will clear a lot of concept of yours. 8:1 will take how much rupees? 3 cube. That is 27 rupees. 16:1 mux will take how much rupees? 3 to the power 4. That is 81 rupees. And let's take the final one, that is 32 cross 1. 2 to the power 5. How much it will take? 243 rupees. Okay. Let's start. You need to design the mux such that the cost of your design is minimum. Let's start with the first one. You need to make 32 cross 1 using 8 and 4. 32 cross 1 using 8 and 4. So this 4 cross 1 is costing you 9 and 8 cross 1 is costing you 27. So you would want to use 8 cross 1 mux minimum. So let's try doing it. If I start from 8, so 8 4 is 32, 4, right? So you would need 4 here and 1 here. These 4 are 8:1 and this one is 4:1. So this is not a good idea because 4 into 27, this will be 108 rupees. This is costing you 108 rupees and this will cost you 9 rupees. Right? So 108 plus 9, total 117 rupees it will cost you. Doesn't seem like a good idea. If I go by, first I go by 4 and then by 8. So first 32 by 4 is 8. So this is costing us 8, 4 cross 1 and 1, 8:1. Okay. So 8 into 9, 72, and this has the cost of 27. 72 plus 27. This is costing you 99 rupees. So this would be a better design, right? But this is not the best design. We have other options as well. This was option A. Let's check for option B. So this is not a good design. It is costing me 170 rupees. This is costing me 99 rupees. So this could be one of my possible design, but let's check these. Use only 2 cross 1 mux. So 32:1 from 2 cross 1. How much it will take? How much it will take? 31, right? You know it, 31 it will take. Say yes or no? 32 is to 1 from 2 is to 1. 31 it will take. So 31 and each is costing you 3 rupees. So 31 into 3, 93 rupees. So certainly you are getting lesser than this. So this option is cut. Option A is gone because this is the minimum. So till now this is minimum. Okay. These options are there 117, 99 and 93. So till now this is minimum. So this option is gone. This option can never be correct. It is not minimum. What if we get even lesser than 93? Let's check that. Option C. 4 is to 1 and 2 is to 1. So 32 is to 1 is there. We have option 4 is to 1 and 2 is to 1. If I do 32 by 4, 4 is 32. Then again I do by 4 only. So 4 to 8 and then I do this. So 8 plus 2, 10. This I have done by 4, this I have done by 4, this I have done by 2. 32 by 4, 8 you get, 8 by 4 you get 2, 2 by 2. So 8 is to 10, this is 4 is to 1 plus 1 is 2 is to 1. So 10 into 1 is taking you how much rupees? 9. 10 into 9 plus this will take how much rupees? 3 rupees. 10 into 9 plus 3 rupees. So this is also taking 93 rupees. One of the option is again matching. That this is also taking 93 rupees. But this can be done by other designs as well. What could be the other design? Let's assume that I start with 2 only. So what I will get? 16 here. Then let's just say I am just going blindly, like you can make it from 4 now. 4 plus 4 by 4. So 16 plus 5. 16 2 is to 1. 16 2 is to 1 plus 5 4 is to 1. So 16 into 3, what that would be? 48 plus 5 4 into 1. 5 4 into 1. 45. So again this is also taking us 93 rupees. So you can try all other combination as well. I have tried everything in rough notebook. So in all the combination you will get 93 rupees as well. Or here also you are getting 93. Right? Let's check option D. 16 is to 1 and 2 is to 1. So option D. 32 from 16 is to 1 and 2 is to 1. So 32 by 16, what you will get? 2. And 2 is divisible by 2. So how much you require? 2 16 is to 1. 2 16 is to 1 plus 1 2 is to 1. So 2 16 is to 1. How much it will cost you? Very much high rupees. 16 is to 1. 81 into 2. 81 into 2, that would be 162. And this will cost you 3 rupees. So total 165 rupees it will cost. So this is not also feasible. So option B and C are correct. So option B and C are correct. Okay, see the last one. Last one I hope you must have understood. 32 is to 1 from 16 is to 1 and 2 is to 1. So 32 I am starting from 16. So 32 by 16. 32 by 16 plus 2 by 2. So 32 by 16 you will get 2. 2 divided by 2. So this can be implemented from 2 is to 1 and this can be implemented from 16 is to 1. So here you will require 2 and here you will require 1. So 2 16 is to 1 you require and 1 2 is to 1 you require. So best design are B and C. So that's it about this video. That's it about this concept as well. I hope you must have found it interesting and you will be able to implement any mux from any other mux. Right? It's not a tough task. It is a very easy task, very straightforward task. Right? So let's meet you in the next lecture. Next lecture is going to be very important. There we will implement any random Boolean function from the mux. Any random Boolean function from the mux. So how should we define select lines and how should we define the inputs I0, I1, I2, I3, I4, I5, I6, I7. So that I am going to tell. So for there are certain patterns. So two kind of cases we will see. So that let's check that in our next lecture. Okay. Thank you very much. Hi everyone. So let's see this topic now. Very important topic. You need to implement logical expression using mux. So for gate examination it is also very important. Like in every year if they are asking questions from the mux, then they will certainly pick this topic only. So you need to implement logical expression using mux. So there will be two kind of cases. In first case, number of variables that I am denoting as n, number of variables will be equals to the number of select lines, and here number of variables will be more than the number of select lines. Here you will solve it by using minterms. Here you will make implementation table, and this I have written input of the mux will be either 0 or 1. This also you will understand. So no need to mug up this table or anything. Just see the examples and then you will be able to understand everything. So this is the first one. You need to make a bar. So this we already know. So here 0 should come and here 1 should come. This will be our a bar. How many number of variables are there? 1. How many select lines are there? 1 only. What are the input? Either 1 or 0. Let's make this one. F is equals to AB. Number of inputs are 2. Number of select lines are 2. So select lines, number of select lines are 2. So in select lines I will put A and B. I will put A and B. In select lines I am putting A and B. This is your I0, I1, I2, I3, and this will be your output Y. Now I know A bar B bar is, when A bar B bar comes, this should be 0. When A bar B should come, this should be 0. When A B bar comes, this should be 0. And when AB comes, this should be 1. So that my output is AB. Or how I should have solved it using minterm. So F is equals to AB. So what is the minterm for this? M3, right? So M3 is there, so only I3 should be 1, rest all should be 0. Basically, what is your Y? Y is A bar, B bar, I0. Again, I am writing everything. A bar B I1 plus A B bar I2 plus AB I3. So A bar B bar is M0. A bar B bar is M0, right? A bar B bar 0 0. It is M0. M0 I0 plus M1 I1 plus M2 I2 plus M3 I3. You need only M3 to be 1. You need only M3 to be 1. That's it. Your Y should be equals to, you need Y equals to I3. Sorry, you need only I3 equals to 1, not M3. You need only I3 equals to 1. Rest all should be 0. So Y should be equals to M3. For that, your I1, I2 and I0 should be equals to 0 and I3 should be equals to 1. So that's why I put this in this one. So what you can do, you directly write down the minterms. M3 minterm is there. So only I3 should be 1, rest all should be 0. That's it. That's all other question. What is F equals to AB? What all minterms are there? First thing is that you will see number of variables that are 2, A and B. How many select lines are there? 2 select lines are there, right? So you can solve it by using minterms. So how many minterms are there? What is this? What will be the minterms for this? F is equals to AB. F is equals to, A plus B. F is equals to A plus B. I can see that max term is 0 because A is 0, B is 0. So max term is 0. So what will be the minterm? Minterm will be 1, 2, 3. Minterm will be 1, 2, 3. So 1, 2, 3. These will be 1. And these will be 0. That's it. You can check here as well. Like if A bar B bar is coming, 0 should come. That means it will not come. Basically A bar B bar into 0 plus A bar B into 1 plus A B bar into 1 plus AB. So here you can see this is 0 and A bar B as it is. You take A as common. So if I take A as common, so B bar plus B will be 1. So A plus A bar B, that would be equals to A plus B only. So just write down the minterms. You get to know 1, 2, 3 are the minterms. So these will be 1s, rest should be 0. That's it. Okay. What are the minterms for this? Do you need to make K-map? This is a very famous expression. What do we call it? When we study half adder, it will again come to us. Okay. So what all are the minterms for this? 3, 5, 6, 7. This is majority number of ones detector. If you remember it, majority numbers of ones detector. So 3, 5, 6, 7. You can derive it using K-map, but minterms are 3, 5, 6, 7 only. or you can derive it using this a, b, c bar, c. But I told you this is a very famous expression, so we need to remember it. This is a self-dual function, and there are other expressions as well, which we will write down. So we will see that this is a very famous one. So 3, 5, 6, 7, 3, 5, 6, 7. Rest all will be 0. That's it. This is how you can write your output. Here also number of this will work only if number of variables and select lines are equal. Number of variables and select lines. So this is the first thing you need to check. Here number of variables are 4 and select lines are also 4. So that will work. So that method of minterms would work. So all here you will get 1 or 0. So let's check what all minterms are there. So I will do it using K-map. C, wherever you see is there, you can get the minterms right like this, right? C bar, D bar, C bar, D bar, ABD, ABD, ABD. That's it. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So all these will be 1. 0 will be 1, 2, 3, 4, 6, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this will be the input. In the examination you will not be doing sir A bar, B bar, C bar, D bar, no. Just get them in terms, put these values. Now you will say sir how they will ask in gate examination, because in gate examination MCQs should come. They can ask these values, no, in option they will put I0 will be equals to 1, I2 will be equals to 0, I3 will be equals to 1. So these kind of things they can put in the options. Then you need to pick one of the option. And in the interview they will ask you to do the design. Now see this question. How many variables are there? 3. Using 4 cross 1 mux, how many select lines are there? 2. So now interesting thing will come. So here number of variables are 3, select lines are 2. So here what you will make implementation table. Okay. So now you need to make implementation table. So I will just make a rough 4 cross 1 mux. So these will be the select lines and these will be the inputs. Inputs will be 4, I0, I1, I2, I3, and one of the output will be there. We will be again and again using this 4 cross 1 mux. 4:1 mux. I0, I1, I2, I3. Select lines are S1, S0, and this is your output Y. So let's see the first question. In first question, you need to take AB as a select line. So how will you proceed in these kind of problems? AB as select line. So select lines are AB. So now these are not in our control. What is in our control? Function is of ABC. So AB are the select lines. They will take their value 0, 0, 0, 1, 1, 0, 1, 1. So AB is not in our control. In our control, C is there. So I will write C is equals to 0 and C is equals to 1. What all inputs are there? I will write I0, I1. You will realize why I am doing so. I2 and I3. Now, how will you get I0 when AB is equals to 0, 0? How will you get I1 when AB is equals to 0, 1? Right, because A is MSB. When AB is equals to 1, 0 and when AB is equals to 1, 1. Now, A is equals to B, sorry, A, B, C. A is equals to 0, B is equals to 0 and C is equals to 0. That means this will show minterm 0, right? This will show minterm 0. A is equals to, in this row I am going. A is equals to 0, B is equals to 1 and C is equals to 0. This will show minterm 2. Look, for this C is equals to 0 and AB is equals to 0, 1. For this AB is equals to 1, 0 and C is equals to 0. So this will show minterm 4. Say yes or no? Because in the function this is your MSB and this is your LSB. So in that manner only I am writing here. So 1 0 0 will show 4, 1 1 0 will be 6, 1 0 0 will be 4, 1 0 1 will be 5, 1 1 0. Sorry, some error I am doing. Sorry. This would be 0 0 1. Really sorry. 0 0 1, 0 0 1, 0 0 1. So this will be 1. What about this? 0 1 1. This would be 3. So now I can see a pattern 0 1 2 3 4 5 6 7. This is how it will be repeated because A B 1 1 1. So whenever you are writing down these values, no, you will see a pattern. You 0 1 2 3 4 5 6 7. So this is the pattern. Now what all minterms are there which I need to find? What all minterms are there? 3 5 6 7. 3 5 6 7. So I will mark on 3. I will mark on 5. I will mark on 6 and I will mark on 7. What does that mean? That from here only C should come. Here is marked, no? This is marked here. So that means C should come because C is equals to 1. Here C is equals to 1. From here as well only C should come because C is equals to 1. Here C and C bar both will come. If there is a mark on both, that means it should be 1. C plus C bar should be 1. And here there is no mark, so this should be 0. So I0 value should be 0. I1 should be C. This should be C and this should be 1. You can check it out. You can check that out. What that would you look? This is the method. This is the way we solve. C is equals to 0, C is equals to 1. I0, I1, I2, I3. AB is equals to 0 0 0 1 1 0 1 1. Okay. Write down the minterms 0 1 2 3 4 5 6 7. What all minterms you need? 3 5 6 and 7. So 6 and 7 both you need. That means C plus C bar you need 1. Here only C you need because this represents C and this will represent C bar, right? In minterms. So C only. Here C only and here nothing is there, so 0. So this is how you need to write it and you can check it. So what will be your Y? Y will be A bar B into C plus A B bar into C plus AB. So here you can see AB will come as it is and C I can take common, so A bar B plus AB bar. So AB plus C A XOR B. This is your Y, right? And Y is same only because we have seen this in our first lecture that it can be written as AB plus BC plus CA, right? This we have already seen in our first lecture itself. Did I tell you this or not in the first lecture? I hope I have told it as far as I remember. Yes, I remember I have told it. AB plus CA XOR B can be written as AB plus BC plus CA. There are other expressions as well. It can be written as A plus B into B plus C into C plus A as well, right? There are a lot of expressions. Let's solve the next problem. Not next problem, sorry, next part of this. You need to take BC as a select line. So select lines are BC. Select line is BC. So what is in our control? In our control, A is in our control. So A is equals to 0, A is equals to 1. I0, I1, I2, I3. BC can take 0 0 value. If it takes 0 1 value, it would be 1. If it takes 1 0 value, it would be 2. If it takes 1 1 value, it would be 3. And B as MSB, C as LSB. So B as MSB, C as LSB. Basically select line. In select line, B will be MSB and C will, this will be S1, this will be S0. This is what they are saying. Okay. Now 0 0 0 0 1 0 0. This is A is 1, B and C are 0. A, B, C. A is 1, B and C are 0. So 4. A is 1. Sorry. If I go in this one. So A is 0, B is 0, C is 1. So this would be 1. What about this one? A is 0, B is 1 and C is 0. So this would be 2. So pattern I can see 0, 1, 2, 3, 4, 5, 6, 7. Hey, let's check for this. So A is 1, B is 1 and C is 0. So 1, 2, 4, this is 6 only. 0, 1, 2, 3, 4, 5, 6, 7. This is the pattern we have seen. Now 3, 5, 6, 7. Na? 3, 5, 6, 7. So 3, 5, 6, 7. So again the same thing we are getting. Let me check back again. 3, 5, 6, 7. Okay. So I1 should be A. I2 should be A and I3 should be 1 and this I0 should be 0. So if I make it in this manner, BC as select line, and 4 input lines will be there and 1 output line will be there. So starting from I0, I1, I2, I3. So 0, A, 1. That's the answer. Let's solve the third one. You should solve on your own. CA as select line, where C is the MSB. C is the MSB of the select line. For the function MSB is A only. For the function MSB is A only. No one is changing it. This is the LSB. But CA as the select line, where C is the MSB and A is the LSB. So this would be your C. This would be your A. Okay. So what is in our control? B is in our control. So B can take 0 value. B can take 1 value. I0, I1, I2, I3. So CA 0 0, CA should be 0 1, CA should be 1 0 and CA should be 1 1, then only you will get I3. Okay. Now for this ABC all are 0, so this will be 0. What about the next one? A is, I am checking here. Okay, A is 0, B is 1 and C is 0. So this is 2. Now I am checking here. So A is 1, B is 0 and C is 0. A is 1, B is 0 and C is 0. So that would be 4. I am checking here now. A is 1, B is 1 and C is 0. So 6. I cannot see any pattern yet. 0, 2, 4, 6. No pattern is there. Let's check for this one. So A is 0, B is 0 and C is 1. So this is 1. Let's check for this one. So A is 0, B is 1 and C is 1. So this would be 3. So there is no such pattern here, right? 0, 2, 4, 6, 1, 3. No such pattern. This would be 1, 1, 1. So this would be 7 and this would be 5. We can check here as well that A is 1, B is 0 and C is 1. So 1, 2, 4, 5. These are the minterms. Minterms I have written in ABC manner because our function is defined as this, where A is the MSB and C is the LSB. Now what do I need to mark? 3, 5, 6, 7. Again the same answer. In everything we got the same answer only. B, and this would be B and this would be 1. So 0, B, 1. Same answer should be there as well. Why it should be there? Because if you clearly remember, our F can be written as AB plus C A XOR B, or it can be written as AC plus B A XOR C, or it can be written as BC plus A B XOR C. So same expression only you will get. No? So for this, luckily all the expressions are same, but it will always not be same. Let's see this example. A, B, C, D. These are the minterms 0, 2, 4, 5, 7, 9, 11, 13, 14. Using 8 cross 1 mux. So here, how many numbers of variable is there? 4. How many select lines will be there? 3. So what is the select line? B, C, D. So A is in our control. A can be 0, A can be 1. I will write I0, I1. How many select lines will be there? 7, no? Sorry, not a select line. How many inputs will be there? 7 input will be there because it is 8 cross 1 mux. So I2, I3, I4, I5, I6 and I7. So BCD, these are the values of BCD. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 0, 0, 0, 0, 0, 0, 0, 0, 1, 1. This would be 2. This would be 3. This would be 4. 0, 1, 0, 0. This would be 5. 0, 1, 0, 1. 6, 7, 8, 9, 10, 1 0 1 0, 11, 12, 13, 14 and 15. So 0, 2, 4, 5, 7, 9, 11, 13, 14, right? So here what will come? A bar. Here what will come? A. Here what will come? A bar. A bar, 1, A bar. So that's the way we need to solve it. So if I make 8 cross 1 mux here, S1, sorry, S2, S1, S note, B, C, D as select line. So here they did not mention which is MSB, so I am by default taking this as MSB and this as LSB. Okay, they did not mention it, and these will be the inputs: I note, I1, I2, I3, I4, I5, I6, I7. So starting from I note, A bar, basically I note, here you can see it is A bar, here you can see it is A. So A bar, A, A bar, A, A bar, 1, A bar. That's it. That is it. Okay. Let's see the next one. Number of variables 4. Select lines. Oh, wait a second. ABC as select line. I forgot this one. ABC as select line. So I need to add a page. So ABC as select line. Second one is ABC as select lines. So what is in our control? B is equals to 0 and D is equals to 1. I note, I1, I2, I3, I4, I5, I6, I7. ABC 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. So this will represent 0 only. What this will represent? 0 0 1 0, 0 0 1 0. This will represent 2. What this will represent? 0 1 0 0. This will represent 4. So better I should go here. 0 0 0 1. This will represent 1. So in this manner we are going. What this will represent? 0 0 1 1. This will be 3. ABC is 0 0 1 and D is 1. So this will be 3. So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 0 1 2 3 4 5 6 7 12 13 14 15. So what all I need to mark up? 0 2 4 5 7 9 11. 0 2 4 5 7 9 11. 0 2 4 5 7 9 11 13 14. 13 14. This will give D bar, this will give D bar, this will give 1, this will give D, this will give D, this will give D, this will give D, this will give D bar. Okay, very important topic I would say. So like they will ask what should be the value of I3, what should be the value of I5 to implement this particular function. So it can take a lot of time, but if you solve by this method, it will not take much time there. Okay, so just solve it by this method. Let's see the next one. Number of inputs are 4 and select lines are 2. So you can do it on your own. You can still do it on your own. So now you are having 2 select lines and number of inputs are 2. So CD is a select line. Basically this is your mux, which is 4 cross 1 mux. So CD is the select line where I will assume C as MSB, S1 S note. I will assume C as MSB and D as LSB. So what is in our control? AB. AB is in our control. Now in the previous cases, D can take 0, D can take 1. But now AB can take 0 0, AB can take 0 1, AB can take 1 0, AB can take 1 1. and 4 inputs will be there, which will be I0, I1, I2, I3. What about CD? So CD can take 0 0, 0 1, 1 0, 1 1. So ABCD is our function where A is MSB here. So 0 0 0 0 0, 0 0 0 1 1, 0 0 1 0 2, 0 0 1 1 3, 0 1 0 0 4, 5, 6, 7, 1 1 1 0 0 0 8, 9, 10, 11, 12, 13, 14 and 15. In this manner we are going. So 1, 3, 4, 6, 8, 9, 11, 12 and 14. Right? Yeah. So what you are getting here? You can write down that it is, sir, A bar B plus A B bar plus AB, or you can say it is A plus B only. Look, if these are the minterms 4, 8, 12, then what will be my max term? Max term will be this. What is that? A plus B only, or you can solve it, you will get A plus B only. What about this? This would be A bar B bar, this would be A bar B bar plus A B bar. So it would be B bar only. A bar B bar plus A B bar, it would be B bar. What about this? A bar B, A bar B, A bar B plus AB. What you are getting? B only. And what about this? A bar B bar plus A B bar. We are getting B bar only. So these were same. What about this? A bar B plus AB. A bar B plus AB. So you will get B only. And here you are getting A plus B. So what is the input? How will you define the inputs now? So I0, I1, I2, I3. So CD is there. So I0 is A plus B. I1 is B bar. I2 is B. And I3 is B bar. So that's how you will make it. And in the examination they will ask like this, these kind of minterms are given, what will be the value of I1, I0, I2 and I3. Take AC as select line. You are taking AC as select line. So BD is in our control. So BD is in our control. So BD is in our control. So BD can take value 0 0, 0 1, 1 0, 1 1, right? And I0, I1, I2, I3. What about AC? 0 0, 0 1, 1 1, 1 0, right? So 0 0 0 0 will be 0. Now A B C D is our function. So in this, if I go here, so here A is 0, C is 1, B is 0, D is 0, so it would be 2. So this is 2. A is 1, B is 0, C is 1, D is 0. 1 2 4 8 10. Not getting any pattern, let's move in this direction. So A is 0, B is 0, C is 0, D is 1, 1. Okay. If A is 0, B is 1, C and D both are 0. 1 2 4 4. Again not getting any pattern, let's move here. So that would be A is 0, B is 0, C is 1 and D is 1, 3. So it seems like that I am getting some pattern here, 0 1 2 3. So if I expect 5 4 5 6 7, is that correct? Let's check that. Let's check this point. What that would be? A is 0, B is 1, C is 1 and D is 1. Yes, 7 I am getting. So certainly this is the pattern. So I have got some pattern here, 10, 11, 12, 13. Let's check this 12 now. So here A is 1, B is A is 1, B is 1, C is 1 and D is 0. This is 10. So how did I write this as 10? In I2 there is some error, I guess. If A is 1, okay, this is 1, 1. If A is 1, B is 0, C is 1 and okay. Here what is the scene? A is 1. Oh, this is the opposite, no? What I am doing? This is 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. So let's check back again. A is 1, B is 0, C is 0, A is 1, B, C, D all are 0. This is 8. So 8, 9, 10, 11. This is what I can expect. So let's check this. So A is 1, B is 0, C is 1, D is 10. That is correct. So 8, 9, 10, 11. 8, 9, 10, 11. 12, 13, 14, 15. So some pattern I got, and because of that I was able to write down quickly. But otherwise I would have to spend a lot of time. Let's check for this 13. So for this 13, A is 1, B is 1, C is 0 and D is 1. So 13 only. Yeah. 1, 3, 4, 6, 8. 1, 3, 4, 6, 8. 9, 11, 12, 14. 9, 11, 12, 14. What you will get here? B bar D plus B D bar. That is B XOR D. Same goes here, right? B bar D plus B D bar. B XOR D. What about this? B bar plus D bar. Say yes or no. Or I can write BD bar. How did I do that? BD is equals to 1, 1. I am writing max term here. B bar plus D bar. Or you could have written B bar D bar plus B bar D plus B D bar. So what you would get here? B bar plus B D bar. So what you would get? B bar plus D bar only. But directly I wrote here B bar plus D bar. And here as well the same 11, 14. 11, 14. So here as well B XOR D. So at the 3 inputs you need to put B XOR D. So this will be your final design. 4 cross 1 mux is there now. So only 2 select line which are AC. Select lines are AC. And this is I0, I1, I2, I3. So B XOR D, B XOR D, BD bar, B XOR D. So the output will be these minterms only. Okay. So this is how you need to solve these particular problems. So I hope you must have understood the point here, how we are solving these kind of problems. So just we are writing A and B value and BCD values. A, B, BCD value. So in that manner we are going. And if number of variables and this select lines are equal, then it is very easy. Now this is the final conclusion point. What is that? So there is an important conclusion we have understood. Look, let's just say there is a mux and I am having 3 select lines A, B, C. So now using this mux I can implement any function. Why so? Because I have A as well, and this mux has the capability of giving me A bar, this mux has the capability of giving me B bar, and this mux has the capability of giving me C bar. Using only one mux, using only one using only one 2 to the power n mux, I can make any n variable function. Say yes or no? Because this mux can give me a bar, this mux can give me b bar, this mux can give me c bar. Everything is about like, what is the problem? Problem is not gate. If you can get the bar, if you can get 180-degree phase shift, no, that is the best thing in electronics. So if you can get a bar, then you can implement any Boolean expression. So if I am having 3 variables and 2 to the power 3 is to 1 mux, then I can implement any Boolean expression. So if this statement is written, what you will think? Okay, you are having 1 2 is to 2 to the power n cross 1 mux. That means you are having n select lines. And if you are having n select lines, it can give you the bar of n Boolean, it can give you the bar of n variables. You are having n select lines, so it can give you the bar of n variables. So you can make any n variable function. You can make any n variable function, right? Now using 2 to the power n minus 1 mux, let's just say I have a mux of 4 is to 1. I have the mux of 4 is to 1. So there will be 2 select lines. Here I can put AB input and AB select line, and in one of the input I can put C. So I can get the function of 3 variables. I can get the function of 3 variables, but I cannot generate C bar. So to generate C bar, I would need a NOT gate. If I am having a NOT gate, then I can generate C bar. I can surely generate A bar. I can surely generate B bar as well. So I can have A, B, C. I can have A bar, B bar, C bar. And if this is I am having, I can make any n variable function. So if I am having 2 to the power n minus 1 mux and 1 NOT gate. So if I am having 4 cross 1 mux and 1 NOT gate, then I can implement 4 can be written as 2 to the power 2. Then I can implement 2 plus 1, 3 variable Boolean function. Any 3 variable Boolean function. Any 3 variable Boolean function I can implement, right? What about this? If you are having 2 to the power n minus 1 is to 1 mux, then some n variable function can be made. Some n variable. Why is that so? Because you will not have this C bar. So you can certainly make 3 variable function, but the function that will involve C bar, that you will not be able to make. And if you are able to make the function that involves C bar, that means you are using AC as a select line, but you will not be able to make the function that involves B bar as a variable, right? And if you are able to implement that means you are using BC as a select line. So you will not be able to implement a function which will use A bar. So certainly one bar will be missing. So for that you need a NOT gate. If you are having a NOT gate and one variable less mux, you need to implement n variable, and you are having one variable less mux, then also you will be able to implement, but the condition is you should have a NOT gate. So if I am asking you the question, you are having 16 is to 1 mux. You are having 16 is to 1 mux. Can you implement all 5 variable functions with that? Can you implement all 5 variable function with that? No. Why so? Because you can get only 4 inverters, basically A, B, C, D, and A bar, B bar, C bar, D bar. You will not get E bar. But if you are having plus 1 NOT gate, then can you implement? Yes, I can implement. So that's the thing. Okay. So in the example, I will write just an example. 116 is to 1 mux plus 1 NOT gate is equals to any 5 variable function. This is the first one. Second, 132 is to 1 mux is equals to any 5 variable function. Why so? Because 32 is to 1 mux will have 5 select lines. If there are 5 select lines, then I can get 5 bars. If I can get 5 bars, then I can implement any 5 variable function, right? Any 5 variable function. Third one, 116:1 mux. Then you can write some 5 variable function and all 4 variable functions. All 4 variable functions. All 4 variable functions you can make. Okay then. So yeah, that's it. That's the complete chapter of multiplexer. And I hope you enjoyed the lecture. I hope you have understood every single thing in multiplexer. We will see an assignment, but before that we need to wait for one more video. There we will study about demux. So in the next video, complete demux will be completed, and after that we can solve one assignment. Okay. So let's meet you in the next video. There we study about demux. Thank you. Hi everyone. So in this video we will start studying about demux. So a very easy topic, and I would say it will set the base of our next topic, that is a decoder. So let's start studying demux. Okay, so it is a single input and many output device. It is one to many circuit. That means there will be one input and many outputs will be there. So it is just the opposite of a multiplexer. In multiplexer, what was the scene? 2 to the power n cross 1. So there were 2 to the power n input and 1 output with n select lines. So here n select lines are there, one information would be there, and these many 2 to the power n would be the outputs. So these are total 2 to the power n outputs. 2 to the power n outputs. Okay, let's see one by one, and it would be more clear to you. What would be your 1 cross 2 demux? This is your 1 cross 2 demux. So what it says, if S is 0, then information will be transferred to Y0 and Y1 will be 0 only. And if S is 1, then this information is transferred to Y1 and this will be 0. So how you can write Y0? So Y0 is, if S is not there, then your information is transferred. And what is your Y1? If S is there, then information is transferred. So this is your S bar I and this is your Si. I hope you are comfortable with that. What about 1:4 demux? So if S1, S0 both are not there, then this information will be transferred to Y0 and rest all will be 0. If this is 0 and this is 1, that means then information will be transferred to Y1 and here information will be transferred to Y2 because decimal equivalent is 2, and here information will be transferred to Y3. So how Y0 can be written? If S1 is not there and S1 is not there and S0 is not there, then information will be transferred. If S1 is not there but S2 is there, then information will be transferred. If S1 is there, S0 is not there, then information will be transferred. If both S1 and S0 are there, then information will be transferred. Can I write it? Can I write this as M0 I? If my function is of S1, S2. If something is a function of S1 and S2, then I can write M0 I. This I can write as M1 I. This I can write as M2 I. And this I can write as M3 I. Say yes or no. Right? Similarly for 1:8 demux, if S0 is not there, let's start from S2 only because S2 is the MSB. So if S2 is not there, S1 is not there and S0 is not there, then my information will be transferred. If S2 is not there, S1 is not there and S0 is there, then my information will be transferred. So basically I can write this as M0 into I, M1 into I, this would be M2 into I, this would be M3 into M4 into I, M5, M6 into I and M7 into I. Okay, so this is your simple demux. This is your 1:8 demux. Okay, very easy question, very easy thing. Now with the enable input, how will you write down output? Tell me. So forget about enable. So if S is not there, then information I will be transferred. But considering that enable is 1, considering that enable is 1, because this is what? Active high enable, right? Active high enable. And what about this? If S is there, then I will be transferred, considering that En is high. What about this? If S1, S naught both are not there, then information will be transferred. Considering that En is 0, because this is active low. This is active low. Considering that En is 0, so here I will put En bar. If En is 0, then this information will be transferred. If En is 1, the circuit will not even be working. If S1 is not there but S0 is there, then information will be transferred. If S1 there, S0 not there, information will be transferred. If S1, S0 both there, then information will be transferred. Okay. Now there is a question, you need to find all the outputs. Okay. A and B is there and this is I. So how I can write Y? If A is not there, B is not there, then I will be transferred here. If A is not there but B is there, I will be transferred here. If A is there, B is not there, I will be transferred here. And here this. Now I am taking, now how I can write this one? M0 into I, right? Now I am taking the bar. So if I take the bar of A bar, B bar into I bar, can I write it as X into, this is my X, this is my Y, X into Y bar, right? I can write it as X into Y bar, that can be written as X bar plus Y bar. So this can be written as A bar, B bar, bar plus I bar. Say yes or no? Are you getting this point? Now A bar, B bar can be written as A plus B bar. Very interesting result we are going to see here. It can be written as A plus B bar, and A plus B bar another bar. What that would be? M0. Basically A plus B, we are getting A plus B. A plus B whole bar got cancelled. A plus B plus I bar. So what is this? Capital M naught, right? Plus I bar. So here you are having M naught I, you are having M naught I, and if you took bar of this, what did you get? M naught bar plus I bar. And what is M naught bar? Capital M naught plus I bar. How M naught bar is capital M naught? Because if M naught is there, and if I am putting bar, that means M1 plus M2 plus M3, right? M naught bar means 0 will not be there, 1, 2, 3 will be there. And what does this mean? That my min terms are 1, 2, 3, then what will be my max term? M0. In the assignment problem, we saw a question like this, if you remember assignment 1. If M naught is not there, that means 1, 2, 3 are there. And if 1, 2, 3 are my min terms, then what will be my max term? This, right? So if the output of this is M naught I, then here output is M naught plus I bar. What will be the output here? M1 plus I bar. What will be the output here? M2 plus M2 plus I bar. And what will be the output here? M3 plus I bar. And what will be your M1? M1 will be A plus B bar plus I bar. Say yes or no? M1 means 0, 1. So A plus B bar plus I bar, right? What about this? A bar plus B plus I bar. A bar plus B bar plus I bar. So this would be your output. Now let's see a very interesting point, that is active low demux. Active low demux. This question that we have solved, that will be used here. Active low demux. So there could be other active low devices as well. When we study decoder, there will be active low decoder as well. Okay. So what do you mean by active low decoder? So what was, forget about this active low sign, forget about this sign. So what was the conventional way? If S was 0, I would be transferred to Y0 and Y1 would be 0. Just the opposite of, just the inverted of that will happen, because inverted sign is there, no? So if S is 0, information I will be transferred here, but inverter sign is there, no? So Y towards the Y0 I dash information will be transferred and Y1 value will be 1. If S is 1, then I information would have been transferred to Y1. This is my final Y naught. Here I am not writing Y naught. Basically, this I am not writing. Now, this particular thing is my Y naught only. So here there is something else. So what is that Y naught dash? What is that Y naught dash? That I know. What is that Y naught dash? That Y naught dash is, if S is not there, then I will be transferred. But opposite of that will happen. If S is there, then information I should be transferred here, but I bar will be transferred, and this should be 0, but this would be 1. Just consider this as an inverter only. This question and this question is same. There is just inverter connected. There is just another inverter connected, nothing else. Active low means active low demux. That means one another inverted connected, nothing else. Okay. So how will you write Y naught? So Y naught I can write S plus I bar. Say yes or no. And Y1 I can write S bar plus I bar. This is your Y1. So this is here. So S bar plus I bar. And for Y naught, how am I writing it? Look, what is my Y naught? Y naught would have been S bar I naught, right? Just take, so only information. So just take a bar of that. So S plus I bar. What about Y1? Y1 would have been S into I. Just take bar of that. What you will get? S bar plus I bar. Okay. So from here only we can write in this manner. Well and good. Or if you directly want to write it down from the max terms, from max term also we can write it down. So when it is I bar, I will not look at 1. If you remember the table, like we used to put here AB input and then the output, then there would be combination, and then these would be the outputs. Then I would only look at 0 if I am writing from the minterm. So I would write Y naught is equals to A plus B. So similarly, I will only look at the minterm, that is S. So I will not look at 1. But if let's just say in some question there is C available as well. So how will you write down the output of this? So A plus B plus 0 into A bar plus B bar plus C, because this is A bar, B bar plus C. Similarly, in this manner, S plus I bar, there is no 0 available again. And what about Y1? S bar plus I bar, because this is S bar. This will represent S bar and this will represent S. In max term, in max terms, right? If you are not able to understand this, forget it, no need to worry. You can derive it in this manner as well. Just consider a simple bar there, and you will be able to write it down. But you should have the concept clear. You should be able to write down if you are able to write down the output of this, then why not this? You are able to write down the output of this. Y naught will be A plus B. I am writing in POS form, A plus B plus 0. Output is 0. This is how I told you. This is how we write the output. 0 we will not write. A bar plus B bar, plus C. We can write for these one as well, like A plus B bar plus 1. But this plus 1 is there, so it will become 1 only, no? So that's why it is not written. That's why this 0 is not written. In the basics we studied it, how to write down the output using minterms and max terms. So this is what we are using. But we are habitual of writing the outputs using minterms, but not max terms. So that's the thing. That if minterms were there, you could have easily written the output, because we are habitual now. But for max terms, sometimes we are not habitual. So that creates some problem, but you can always take a bar, right? So this could be the answer. Let's write down the answer here. Okay. So how will you write it down? So I will write down in this manner in the examination, that if S1 is not there and S0 is not there, the information I would have been transferred, but there is a inverter, so bar. So S1 plus S0 plus I bar. This can be S1 plus S0 can be written as M0 plus I bar. What about this? If S1 is not there, and S0 is there, then information I would have been transferred. So S1 plus S0 bar plus I bar. So M1 plus I bar. What about this one? This would be S1 bar plus S0 plus I bar. That would be M2 plus I bar. And what about this? S1 bar plus S0 bar plus I bar. So this would have been M3 plus I bar. Well and good. Very easy. Okay. Let's solve some problems now. This input 1 is given, AB is given. You need to find the minterms of YA and YB. So if this is Y0, Y1, Y2 and Y3. If A is not there and B is not there, then information 1 would have been transferred. If A is not there but B is there, then information 1 would have been done. Basically multiply 1 is also there. Then both are added. So A bar B bar plus A bar B, that would be A bar only. Till this time you should be comfortable with these kind of calculation. It would be A bar only, right? This is A bar. And here you are having A bar B, right? So now your YA is A bar XOR with bar of this, right? So like you can make it XNOR gate, but why we should make it XNOR gate? Let's solve it directly. Or what could be the easier way? If I do A plus B here, it would be of no use. Let's solve it. Let's just solve it. So first as it is bar of second plus second as it is bar of first. So what I am getting here, A bar B plus A plus B bar into A. So A bar B plus A plus AB bar. So this would be A only. A plus AB bar would be A only. So final answer I am getting is A plus B. And this is A plus A bar B. A plus A bar B can be reduced to A plus B. The final answer of YA you are getting is A plus B. You can solve it any day, you can solve it, right? This is your A bar, this is your A bar B. So A bar XOR A bar B bar. So first as it is bar of second, second as it is bar of first. So A bar B, I will be left with A plus B bar into A. So A into A I will get here, and this is A plus B bar. So A will come common, so this will be reduced to A only. A plus A bar B would be A plus B. So this is what you are getting, and this is what? Capital M0. So what will be the minterms? 1, 2 and 3. These will be the minterms, right? What about this? What about this? What you are getting here? You are getting here is A is there, B is not there. And what about this? You are getting both A, B is there. Multiply of both. What you will get? 0. A, B bar into A, B. What you are getting? A into A is A, B bar into B, 0 you are getting. So you are getting as answer as 0. So this was the method 1 of solving it. Very easy method, very easy question as well. Okay. So if answer is 0, yeah, tell me. Answer is 0. So what are the minterms? No minterms are there, no? Because always answer is 0. So if what they are asking, max terms of YB. So what will be the max terms? Max terms will be, because output is always 0. If output is always 0, then all will be the max terms. That is 1, 0, 1, 2, 3. Okay, so all will be the max terms. No minterms are there. So this is the output. This was just a simple calculation which we did here. Okay. So this is the answer of this. This is the answer of this. Let's see the method 2. What I can do here. What I know, this will be M0 into I. M0 into 1. And what is this? M1 into 1. This is M0 into 1. This is M1 into 1. This is your XOR gate. XOR gate, what it does? It will add them minterms. And here M1 will go. After the bar here, which all minterms you will be having? 0, 2 and 3. Here you are having M1. So after the bar you will be having 0, 2, 3. And here you are having M0 and M1. Here you are having M naught. How did I say it will add? Do you remember what is the property of XOR? Sorry, what is the property of OR? A plus B. Remember the Venn diagram? All the minterms will come. So whatever that is here, whatever that is here. So M naught, M1 both will come. Okay, we can write it in the form of addition as well. So, and what XOR gate, now after the bar we have found M naught, M2 and M3 are there. So basically this is your XOR gate whose input is M naught, M1 and M naught, M2, M3. So what XOR gate does? If you remember, XOR gate, A bar B plus A B bar. So everything but not common. So what is common? Common is M naught. So everything will come but common will not come. So M naught will not come. So M1 will come, M2 will come and M3 will come. So in the output your M1, or you can write summation M1, 2, 3. That's it. This is your output. So this is how you can solve it. And what about this? Here you are having M2 and here you are having M3. What this gate does? Takes only the common. AB takes only the common. What is common in between them? 0. What this gate is actually doing? Multiplying both, right? M2 into M3. What you get to know? That it is 0. What is the conclusion you can make from here? Something very interesting, not I wouldn't say very interesting, but very common, that multiplication of 2 or more minterms is always 0. Do you remember addition of all the minterms is 1? Addition of all the minterms is 1. Remember this statement? Multiplication of all the maxterms is multiplication of all the maxterms is 0. Multiplication of all the maxterm is 0, right? And here multiplication of 2 or more minterms is always 0. So addition of 2 or more minterms will be always 1. Okay, addition of 2 or more maxterms, sorry, addition of 2 or more maxterms will be 1. And addition, these statements, I will repeat it again, don't get confused. First statement, addition of all the minterms is 1. M naught plus M1 plus M2 plus M3 would be equals to 1. This is the statement 1. Statement 2, multiplication of all the maxterms will be 0. Statement number 3, add multiplication of any of the two minterms, any of the two minterms will always be 0. Statement number 4, this will come later on, okay, later on it will come. Addition of any two minterms will, maxterms would be M naught plus M2 also you can do, or M1 plus M2, anything you can do, M1 plus M3 would be 1. Say yes or no. These 4 statements are there, which is very important. Okay, in MSQ they can frame these kind of conceptual problems where they can put the statement and ask you the problems. Okay, in the examination if it is not clicking, just like let's just say in the statement it is written that multiplication of any two minterms will be what? Multiplication of any two minterms. So just take the example a bar b into ab, 0 it is there. Okay, that's it. Okay, in that manner you can go. And here also you can check the addition of two maxterms. So what is M0? That is a plus b. And what is M1? M1 is a bar plus b. So a plus a bar will be 1 and b plus b will be b only. So 1 plus anything will be 1 only. So always it is going to be 1. Okay, because 1 bar will be there, and if 2 bars are added it will always be 1. So this is the question, this was the method 2. This is also how you would have solved it. Okay, let's go to the next one. Now you need to find output YA and YB. Let's try solving it with some different method. You can solve it any day. like let's solve it by two methods. So first one, we should go with the conventional approach. So how will I solve it? How I would have solved it if I had been the student, if I am going with conventional approach. So what I would have done, that if a bar is not there, b bar is not there, then 1 would come. So basically here it would be, if a bar is not there, b bar is not there, then 1 would come. But I need to take the bar because inverter is added. So a bar dot b bar bar, it would be a plus b, right? Because a plus b bar is equals to a bar dot b bar, and then bar is there, so another bar is there, so it would be a plus b. So here I am having a plus b. How can you verify? This is your m naught only, right? This is your m naught only. So m naught plus I bar is there. So I is 1. So this is your m naught. What it would be? This would be m1, which is a bar plus b. Is it correct? 0, 1. Sorry, a plus b bar. A plus b bar. And multiplication of both of them. A plus b, although it would be m naught into m1 only. Here I will get m naught into m1 only, but let's do it. So a plus ab bar plus ab plus 0. So this would be a. You are getting a only, right? You can do the multiplication, you will get a only. So this is a. What about this? Look, this inverter can travel here, and this inverter can also travel here. A bar XOR B bar will be equals to what? A XOR B only. Yes or no? If this inverter is traveling here, this inverter is traveling here. Basically, this is the, this is what? This is traveling here, this is traveling here. So this is M2 XOR M3 only. Initially the scene was, it was capital M2 XOR capital M3. You can say this is your capital M2 and this is your capital M3. So capital M2 XOR capital M3. Capital M2 can be written as M2 bar XOR M3 bar. This is how it can be written. So two bars are there, so it would be simple M2 XOR M3, right? Could be multiple ways to solve the problem. This is what I am telling. So what this would be? A bar plus B, and what this would be? A plus B, and I need to take XOR of that. That would be a tough task for me because I need to take XOR of that. This is actually a bar plus a bar dot b bar because AB would be 1. So M3 is a bar plus b bar, and this is a bar plus b, and take XOR of that. That is a tough task. But what did we reduce to? We got to know that this is your small m2, this is your small m3. This can also happen. So what does this function does? What do we call it? XOR gate. So what XOR gate do? Everything but not common. So this will deliver m2 plus m3 here. So what is m2 plus m3? M2 is a b bar and m3 is ab, right? So it would be a only. So very easily I got this is a. Are you getting my point? What I did here? So this will give me m2 plus m3. Here it will give me m2 plus m3. Am I doing it correct? Yeah, it is fine. So you are getting m2 plus m3 here, because if m2 is there, m3 is there, then what XOR gate will do? Everything but not common. So everything but not common, there is nothing common. So this will be m2 plus m3. And what is m2? M2 is a. What is m2? M2 is ab bar, and what is m3? That is ab. So here you are getting a, and a XOR a is 0. This is the answer. So smartly, like, I will have to use these inverters in the examination. If I had gone for making this XOR gate, then it would be very difficult for me. Like if I had gone getting XOR of these two, then it would be very difficult, right? Well and good. Let's go here. This is your M2 and this is your M3 again. So M2 plus M3, YB is M2 plus M3. What will be M2 plus M3? 1 only. How? What is M2? M2 is A bar plus B. And what is M3? A bar plus B bar. So B plus B bar is 1. A bar plus A bar is A bar. B plus B bar is 1. So answer would be 1. So answer is 1. Okay. So YA is 0, YB is 1. Well and good. Let's implement higher level demux from the lower level demux. So you will be able to solve these kind of problems in the examination. No need to worry. It seems like that it is a big problem, but we have reduced it. We have a lot of methods to solve it. I could have done more things here. What I could have done? That this is the scene no here. If I talk about this scene, so can I convert this scene into this? Surely I can, right? So here you are having M0 and here you are having M1. So M0 plus M1 bar you would have got, because NOR gate will just OR gate will just add it up and this will take bar. So basically you will get M2 plus M3. And what is your M2? M2 is M2, yeah, again the same thing you are getting, AB bar plus AB. So again you are getting A only here. So just multiple ways I am telling you, like in the examination, who knows which method will be useful for you. If you go by conventional as well, you will be able to get the answer. If you go like any method you can go with. Okay, in the examination these questions will not be difficult. Combinational is very easy and sequential is also very easy. Whole digital electronics is also very easy, right? So implementing higher level demux from the lower level demux. Lower level demux. So you need to make 1:4 demux from 1:2 demux. 1:4 demux, that means there will be 4 outputs. Do you agree? 1:4 demux means 4 outputs. 4 outputs. So there will be 4 outputs. 1 output, 2 output, 3 output, 4 output. Now you have only 1:2 demux. That means 1:2 demux. 1:2 demux can take only 2 outputs, and this can take only 2 outputs. Now if 2 outputs are there, they will certainly have some input as well. They will certainly have some inputs as well. Now there are 2 inputs, but you want only 1 input. That means these 2 inputs will work as a output of another 1:2 demux, right? They will work as the, there you go, and this will be their input. 1:2, 1:2, 1:2. They will have select line. Let's not write which select line is this. This will also have select line. This will be the information. So basically this was your block. This was the information. And this was the output. So I am saying this is my I0, this is my I1, this is my I2, and this is my I3. This is your 1:4 demux. This is your information. This is your S1, this is your S0. I0, I1, I2, I3. Now, which one will be S1, which one will be S0? Let's assume this one as S1, or this one as S0 and this one as S1. So let's take a random value. If I put S1 equals to 1 and S0 equals to 0, where I would expect what I am doing? Why I am writing Y0, I0? These will be Y0, no? Y0, Y1, Y2, Y3. Similarly these Y0, Y1, Y2, Y3. Y2, Y3. If I put S1 equals to 1 and S0 equals to 0, where do I expect this information to go? This information to go here. This is what I would expect. That my I would, because this is decimal equivalent 2. So my I would go here. This is what I would have expected, right? So if you put S naught equals to 0, this is 0. If S naught is equals to 0, that means this information will be transferred here, right? And if S1 is equals to 1, so here this will be its y naught dash and this will be its y1 dash. So if S1 is equals to 1, then this information will be transferred here. So whatever the information that is coming here, that is being transferred here, which is being transferred to y2 only. So this is what we wanted. So here this is y1 bar. So here your LSB bit will be near to the output. LSB bit near to the output. LSB bit near output. Just the opposite of mux. In mux, your MSB bit was near to the output. Let's take another example. It will be more clear to you what I am saying. Basically, this is your y naught bar. This is your y1 bar. This is your y naught bar. This is your y1 bar. So let's take another example. If I put both equals to 1. So if S1 is 1, that means this information will be transferred here, right? And if S0 is 1, then this information will be transferred here. So where did you expected the information to come? At Y3 only. So yes, it is coming at Y3 only. So that's correct. Okay. So this is how you implement it. What could be the shortcut method? You need to implement 1:4 demux from 2. So 4 by 2 plus, what do you get? 4 by 2 is 2. 2 by 2 and 2 by 2 will be 1. So 1 we will not count. So 2 plus 1, basically 3 demux, right? If you want to implement this, so 8 by 2, what you will get? 4. 4 by 2, what you will get? 2. 2 by 2, what you will get? 1. So 4 plus 2 plus 1, 7 demux, right? What about this? What will be the answer? 511. Why so? Just 1 less. The same kind of thing that we have done in multiplexer, the same thing we are doing here. Nothing new. 1:16 I need to make. 1:16. So 16 by 4. 4 you will get. 4 by 4, that would be 1. So 4 plus 1, 5 will be required. What about this? You are making 1:32. So one type of mux we are having, that is 1:4. Other type of mux you can make on your own. So let's start with 32 divided by 4. So 8 you will get. Again you can divide by 4. Now you will get 2. So you can use another 1:2 mux. And this will be for 1:4 mux. Right? So basically 8 plus 2, 10. 10, 1:4. Plus 1, 1:2. Not mux, yaar. Whole demux. I have the habit of writing it mux. Whole demux. Okay. So 1, 1:2 demux. So 10 and 1. What else could be there? What else we can do? Like there will be n number of ways, na? Our target is just we need to use 4. Rest all anything we can use. If I go by 32 by 8, so 4 by 4. So 32 by 8, and this is 4 by 4. So 32 by 8, that means 4 you need to use 1:8 mux, and 1 you need to use 1:4 mux. So this is how this is also I could have done. Like at the question mark, this could also come, no? 4 1:8 mux. This could have done. This could be there. N value could be 1 and 1:8 mux, and here 4 could be written. If I try by 36, so if I try by 16, so here I will get 2. So this I cannot try because I need at least 1:4 demux. Do you understand the problem? In the problem I am saying that I need 1:4 demux. I can implement my 1:32 demux like this, that I will use 2 1:16 demux, and I will use 1 1:2 demux. Yes, I can certainly implement like this. But in the question it is asking that you need to use at least 1:4 demux. What else I can try? What else I can try? I can try with start with 2, 16, 16 then 4, right? 4 4 is 4, then 4, then 4. What you are getting? 16 you need to use 2:1, and 5 you need to use 4:1. So multiple ways could be there. Just some possible ways I have written. Okay, multiple ways could be there. These are very easy question. Usually these are not asked. Okay, that's why we are not that much serious about it. Just very easy kind of problems. Usually they ask the question from multiplexer. Now implement the following function. So this we have seen. Now our next topic is implementing any Boolean expression using demux. So implement the following function using demux. That demux you need to use it. Use is a one ratio 1:8. Okay, 1:8 you can say, or 1:8. So you need to use the demux 1:8, and you need to implement the following function, that is 1467. Make all the possible design using active low and active high demuxes. Again muxes. Active low and active high demuxes. Okay. So I have the 3 select lines which I will put A, B, and C. A, B, and C. Where this is my S2, this is my S1, and this is my S0. What will be my Y0? Y0 will be M0 into I. If this is the information, this would be M1 into I. So better what I do is that I put this as 1. So my outputs will be M0, M1, M2, M3, M4, M5, M6, M7. And what do I need? Summation of M1, summation of M1 plus M4 plus M6 plus M7. So this will be my F. Now my question is this the only way you can implement it? Is this the only way? No, this is not the only way. Why so? What I can do is that I can pick 0, 1 is already there, no? So I can pick 0, 2, 3, 5. 0, 2, 3, 5. 0, 2, 3, and 5. I can pick these, connect it to an NOR gate. Basically what this will be, M0 plus M2 plus M3 plus M5 bar, and what that would be, M1 plus M1 plus M4 plus M6 plus M7. So there are two ways, no? If you are having NOR gate, then you will do this thing. So this will also be F, A, B, C. Let's try implementing the same using active low demux. So if this I put 1, what will be my here? M0 I bar, and I is 1, so this would be 0. So I will be getting M0 only here. So these outputs are M0, M1, M2, M3, M4, M5, M6, M7, right? Now what you need to make? 1467. Minterms are 1467. Minterms are 1467. So what will be the max terms? 0, 2, 3, 5. 0, 2, 3, 5. So these will be the max terms, and multiplication you need. Multiplication you need. So what you will use? 0, 2, 3, 5, all that to there you go. Okay, or this should be written here only, and this should be your F A B C. This will have these minterms or these maxterms, you can say. Now let's just say in the examination, if this circuit is given and they are asking you the minterms of F A B C, how would you solve it? They are asking you the minterms of A B C. How would you solve it? You will say that, sir, this inverter can come here, this inverter can also come here, all these inverters can come here, right? So the scene is, if all these converters are coming here like this, in the examination they will ask the analysis, like they will give this circuit and they will ask what will be the minterms of F. Then what you can do? So this is the scene. So if this is the scene, that means I can replace this as all these inverters and then there is a bar. So you will say that, sir, M0 plus M2, small M0 plus small M2 plus small M3 plus small M5 will not be there. Its bar we will take. So answer will be M1, M4, M6, M7. So if you are not that comfortable with max terms, then you can easily solve it using min terms as well. Just carry it forward, carry this forward, carry this forward, carry this forward. So this will become this. Very easy now. If you are not that comfortable with max terms, because we do not see max terms much, but you should be comfortable. This is my thing, that you should be comfortable. But if you are not comfortable, then I am telling you the multiple ways. Now my next question is this the only way to implement it? No, this is not the only way. Which could be the other way? Which could be the other way? That your max terms in function f a b c. What was your function f a b c? Their max terms was 0, 2, 5 and 0 to 3, 5. 0 to 3, 5. 0 to 3, 5. Right? So what I can do? This would be equals to 1, 4, 6, 7 bar. Say yes or no? Screen को क्या हो गया? Screen lag तो नहीं कर रही. So yeah, it would be 1, 4, 6, 7 bar. So we'll take 1, we'll take 4, we'll take 6, we'll take 7. Multiply all of them. And take bar of that. That would be your function A, B, C. So there are 4 ways of denoting it. 4 ways we have seen. Right? Now if you need to analyze this one, what you will do? I can introduce this inverter at the input side. And these inverters will cancel it. If these inverters cancel each other, then that means it is minterm y1, minterm y4, minterm y6 and minterm y7, and this is what you wanted. Minterm 1, 4, 6, 7, right? So this is how also you can analyze it. In the examination, there will be multiple ways of analyzing it. So that's it. This is about our demux. Demux is also completed. Now we will move to encoder and decoder. So I will see whether we need to pick an assignment first or we can do encoder and decoder, because most of the problems we are already dealing in our course itself. So let's see whether I would make an assignment or I will go with decoder and encoder. So better we should go with decoder and encoder, so that we can start. Let's see what we are going to do. Hi everyone, so in this video we are going to start studying about decoder. A very easy topic, a very straightforward topic. It is similar to demux only. So what it will do, there will be n input lines and 2 n output lines will be there. So n into 2 to the power n decoder it will be, okay. So it will convert the binary information into a symbol or a number. We will see about it, what it does, that we will see, and at a time only one output line will be active. We will see the working. So just What you need to see from this slide, you just need to see that there will be n input line and 2 to the power n output line. So let's see 1:2 decoder. So 1 input line and 2 output line. 1 input line and 2 output line. So what does it mean? What does it say? That if x is 0, then this y0 will be lit and y1 will not be lit. That means y0 will be on and y1 will not be on. And if x is 1, what is the decimal equivalent of 1? 1 only. What is the decimal equivalent of 0? 0 only. So decimal equivalent of 1 is 1. So this y1 will be 1 and y0 will be 0. From 1:2 it is not much clear. We will see 2:4, then it will be more clear. So for now, what will be your y0? Y0 will be x bar. And what will be your y1? Y1 will simply be x. If x is 0, then y0 will be lit, and if x is 1, then y1 will be lit. Lit means it will turn on. If x is 0, y0 will turn on. If x is 1, y1 will turn on. It's not that clear from 1:2 decoder, but from 2:4 it will be all clear. Okay. And here I have written active high enable and active high output. That means this enable will be working at 1. If you put in enable equals to 1, then the circuit is working. If enable equals to 0, then no matter whatever the input is there, all the outputs will be 0, because circuit will not even work. This we have already seen in the previous video of demux, right? If enable is 1, that means circuit is working. If enable is 0, that means no matter whatever the input is there, circuit will not work. That means y0, y1, y2, y3 all will be off. Now, if circuit is working, then if x0 and x1, x0 is LSB and x1 is MSB. If both are 0, then what is the decimal equivalent? That is y0, right? Decimal equivalent is 0. x1, x0. Both 0, 0, that means the decimal equivalent is 0. So y0 will be 1, rest all will be 0. Now, if x0 is 1 and x1 is 0. Wait a second. This I have written opposite, right? If MSB is x1, then this should be written in this manner. So yeah. So x0 is 1, 0. Decimal equivalent is 1. If decimal equivalent is 1, that means y1 will be 1, rest all will be 0. 1, 0, 1, 0. Decimal equivalent is 2. That means y2 will be on, rest all will be 0. And for the last decimal equivalent is 3. So y3 will be on, rest all will be 0. Very easy thing. Very easy thing. So what will be the expression of y0? When y0 is 1? For all the time y0 is 0. y0 is 1 only for when x1 is not there and x0 is not there. Also enable button will be there. So that is the expression of y0. What is the expression of y1? y1 is 1 only when x1 is not there and x0 is there. Certainly enable button will be there, right? What is the expression of y2? When x1 is there but x0 is not there. Certainly enable button will also come. And what is the expression of y3? When x1 is there, x0 is there, certainly enable button will come. Okay. What is x1, x0? If my function is of x1 and x0, there is some function which involves only two variables, that is x1 and x0. So what I can write this? This is your m0. This is your minterm m0. This is your minterm m1, right? This is your minterm m3, and this is your minterm m2. So simply your y0 is equals to m0. This is m1, this is m2, this is m3. So what does a decoder do? Just a second. Yeah, so what I was saying, so what does a decoder do? So a decoder converts the input as all the possible minterms. So there were two variables, all the possible minterms you are getting, m0, m1, m2, m3. So if it is 0, 0, then y0 will be lit. If it is 0, 1, then y1 will be lit. If it is 1, 0, then y2 will be lit. If it is 1, 1, then y3 will be lit. That's it. Okay. So this was your active high enable, active high output. Now we will see. So this will be the truth table, just for the fact I am saying that if enable is 0, then no matter whatever the input is there, all will be 0. Just like if people are confused, so I am making this table. Like no matter whatever the input is there, all will be 0. And if enable is 1, it will be working as it is. So what is the decimal equivalent? Again, there is an error. It should be x1 and this should be x0. So decimal equivalent is 0. So y0 will be lit. Decimal equivalent is 1. So y1 will be lit. Decimal equivalent is 2. So y2 will be lit. And if decimal equivalent is 3, then Y3 will be lit. That's it. This is your 2:4 decoder. This is the circuit design. What is your Y naught? Why I have written En bar here? No En bar would be coming. Why I have written En bar? Okay, that's an error here. It would be En, and this input would be coming from En only, not from En bar. All the inputs will be coming from En. That's a blunder from my side. All these should be coming from En. Okay, so this is the circuit design, very easy, very straightforward. Like no one will ask you this, just for the fact I am saying. This is x1 bar is going here, x naught bar is going here, and En is going here. So this is your Y naught. So Y naught, what is Y naught representing? M naught into En. And what Y1 represent? M1 into Em. What Y2 represent? M2 into En. And what Y3 represents? M3 into En. Okay. Now you will see the same decoder, but active high enable and active low output. We saw this case in Mux and Demux. Active low output. What do you understand by that? If this inverter was not there, if these inverters were not there, then what my output would have been? If enable is 0, then circuit will not work. Then here you will get 0, 0, 0, 0. But there is an inverter, so rest you will get 1. Basically, every one will be lit if this is not working. But if this is working, then what is the decimal equivalent of 0, 0? X naught, x1. Again, the error I have done. This should be x1, this should be x naught. Because this is our MSB bit, this is our LSB bit. Okay. So what is the decimal equivalent of 0, 0? Decimal equivalent of 0, 0 is Y0. So this will be 1 and rest all will be 0. But since there is an inverter, so this will be 0, rest all will be 1. Say yes or no. So what is the decimal equivalent? Y1. So this will be 0, rest all will be 1. This will be 0 here, rest all will be 1. What is the decimal equivalent? 3. So this will be 0, rest all will be 1. Say yes or no. Right? So let me remove this. Just you need to see this is a same kind of decoder, but there is inverter. That's it, nothing else. Can you write down Y naught expression? So Y naught is 0 only for the one time. Y naught is 0 only for one time. So I will use max terms here, right? I will use max terms. So how will I write? X1 plus x naught plus En bar. So I can write it. I can write this as M0 plus En bar. Or what could be the other way of writing Y naught? I know that here I would be receiving, if this inverter was not there, so what I would be receiving here? M naught En, right? M naught En. I would be receiving here M naught En. Because 0, 0 it would be, this would be 0, 0. But what I would be receiving is that if x1 is not there, x naught is not there, and En is 1, then output will be 1. This is what I would be, this is what I would be receiving. I can write this as M naught En. The same kind of thing we have done in Demux. The same kind of thing we are doing here. But there is an inverter. So Y naught is inverted. There is an inverter. So this would be M naught bar plus En bar. And what is M naught bar? M naught bar is capital M naught plus En bar. So this is what you are getting. Or directly you can write from here. Or if you don't want to remember this, you just need to consider this as a active high output only, but there is inverter involved. There are some inverter involved. So here you are getting M naught En. Just if you take the bar of that, what you will get? Capital M naught plus En bar. Right? What about Y1? So your Y naught is capital M naught plus En bar. What about your Y1? Y1 is capital M1 plus En bar. What about Y2? Capital M2 plus En bar. What about Y3? Capital M3 plus En bar. Okay. So now let's see this active low enable and active low output. So if enable is 1, then it will not be working. If enable is 1, then it will not be working, because enable needs to be 0, then it will be working. And no matter whatever the input is there, output will always be 1. Why output is always 1? Because it is inverted. So if circuit is not working, then output should be 0. But since there are inverter, output will be 1. And if input were 0, 0, then this one should be lit. But since there is an inverter, so this will be 0, rest all will be 1. Ideally, this should be the response, that it should be 1, rest all should be 0. but there is an inverter, so this should be 0, all will be 1. Okay, so this was the condition for 0 0. For 0 1, what is the decimal equivalent? That is 1. So only this one will be 0, rest all will be 1. Here only this one will be 0, rest all will be 1. Here only this one will be 0, rest all will be 1. So if I need to write my y naught, what will be my y naught? So my y naught will be x1 plus x naught plus en, right? x1 plus x naught plus en, because y naught is 0 only at this. So it will be m naught plus en. If I wanted to write in min terms, then what I would have written? So what this would be? M naught into en bar. Say yes or no? M naught into en bar. Because if en is 0, then it would work. So m naught into en bar. So y naught is m naught into en bar. But there is an inverter, so you need to take bar. So you will get m naught bar plus en. So it would be capital M naught plus en. And what will be your y1? y1 will be capital M1 plus en. y2 will be capital M2 plus en, and y3 will be capital M3 plus en. So all the max terms can be generated from here. All the max terms can be generated from here. All the max terms we are generating. En will always anyway will be 0. If enable is anyway 0, then no issue. And if en is 1, then y naught will be 1, y1 will be 1, y2 will be 1, and y3 will be 1. So this is the expression of y naught, y1, y2 and y3. Well and good. Let's see 3 cross 8 decoder. So directly let's write down the output directly. How will you write down the output directly? This is active high output, active low enable. So what will be your y naught? If x naught is not there, if x1 is not there, and if x2 is not there, then it will be lit. Considering that my en is also not there, because if my en is 0, then it would be working. So I can write this as m naught en bar. What this would be? M1 en bar. Basically all will be the min terms. M2 en bar. And why they are the min terms? We know, because if these are what about this? 4. That means x2 should be 1, rest 2 should be 0. That means x0 should not be there, x1 should not be there, but x2 should be there. So x2 should be 1 and dot en bar. Although I am writing it opposite, x2 in dot x1 bar dot x0 bar I should have written, but let's just let it be. So this would be m4 en bar, because x2 is MSB, m5 en bar, m6 en bar, and this would be m7 en bar. So decoder just give all the min terms. That's it. This is the task of decoder, giving all the min terms. Okay. So this table let's remove it, because we can directly write down the output. Why should we again and again make the table? Okay, in the examination you are not going to make these tables. If no enable button is given, if nothing, no enable button is given, here enable is not given, so we will consider it to be on only. We will consider this to be on. Now here are inverted output. So what you can write here? Capital M naught. Say yes or no. This will be simply M naught. If there is an inverter, it will be capital M naught. Because if X naught is not there, if I would have written it that this could be written as, if X naught is not there, if X1 is not there, and if X2 is not there, then this should be lit. But there is an inverter, so inverted sign will be there. So it would be X naught plus X1 plus X2. So you can write this as M naught. This will be your M1. This will be M2. You can skip this part. M3, M4, M5, M6, M7. Okay. Needless to make the table. Let's not make the table. Now decoder versus demux. You might be feeling like that, sir. We are studying, I guess, demux only. It is not something new. Yeah, it is not something new. To make this work, I should put en equals to 1, right? What will be my y naught here? Y naught will be x naught bar, x1 bar dot en, you can say. And what will be your y naught here? Y naught here will be, if s1 is not there, s naught is not there, then I should come. Can you relate both of them? Right here, this is MSB, this is your MSB, and this is your LSB. This should be given in the problem. In the problem, it will be given. So I will write x1 bar, x naught bar. Let's write down other. Here what will be my y1? It would be if s1 is not there but s naught is there, then information will be transferred. Here if x1 is not there and x naught is there, then information will, then and enable should be 1. So this y1 will be lit. Y1 will be lit, right? So basically this y naught is your minterm en. This y1 is your minterm 1 en. Y2 is your m2 en and y3 is your m3 en. Here as well it is same. m0 I, m1 I, y2 is m2 I, y3 is m3 I. So what do you see here? If you put enable equals to 1 here, if you put I equals to 1 here, then it would all be same. S1 is equals to x1 and s0 is equals to x0. Similarly, x0 is equals to s0 and x1 is equals to s1. Both are similar. Both have the same working. Okay. So this is the similarity between decoder and demux. You can say a decoder with enable button will work same as a demux. Active high enable it is. If it is active low enable, then you put information equals to 0. If it is active low enable, then you put information equals to 0. Right? Or we should not say like that. No. If it is active low enable, that means it will be turning on at en 0. So all will be off. If you put en equals to 0, now you can directly compare between these two. Okay, just compare between these two. That active enable is there. That means this is same as decoder and demux. And if you want to make it active low enable, then this you need to put. This would be active low enable. So here also you need to put a inverter. Okay, then it will be active low enable. This will be active low enable decoder will be equals to demux if you put an inverter here, and that inverter should come here. So basically information should be equals to the en. Okay, this information should be equals to the enable bit and these select lines should be equals to these input bits, right? So very simple thing it is. Let's see a question. What the examiner is asking or what the interviewer is asking. He is asking that you need to generate all possible minterms of any two variable function. Minterms should be separated. That means separately you need to generate m0, m1, m2 and m3. So what you are going to use? I can either use a demux or I can either use a decoder for two variable. That means I need two inputs and these will be my outputs. I will design a 2:4 decoder. This is my enable bit, which is always 1. So if I am putting, let's just say A here and B here, I am calling this as MSB and this as LSB. This is my Y0, Y1, Y2, Y3. When Y0 will be on? If A is not there, B is not there. If A is not there but B is there. If A is there but B is not there. If A and B both are there. What is this? This is simply M0. This is simply M1. This is M2 and this is M3. So these are the minterms. Okay. What about doing the same from demux? So in demux there will be only one input and two select lines will be there. So if I make my information 1 and make these as A and B, this one will be your S1, this one will be your S0. Here also I would have written that this is my X1, this is my X0. X1 being MSB and X0 being LSB. So there will be 4 outputs. This being your Y0, Y1, Y2 and Y3. So A and B, if A and B both are not there, then this 1 will be transferred here, right? So this will be your M0, this will be your M1, this will be your M2 and this will be your M3. So in the interview these kind of questions can be asked that you need to generate separate minterms using one device. What is that device? Demux and decoder. So the task of our demux and decoder is to generate all the minterms, right? Write down the output expression. Let's solve the problems now because it is a very straightforward concept, very straightforward. So what is this? This is your AB. And what is this? A plus B. Can you tell what will be AB XOR A plus B? Look, first thing, this example we have already taken. You are not going to do this thing. I hope you remember it. We cannot do it like this. I hope no one will be doing this thing. That AB XOR A plus AB XOR B. Nah, absolutely wrong. There is no law like that, right? So what I can see, what is this? This is M3, right? Say yes or no. I am telling just methods. You can solve it any day. What you are going to do first, as it is, bar of this. What will be bar of this? A bar dot B bar, I guess. Bar of this will be A bar dot B bar. Plus second, as it is, bar of the first one. That would be A bar plus B bar. So this is gone. And what is this? This is A XOR B only. So eventually you are getting A XOR B only here. This is how you could have solved. But what I am saying is that AB is minterm M3. M3 XOR with, what is this minterm? 1, 2, 3. Say yes or no. Do you agree to this point? A plus B is max term 0. So it will be minterm 1, 2, 3. Right? It is max term 0. So minterm 1, 2, 3. So let's write it better. It is max term 0. So minterm it is 1, 2, 3. What does XOR gate do? XOR gate will take everything but not common. So final answer is minterm 1, 2. And what is minterm 1, 2? A bar B plus A B bar. And that is A XOR B. Just like I just want to tell you the method, like who knows which method will be useful in the examination at a particular point. Like it is simpler from this method, I know. But what if in some problem you might use these methods? So I was highly focusing on Venn diagram. This is the reason that any kind of operation can come, and you can if you can write down in min terms, then you can tell, okay, this will pass this will pass this, just by remembering the Venn diagram. So that's why I focused a lot on Venn diagram. Okay, so this is A XOR B, and here it should be written which is MSB, which is LSB, right? So let's take this as MSB and this as LSB. This is your LSB, this is your MSB. Okay, so what will be my YA? So now I cannot write that M not, I can write, still I can write basically, this is your enable button, this is your enable button, this is your enable. So this should be 1. So if C is not there and D is not there, so and enable is 1. If C is not there and D is not there and enable is 1, then this one will be lit. If C is there, sorry, which is LSB, this is LSB. So D is not there, C is there, D is not there, D is MSB. Then this one will be lit, considering that your enable is 1. If C is not there but D is there, both are there. That's it. Okay. You could have solved this in this manner as well. Very easy problem. Okay. C bar is not there, D bar is not there, then enable button is there. So this one should be lit. And this is, since this is your MSB. So if C is there and D bar is not there, then this one will be lit, considering that your enable button is 1. And then this and then this. Okay. Let's see the next one. Implement the following function using decoder 3:8 decoder. Very easy. Enable should be 1, then it would be working. My inputs are A, B, C. What is the minterm I require? What all are the minterms I require? So here I will get M0 minterm, here I will get M1 minterm. Let's write it down here. So this I will get M0 minterm here. Here I will get M1 minterm. Here I will get M2 minterm. Here M3. Here M4. Here M5. And here M6. And here M7. So all these minterms I am getting. What I need to do? Take the summation of all of them. 1, 2, 4, 7. 1, 2, 4, 7. Take summation of all of them. This is your function ABC. which I have noted. Is this the only way? From the same circuit I can make it. How? Take the summation of M0, M3, M5 and M6, then take a bar. We did the same thing in Dmux, so I can move fastly here, right? Take the summation of M0, M3, 0, 3, 5, 6. 0, 3, 5, 6. So these minterms I have taken 0, 3, 5, 6. These all minterms I have taken, but I do not want these minterms, I want the bar of that. So that would be the answer. Okay. What about this? This is my max term M0, max term M1, max term M2, max term M3, M4, M5, M6, M7, right? These are my max terms. What do I require? 1, 2, 4, 7. That means which max terms I want. Sorry, for max term I will put the pi sign. So which max terms I want? I want 0, 3, 5, 6. 1, 2, 4, 7. 0, 3, 5, 6. Max terms will be 0, 3, 5, 6. So I want 0, I want 3, I want 5, I want 6. So these I want, right? And then multiplication of that. So what I will be using here? AND gate. Now can you relate this? If these bubbles come here, that means if this bubble travel, basically this is a NOT gate, no? So if this NOT gate comes here, all these travels, if all these travels, then this will be replaced with this thing. So directly this output will be connected here. Basically this bubble I have made it travel here. So if it has come here, then this will be coming like this, because if you remember this diagram, this is equivalent to this diagram. So if four are there, so basically this will be the final diagram, right? So if M0 is traveling here, M3 is traveling here, M5 is traveling here, and M6 is traveling here. So this will be the diagram, and this will be same as that, because bubble will be gone. If bubble is gone, then this will be same as that, right? So in this way as well you can see. Okay, this is your output Y, this is your output Y. What about this? Another way. What could be the another way? What could be another way? So I can take M1, M2, M4 and M7. I can take M1, M2, M4 and M7. M1, M2, M4, M7. I can take these max terms. I can take these max terms and do the AND. But these max terms I don't require. I want the inverter of that. That's it. So here what I am getting? Max terms M1, M2, M4, M7 and inverter of that. Okay. So what I will be getting here? You can say max terms 0, 3, 5, 7 and which is equivalent to min term 1, 2, 4, 7. So in the examination this circuit will be given and they will be asking you to analyze. So how will you analyze this circuit in the examination? What I would be doing, that I will be replacing this, I will be taking these bubbles here, these bubbles here. So this AND gate can be replaced with OR and then inverter. Then another inverter is there. So inverter got cancelled. So basically I see this thing. So M1 plus M2 plus M4 plus M7. I can see these minterms. Right? I will be solving it using the minterms. I will take this bubble here, I will take this bubble here, take this bubble here and take this bubble here. Then bubble got cancelled. This is simple OR gate. And in OR gate Y1 M1 plus M2 plus M4 plus M7. Okay. So try solving this question on your own. So this is a very good question. You need to find out the minterms of this Y. this y, minterms of this y you need to find out. Okay, so input are a, b and c bar, a, b and c bar. Now if you go by max terms, then it would be very difficult, at least for me. Okay, in the examination, here I can solve it, like I can take time, but in the examination to do it quickly, what I would do, I will take this bar here, take this bar here. So this is my XOR gate, and if two bars are there, a bar XOR b bar, one bar can be made full, this bar also can be made full, so it will be a XOR b only. So this is simple XOR gate only. So whatever the minterm is coming here and here, like basically whatever the minterms you get here at y0 and whatever the minterms you get here at y2, the same will be transferred. But tell me one thing, can I write that my y0 is equals to m0, y1 is equals to m1 and y2 is equals to m2, and in that manner? Can I write that? No, because my input is not ABC. This y0 will be lit when? This y0 will be 1 when a is 0, b is 0 and c, this should be given here that this is your MSB x2, x1, x0, this should be given in the question, and c is 1. If a is 0, b is 0 and c is 1, then y0 will be lit. So this is 0, 0, 1. If it is 0, 0, 1, that means this is m1. Say yes or no. So we need to write down all the minterms here, all the minterms. I am writing all the minterms here. This is the minterm, and here you will get capital M1. You will get capital M1 here, but we are not caring about that. I am not caring about capital M1. I will care about only small m1. So this is my small m1. Basically, I should put here m1 bar. I will get m1 bar here. What about this y1? Why I am putting m1 bar? Because there is a bubble. So basically, this is my m1 bar. This is my m1 bar. When y1 will lit? Y1 will lit when x2 is 0, x1 is 1 and this c bar is 0, that means this should be 1. So basically what I will do is that first I will write down all the condition, all the possible variable. So now at this condition a, b, c bar, y0 should be lit. At this condition a, y0 should be lit. For what it will be for a, b, c? It would be 0, 0, 1. This would be 0, 0, 0. This would be 0, 1, 1. This would be just the inverter of the last bit, nothing else. 1, 1, 1, and this would be 1, 1, 0. So this first one, y0 represent your m1 bar. This will represent m0, but since there is an inverter, it would be m0 bar. Are you getting this question? Are you understanding this point? This would be m3 bar. Basically, this y2 will be lit when a is 0, b is 0. So sorry, m3 is no. A is 0, b is 1, and c bar is 1. That means c should be 0. Okay, we are talking about y2. Sorry, we are talking about y2. When y2 will lit? If a is 0, b is 1, and this c bar is 0. This c bar should be 0. That means c should be 1. So what is that? This shows m3. If I talk about function ABC, if I am saying my function is ABC and these are the values of ABC, that means this is minterm m3. So this represents minterm m3. So this is your m3 bar. And what is the next? m2 bar. What is the next? m5 bar. Next would be m4 bar. Next is m7 bar. And this is m6 bar. Right? So let's remove it off. I hope you must have understood how do we write the minterms. So both goes here, what you will get here? XOR gate is there. And this bar got cancelled. This bar and this bar got, sorry. This is after the bar. This is after the bar. But what is happening is that M1 bar XOR M0 bar. So this bar can be converted to full. This bar can also be converted to full. So M1 XOR M0. What that would be? What you will get? It will take everything but not common. There is nothing common. So here you are getting 1 and 0. 0 and 1. So here the minterm you are getting is 0 and 1. Okay, what about this? Wait a second, here M1 and M3 are going, really sorry, M1 and M3 are going. So in this one, 1 and 3 you are getting. Here M0 is there, and in this one what all are going? M0 bar, dot, M2 bar, M5 bar, and M4 bar. 0, 5, 2, 4. 0, 5, 2, 4. But how do I solve it? If I solve by this bar and bar, 0, 2, 5, 4, this will be the answer, right? Or I can write this as M0 plus M2 plus M5 plus M4 bar. So apart from 0, 2, 5, 4, everything will be coming. Or what I would have done is that I would have taken this bubble here and would have converted this bubbled NAND gate into NOR gate. It would be bubble AND gate. Bubbled AND gate will be equals to the NOR gate. So from NOR gate I would have got M0 plus M2 plus M5 plus M4 and then bar. This is what I am getting. So apart from these minterms, everything will be there. So what all will be there? 1 will be there, 3 will be there, 4, 5, 6 and 7 will be there. Now there is an XOR gate and then there is an inverter. You can say this is XNOR gate, or you can say there is XOR gate and then inverter. So what you will get here? You will get here is that XOR gate will take everything but not common. So 1 and 3 it will not take. So here you should get 6, 7, but bar of that you will get. Bar of 6, 7. Because there is an inverter. So here you are getting bar of 6, 7. What about this? What is this? What do you think? What is this? This is M7 bar dot M6 bar and then bar. It is M7 plus M6 only. Right? So this is 6, 7. So this minterm you are getting, that is 6, 7. Let's just call it X. If this is your X, then what is this? This is X bar. So X plus X bar is what? 1. So this is your answer. So Y is equals to 1. How did we solve it? You get to know. Here we can solve it all by max term as well, but max term we are not that comfortable. So I am solving with min terms. So this is your M1 bar and M3 bar. M1, 1, 3 you get here. Here 0, 2, 5, 7. But bar of that, this bubble can be converted into bubbled AND gate can be converted into NOR gate. The same thing here. It could have also been converted into OR gate, because bubbled NAND it is. Bubbled NAND is OR gate. So M7 plus M6 you are getting here, and this is your X bar. So answer is 1. Well and good. Very easy problem. Let's see a very interesting point. Like it will be used in our next analysis. It will be used. So there is a tri-state buffer. This is your normal buffer. No? This is your normal buffer. So if input is A, output should be B. But there, if I connect a enable bit, then it is known as tri-state buffer. Okay. So if I am calling this input as X and output as Y. So if En is 0, if enable is 0, then this will not even be working, and this will be the condition. So this is known as high impedance, high Z we call it, high impedance state. If En is 0, then it will be off. If it is off, that means it will be open circuit. So this will be your Y, this will be your X, or this will be your Y. This is the condition for En equals to 0. And for En equals to 1, it will act simple as inverter only. Sorry, not inverter, buffer. It will simply act as buffer. Okay, if En is 1, then it is simply acting as a buffer. Buffer you can directly say, this is my buffer. This is your X, this is your Y. So simply acting as a buffer. So Y is equals to X. Okay. And what is inverter? The same thing, just a bubble here. So if En is 0, if En is 0, then it would be high Z. And if En is 1, then y will be equals to x bar. It could be, this is one of the possibility, it could be active low enable as well, right? It could be active low enable as well. Active low enable. You can see this as well sometimes in the questions. So if En is 0, then y will be equals to x, and if En is 1, then high G state is there, high impedance state is there. Same thing could happen here as well, that active low enable. So this is your x, this is your y. So if En is 0, then y will be equals to x bar, but if En is 1, then it is high G state. So now we will see this topic. In this topic you need to implement muxes from the decoder. Okay, so you need to implement 2:1 mux from 1:2 decoder. 2:1 mux from 1:2 decoder. Actually in this video there are a lot of breaks in between because there is a lot of disturbance here. So that's why there are some breaks. So I hope you are not feeling disturbed. So this you need to make, and this is already there because this is an easy lecture. So in this easy lecture you might not be feeling that much disturbed here. So if s is 0, y should be equals to I naught. This is my target, and if s is equals to 1, then y should be equals to I1. This is my target. Okay. So if s is 0, then y naught will be lit. Then y naught will be lit. Now what I can do, I can give this as an enable button to my tri-state buffer, and the input of this buffer will be I naught, and this I can call my output. So if s is 0, this will turn on and it will go to the output. Now if s is 1, then this will turn on. So this I can give as an enable button, and here I can pass information I1. So now see, if s is 0, then y naught is equals to 1, y naught will be lit, and I am calling this as tri-state 1 and this as tri-state 2. So tri-state 1 will be working, and what about tri-state 2? Tri-state 2 will be high G, high impedance node. High G means it will be open circuited, so nothing will be going towards output, only I naught will be transferred. So y will be equals to I naught, and if s1 is 1, then y1 will be 1. If y1 is 1, that means T2 is working, and if T2 is working, that means T1 is high G. So from upper side nothing will be coming, but from downward side y will be equals to I1. Let's see the next one. You need to make 4 cross 1 from 2:4. So from 2:4 you need to make 4 cross 1. So if both are 0, then this should be lit. If both are 0, then this should be lit. So I will pass my I naught information from here to my output y. Here I will pass my I1 information to my output y. Here I will pass my I2 information to output y, and in this one I will pass my I3 information to output y. So if both are 0, then this will turn on, this tri-state will turn on, and output y will be equals to I naught. If this is 0, sorry, if this is 0 and this is 1, so this I am calling as my x naught, this I am calling as my x1. Then y1 will turn on and I will be transferred. So in that manner you can design it. Okay. So if in interviews, if these kind of questions are asked, then you will be able to tell. Okay. Now we will design higher order decoders from the lower order decoder. So you need to design 2:4 decoder from 1:2. So you will always look at outputs. Okay. Always in decoders you always need to look at output. So 4 is divisible by 2, what you will get? 2, and 2 by 2, what you will get? 1. So 2 plus 1 is equals to 3. So you need 3 decoders. Okay, you would need 3 decoders. So in 2:4 decoder there will be 4 outputs, right? 1 output, 2 output, 3 output, and 4 outputs. So there will be 4 outputs. And one input. So this is your 1:2 decoder. In 1:2 decoders, in 1:2 each 1:2 decoder there will be two output. This is what you are having, 1:2, 1:2. Now it feels like that in 2:4 there should be two input, so I should give this thing, I should give this thing, right? It feels like that. Let's check what happens if I do like that. Then let's check what happens. So if x naught is 0 and x1 is 0, then y naught should be lit, right? If I put here, if x naught is 0 and x1 is 0, then basically the scene is like this will be y naught bar, this will be y1 bar, and this will be y naught bar, this one will be y1 bar, because both are different decoders. So if x is 0, then this one will be lit, and if x1 is 0, then this one will be lit. So two are lit, and this is what we don't want. So that is a wrong idea, that we thought that if two inputs are there we should put x0 x1. So that's a wrong idea, we cannot do that. So let's see what we can do. Let's say I put both as x0, okay. Then I take another 1:2 decoder. 1:2 decoder means one input will be there and two outputs will be there. So now what I do is that I take one of the output and give this as enable. I take other output and give this as enable, and this input I am calling x1. So my two inputs are x0 and x1, and these outputs here, this will be my y0 bar output, this will be my y1 bar output, and this is my 1:2 demax. So this will be my enable and this will be my enable. Let's check now. If I am putting x0 is equals to 0 and x1 equals to 0, if x1 is 0, then this one will be working. If x1 is 0, this one will be 1. That means this decoder is working. This decoder is working. Now x0 is 0. If x0 is 0, that means this one will be lit. So only y0 is lit. Only y0 is lit, because this decoder is not even working. This is 0. If x0 is 0 and x1 is 0, this is 0. So this is not even working. So these are 0. And here only this is 1 and this is 0. And this is what you wanted. So yes, this is how we do. So MSB, your LSB bit near to the output. LSB bit near to the output. LSB near to the output. It is same as Dmux only, but we need to make sure that if we see two input doesn't mean it should be different. If we check it here, we got to know that it is not working fine. We can take another more example. What I can do is that I put x1 equals to 1 and x0 equals to 0. So what you should expect? This you should expect. x1 equals to 1. x1 is MSB here and x0 is LSB. So this I should expect is if x1 is 1 and x0 is 0. That means y2 should lit. So if x1 is 1, so this will be 1 and this will be 0. Then this will not be enabled, but this will be enabled. So this will not be working, but this will be working. Now if this is working, and what is x0? x0 is 0. If x0 is 0, then this one will be lit. So y2 is lit, right? So what we are doing is correct. Okay. So in that manner we need to proceed. Next you will design on your own, and you will tell the numbers, because mostly in the examination numbers will be asked. So for finding numbers we will always look at outputs only. So 8 by 2, what you will get? 4. 4 by 2, what you will get? 2. 2 by 2, next one we don't need to write. So 4 plus 2 plus 1. So 7 will be used. We'll make the design because I am an educator, but for you, you can skip it, like you can quickly skip it and make the design on your own in your rough notebook. Okay, make it on your own. I will highly recommend to make on your own at least, so that at least if you are preparing for interviews, then in there you need to make it on your own, like no one will make it for you, right? So there will be these inputs. I am making the inputs now. So MSB, that means x0 will be here, x1 will be here, and this will be your x2. And if they are producing two outputs, y0 bar, y1 bar. So these two outputs they are producing. This will be enabled. This is the enable bit. Okay, here this, yeah, in this one as well, this is also enable, but this enable is always on. Okay, here there is also an enable, but that is always on. Yeah, fine. Now they will also produce outputs. This will produce two output, one here and another one here. So this will be going here and this will be going here. This will also produce two output, one here and another one here, another one here. So this will be going here, this will be enabled for this one. Okay, and what about the final output? So final outputs, you are expecting 8 outputs, 1 2 3 4 5 6 7 8, y0, y2, y3, y4, y5, y6 and y7. This is your y0 bar, y1 bar. Same goes in this one. This is your y0 bar, this is your y1 bar. Same goes here as well, y0 bar, y1 bar. All are 1:2 max. You can check for any random combination. Let's check for any random combination. So x2, x1, x0. Let's put 1 0 1. So 1 0 1 means I expect y5 to be lit. I expect this one to be lit. Okay, so let's start. If x2 is 1, if x2 is 1, then this will turn on. If x2 is 1, then this will turn on. If x1 is 0, if x1 is 0, then this will turn on. If x1 is 0, this will turn on. If x0 is 1, if x0 is 1, then this will turn on. Yeah, correct. Okay, for any combination you can check. So after making your design, you should check for any random combination. So if it is working, then your answer is fine. Let's move to another one. You need to make 5:32 from 4:16 and 1:2. So 32, I will look at this only. So first 16, then 2 will be left. Now 2 can be divisible by 16 as well. So it can be made from 4:16, but 2 can be divisible by 2 as well. So 2 16:1 you require. 2 16:1 you require. And 1, not 16:1, sorry. You will require 2 4:16 and 1 is to 2. Okay, do not skip it. I will be dealing with some one important point here. Okay, do not skip it. So I will make it first. Four into 16 output I will have to make. So those 16 outputs I am not going to make, but I need to make a point here. What is that point? Here will be 16 output and here also there will be 16 outputs. This is your 4:16. This is also your 4:16. This is your y0, y1 till y15, and this is your y16, y17 till y31. 4 inputs will be there, right? Four inputs will be there. So all the LSB1 will come and this will be fed with the MSB1. So all the LSB1, what those will be? X0, X1, X2, X3, X0, X1, X2, X3. All the LSB1s are there and this will get the MSB1. So here there will be two outputs like this. This will work as enable button, right? They will work as enable button. So this is your 5x32. This is your 1:2. Okay, and this is your y0 bar and this is your y1 bar. Now what this what a 2:1 decoder do? If I apply X input here, what will be your two outputs? One will be X bar and one will be X. So this is your 1:2 decoder. It can give you inverted output and a buffer output. Say yes or no. What does a 1:2 decoder does? If X4 is 0, then this one will be lit. So this is your X4 bar and this is your X4. So instead of using this decoder, I can simply use an inverter. If I simply use an inverter and one I give this and another I give this, that's it. So this enable goes here and another enable goes here, and this is here my X4. If I am calling this as enable 1, this as enable 2, so here bar is going, so enable 1 and this is your enable 2. So I don't need to use a 1:2 decoder here. So in the examination, the option can be framed in this manner, that two 4:16 decoders and one inverter. This can also be the option. Okay, so 2:1, basically here you used inverter only, no? This is a buffer, so this is a simple line, so you do not need to use anything else. So 2 4:16 decoder and one inverter you need to use. So from there as well you can make it. So from 1:2 decoder you get an inverted output and a simple output. So this is simply X4 going here and this is X4 bar going here. So here you did not use any gate or anything like that. Neither you use decoder, neither gate, neither mux, nothing. No combination circuit is there. Simple wire is there. But here you used a NOT gate. So this could be done using two 4x16 decoder plus one NOT gate. So 1:2 decoder can be replaced with NOT gate as well. Well and good. Let's move to next one. You tell the numbers. How many numbers will be there? 256 by 16. So what will we get? 16 only. So 16 by 16, because we need to focus here only. 16 by 16. So 16 plus 1, that is 17. So n value is 17. Value of n is 17. Very straightforward. Okay. Let's write another question. What I need to leave 2 anyhow. So 64 if I do 6 into 64. 6 into 64 if you need to make. So 32. Okay. Yeah. So from 5 into 32 plus logic gate, you need to make 6 into 64. So look here, look here. So 64 by 32, what will be left with? 2. So 2 by 2. So what would be your answer? That I need 2. I should write 2. I need 5 into 32, and 1 I need 1:2, and that is equals to 1 NOT gate. So to make 1:2 decoder, you need only one NOT gate, nothing else. So from one NOT gate you can make this decoder. Well and good. Okay, so these kind of questions can be coming. So you should be comfortable with this option as well, that one NOT gate can also be there. Okay. Now we are going to study about encoder, and that we will see in the next video, and that will be very easy topic only. So in next video we will wrap it up. So encoder is also pretty easy. It will be completed in roughly around 30 minutes only. Okay then, thank you very much. Hi everyone, so now we are going to study about encoders. So very easy topic, just the opposite of decoder. So there will be 2 to the power n inputs and n outputs. 2 to the power n inputs and n outputs. Now there is a thing like people get confused, like decoder will have n inputs or 2 to the power n outputs, or encoder will have 2 to the power n inputs. So this is confusing sometimes, like you forget sometimes. So how you can remember? So decoder, demux, right? In demux you remember that there will be one input and 4 output, like basically one input and 4 output, or one input 16 output. So there will be less number of input and more number of output, right? So DD word is same, no? So in decoder there will be less number of input and more number of output. Or how you can remember? Decoder, if you are decoding something, then you will elaborate it, right? If you are decoding something, let's just say I give you three numbers and I am asking you decode it, then you will decode it in elaborate manner, no? You will decode it in more numbers. So output will be more. This is how also you can remember. Like usually I used to get confused. Like, okay, encoder is coming. So how many inputs will be there? How many outputs will be there? So in that manner you can remember. For decoder there will be less input and more output. And for encoder there will be more inputs and less output. So encoder is like a button. I will tell you it is like a button. How it is button? So let's check that out. And it will take input decimal, like input is like decimal digit. It's not decimal digit, it will certainly a bit, but it will act as a decimal digit and output will be binary code. Similarly in our decoder what was happening, like input will be 3 bits, but y0, y1, y2, y3, y4, y6, y7. So we can say it was like a decimal output. So similarly here the input will be like decimal but output will be binary. How will that happen? Let's check that out. So I am writing 4:2 encoder. So what I will do, if I click on the button denote, I will click on the button denote and I am not clicking on any button. So if I only click on denote button, then what it will take, that 0 is applied. And if what is the 0, what is the binary equivalent of 0? 0, 0. If I click on D1 button, if I click on D1 button, then it will say that 1 is applied. And what is the binary equivalent of 1? That is 0, 1. If I click on D2 button, then it will say that, then if I click on D2 button, it will say that 2 is applied. So 1, 0. And if I click on D4 button, D3 button, so it will say that 3 is applied. So 1, 1. What is the equation of A? When A is 1, when D2 is there and D3 is there. D2 is 1 or D3 is 1. A is 1 when D2 is 1 or D3 is 1. I know you will have the doubts. I know you have the doubt that then sir what will happen if we do this? That we will cover, okay? You will have this doubt, I know that. That what will happen if we click on D2 and D1 both together? Wait a second. Yeah. So this will be your A. What about B? What will be your B? So B will be 1 when D1 is clicked or D3 is clicked. Okay? This is the same. A is 1 when D1 is clicked or D3 is clicked, and B is 1 when D1 is clicked or D3 is clicked, right? Or D3 is clicked. So this is the expression. A is equals to D2 plus D3 and B is equals to D1 plus D3. Let's do the same for 8:3 decoder. So if I click on only D1, only denote. Denote means it will think 0 is applied. So 0, 0, 0. If I click on D1, then it will think 1 is applied. If I click on D2, then it will think 2 is applied. If I click on D3, it will think 3 is applied. If I click on D4, it will think 4 is applied. 5, it will think 6 is applied, and now it will think 7 is applied. So what is your A? Now your doubt will be cleared. What is your A? So A is 1 when D4 is clicked or D5 is clicked or D6 is clicked or D7 is clicked. B is 1 when D2 is clicked or D3 is clicked or D6 is clicked or D7 is clicked. And this C is 1 when D1 is clicked, D3, D5, D7. Now these A, B, C. Okay. So now what do I do? How do I design it? This is how I will design it. Denote. What about A? So A is D3 plus D4, D3 plus D5 should be there, no? Why it is D4? Why I am feeding D4? D3, D1, D0. Yeah, sorry. D4, D5, D6, D7. So this is A, this is B, this is C. Now I design this and go to my manager and tell him that, sir, I have designed this block. If you click on anything, if you click on denote, it will give 0, 0 output. If you click on D3, it will give the binary equivalent of that. If you click on D5, it will give the binary equivalent of that. So I got this design. I went to my manager and I told him. Now my manager is pressing D5 button. If my manager presses D5 button, then what will happen? D5 will be 1. If D5 is 1, then this is 1, so A will be 1. What about B? Can you see any D5 here? So he only pressed D5. That means D2 is 0, D3 is 0, D6 is 0, D7 is 0. So B is 0. What about C? He only pressed D5. So D5 is 1. D1 is 0, D3 is 0, D7 is 0. So ABC is 1, 0, 1. And 1, 0, 1 means 5 only. So okay, your manager is happy. Right? Now what your manager did? He clicked on both of the button, D5 and D6. He clicked on D5 as well, he clicked on D6 as well. Now what will happen? D5 is 1. He clicked on D5. And D6 is also 1. 1 plus 1, 1 plus anything will be 1 only. D5 or D6. If anything is there, D6 is there. So D6 is 1. So B will be 1. What about C? D5 is there. So if D5 is 1, that means C is also 1. So ABC is coming out to be 1, 1, 1. 7. Your manager clicked on D5 and D6, but your output is showing 7. That is wrong. Right? Now your manager is not happy. He will ask you, what did you design? So now you will say that, sir, I designed, but it can take only one input. You will say that, sir, I have designed it, but it can take only one input. Now what your manager will say? That this is not what I require. Look, if I am clicking D5 and D6, if I am clicking on D5 and D6, that way, then at least it should give one of D5 or D6. No, you are clicking on D5 and D6, it is giving D7. So at least one of them it should give. No, like I am clicking on D5 and D6 together. So either it should give me D5 or at least D6. So one it should give. So what is the issue? What is the issue here? That your encoder cannot take more than one input. Can't take more than one input. So now you will go back and what you will design? You will design such that if your manager is clicking on D5 and D6, then what is in your priority that will come out. So you will decide the priority order, that you will go to your bench, you will open your software and there you will design and you will decide your priority order, that my priority order is D6 is greater than D5. So if my manager is clicking on D6 and D5 together, then D6 will turn on because this is my priority. So you will decide the priority. So this is known as priority encoder. So that's why we need priority encoder. So if in the interview if they are asking why do you need priority encoder, then you will explain them by this example, that it cannot take more than one input. It cannot take more than one input. Okay. So this is our priority encoder. So I have defined the priority order here. So it can be anything. So for me the priority order is this: D3 is greater than D2 is greater than D1 is greater than D0. So this is how the user will define, not the user, designer will define it. Designer will define it. That, sir, if you are clicking on D3, then no matter what you click, it will consider this as 3 only and will give output as 1, 1. Now, sir, if you are clicking on D2, then no matter if you are clicking lesser than that, look, D3 is our priority. If I click on D3, no. If I click on D3, then it will consider D3 only. So at least D3 should be 0. What I mean to say that you are having, sir, 4 buttons. If you are clicking on this D3, then it will take D3 only. But for D2, if you want D2, then you can click on D2, but you cannot click on D3 because that is my priority. So D3 should be 0. Are you getting this point? Now it will take it as 2. 2 means 1, 0. Now, sir, if you want D1 in your output, then you can click on D0. Do not care about D0. But you cannot click on D2 and D3 because these are my priority than D1. This is my priority order. So this I am prioritizing over D1. So, so it will consider it as 1. And now if you are clicking on D0, if you want if you want your output to be D0, then you should click on D0 only. You should not click on these. Right? You should not click on these. If you click on these, then the one having the more priority will come up. So if I do this click, that I am clicking on D2 as well and I am clicking on D0 as well, then what will be the output? D2 will be the output because that is my priority, right? So how would I define A? And here it would be 0, 0. Okay, so what will be my A? So really sorry for the disturbance. I have, yeah. So what will be my expression A? So before writing A, I forgot to tell you one thing, that is what will happen if no button is pressed. If I am not even pressing any button, so both of the outputs will be don't care. I don't even care about the output, so both outputs will be don't care. So this is the truth table of A. Basically these are the outputs of A. 1 1 0 0 don't care, and this is for B. 1 0 1 0 don't care. So can I directly write it down? No, I should make K map. Why so? Why I should make K map? Because there is a don't care involved, no? So this 0 0 0 0 is don't care. Now how I can mark these ones? So whenever D3 is 1, whenever D3 is 1, do not care about D2, D1, D naught. So whenever D3 is 1, every time it will be 1 only. And whenever D3, D2 are 0, 1. So in this line, D3, D2, 0, 1. So do not care about anything else. Do not care about D1, D naught. So do not care about D1, D naught. It will always be 1. So this is how the truth table looks like. And here you can see there are 2 octet. One octet and another octet. So there are 2 octet, and directly I can see here D2 is constant and in the next one D3 is constant. So this is D2 plus D3, right? Here D2 is constant and here D3 is constant. And what about B? Now for B as well you will have to make another. So another I will have to make here. So what I can do is that I can pick this one up here. Yeah, it will work. So this was for your A. This was for A. Now for B this will be for B. So when D3 is 1, do not care about anything else. When D3 is 1, do not care about anything else. In that time B is 1, and when another time B is 1, another time B is 1 is 0 0 1, D is 0 0, and D1 is 1, and D1 is 1, 0 0 1, and do not care about D naught. So D naught can be anything. It can take any value. It can take 1 value as well, it can take 0 value as well. So that's the same. So here you can see there is a quad. Sorry, not a quad, octet is there, and quad is there. So what will be your expression B? So in this expression B, D3 plus here D1 is constant and D2 bar is constant. So D3 plus D2 bar, and this was your don't care, which was not included. Now if someone says I am smart sir, I would have directly written it that from here only, that A is 1, D2 rest all don't care, and then D2 bar, sorry, D A is 1 when D3 is there, plus D3 bar D2. That's it. So this can be reduced to D3 plus D2. So same expression I am getting. And for B, sir, I could have written in this manner, that for B, sir, when D3 is there, plus when D3 is not there, D2 is not there, and D1 is there. So what I would be getting? D3 plus D2 bar D1, because this can be reduced. So D3 plus D2 bar D1. So same expression I am getting. So sir, smartly I could have written it quickly rather than making the K map. Okay, you can write it. Because here this don't care was not used. But what if I ask you question like this in the examination? A 4-bit priority encoder is there. It has the input D3, D2, D1 and D naught in descending order of priority. So D3 is more important than D2, then D1 and then D naught. So this is the priority. D3, D2, D1 and D naught Outputs are AB, where A being the MSB, right? If you click on D3, do not care about anything else. Output will be with respect to D3, but with respect to D3, the output is 0, 0. Here there is a change. With respect to D3, output is 0, 0. Now, if you click on D2, do not care about anything. Sorry. If you click on D2, you should not click on D3. Now, do not care about anything else. Your output will be 0, 1. If you are clicking on D1, do not care about D0, but these should be 0. Output will be 1, 0. If you click on D0, these should be 0, and your output will be D0. That means output will be 0, 0. Sorry. For D0 output is 1, 1. For D0 output is 1, 1. But wait a minute. We forgot something. What is that? That if nothing is there, if no input is there, then both outputs will be don't care, right? Now, if I had solved it in this manner, what I need to find? Minimum number of literal count in the expression of B. So if I solve it like this, B is equals to D3 bar D2 plus D3 bar D2 bar D1 bar D0. Then what I would be getting? From here I can take D3 bar common. So this would be D2 plus D2 bar plus D1 bar D0. So this can be written as X plus X bar Z. So this X bar can be gone. So D3 bar D2 plus D1 bar D0. So what is your literal count here? So you will mark the answer 1, 2, 3, 4. 4 is my literal count. Wrong. Why is that so? Because this is don't care. It can take 0 value as well. It can take 1 value as well. So there might be the scene that it may come up. It may come up in the action. So always, whenever you see don't care in the output, always solve the problem using K-map. Don't be smart in the examination. Okay. Although in GATE 124 examination this question was asked, very straightforward. But in the examination, if in the truth table, I am talking about complete chapter. Okay. Whenever in the truth table, if you see a don't care, never ever solve it directly. Always use the K-map. So when B is 1, 0, 1, cross, 0, 1, and don't care about anything else. Rest 0, 0, 0, 1, 0, 0, 0, 1. Here it is 1. Rest all are 0. But for 0, 0, 0, 0, it is B is don't care. So this is don't care. So see here, you are using don't care in action. So one quad you are making, another quad you are making. So what is your B? Here what was our literal count? Here I did something wrong. Actually the thing is literal count 4 is the answer, but here literal count is not 4. For literal count you need to completely solve it, no? Luckily if I had done this error, it would be correct. So you have to solve this, no? So 1, 2, 3, 4, 5. 5 will be my literal count. You need to get it in the complete form. So 5 will be my literal count. Here if I say this is my reduced expression, this is my reduced expression, so this would be wrong. Or it could be in the option, no? What will be your reduced expression? So this would be in the option. So is it the reduced expression? No, this is not the reduced expression. Reduced expression is this, which is here 0 is constant, and here also 0 is constant, D1 bar is constant, plus in this one D3 bar D2. So that's the correct answer, and literal count is 4. So these kind of questions can come up where they can change the priority order and they may use this don't care. So that you need to take care in the examination, that even that don't care can be used. So I should not be that I will directly write down the expression. If this standard circuit is coming, then you could have directly written the expression, but better always use your K-map. Okay then. So that's it about encoder. Very easy chapter it was. It took roughly around 20 minutes only. So I will add it in the encoder video. Sorry, that's it about encoder. Okay. That's it about encoder, and I will just add it in the decoder video only. So because decoder and encoder combined will be of somewhat around 80 to 85 minutes. So interesting topic these are, but not that tough. Very straightforward, very easy. Now we are going towards adders. So those are very important, and in adders I will want your full attention. Just give your full attention, because a lot of people are confused in that particular chapter. So that we are going to cover very in depth. Okay then, thank you very much. Hi everyone, so now we are going to start studying about adders, a very important topic, and in your examination the questions will be coming from this topic. So I need your full concentration, and let's start this topic. So first we will study about half adder, then we will study about full adder. So what is a half adder? It will take 2 bit of input and will give sum and carry as output. Will take 2 bit of input, give sum and carry as output. Let's just say if I add 1 plus 1, sum I am getting, that is 0, carry is 1. Although you would say that sir, sum is 1 0 only, no. But what may happen is that, let's just say this calculation is there. So 1 plus 1 is 0. Then 1 is being carried. So this is what we mean, that this result will be there and this will be the carry. So that's why we call this as sum, this as carry. If you add 1 plus 1, this is your total sum. But we call this as sum and this as carry, because this calculation can be involved in a bigger calculation, right? So this will be your block diagram. 2 bit input is coming, sum and carry is there. So if A is 0, B is 0, so what will be sum? 0. Carry will be 0. If A is 0, B is 1, what will be sum? 1. Still there is no carry. If A is 1, B is 0, what will be sum? 1. Still there is no carry. If A is 1 and B is 1, what will be sum? 0 and carry is 1. Okay. So to the next calculation, this carry 1 can go. So sum is 0, carry is 1. Right. So from here what you can see, what is the expression of your sum? The sum expression is A bar B plus AB bar, or directly you can see it is A XOR B. And if you want to write down the minterms, that are 1 2. And what is the expression of carry? That is A into B. So this is your carry. Okay. This is how the circuit can be implemented. AB is coming, A XOR B, and this is your AND gate. Right? Very straightforward, very easy. But do it in your rough notebook. Draw it once. A XOR B, C is equals to AB. Draw it once. So if I say here AB is written and a block diagram is given, that is of half adder. So what will this bit represent? This bit will represent sum. So here I can write A XOR B, and here I can write AB. Well and good. Everything is crystal clear, right? So how will you make half adder using NAND gate? So I need to make A XOR B. So A XOR B using NAND gate, I get somewhat like this. But I need to make AB as well now, right? I need to make AB as well. So this is my sum, this is my sum, and this is my carry. So one thing I know, that is this is AB bar. AB bar is there. So what I will do, I will pick this AB bar. I will pick this AB bar here and give it to directly a NAND gate. NAND gate as an inverter, right? That's it. What this will generate? This will generate my carry. So my sum is also generated, carry is also generated. So carry is AB, sum is A XOR B. Very straightforward, right? If I want to use it, if I want to make it using NOR gate, so I know one thing, there are two ways of making NOR gate, right? What is the first one? I will quickly draw it. This was the first one, right? You can skip this part if you already know that. First you make the first you make XNOR gate, and once you are done making the XNOR gate, okay, let's just quickly draw it now, because we are not going to eventually use it. Then after making this, we add inverter. So this is how we make it, right? This is the first way of getting A XOR B. Here also 5 are used, but when we were studying, there also I told you there is one more method. What is that? I can plot this as A bar plus B bar into A plus B. I can write this as in this manner, right? Here at nowhere, here what I will be getting? I will be getting here A plus B bar. So I am not getting the sense that I can get AB. Can I get AB anywhere? Like it would be very tough to get AB from here. But what do you see in this one? That this is your AB bar and this is A plus B. You know how to plot this one. How to plot this one? How will you plot this? A bar plus B bar. How will you plot this? So first you will take the bar of A, then you will take the bar of B, A bar plus B bar, A plus B, and then the multiplication, right? Now to make this XOR gate, you need to add an inverter. Here also you need to add an inverter. Here also you need to add an inverter. Here also you need to add an inverter. So 1, 2, 3, 4, and 5. This is what you already know, right? And this is your sum. Sum will be A XOR B. Here you will be getting A XOR B, which is A bar plus B bar into A plus B. So if this is A and this was your B, so what you are getting here? A bar, B bar. And what you are getting here? A bar plus B bar bar. And what is that equals to? AB. And what is that equals to? Carry. So in this design, here only you are getting your carry bit. So you do not need to introduce other NOR gate. Only using these NOR gates you have introduced your carry as well. So this is how the design will look like. This is, here you are getting A bar, here you are getting B bar. This would be A bar plus B bar bar. So that would be AB, and this represent your carry. So this bit is your carry only. So directly you are getting carry here. And what this will be? This will be your sum. And if I say that sum of each NOR gate is TD, sorry, the delay of each NOR gate is TD. The delay of each NOR gate is TD. Then to get sum, how much time it will require? TD plus TD plus TD, 3 TD time. And to get carry, how much time it will require? TD plus TD, 2 TD time. So here the time delay was very less as well, 3 TD only. But if you had made the other design, then I told you we will use 4 levels there. So the delay would be more there, right? So that's why we will not go with this design, but we will go with this particular design only. Okay, so that's the best design, and we, without using any other extra NOR gate, we are getting our carry. So how many NAND gate you need to use? 5. First draw it on your own as well. Okay, you need to use 5 NAND gate. 4 half adder. To implement half adder, we need to use 5 NAND gate. And how much NOR gate you require? 5 NOR gate only, right? NOR gate is also 5 only. So 5 NAND and 5 NOR. Okay, now let's make half adder using Mux. So Mux has only one output, so we will have to use 2 Mux. So first we are making from 4:1 Mux. So what we need? We need A bar B plus AB bar, or simply I can say that I need my minterms M1 and M2. So these two will be 1, rest all will be 0, right? So this will represent my sum. Or you can see A bar B bar is coming, you need 0. If A bar B is coming, then you need 1. If A B bar is coming, you need 1. And if AB is coming, you need 0. That's it. And if I need to make carry, so if AB is coming, then only I need 1. Rest of the time I need 0. So this will be my carry. That is AB, right? If I need to make it using 2:1, so let's just say if this is my B, so if B bar comes, I need A. Sum is B bar A, or you can say plus A bar B. And if B is coming, you need A bar. So how will you get A bar? Put A here, this would be 1 and this would be 0. This will act as inverter. So A bar is coming, 1 will come, so here A bar you will get. So this is your again sum. Very easily you can write, right? This is your A XOR B. What about your carry? Carry is AB, very straightforward. If this is my B, so if B is coming, I would need A, otherwise 0. So this is my carry, which is AB. So very easily you can make the designs, because we have studied all these block diagrams or all these black boxes in a very in-depth manner. So now make half adder using demux and decoder. So what we need to do? So using demux, if I am making, so I will keep the information 1, and if I put A here, B here, that means this will show minterm M0, this will show minterm M1, this will show M2, and this will show M3. What you need? You need sum as A XOR B. And what all are the minterms there? The minterms are 1 and 2 and carry as AB. Wait a second, charger, just one sec. अभी चार्जर ऑन तो करने गया था बट लगाना ही भूल गया था, तभी ये स्लो चल रहा था. अभी ऑन है. हाँ. So carry is AB, right? And the minterm is M3. So this represent directly carry only. The screen will get better with time. No need to worry about that. So C will be AB only. And what about these two? These two will pass through your OR gate, right? So this will represent your sum, which is A XOR B. Or if you don't remember in terms of minterm, then you would know that, sir, if A bar, B bar, if A is not coming, B is not coming, then information will be transferred to Y0. If A is coming, if A is not coming, B is coming, then information will be transferred to Y1. So this would be A bar B, and this would be A B bar. So A bar B XOR with A bar B plus A B bar. So that would be my final answer. Okay, that would be A XOR B, and this is the carry which is AB only. Now here you put A, here you put B, because demux and decoders are similar only, just this information bit is here and these are the inputs. S1 is similar to X1 and S0 is similar to X0. Or if you don't remember this, then what you would say, so that if A is not coming and B is not coming, then Y0 will be 1. That means Y0 is A bar B bar. So this is your M0, this is your M1, this is your M2 and this is your M3, and I just need to add M2 and M3. Okay, and this will represent my carry, which is AB, and this will represent my sum. Well and good, very straightforward, very easy, right? So now as a summary, using NOR gate, if I am making half adder, how many NOR gates were required? 5. And how many NAND gates were required? 5. So this you need to remember. Sometimes directly in 1 mark it can be asked to make the function like sum and carry of half adder, how many NOR gates will be required to how many NAND gates will be required. So that answer you can make. So you need to remember it. Okay. Now you need to write down the minterms of Y1 and Y2. So let's try writing down the minterms. So minterms of F1 is given, that is 3, 6, 9, 10. F2 is given 5, 6, 9, 12. So here what I will get? A XOR B. Right, and here what I will get? AB. AB means, sorry, I should have written in F1 XOR X2, F1 XOR F2, and here I will get F1 F2. So for what does XOR gate do? Takes everything but remove the common part. Takes everything but remove the common part. So 6 is common, 9 is also common. So 3, 5, 10, 12. You will get 3, 5, 10, 12 here. 3, 5, 10, 12. What AND gate does? Since we have already solved these kind of problems, so directly I am telling now. Otherwise you can make the Venn diagram. AND gate, common only, A and B. So it will give only common. So AND gate will take only common. So 6, 9 will be coming here. So this input will be going here. So this will be 6, 9. What about this? This is your F3. Now between 3, 5, 10, 12 and this, what should be coming? Everything but not common. Everything but not common. So what is common? 5 and 10 are common. So what will be coming here? 3, 12, 1 and 14. So 1, 3, 12, 14. That's it, right? Because this is just the XOR. XOR of F1, XOR F2, XOR F3. So F1, XOR F2 you are already having 3, 5, 10, 12. Here it is 1, 5, 10, 14. So everything but not common. So 5, 10 will not come, 5, 10 will not come. So 1, 3, 12, 14. And what about this? Here you are having 6, 9. What you will have here? Dot of these two. Basically this is F1 XOR F2 dot F3. So end product of this and this. So end product of F1 XOR F2 is having 3, 5, 10, 12. And F3 is having 1, 5, 10, 14. So it will give only common. So what all common are there? Because this is AND gate. So common from here and here. 5, 10, 5, 10, 5, 10. 5, 10. And what OR gate does? Takes everything. So it will take everything. So here minterms will be 5, 6, 9 and 10. That's the correct solution. Okay. Very easy problem. So these kind of if block diagrams comes, so you will be able to solve it. right? Because these kind of questions can be coming up in your examination. Very easy, very straightforward. Now we will study about full adders. So in full adder there will be three inputs, okay, A, B, and this I will be writing as Ci, and they will produce sum and carry. What do you mean by this Ci? You will say that, sir, we can add only 2 bits only, no, at a time. So why are you saying there are 3 inputs? Yeah, you are correct, but 1 plus 1 is 0 and carry will be 1. So this addition we are doing this time. This addition you can do with the help of a half adder, right? This you can do with the help of half adder. How you can do? Because there will be 2 input, sum is generated, carry is generated. But here if you need to do this calculation, you need to use full adder. These 3 input you will give into full adder. So here full adder will be required. So this is what I mean by Ci. Carry generated in the previous term, and this is Ci plus 1. Ci plus 1 will be 1 plus 1 is 0, and carry will be 1. So this will be your Ci plus 1. Ci plus 1, and this is known as sum, and this is your Ci. Carry generated from the previous stage and added with AB. This is your A, and this is your B. So this Ci you are getting somewhere from here. It is being added with AB. You are generating a sum and a carry. Understood? Okay, because this thing will be used in binary parallel adder. That's why I am telling here. So let's derive the functions. What we will be getting. So 0 plus 0 plus 0, sum is 0, carry is 0. 0 plus 0 plus 1, sum is 1, carry is 0. Sum is 1, carry is 0. 0 plus 1 plus 1, sum is 0, carry is 1. Sum is 0, carry is 1. 1 plus 0, sum is 0. Sorry, sum is 1, carry is 0. Here sum is 0, carry is 1. Here sum is 0, carry is 1. Here both are 1. Sum is also 1, carry is also 1. 1 plus 1 plus 1, that would be 3. 3 means 1, 1. So sum is 0 and carry is 1. Sorry, sum is 1 and carry is 1. Right? So if you see the min terms of S, that would be 1, 2, 0, 1, 2, 3, 4, 7. 1, 2, 4, 7. What does this represent? Let's check. 0, 1, 0, 1. If in the K map I would have written something like this. In the K map, if I am writing something like this, so what is that? 0, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. So 1, 2, 4, 7. What does this represent? XOR gate, right? Although there are 3 inputs, so XOR and XNOR will be same only. So sum will be your A XOR B XOR C. That can be written as XNOR as well, but we generally write XOR only. And what will be your carry? What all are the min terms? 0, 1, 2, 3, 5, 6, 7. Do you remember this? I asked you to remember it very, like I focused a lot on this, right? So what is this 3, 5, 6, 7? In the first video only you would see that I was focusing a lot on this. 3, 5, 6, 7. AB plus, here I should write Ci, and here I should write Ci plus 1. So Ci plus 1 would be AB plus BC plus Ca. Or what you can write? AB plus Ci A XOR B. Anything else also you can write. A lot of things you can write. BC plus AI B XOR C. And in that manner there are a lot of expression, but we will be focusing on this and this. Okay. AB plus BC plus Ca, AB plus Ci A XOR B. Okay, we will be focusing on this, right? So this is the sum expression and this is the carry expression. Now let's see a very interesting observation. So here I am writing down the carry terms, not the sum term. So sum is 0, carry is 0. Sum is 1, carry is 0. Sum is 1, carry is 0. Sum is 0, carry is 1. Sum is 0. Here, sorry, carry is, here sum is 1, carry is 0. Here sum is 0, carry is 1. And here sum is 0, carry is 1. And here also carry is 1. Can you see these two cases? When my input A and B are both 1, in this case my input A and B are both 1. then irrespective of the previous carry, my carry is always 1. So I will give you a very good intuition here. Okay, I am writing down the expression of Ci plus 1. So if my A is 1 and B is 1, I do not need to care about these. If my A is 1 and B is 1, then I don't need to care about Ci. My sum will be 1. Sorry, my carry will be 1. Forget about sum, I am only writing about carry. If my A is 1, let's call it Ai for now and Bi. Basically, these terms I am calling this term. This is Ai, this is Bi. Okay. So for now I am calling at Ai and Bi. So if my Ai is 1 and Bi is 1, then I do not need to care about Ci. Whether it is 0 or 1, my carry will always be 1 only. Let's see one more thing. See these 4 terms. Here, if this is 0, this is also 0. If this is 1, this is also 1. If this is 0, this is also 0. And this is 1, then this is also 1. So what all are the other condition? So if one of Ai or Bi is 1, if A is 0, B is 1, A is 0, B is 1, or if A is 1, B is 0, A is 1, B is 0, then my carry will be propagated. Then Ci will be propagated. What does this represent? That either of A or B is 1. Either of A or B is 1. Both cannot be 1 and both cannot be 0. Then only Ai XOR Bi will be high, right? Ai XOR Bi, when it will be high? When one of them is 1. So either of A or B is 1. So if either of A or B is 1, then this carry will be propagated. So if this is 1, then your answer will be Ci only. Do you remember magnitude comparator? There we wrote the expression in that manner. So you know this carry expression, but I gave you an intuition. Like you would know that this, like those who have already studied this chapter, they would know that this term is known as carry propagating term. Sorry, this is known as carry generating term. And this term is known as carry propagating term. And this is your Ci. So your Ci plus 1 is written as Gi plus Pi into Ci, where Gi is your carry generating term. And this is equals to Ai Bi. So if my Ai is 1 and Bi is 1, then irrespective of the previous carry, Ci plus 1 will always be 1. And what about this? If one of Ai or Bi is 1, then carry will be directly propagated. So carry propagating term. Okay, so that would be Ai XOR Bi. So if one of them is 1, then carry is propagated. So this is how you get the expression of Ci plus 1 without even deriving anything, nothing like that. Okay, and this intuition I will be using in binary parallel adder. That's why I taught this here. So there I am not going to teach it. In after 1 or 2 lecture you will see binary parallel adder. So there I will be using this intuition. So what all the conclusion we can make, that if when A is 1 and B is 1, then irrespective of the previous carry, my carry will always be 1. So in some calculation, let's just say in some calculation, I get these terms. So here carry is 0, no need to worry about. Now if I ask for this calculation, what will be your sum and carry? Then you will say that, bro, for sum I will have to look at the previous state, because if my Ci is 0, then sum will be different. If it is 1, then sum will be different. But for carry I do not need to look here. No matter whatever there is, no matter whatever bit is there, it will always generate 1 carry. So in my device, if I put 1 and 1, then without even thinking about the carry, I can tell that my carry will be 1, that's for sure. No one can stop it. Say yes or no. Right? And one more thing, that let's see this calculation. So if I see this calculation, 0 and 1, 0 here and 1 here. So if I see this calculation, what I will say, that whatever the carry I get here, that will be propagated. Whatever the carry that I get here, that will be propagated. So I have to wait for the previous carry, that what carry comes. If this carry is 0, then this 0 will be propagated, and if this carry is 1, then this 1 will be propagated. So it will depend on the previous carry, right? It will depend on the previous carry. So whatever is the previous carry, for that we have to wait, right? Okay then, yeah. And what all terms will never generate any carry? If a and b both are 0, then there is no carry. If a and b both are 0, there is no carry. And whenever you get 0 carry, if a is 1, sorry, if a is 0, b is 1, or if a is 1, b is 0, and the previous carry is 0. Look, see these two, this one and this one, and see these two as well. So when your carry is 0, when your carry is 0, when a and b both are 0, so that's it, there will be no carry. Now if your a is 0 and b is 1 and your previous carry is 0 and this carry is 0, I am taking this condition, no? A is 0, b is 1 and this carry is 0, then this carry will be propagated, then your carry will be 0 only, final carry will be 0. And if a is 1 and b is 0, if a is 1, b is 0, and if your previous carry is 0, then there will be no carry generation. And when there will be certainly carry generation, if you are getting 1 1, so certainly there is carry generation. If you are getting 0 1 and 1 here, then certainly there will be carry generation. If you are getting 1 0 and 1 here, then certainly there will be carry generation. Can you keep this thing in your mind? Certainly you will be able to keep these things in your mind when we do the problems of binary parallel adder. But there I will be using it directly. Here I have given the intuition. What all are the intuition? I will repeat everything. Let's start from the beginning. This is very important point, and like those questions which are very good from your previous year gate problems, those will be solved very quickly. So very important intuitions these are. So if your a is 1 and b is 1, if a is 1 and b is 1, do not care about the previous stage, directly take an action. Okay. If a is 0, b is 0, certainly there will be 0 carry only. No need to worry about that. Now if a is 1 and b is 0, then you need to take care of the previous state. Here what will come? But if a is 1, b is 0, or if a is 0, b is 1. But here in the previous state, if you are getting carry 1, that means this carry will be propagated and 1 carry you will get. And here as well the same thing will happen. This carry will be propagated. But if a is 0, b is 1, a is 1, b is 0, or if a is 0, b is 1 and previous state carry is 0, then your carry will be 0 only. So the condition that when your carry is 0, when a and b both are 0, or a is 0, b is 1 and ci is 0. If I need to write, what will be my ci plus 1 bar? Not important, just I am writing. If a is not there, b is not there, then certainly my ci plus 1 will be 0. Or a is there but b is not there, and a is there, b is not there, and my previous carry is 0. Or if a is not there, b is there, and my previous carry is 0. So you can write this as a bar b bar plus a XOR b c bar. And what is bar of that? This is your self dual. So you can take individual bar. Here also you will take bar only, and here you will add bar. So bar and bar will get cancelled, and this is the only expression you will get. We have seen this thing, right? Already we have seen this thing. So what did you get to know? So this is how I wrote the expression of ci plus 1 bar. Okay. So when you don't get a carry and when you get a carry, that I wanted to tell. So when you don't get a carry and when you get a carry, that also you understood. And why these terms are known as generating term, carry generating term, and why this term is known as carry propagating term, that also you get to know. Okay. So let's remove the extra part. Yeah. Okay. So these are the important points. When a is 1, b is 1, irrespective of the previous carry, your next carry will always be 1. When a is 0 and b is 1, or a is 1 and b is 0, and in both of the cases ci is equals to 1, then carry 1 will be forwarded, but it is depending on the previous carry. It is depending on the previous carry. It is depending here. Here I did not even mention about CI. CI don't, so CI doesn't even matter. So in these two cases, your CI plus 1 is 1. That's the thing. So these two cases are for CI plus 1 is equals to 1. And if this was 0, then there will be no carry. Carry will not be generated. If this was 0, then carry will not be generated. But if it is 1, then carry will be generated. Now, for rest all the cases, your CI plus 1 is 0 only. Okay. Here I have written if A is 0, B is 1 and CI is 0, then CI plus 1 will be 0. A is 1, B is 0 and CI is 0, then CI plus 1 will be 0. Very easy thing. Okay. So these we will be using, but here only I wanted to give you the intuitions that I have given. Let's go to the simpler things now. What we need to implement? We need to implement full adder using NAND gate. So how we will do it? First we will make A XOR B using NAND gate, and then we will make XOR C. Basically, first I will make A XOR B, and then I will make XOR CI, right? So that's it. First A XOR B, then from here CI is coming. So from here what you will get? A XOR B XOR CI. This is your sum term. How do you get your carry? So what an AND gate do? X into Y bar. So X bar plus Y bar, right? X bar plus Y bar. You need AB. That means you need AB bar to bar. Somewhere you will require AB. Somewhere you will require AB bar. And somewhere you will require CI into A XOR B bar. So let's see where do you get it. Here what you are getting? What you are getting here? AB bar. You are getting AB bar here. And what you are getting here? CI into so you are getting CI into A XOR B bar, and this is your AB bar, and this I will pass through your NAND gate. If I pass through the NAND gate, what I will get? This is your Y. So multiplication of these two into bar. Let's just say I call this as X. So X bar into Y bar to the bar. So what that would be? X plus Y. So here I will get AB plus CI A XOR B. So this is not Y, this is actually your carry only. So you generated the carry. So 4 NAND gate here, 4 NAND gate here, and 1 NAND gate here. Total NAND gate are required are 8 NAND gate. 8 NAND gates, right? Total 8 NAND gates were required. Well and good. Understood? Yeah, actually a slight error. This would be 9 NAND gates, no? So 9 NAND gates are required. So to generate the sum, 8 NAND gates are required, but to generate sum and carry both, 9 NAND gates are required. Okay, let's move forward in this lecture. Now let's see how to implement this using NOR gate. Okay, so this seems very easy. This you can make on your own. How will you make it? You will not make XOR gate, you will make XNOR gate, right? Because XNOR and XOR are equal, and I can make XNOR using 4 only, right? So here I will require 4, and for this as well I will require 4. So 4 plus 4 in 8 I will be able to make. So 4 first and then another 4. So this is your A XOR B, and this is my A XOR B XOR C. Basically this C is going here, this is CI, and this is also CI, this is CI, right? But now this will be interesting. How will you think of it? Look, I can directly tell that's take from here, but we need to take the intuition. Okay, don't directly look at the circuit. You need to understand that how it came. And what if in the examination you need to implement a random function? Then how will you implement that particular random function? So that's why I am telling you in the previous problem as well that I told you how to approach this. So here I will also tell how to approach this, how to implement this using XOR. So if I try to go that what XOR will give me x plus y bar, but here I need only x plus y. I do not need x plus y bar, right? So this doesn't work. So what if I go with this one, x bar dot y bar? Doesn't seem like that it will give me x dot because already it is x plus y. So what I can do, what else I can think? What else I can think is that this is a self dual function, right? Self dual. Can I take dual of this? Certainly I can take dual of this. Ci plus 1 dual will be equals to Ci plus 1 only, and that will be equals to a plus b. This will be converted into dot. This will be converted to plus a plus b. This is converted to dot. This will be converted to plus, certainly converted to dot. So this term will be there, and what this will be converted to? X no, right? A bar b plus a b bar. If you take dual of this, what you will get? A bar plus b dot a plus b bar. And what is this? X nor only, right? And why did I put this bracket? Because this term was completely in addition to this term. So now this term will be completely in multiplication to this term. So that's why I put the bracket there. Okay. Now I can think something, because I can get x plus y bar. So now it feels like that something can happen, because this is a plus b, right? This is a plus b. So a plus b bar already I am getting from here. A plus b bar already I am getting from here. So now I can think of taking this out. And what I am getting here? Ci plus ax nor b. So Ci plus ax nor b bar I am getting here. Ci plus ax nor b bar you are getting here at this term. Then you can think of taking out these two. So if I think of taking out these two, if I am taking out these two, and then if I connect two inverters and a AND gate, this is what we are having here, right? And of these two. So bar is there, so dot. Bar is there, so bubble, and then AND gate. So what is this? This is NOR gate only. Bubbled AND gate is NOR gate. So this was your NOR gate only. So this is how you got the expression. Although people will usually remember it, that take output from here and take output from here. That's it. Same thing. You took output from here, you took output from here, and it will be remembered to you, because this is very standard circuit. But what if in the examination you need to think in this manner? So that's why I am telling you can think as well. So before the examination we will think everything, but in the examination we will think as less as we can. If we have thought enough in our preparation, if we mug up less thing and we think enough in our preparation, then examination will be very easy for us. So this will be your Ci plus 1. I do not need to write the final expression, you already know the final expression. So this is your Ci plus 1 and this was your sum, right? And if I ask you a question that all the gates are having TD delay, all the gates are having TD delay, then what will be the total delay in receiving the sum? What will be your answer? TD plus TD plus TD plus TD plus TD plus TD, 6 TD. If all the gates are having TD delay, then what will be the total delay in receiving Ci plus 1? TD, TD, okay, plus TD, plus TD, plus TD. So this will be stable after 4 TD and this will be stable after TD only. But this guy will have to wait for this guy. These concepts we will see in the next video. If you are not able to understand, you will understand in the next video. In the next video only we will be dealing with these concepts. So here this will take TD, this will come after TD, this will come after TD. So our Ci plus 1 is depending on these two inputs, right? This input is stable after TD time, but this input becomes stable after 4 TD time. So it is taking 4 TD time. So it will be stable after 4 TD time. So this guy will have to wait. This guy will have to wait for him. If both input are stable, then both will go. So 4 TD plus TD, 5 TD. So Ci plus 1 you will receive after 5 TD and sum you will receive after 6 TD. Okay, same goes for NAND as well. So these delay problems we will see. Just here I wanted to give you a question only, like if you are able to solve here then it is fine, if you are not able to solve here then it will come to you again. Okay, these delay based problems are very important and we are going to solve a lot of problems based on that, right? Now you need to make full adder using half adder. So try making it on your own and then see my final solution, because you can make it on your own as well. It is not that tough. Two half adder we will use, and this is your input. Input is A and B. Input is A and B. So what we will receive as sum? Sum we will receive as A XOR B. A XOR B. Right? Now this will be fed to this input. This is the sum which is A XOR B. This is fed to the other half adder. Okay, and this Ci which is there, it will be fed here. It will be fed here. Ci which is there, it will be fed here. So here one input is there, another input is there. So what will be the output? Output of half adder is, some output of half adder is XOR of these two. So XOR of these two, it will be A XOR B XOR C. So this is your sum. What you need to generate now? I need to generate carry. What I need to generate? I need to generate carry. So for carry, what do I need? AB. So first I need AB. So from here I will get AB. Right? From here I can get AB. Next, what do I need? Next I need Ci into A XOR B. So what is the input of this? A XOR B. And what is the other input of this? That is Ci. Right? So what is the carry of half adder? Multiplication of these two. Multiplication of these two input. So multiplication of these two input, what that will be? Multiplication of these two input will be what? Multiplication of these two input will be A XOR B into Ci only. And now both should be added. So how both can be added? Using your XOR gate. Sorry, not XOR gate, using your OR gate. That's it. Okay, so this is your carry. Now if you are watching this lecture and you listen to my words, okay, if you listen to my words, if I mean something to you, then I am asking you to draw this circuit in your rough notebook at least 3 times. Right now only, pause the video, draw it for 3 times. If I mean something to you, and if you want to learn from me, if you want to learn something good, draw this circuit 3 times on your own. Okay, I hope you have drawn it at least 3 times. This should be fit in your mind. Even if you close your eyes, half adder, input goes here, this output comes back, this input goes here, this output here, this goes here, and OR gate. It should be clear in your mind. You should not take this much time. This I was explaining here, but if I had to draw it quickly in the examination, I can draw it in seconds. Because it will be used, highly used. It will be highly used. Okay. So this manner we will be drawing. Can you draw it on circuit level without watching the next slide? Draw it on the circuit level. What do I mean by circuit level? You will make the half adder using the circuits. How did I make the half adder? How did we make the half adder? A XOR B. AB was there, right? And this AB again was fed to AND gate. So this is how we made the half adder, right? So just draw it on the circuit level. On the circuit level, this is how it will look like. So if I mean to you, if I mean anything to you, draw it on your own. Pause the video 3 times in your rough notebook. Why I am focusing so much on this, you will realize when we study binary parallel adder. That is the most important point or most important topic you can say of this particular combinational circuits. Okay, so for that only we need to make it. So A XOR B coming from here, AB coming from here. So this is our one half adder, this is our another half adder, and this is our OR gate. So full adder will take two half adder and one OR gate. So what do you think? What will two full adder take? Two full adder will take four half adder plus two OR gate, right? What three full adder will take? Three full adder will take six half adder plus three OR gate. So if I say n full adder, so n full adder will take 2.5 adder plus n OR gate, right? Sometimes it can also be used that n full adder will take 2.5 adder and n OR gate. So now I hope you are understanding this concept, right? Okay. So I hope you must have drawn it at least 3 times in your rough notebook. It will be used a lot of time, right? So this picture is clear to you now. Now we will make it using muxes. Very easy, very straightforward. Let's make it using 8:1 mux. So what I need to make? I need to make, here I am making sum term. So what is that? A XOR B XOR C. And what that would be? 1 2 4 7. 1 2 4 7. Do you remember it? 0 1 0 1 1 0 1 0. This is 0 1 2 3 4 5 6 7 1 2 4 7. So 1 2 4 7 will be 1 1 2 4 7. Rest all will be 0. Okay. So this is these minterms we are getting. And what about your output? Carry plus 1, Ci plus 1. This is your Ci. This is also your Ci. Ci plus 1. What all minterms it will have? 3, 5, 6, 7. I asked you to remember it. At least you should remember these. This will be the diagram we get, right? 0, 1, 2, 3, 4, 5, 6, 7. So I highly recommend you to remember this 3, 5, 6, 7. For minterm 3, 5, 6, 7, you get AB plus BC plus CA. And if you get AB plus BC plus CA, that is a self-dual function, and a lot of expressions are there. AB plus BC plus CA, but we can write it in this manner as well. So that is very important. Okay. Now you can make full adder using decoder as well. How will you make it? So we know the minterms. What all minterms you require for this one? For sum, what all minterms you require? 2, 4, sorry, 1, 2, 4, 7. 1, 2, 4, 7. So 1, 1, 2, 4, 7 I require. 1, 2, 4 and 7. So this will be your sum. And what about carry? 3, 5, 6, 7. 3, 5, 6 and 7. So this will be your carry. So generally what easy level problems can come is that they will implement this function and they will ask you this particular diagram represent what. So you will say this particular diagram represent your full adder. Okay, they will make this particular circuit. Here they will write y1, here they will write y2, and they will ask what this particular circuit diagram represents. So directly you can see what all minterms are there. 1, 2, and in this one 4, 7. 1, 2, 4, 7. So sum. This will represent sum. And what about this? 3, 5, 6, 7. 3, 5, 6, 7. That means this will represent carry. So this is a full adder. So these kind of questions can be asked, and in the interview they can ask you to draw it as well. Okay. Now full adder can be made in this manner as well, right? So this is known as two-level XOR. Two-level XOR, level 1 and level 2. So this is made using two-level XOR and two-level AND OR. So So AB plus BC plus CA. Here you are getting AB, here you are getting BCI, and you are getting CIA. So AB plus BC plus CA. So if I ask you what will be the delay of sum, so what you will say? Delay of XOR, delay of XOR. That will be your sum delay. And here if I ask you what will be the delay of sum, so delay of these gate plus delay of this. Delay of these gate plus delay of this. That will be your carry delay. Okay. So these two types can be there. So in the next video we will see delay based problem on that. Okay. That is our next particular video. So we will see delay based problem. So there we will use these structures. So for different structure, different delay can be there. So how we will see what kind of delay would be there and how much delay will be there. So that we will see in the next lecture. So what is the summary? Using NAND gate, you need to make half adder using NAND gate. How many NAND gate are required? 5. Here also 5. Here 9. Here 9. And full adder using half adder, 2 half adder plus 1 OR. Right? So that's it. This is the analysis of our half adder and full adder. The most important discussion here, what was the most important one? This is very important, that you need to make full adder using half adder. Circuit diagram should be crystal clear in your mind, right? And this was also very important. Which one? This one, the carry one. The carry one. Again I am repeating, both are 1, then directly it will be always be 1. And if one of them is 0, one of them is 1, then carry is propagated. And in which cases carry is 1? When the previous carry is 1 only. Otherwise carry is 0. So this you need to remember. Only this much is the summary of this particular slide and this slide as well. And it is very important. So we are setting up our base for binary parallel adder. In next video we will study delay in full adders, that will set up our base more. So if we take this much of base in binary parallel adder, then it will be a cakewalk. Otherwise it will be very difficult to solve all the problems. Very difficult, like quite impossible. Okay, so let's meet you in the next video. There we will see very interesting concept of delay in full adders. Okay, thank you very much. Hi everyone. So in this video we are going to study the concept of delay based problems on full adder. So this is a very important concept and very conceptual. If you haven't studied it, you will not be able to do the problem in the examination. And it is a very important concept. Till now these kind of questions haven't been asked, but certainly it will come. Okay, and I want your full concentration, then only you will be able to understand it. So let's start with the first problem. So a full adder is made from 2 half adder and OR gate. I hope you know how to make a full adder from 2 half adder and OR gate, right? The delay for half adder, the delay of producing sum is 20 nanosecond. The delay of producing carry is 30 nanosecond. The delay of OR gate that you will be using, that has the delay of 10 nanosecond. Find the delay in receiving the sum and carry of full adder if all the inputs are stable at t equals to 0. That means input A, B, C will be stable at t equals to 0. So these inputs are applied at t equals to 0. Okay. Now this sum will depend on this A and B both, right? This sum will depend on A and B. What is the sum? We don't care. But I know that this sum will be function of both A and B. Say yes or no. This carry will also be a function of both A and B. Actually sum is A XOR B and carry is AB. But they are certainly function of AB, right? They are certainly the function of A and B. Now this is your CI. And I am calling this function as, I am calling this as a variable A. So this sum will be function of this A and CI, right? And this carry will be function of, although it will be a different function, so I should denote it with G. This I should denote with HI. So this will be a function of, and this will also be a function of A and C. A and CI, right? So what do you understand by that? That this output will depend on both of these input, and this output will depend on both of these input. Say yes or no, right? Now let's remove it off. Just I wanted to give this point to you, that both of the outputs of half adder will depend on both of the inputs. This is what I wanted to tell here. Now these inputs are applied at t equals to 0, right? So they are stable at t equals to 0. So this input is stable at t equals to 0 nanosecond, and this input is stable at t equals to 0 nanosecond. Now this half adder has the capability of giving the output at t equals to 0 nanosecond. Say yes or no. Do you agree to this line? This half adder has the capability of giving the output at t equals to 0 nanosecond because inputs are stable at t equals to 0 nanosecond. Now to produce the sum, how much time it will take? 20 nanosecond. Look, inputs were stable at t equals to 0 nanosecond. Now from here to go here, it will take 20 nanosecond time. So this you will receive at 20 nanosecond. And this you will receive after 30 nanosecond, because to produce carry it will take 30 nanosecond. So to go from here to here it will take 30 nanosecond. Till now the things are clear. So if this is stable after 30 nanosecond, that means this input is also stable after 30 nanosecond. Say yes or no. This input is also stable after 30 nanosecond, right? Now this input is stable at 0 nanosecond only. This input is stable at 0 nanosecond only. Now output of this half adder is depending on this input as well and this input as well. But this input is being stable at 20 nanosecond, although this is stable at 0 nanosecond only. But this is being stable at 20 nanosecond. So this half adder has to wait for 20 nanosecond. So this half adder will be in position of giving the output at t equals to 20 nanosecond. Are you getting this point? Let's revise it again. We started from here. They were stable at t equals to 0 nanosecond. So this has the capability of giving the output at t equals to 0 nanosecond only. So it will take 20 nanosecond time. It will take 30 nanosecond time. Now this has become stable at t equals to 0 nanosecond. But this became stable after t equals to 20 nanosecond. So this half adder has the capability of giving the output after 20 nanosecond. Say yes or no. Right? Now this sum will take 20 nanosecond and this carry will take 30 nanosecond. So these inputs are stable. The inputs are stable. Both of this was stable at 0 nanosecond, this was stable at 20 nanosecond, but this input has to wait for this guy. So this guy is waiting for this guy. Now both of the guys are stable at 20 nanosecond. Although he was stable at 0 nanosecond, but both came together at 20 nanosecond. Now both came together, now both will go to output. So if both came together and both are going to output, how much time they will take? 20 nanosecond more. So this sum will be stable after 40 nanoseconds. Say yes or no. Understood? Now this is 0 nanosecond. This was stable at 0 nanosecond, right? But this output C is depending on both of the inputs. This will take 30 nanosecond time, so this will be stable after 15 nanosecond, right? Because both were stable at 20 nanosecond, so both will take 20 nanosecond, they will start going, and now they will take 30 nanosecond time to reach here. So now this input has become stable after 15 nanosecond, and this input has become stable after 30 nanosecond. So this guy was waiting for this guy, that when this guy comes and we start going. So this guy was waiting for this guy, right? Now when they will start going? After 15 nanosecond they will start going. Plus how much time they will take to cover this OR gate? 10 nanosecond time. So what will be the delay here? 60 nanosecond. So for the carry it will take 60 nanosecond time, and for sum it would take 40 nanosecond of time. That's the delay. Are you able to understand it? Let's see it again. All were stable at 0. This has the capability of giving the output. So this will give the output after 20 nanosecond, and this will receive the output at 30 nanosecond. So this becomes stable at 30 nanosecond. Let's wait here. Now this, for this full adder, for this half adder, the output is depending on both of the inputs. So both inputs becomes, this input becomes stable at 0 nanosecond only, but this guy has to wait for this guy, because this guy will become stable after 20 nanosecond. So after 20 nanosecond this guy became stable. Now this guy has become stable. Now they both will start going. So to reach till sum they will take 20 plus 20, 40 nanosecond time. To reach till carry they will take 20 plus 30, 50 nanosecond time. Now both are stable at 50 nanosecond, because this guy was waiting for him, right? This guy was waiting for him. Let's just say if you have got, anyhow if you had got 25 nanosecond here, then what would be the delay in CI? That would be 30 plus 10, because this guy will have to wait for this guy, because this guy will come after 30 nanosecond. Are you getting this point? By any chance if you had got 25 nanosecond here, so this guy would be waiting for this guy, because both will become stable if both are stable. So one guy alone cannot go, because your output is depending on both of the inputs. So stable output it will give only after both are stable. So in this question it was stable at 50 nanosecond. So it gave the output 50 nanosecond plus 10 nanosecond, that means after 60 nanosecond. So carry is received after 60 nanosecond and sum is received after 40 nanosecond. I hope this is clear. Let's move towards next question. So difficulty level will increase. This was the least difficulty level, now it will increase. So this question is given, okay. For t less than 0, a is 0, b is 0, ci is 0. For t greater than 0, a is 1, b is 1, ci is 0. Same question is there, same delays are there, and same question is also there, just I have changed the condition. Do you think there will be any change in the final answer? Well, 98% people will say, sir, there will be no change. Why there will be a change? But there will be a change. Let's check that out. For t less than 0, a was 0, b was 0, and c was 0. So this sum was 0, this carry was 0, everything was 0. This 0 plus 0 will be 0, carry is 0. This 0 is fed here, 0 plus 0 is 0, carry is 0, and this is also 0. So everything was 0. Now 1 1 0. So this has become 1, this has become 1, and this has become 0. So what will be your sum? 1, if you talk about this half adder, 1 plus 1, sum will be 0 and carry is 1. Do you understand this point? In this half adder, 1 plus 1 is fed. So sum is 0, carry is 1. So this 0 is going to 0 only. This 0 is going to 1, right? And this 0 is 0 only. This 0 initially was 0 and now it is also 0. So 0 plus 0, this will also go to 0 only. And what will be the carry? This is 0. Okay. And what will be the carry here? If 0 plus 0 is being added, so this carry is also 0. Now this 0 has become 1. This 0 has become 1. Basically, this 0 has become 1. So what will this output will become? This output will become 1. Now if I ask you, at what time you get stable output of sum, what will be your answer? 0 nanosecond. Say yes or no? Because for t less than 0, your output was 0 only, and here also your output is 0 only. This output did not change. Sum did not change. That means sum will be stable at t equals to 0 nanosecond only. So if they are asking how much time they are taking to receive the sum, you will say 0 nanosecond, because it never changed. For t less than 0 as well it was 0, for t greater than 0 as well it is 0 only. The sum did not change. So this is the important point. If you have done in this manner, you would have got 40 nanosecond answer, but that is wrong. Here also you can see, what you can see, here the sum was, what was the sum? 0. What was the carry? 0. What is the sum here? 1 plus 1, sum is 0, but carry is 1. So sum did not change, and if sum is not changing, it will take 0 nanosecond time. So this is the answer for the sum, 0 nanosecond time. This is the answer. What about carry now? So this carry is changing, so that we have to analyze now. So these inputs became stable at t equals to 0 nanosecond, right? Both of the inputs became stable at t equals to 0 nanosecond. So now this half adder has the capability of giving the output at t equals to 0 nanosecond only. But you do not need to see the change here, because this is changing, this is not even changing. So I will need to see the change here. So how much time it will take? To go from here to here, it will take 30 nanosecond time, because for producing the carry, the delay is 30 nanosecond. So this will become from 0 to 1 at 30 nanosecond. At 30 nanosecond. Right? So this has become 0 to 1 at 30 nanosecond. Tell me one thing, this change? No, this did not change. This also did not change. This also did not change. So this was stable at t equals to 0 nanosecond only. This was stable at t equals to 0 nanosecond only, no? Because it did not change. But this came after 30 nanosecond. This guy came after 30 nanosecond. So this guy has to wait. This guy has to wait for this guy, that when it becomes stable. So it will become stable after 30 nanosecond. So 30 plus 10. So after 30 nanosecond, they both will go, and it will take them 10 nanosecond to cross. So 30 plus 10, that means after 40 nanosecond, this will become stable. So for carry, it is 40 nanosecond. So that's the answer. That's the answer of both of the questions. So every time when inputs are given, you need to be aware that what is changing, what is not changing. Let's see more problems. Full adder is made using half adder and two adder. Same things are given. At input A and B are stable at t equals to 0, but Ci arrives after 40 nanosecond. Ci arrives after 40 nanosecond. Find the maximum delay in receiving the sum and carry. So again here no inputs are mentioned. Again no inputs are mentioned. So this would be an easy problem. But the thing is, this becomes stable after 40 nanosecond. Now this is stable at t equals to 0 nanosecond, and this is also stable at t equals to 0 nanosecond. The input of both of the adder are stable at t equals to 0 nanosecond. So this has the capability of giving the output now. So the sum will be stable at 20 nanosecond and carry will be stable at 30 nanosecond. Now the input of this became stable at 40 nanosecond. The input of this half adder, one of the input of this half adder became stable at 20 nanosecond, but one of the input of this half adder became stable at 40 nanosecond. So they both will go after 40 nanosecond because this guy will have to wait for this guy. So both will go after 40 nanosecond, and to go here, how much time they will take? 20 nanosecond more. So 40 nanosecond plus 20 nanosecond, that means 60 nanosecond. And to go from here to here, how much time they will take? 40 plus 30, that means 70 nanosecond. So this guy is stable at 70 nanosecond, and this guy became stable at 30 nanosecond only. Right? This guy became stable at 30 nanosecond only. So this guy will have to wait for this guy. So here 70 nano plus 10 nano, because after 70 nano they will start going, they will have to cross 10 nano. So this will be 80 nanosec. Well and good, understandable. This was also easy question only, just the difference was this came later on. Let's solve this question. I just made the block diagram here. Okay, for t less than 0, a was 1, b was 0, and ci was 1. And for t greater than 0, this has become 1, but that means this is 1 only. This has become 1 and this has become 0. Okay, so let's see the first condition, 1 0 1. So if 1 0 was there, so sum will be 1, carry will be 0, right? So let's remove it off, otherwise it will make the confusion. So I am analyzing for t less than 0. For t less than 0, so 1 0 1. So sum 1 plus 0 is 1, carry is 0. So this carry is gone here. Now this is 1. 1 plus 1 is 0, carry is 1. 1 plus 0 will be 1. Okay. So here also you can check, your sum was what? Sum was 0 only, and carry was, your sum was 0. 1 plus 1, sum is 0, carry is 1. Right? And here what will be the sum? In the next condition, the sum will be 1 plus 1. Again sum is 0 and carry is 1. So this sum will become 0 only. Let's check it. A has become 1 only, and this has become 1. So 1 plus 1, this will become 0. This will become 0, and this has become 1 plus 1, this will become 0 and this will become 1, and this 1 has become 0. So this 1 has become 0. This all happened at t equals to 0. About this I am saying. So this has become 0 and this has become 0. So sum 0 plus 0, sum will be 0 only and carry will be 0. So 0 plus 0, this will become 0. Wait a second, there is some error. 1 plus 1, sum is 0, carry is 1. Okay. This is 0. So this is going to be 0. So 0 plus 0, 0 it is there, 0 it is 1. Okay, so this has become 1. No, this I forgot to check. This has become 0 to 1. So this is 0, this is 1. So what you will get? 1 plus 0 will be 1 only. So both carry and output, both are not changing. So when they are stable at t equals to 0 nanosecond only. The outputs are stable at t equals to 0 nanosecond only. That's the answer. That's it. Both carry and sum. Did you understand this? Here your sum was initially 0 and carry was 1. Now here your sum is 0 and carry is 1. So both did not change. In the mid they could have asked that when this will become stable. These kind of questions could have been asked, because this is changing the state. If this is changing the state, then you can see when it will become stable, because since they are becoming stable at t equals to 0, so this will become stable after 20 nanosecond. This guy will become stable after 20 nanosecond, right? But this guy is stable only, because it does not change. Let's see the next question. This 20 nanosecond, just let's keep it written. And what about this? This will be after 20 nanosecond as well, and this became stable at t equals to 0 nanosecond only. Although they are of no use, but still, what if someone asks? And this became stable at 20, this became stable at This became from 20. Wait a second. Yeah, so input for this half adder, this was stable at 20, this was stable at 10. So this will take 20 plus 20. Sorry, it will not take 20 plus 20 more time because this is stable at 0 only. But this is changing. If this is changing, so 20 plus 30, this will be stable at 50 nanosecond. Okay. And what about this guy? This guy was stable at 20 nanosecond. So if you are not aware of the concept, you will say that, sir, the Ci plus 1 will be stable after 60 nanosecond. This is what you can say, but that is wrong, because this Ci plus 1 is not even changing. And here you will say that, sir, this is stable after 20, so 20 plus 20, it will take 40 nanosecond. So that is also wrong, because this S is not even changing. If they are not even changing, then what is the concept of, what is the meaning of saying that they are becoming stable after that much time? They are already stable, right? Let's see this question. So same kind of questions can be asked on circuit level as well. So now I have drawn the circuit level. This is half adder, this is half adder, and this is your OR gate. So what you can do, you can convert them to half adder. But why would you do these kind of things in the examination? In the examination, you will be solving it, right? So for t less than 0, A is 1, B is 1, and Ci is 0. So let's analyze it. So 1 XOR 1, this would be 0. 0 XOR 0, this would be 0. Or first you can check here as well that my sum will be 0 and carry will be 1, because 1 plus 1 plus 1 plus 1 plus 0, sum is 0, carry is 1. And in this case, sum is 1 and carry is 0. So here both are changing. If both are changing, then things will be different now. Okay, so 0 0 0, now 1 1, so this is becoming 1. This was the initial condition. Now this is 0, this is 0, and this is also 0, and this was 1, this was 1, right? So this was 1 only, this is 0, this is 0, so this would have been 1 only. Okay, now let's see the solution. Now what will happen? A1 will go to 0, B will go to 1, and C will be at 0 only, right? So 1 XOR 0, this will change, right? So both were stable at, these two input were stable at t equals to 0. So this will change after 10 nanosecond, right? Because both were stable at t equals to 0. So they have the capability of giving the output directly at t equals to 0 nanosecond only. So for traveling them, it will take 10 nanosecond time. So this will be stable at 10 nanosecond. So this input is stable at 10 nanosecond, right? This input here, it is stable at 10 nanosecond. And this was stable, this has become 1, right? This has become 1, which is stable at 10 nanosecond. So this was, now this 0 was already stable at 0 nanosecond, but this guy has to wait for this guy, right? So 1 XOR 0, this will become 1 after 10 plus 20, 30 nanosecond. If this is changing, that means it will become 30 after 30 nanosecond, right? Now this guy was 0 at 0 nanosecond only, and this guy became 1. This guy became 1. Look, it is going from 0 to 0. That means it was stable already. This is already stable. This guy became from 0 to 1. This guy became 0 to 1 at 10 nanosecond. Now you tell me one thing. Where this output is stable? When this output will be stable? At 0 nanosecond or 10 nanosecond? At 0 nanosecond. Why so? Because at 0 nanosecond it is 0, right? At 0 nanosecond this is 0. Now this guy will not wait for this guy. Why is that so? Because this is AND gate, and the output of AND gate will not depend on the other number if one of the number is 0. Say yes or no. Are you getting this point? I hope you are understanding. Or you can directly see that this is 0 only, this is 0 only, so it is not even changing. That means it is stable at directly t equals to 0 nanosecond. If it is not changing, that means it is already stable. What about this? This has become 0, right? This has become 0 and this has become 1. So A has become 0 and B has become 1. So A has become 0, B has become 1. So this output has changed. So both changed at t equals to 0 nanosecond. Both guys changed at t equals to 0 nanosecond. So 0 plus 8. So this will take 8 nanosecond time. So this guy is stable at 0 nanosecond, but this guy is stable at 8 nanosecond. This guy is stable at 0 nanosecond, but this guy is stable after 8 nanosecond. So 8 plus 10, 18. So this will be stable after 8 plus 10. That means 18 nanosecond. Right? And 0 plus 0, this will become 0. So carry will become 0 after 8 plus 10, 18 nanosecond. Let's start again. 1 1 0. In that manner it is written. We got to know that sum and carry both are changing. That means both will take some time to change their outputs, right? 1 is going to 0, 1 is remaining at 1 only. So this output is changing from 0 to 1. So this will take 10 nanosecond because they are stable at t equals to 0. Now this guy is remaining same as it is. This guy is remaining same as it is. What about this guy? This guy is changing at 10 nanosecond. So this guy is stable at 1 at 10 nanosecond. So this guy has to wait for this guy, right? Because output of this is changing. Output of this is 1. So it is changing from 0 to 1. So this guy will be waiting for this guy. So 10 plus 20, 30 nanosecond. Now here if you see, this output is changing from 0 to 1, and this is changing to from 0 to 0 only, because this is simply Ci only. So this is from 0 to 0, and this changed at 10 nanosecond. But the output of this AND gate, did not change. Output of this AND gate is same as it is, 0 to 0 only. So this was already stable at t equals to 0 nanosecond, because it did not even change. And what about this guy? So about this guy, so 1 to 0 and 1 to 1. So 1 to 0 and 1 to 1. So both change at t equals to 0. These changes happen at t equals to 0 second only. So after 8 nanosecond, it will take time to reach here. So at 8 nanosecond, this one has become 0. So this guy has to wait for him now, right? Because this output is changing. This output is changing from 1 to 0 now. So if output is changing from 1 to 0, so 8 plus 10, 18 nanosecond. So for answer is, for carry it is 18 nanosecond. And for sum it is 30 nanosecond. And I am pretty hopeful these kind of questions are soon coming in your examination, very, very soon. Let's see this question. So now full adder is implemented using 2-level XOR and a 2-level AND OR gate. 2-level XOR and 2-level AND OR gate. Okay. For t less than 0, a is equals to b 0. This you need to solve on your own. B is equals to 0 and Ci is equals to 1. So 0, 0, 0, 1, 1, 0. So basically 2-level means here you are collecting your output, that is sum, and here you are collecting your carry, that is AB plus BC plus CA, right? So before that this was 0 only and this was 1, right? So sum was 1 and carry was 0 only. 0, 0, 0. So carry was 0. In this case sum was 1 and carry was 0, and in this case sum is 0 and carry is 1. Okay, so these are changing, these guys are changing. Sum is going from 1 to 0, this will change from 1 to 0, and this will change from 0 to 1. So certainly it will take some time, it will take some time to change. Now A has become 1 and B has become 1. These guys have changed at t equals to 0 only. These guys changed at, and C has become 0. C has become 0. So 1 XOR 1, this will become again 0 only. This will again become 0 only. So this is going from 0 to 0. This has become 1 to 0. So this is going from 0 to 0. So at t equals to 0 nanosecond it is stable, and it has changed 1 to 0 at t equals to 0 nanosecond only. This changed from 1 to 0 at t equals to 0 nanosecond only. So this is also stable at t equals to 0 nanosecond. So both of the inputs are stable at t equals to 0 nanosecond. So both can go at t equals to 0 nanosecond. So it will take 0 plus 20. So this output will be stable after 20 nanosecond. That's it. What about this one? So this will become 1. This will become 1 at 15 nanosecond. This will be 0 only, and this will be 0 only, because 1 into 0, 0, 1 into 0, 0. So this changed, this guy changed, and output of this OR gate is depending on him, right? Output of this gate is depending on him. So these two guys have wait for him, although they are stable at t equals to 0 nanosecond only. But these two guys have to wait for this guy, right? Why they have to wait for this guy? Because output is depending on him. If output was not depending on him, they would not be waiting. But output is depending on him. So 15 plus 10. So this will be stable after 25 nanosecond. So that's the answer. Maximum time in receiving S and I. So for S it is 20 nanosecond, and for Ci plus 1 it is 25 nanosecond. So these kind of questions can be coming in your examination. So you should be able to solve. Let's see if there are any other problem. No. So these kind of questions can come in your examination, and you should be comfortable with these kind of analysis. Okay, so we saw a lot of problems. If you are able to understand, that's pretty good. Just revise it once again. Just revise everything once again, and you will certainly feel pretty good about it. And it will help you a lot in binary parallel adder. When we study binary parallel adder, it will help you a lot. There, 4 bits will be coming all together. So there also some good analysis will come up. In one analysis, there will be no inputs given, like in this manner. No inputs are given. A, B, C, D. So simple analysis was there. But if inputs are given, then the things changes. Then you need to see the previous state as well. That if anything is actually changing or not. If nothing is changing, then let it be. Okay. So yeah, that's it. And we have already launched our full course for digital electronics. So if you are interested in studying digital electronics in this much of depth, then you can certainly come to our course. So digital design course for placements as well has been launched, and for digital electronics course also has been launched for GIT. So if you are interested to learn in this much depth, and we are giving it in just 199 rupees. Okay, you need to apply the code Titans40. So you can visit our website, and there you can purchase the course. Okay, it is very cost effective. Like, it is taking a lot of efforts in designing these kind of problems, thinking of these inputs, but I just want to give the feel of digital electronics to all of you. So if you are thinking to purchase the course, then you can purchase the course. Okay, then thank you very much. Hi everyone. So before moving on to the binary parallel adder, we will see a small topic. It would be of roughly around 30 minutes video only. So we will study about half subtractor here. Okay, so just like addition, we will do the subtraction as well. Half subtractor and a full subtractor. Okay, so there could be two inputs, A and B. It will generate a difference output, and it will generate borrow output. What do I mean to say is that if I am doing 1 minus 1, so what I am getting? 0. And what is the borrow did I take? I did not take any borrow. So borrow is also 0. If I am doing 0 minus 1, so can this be subtracted? No, you need to take a borrow. So borrow I took, and 2 minus 1 will be 1. So my difference is 1. I hope you know the calculation. If you know because we have already studied in our number system, and this is our what? Borrow. Okay, so that's the scene. So this is B out, A, B, and difference. Now you can either calculate A minus B, or you can calculate B minus A as well. So for both of them we will study. Okay, and this is your B out. Inputs are A and B. So let's see the truth table for A minus B. So for A minus B, if 0 is subtracted from 0, 0 is subtracted from 0, what you are getting? 0, and there was no borrow out. If 0 is subtracted from 1, then you need to take borrow. So you took a borrow. Plus 2 minus 1, what that would be? 1. So difference is 1 and borrow is 1. Did you understand this point? Right? 1 minus 0. Difference is 1, borrow is 0. 1 minus 1 is 0, borrow is also 0, because I did not take any borrow. So only borrow I took here. 0 minus 1. For that I took borrow. So 2 minus 1 will be 1. Right? You know how to do the calculation. If I am taking the borrow, that means I am taking the base. So 2 minus 1 will be 1 here. So what will be your B out? So your B out, you can directly see it is A bar B. It is 1 here only. And what is your difference? It is same as the sum only, A XOR B. Right? What about difference here, B minus A? This will be 0. B minus A, 1 minus 0, 0 minus 0 is 0, and B out is also 0. 1 minus 0. So 1 minus 0, difference is 0. B out is also 0. 0 minus 1. So same thing will come here, 0 minus 1. You need to take a borrow, and 1 borrow will be there, and difference will be 1. And 1 minus 1, 0, and there is no carry. So no B out. So the difference is also 0, and borrow is also 0. So what is your difference? Difference is A XOR B. And what is your B out? B out is A B bar. So if I am writing C minus D, what do you think, what will be your B out? C bar D. One which is here will be bar. Okay, A minus B, A XOR B. B minus A B bar, or you can write B bar A. It would be better to write in this manner. So the one which is in the initial, that will be bar. So B bar A. Okay. Circuit diagram we can make. What we need to make? XOR gate. So this is our XOR gate, which will give the difference A and B, A XOR B. For A minus B we are drawing. So A will be bar there. So A bar B. So for making your half adder, you needed XOR gate and AND gate, but here you need XOR gate, AND gate, and then NOT gate as well. Okay, so carry is A bar B. You can make the same for B minus A as well. Okay, do it on your own. I am putting the space here, you can draw it on your own. B minus A, just this will be inverted, everything will be same. Okay, let me do it, otherwise people will say, sir, we have paid the fees. Just I will copy it, but I am smart, I will copy it. You cannot copy. B minus A. B bar A. Okay, sum and carry. Well and good. Let's make half adder using NAND gate. So this we already know. This will be the difference A XOR B. Using NAND gate A XOR B. What I need now? A bar B. So NAND gate will do XY bar, right? Or you can say X bar plus Y bar. This is what you will get. You need A bar B. Not getting anything. Let's check something what we are getting here. Let's check that. Okay. So it would be AB bar, and what you will get here? A into AB bar, right? So what you are getting? A bar plus basically this will be bar plus bar of this. So that would be A bar plus A B bar. Something is wrong. Basically you are getting here AB bar into A and then whole bar, right? So this bar will come here, AB plus A bar. This is what you are getting, and here you are getting, that is A bar plus B. So here you are getting A bar plus B, and similarly this side you would have got B bar plus E. If I take double bar of that, what do I get? A plus B bar bar. A plus B bar I am having? Yes, I am having. This is A plus B bar I am having. I just need to take the bar of it. There you go. So this is the B out I have generated. B out I have generated, that is B bar plus A bar, or you can say A bar B. Okay. So like nothing, if nothing clicks, then take double bar. So nothing was clicking to me, but A plus B bar I required. So A plus B bar I required. Here, there you go. From here I can get A plus B bar. Okay, then just take the inverted output. So B bar plus A to the bar. So B dot A bar. So A bar B. Well and good. Now you will need to make it using NOR gate. So try doing it on your own. Make it using NOR gate. So if I make it using 3-level NOR gates, okay, 3-level gate, then this would be tough to get A bar B. If you make it using 3-level, first you take A bar plus B bar, then A plus B, and then multiplication of both. So from there it would be tough. So what I have done is that I implemented using 4-level. Why did I do so? Let me tell you. Let's see here what you are getting. Or let's see here. So this is a plus b bar, or you can call it a bar dot b bar, and this will be your a. So what you will get here, a plus a bar b bar to the bar, and that would be a bar dot a plus b. So it would simply be a bar b. So this is your b out only, directly b out you are getting here. This is your difference, no one can stop it. A XOR b. But here you are directly getting a bar b. Did you notice it? You are directly getting a bar b here. Okay. And here similarly you would have got b bar a. But you don't care about that, you care about this. So this is your b out. So in 5 NOR gate, here how much you required? 5. Here how much you require? 5. So in 5 NOR gate and 5 NAND gate you have implemented the function. Half subtractor using NOR gate you required 5 only, and using NAND you require 5 only. Let's solve this question. What this will do? This will give the XOR. Okay, so what is XOR of this? Everything but not common. So 3 and 7 will not come. So 1, 2, 5, 10. 1, 2, 5, 10. What about B out? A bar B. So what is not there? What is not there? 0 is not there, 2 is not there, 4 is not there, 6 is not there. And common between these two. So 2 is common, 0 is not common, 4 is not common, 6 is not common. So only 2 you will get here. You will only get 2 here. Did you understand this point? What did we do? Here we need bar of this into F2. So bar of this will be 0, 2, 4, 6. Bar of this will be 0, 2, 4, 6. And what F bar dot F2. So what it does? Takes the common in between them. So what is common? Only 2 is common. AND gate takes the common. So only 2 is common. Right? Or you could have done it easily as well. That what would be your A bar B? You need to find A bar B. This would be your A bar B. So whatever that is common, that will not come. Whatever that is common, that will not come. F1 bar F2. Right? So everything of F2, but whatever that is common, that will not come. So everything of F2, but whatever that is common, that will not come. So what is common? 3 and 7. So that should not come. So 2 and 10 should come. 10 should also come. Okay. Sorry. I forgot, like, these are total 16, no? The minterms are total 16. 0, 1, 2, 3, 4 till 15. So that I did not notice. So 10 should also come, no? 10 should also come. Look here, what we did, 0, 2, 4, 6 only we wrote, but 8, 9, 10, 11, all these will also come, right? 0, 2, 4. So better solve it with, always solve it with K-map only. Sorry, Venn diagram only. So just as I solved with Venn diagram, I got to know my mistake. Otherwise, I would have got it wrong. Okay. So bar of this will have 0, 2, 4, 6, 8, 9, 10, 11 in everything. Okay. So 2 and 10 are common. So here 2 and 10 will go. Now what this will do? What is F3? This is 3, 5, 10, 12. 1, 2, 5, 10. So it will only take the common one. So 5 and 10 are common. Because here you get the XOR. So only 5 and 10 are common. So 5 and 10. So this is your Y1. Okay, Y1 is 5 and 10. What about Y2? So you need this now. So what it will do? Take the bar of this. This is your B out. Take the bar of 1, 2, 5. Let's call this function as fx, not fx, fk. So it will do fk bar into f3. So whatever that is there in f3, everything will come, but not common part. Complete f3 will come, but not the common part. So what is f3? 3, 5, 10, 12. What is common? 5 and 12. 5 and 12. So 3 and 12 will come here. 3 and 12 will come here. I hope you must have seen that particular lecture, that how to get the minterms. Then you will be able to solve it. Okay, what did I do? Bar of this into F3. That means F3 completely will come, but whatever that is there in F2, that will not come. So that means in F2, what is there? 2 and this is your F3. So 2 and 10. No, sorry. 10 and 5. 5 and 10, sorry. 5 and 10. So 5 and 10 will not come. 3 and 12 will come. 3 and 12 will come. And all will be added. So 2, 3, 10, 12. 2, 3, 10, 12. That's the answer. Okay. So this is your Y2, this is your Y1. Y1 is 5, 10 or Y2 is 2, 3, 10, 12. 2, 3, 10, 12. Very easy. So these kind of questions can come up in your examination. You just need to see the minterms and in that manner you need to solve. Full subtractor. So what it will do? So it will do the subtraction of 3 bits taken one at a time. That means it can do first A minus B and then minus C. Okay. So, and what will be B out? B out is simply the borrow out only. It can do in this manner as well, that A minus B minus C, or better, no sorry, that is wrong. A minus B minus C, that is wrong. So what it can do is that B minus C minus A, or it can do A minus C minus B. Basically all other combination can also be there. B minus A minus B, I have written like C minus A minus B. So 2 it will take at a time, perform the subtraction, then subtraction with the other one. So we will see first for A minus B minus C. So A minus B minus C. So A minus B first and then C. So 0 minus 0, 0. 0 minus 0, 0. Difference is 0, no borrow out. 0 minus 0, 0. 0 minus 1, you need to take a borrow. You need to take a borrow. And if you take a borrow, it will be 2. Plus 2 minus 1 will be 1. 0 minus 1, first 0 minus 1. You need to take a borrow. If you take a borrow, it would be plus 2. So 2 minus 1 will be 1. And then minus 0. Minus 0. So difference is 1 and you also took a borrow. Did you understand this point? Let me explain it again. 0 minus 1. If I am doing 0 minus 1, that means I need to take a borrow. Plus 2. So plus 2 minus 1. So 0 minus 1 is 1. Now I need to do minus 0 as well. So 1 minus 0 is 1. And here I took borrow. Because of that 1 came. Okay. So try writing the expression of the next one on your own. So what is that? 0 minus 1. Again you need to take the borrow. 0 minus 1. So again take the borrow plus 2. So if I am taking borrow, 1 would come. So 2 minus 1. Here you get 1. And 1 minus 1. That would be 0. Say yes or no. Right? 1 minus 0 is 1 minus 0 is 1. Then 1 minus 0 is again 1. So this will be 1 and there is no borrow out. 1 minus 0 is 1. 1 minus 1 is 0. There is no borrow out. 1 minus 1 is 0. 0 minus 0 is 0. There is no borrow out. 1 minus 1 is 0. 1 minus 1 is 0. Now 0 minus 1. So you need to take a borrow. Right? So this is a borrow. And 2 minus 1 will be 1. So that's it. What all are the minterms there? What all are the minterms? Minterms are, for difference I am asking. For difference, what all are the minterms? So here I should write. The minterms are 0, 1, 2, 3, 4 and 7. What does this represent? A XOR B XOR C. That's it. 1, 2, 4, 7. XOR gate, or you can say XNOR gate as well. Both are equal. Let's talk about B out. So when it is 1, A bar B bar C, A bar B bar C, A bar B C bar, A bar B C bar, A bar B C, A bar B C, A B C, A B C. Okay. So 1, 2 and 3. So I can see A bar C plus B C plus B is constant, A bar B. So I can write this as A bar B plus B A bar plus C, wait a second, AB plus BC plus CA. Let's write it down again. A bar B plus BC, this is what I can write, A bar B plus BC plus C A bar, right? So isn't it like that only? A bar B plus BC plus CA bar. So AB plus BC plus CA, just A is replaced with A bar. AB plus BC plus CA, A is replaced with A bar. Isn't it the same thing? Are you getting this point? So you are getting the same output only. So this will also be self-dual. This is also self-dual. Why it is self-dual? Because if I say my A bar is X, so what that function will be? XB plus BC plus CX. Now is this self-dual? Yes, it is self-dual, because we have studied that AB plus BC plus CA is self-dual. So certainly this is also self-dual. Okay. And what can be alternative expression of that? Let's see the alternative expression of B out. So what we know? For AB plus BC plus CA, we know the alternative expression. What is that? That is AB plus CA XOR B, right? Now A is replaced with A bar. A is replaced with A bar. That's it. So what you will get? A bar B plus C A XOR B. Say yes or no? So that we will get. So A bar B plus C A XOR B. For AB plus BC plus CA, what else you could have written? I could have written that BC plus A B XOR C. But now A is replaced with A bar. So only A bar will come here. That's it. Are you getting this point? How did I write it? For AB plus BC plus CA, what I could have written? BC plus A into B XOR C. But A is replaced with A bar. So A is replaced with A bar. Or what I could have written? CA plus B A XOR C. But A is replaced with A bar. So this will also be A bar. So A bar or this plus, that will become your dot. So this is how it can be shown. So multiple ways, but we are going to use this and this. A bar B plus C, A XOR B. So in the examination, you do not need to mug it up. What you will see, that if my A minus B minus C is given, then what I will do? What is my sum? Sorry, what is my difference? That is same. A XOR B XOR C. What is my sum? A XOR B XOR C. What is my carry? That is AB plus BC plus CA. And what will be my B out? That would be A bar B plus B C plus C A bar. Okay, for A minus B minus C. So this can be written as A bar B plus C A XOR B. Why XOR B? Because this is same as AB plus C A XOR B. So if this is replaced with A bar, this thing is replaced with A bar, and this is replaced with A bar, so this will be dot. So in the examination, you will be able to think it very quickly, right? You do not need to mug it up. You remember this thing, you remember this thing. That's it. Apart from that, everything you will be able to write it down. Okay then. So this will be your B out. Now let's write down the different B out expression. So what will be the difference? The difference will always be same. That is XOR only. Or you can say XNOR as well, because both are the same thing. Right? Both are same thing. For this, what B out you will write? A bar B plus BC plus CA bar, and it can be written as A bar B plus C A XNOR B. Here what is in front? B is in front. So B bar A, AB plus BC, B bar C plus CA. Basically only AB plus BC plus CA, on B I will put bar. And what here it will come? So what I can write is that, so B bar A plus C B XOR A, XNOR A, right? Or what I could have written, b bar c plus a, b bar c plus a, b XNOR c. What I would be preferring? What do you think? What I would be preferring? I would be preferring this one. Why is that so? Because from b minus a I can get b bar a. From b minus a, first b minus a will take place. So from b minus a I will get b bar a. So I will be already having b bar a, but I will not be having b bar c, because b minus c we are not doing. So I will be preferring this. In the examination I will be preferring this. Although if this question is coming in MSQ, then you need to mark everything. But if the question is coming design it, so which one I will pick? I will pick this one if I need to design, because I will be already having b bar a. From first half subtractor you can say I will be already having b bar a. Okay. And why did we pick a bar b here? I would have picked a bar c as well. So here I will be already having a bar b, right? And what it can be replaced with? C is in front. So ab plus bc plus ca, but c will be bar. So what I will be picking? C bar a. C bar a plus b c XNOR a. C bar a plus b c XNOR a. So this I will be preferring, because I can directly get c bar a here. More expressions can be written that you can write it on your own. If this is coming in MSQ, you will mark it. But if they are asking you to design, then I will pick this option. Okay. Let's move on. Designing full subtractor using NAND gate. So using NAND gate, first we need to design this A XOR B XOR C. Same, everything is ditto same here. A, B, and this is your difference. A XOR B XOR C. Now what is the task? Task is to design A bar B plus C A XOR B. C A XOR B. So something multiplication I can get from here, right? Something C into A XOR B, something I can get from here. So I will look at it first. First I will look at this. First I am looking at this. So what I can get from here? So C into A XOR B bar. This is what I am getting from here. Okay. Rest I need A bar B. A bar B. Let's look at these two terminals. So here you are having AB bar and here you are having A. So what you are having here? A into AB bar to the bar. So it would be A bar plus AB. So this would be A bar plus B. And here you will be having B bar plus A. Can I write this as A bar B bar? A bar B bar it is. A plus B bar. A plus B bar is A bar B bar. So A bar B I got somehow I got A bar B. So from here I need to pick something. Right? And then A bar B, and from here I am getting this thing. Now what do I need? Multiplication and then bar, right? Yeah. So another NAND gate I can use here. Basically you are having this as well. Let's just say you are having X bar and you are having Y bar. Multiply this and get bar. What you will get? X plus Y. So the same thing we did here. A bar B is our X and C dot A XOR B is our Y. So X plus Y I am getting. So this is X plus Y I am getting. This is the B out. So what is our B out? So B out is A bar B plus C A XNOR B. Okay. So like here I had to derive it actually. At least I had to see what we are getting here. Like I could have told that consider this as a bubbled OR gate. If you consider this as a bubbled OR gate, then you can think of what can be coming here, right? Because eventually here you need A bar B plus B bar A. Say yes or no? So if I consider this as bubbled OR, that means there should be B bar A bar, because another NOT will come that will convert it to B bar A. and then it will be added. Did you understand this point? Right? I know the output here, then I can think of inputs here, and these inputs will be these terminals only. So in that manner also I could have one, or I could have analyzed in forward manner, or I could have analyzed in backward manner as well, because now we have studied a lot of combination circuits. We are very much comfortable with logic gates now. Okay, so we derived in this particular problem, we derived parallel, like we derived forward. So in forward we got to know this thing. Okay, so B out we are getting. Let's see for let's see for NOR gate. So this is the difference. Certainly you are getting the difference, no doubt about that. Difference very easy. Getting the difference is very easy. But the thing is about B out. So A bar B plus C A X NOR B. If I take dual, because this is a self dual function, self dual. So what I have taken here, I have taken the dual. Here I have taken the dual. The same manner where we took dual, in half adder we took the dual, right? So there I wrote dual or complement. Dual. Fine. So we have taken the dual as well in full adder. So same thing we are doing here. Here we have taken the dual. So B out dual we have taken. So A bar plus B dot C plus A XOR B. Right? Now let's look at these outputs. What do I get here? So this is A plus B bar. A plus B bar, and this is B. So B plus A plus B bar to the bar. So B bar dot A plus B, right? And you are getting AB bar here. Did I do anything wrong? A bar B plus B to the bar. So bar of this, so AB bar. So here you are getting AB bar. AB bar. What do you need? A bar plus B. Okay. AB bar you are getting here. And what about this? This is A XNOR B, right? A XNOR B, and this is your C. So what that would be? C into A XNOR B, C plus A XNOR B to the bar. C plus A XNOR B bar. If I take both of them, A B bar plus this function, C plus A XNOR B bar, and take the whole bar. So what I will get? X plus Y bar. That would be X bar dot Y bar. X bar dot Y bar. So bar of this, what that would be? A bar plus B. Dot bar of this, what that would be? C plus A XNOR B. So yeah, I got my idea. What is the idea? That AB bar I will pick. I will pick AB bar. And I will pick this one. And then I will give it to my another NOR gate. Another NOR gate. So how many NOR gates required? How many NOR gates were required? So this is your B out. How I am getting it? You can solve this. What you need to do? A B bar plus C plus A XOR B bar, and then whole bar. This is what you need to solve. So X plus Y whole bar. So X bar plus Y. X bar plus Y bar, and Y bar is C plus A XOR B only. And dot bar of this, what that would be? A bar plus B. So A bar plus B, and then this function. So that's the answer we are getting. So that is our B out. So this is our difference, and this is our B out. So how many were required? 9. Here also how many were required? 9. So now what full subtractor using half subtractor. Okay, we will make it, but let's write down this thing that in a half adder, how many NAND gates were required? 5. NOR 5. In half subtractor, how many NAND gates were required? 5. NOR 5. You can check, right? Full half subtractor, half subtractor. So 5 were required. Here also 5 were required. Okay. 9, 9. Here also 9, 9. Here what you needed? 2 half adder, sorry, 2 half adder plus 1 OR. Similar thing will happen here. 2 half subtractor plus 1 OR. So try implementing on your own. You need to implement using half subtractor, you need to implement your full subtractor. So you are having half subtractor with you. What would be your input of half subtractor? AB. So if these are the inputs, what you will receive here? A XOR B XOR C. If I am considering this is my A minus B, then what I will get here? This will be my B out, which will show A XOR B. Okay, and if I give this particular input as C, this particular input as C, and if I am calling this as Fx, or let's call it D, I am calling this function as D, and if I am doing D minus C here, that means what I will be receiving here? What will be my output here? That would be bar of this, sorry, how do I write XOR? So here I will get XOR, right? So I am calling A XOR B as D. So D minus C, if I am doing, what I will be getting? XOR of these two. So XOR of D XOR C. So what is D? A XOR B. This would be your C. And what I will be getting here? That would be my B out. So what that would be? Bar of this into C. Bar of this. What that would be? A XOR B into C. Bar of this into C. Bar of this into C. Okay. So now what do I need? This this difference I have got. So A bar B I am having, A XOR C I am having. So simply add them up. Right? I just need to add them up. So what I require now? I require OR gate. So this is how we can implement it. Not important, okay, not important, but still it is exactly same as half adder, right? Exactly same as half adder. So not that important, but still you can remember it because it is exactly same. So what we are getting here? We are getting here is, that is our B out. So we are getting B out here. Okay. So that's it. This is how you can implement, right? This is C which is going here. Okay. Let's see this question. So full subtractor is there. So what will be the difference here? Difference will be 1. What will be your B out? That will also be 1. How did I do it very quickly? 1 minus 1 is 0. 0 minus 1 plus 2 will be coming here. That means bore out is 1. Plus 2 minus 1, that is 1. Here you will not see that, sir, okay, what is difference? A XOR B XOR C. So 1 XOR 1 XOR. No. You can solve this calculation, no? You can do this calculation. And what about B out? B out for B out as well, you can do this calculation. Or you can apply that particular expression, A bar B plus B C plus C A bar. But let's not do that, right? Let's not do that. We can directly solve it. The job of this is to do the subtraction that we have done. And we have implemented the difference and B out. What half adder will do? Add both of the bits. So 1 plus 1 is 0. Will generate carry 1. What full adder will do? Full adder will add everything. So 1 plus 1, 0, and carry will be 1. What this will do? This will 0 minus 1. This will do 0 minus 1. So 2 will be carried here. So borrow out is 1 and summation is also 1. So here also you are having high, here also you are having high. And what they are saying, that if there is high and there is ground, that means this is on and this is also on. That's it. This was the question. Okay, both are on. Operating condition of B1 and B2 is that both are on. Now what is your task? You need to do it on your own. What is your task? Make a full subtractor using 1:4 demux, 2:4 decoder, 1:4 4:1 mux. So using mux, demux, decoder, you can make it, right? At least you can do this thing on your own, because we have done enough analysis of mux, demux, decoder. Using encoder we are not going to make anything, but using mux, demux and decoder we are making a lot of things. So that you can make full subtractor. I am keeping this up to you. Your task is, you can take it as a homework or you can take it as a self task, that you need to make half subtractor or full subtractor, half and full, both of the subtractors using those particular ICs. What all ICs? Mux, demux and decoders. That you can do on your own. Not that important, but who knows, in the interview they can ask. In GATE examination it will not be coming, but who knows, it can be asked in the interview. Okay then. So yeah, that's it about our subtractor. Now the most important topic will be coming, that is binary parallel adder. Now we will do the parallel addition of 2 or more bits. We were adding one bit now, 1 plus 1 plus 1. But now what if 1 plus 1 0? So how we will add that up, how we will design the circuit for that. So that we are going to see now. Okay then, thank you very much. Hi everyone, so in this video we are going to start studying about binary parallel adders. So before that, let's get to know there are two kind of addition, serial addition and parallel addition. So serial addition is the simple addition that we do just in a normal form. First 1 and 1 will be added, you will get 0 and 1 as a carry. Then 1 plus 0 plus 1 will be added. So what you will get? 0 and 1. So this is the normal addition, this is the serial addition, and this we will do with the help of shift registers. So once we are done with our sequential circuits, after that I will tell you how to do the serial adder circuit. Not important, but still I will just give you a block diagram that how serial addition happens. But once we are done with sequential circuits, now we are studying combinational circuits. So in combinational circuit we are going to use parallel addition. So in parallel addition what happens? All the bits are applied at a time. So here there is a full adder, there is another full adder. So 1 will be added with 1. So 1 I am writing here, and 0 will be added with 1. So 0 1 I am writing here. So all these bits will be coming at a time. All will be going to the full adder. Here initial carry is 0. Now here also initial carry is 0. Like at t equals to 0. At t equals to 0, this was applied. There was nothing here. Here also there is nothing. At t equals to 0, we only applied these bits. Here there is nothing. Here there is nothing. So they will consider that my input bit is 0 only. My input carry bit is 0. So 1 plus 1, it will give you 0. And carry 1. So it will get updated later on. But at t equals to 0, what will happen? 1 plus 1 will be added. It will give 0 addition, and this bit will be generated after some time. Carry bit will take some time to be generated. At t equals to 0, this will think that 0 is applied, 1 is applied and 0 is applied. At t equals to 0, it will consider carry to be 0 only. So it will give addition output as 1 and this final carry as 0. But after that what will happen? It will realize that my carry is 1 now. Here the carry is same. Here also it consider carry to be 0. So here carry is same. So this did not change. This will be there as it is. But now the carry is 1. So it will consider carry to be 1. So 1 plus 0 plus 1. What it will give? 0 and carry as 1. So this will be the final output. After that carry is not changing. Carry is 1 only. So after that nothing is changing. In the circuit at t equals to 0, 1 1 was there, 0 1 was there. So 1 1 thought that 1 plus 0 I need to do. And this guy thought that 0 plus 1 and carry is also 0, because this 1 came later on. After some time it came. So 0 plus 1 it gave 1 and carry as 0. But after some time it got to know that my bit is updated here. So that bit is 1. So now I need to give the answer 1 plus 0 plus 1. So 0 and 1. So this is your stable output. You can see if you do 0 1 and 1 1, this is what output we get. So this is our stable output because nothing is changing after that. Nothing is changing. This is remaining at 1 only, this is remaining at 0 only. So nothing changes. So this is stable output and this is your unstable output. So in between there was an unstable state. So I will call it at unstable state. Okay. Let's see more examples. So unstable state in parallel addition we will see. Let's see this example. So initially what will happen? 1 1 will come and it will give carry 1, but it will take some time. It will take some time. Now 1 0 will think that I will generate 1 and carry 0. Okay. So now after some time this carry 1 will be fed here. So what will happen now? There is no change here. So this will be as it is. Now it will give the answer as 1 plus 1 is 0 and carry is 1. So this will be the final answer. So this was the unstable state. This was the unstable state. And this is the stable state. Let's see it in 3 bits. So at t equals to 0, all these are applied. So what they will do? 1 plus 1, 0. 1 plus 0, 0. 1 plus 1, 0. 1 plus 0 is 1 actually. So considering 0 carry, they all considered 0 carry. Considering 0 carry, they generated this output. That my sum is this guy 1 plus 1. It generated sum is 0 and carry is 1. So it gave carry later on. And what this guy did? Sum is 1 and carry is 0. So it gave carry later on here. Okay. It gave carry later on here. Now what will happen? Now they will produce the output considering this thing. So they will think that 1 plus 1 plus 0. So that means sum is 0. Here nothing got changed. This is same only. So now this guy will think that to my block 1 0 is already there and another 1 is applied. So with respect to that, my sum will be 0 and my carry will be 1 now. But this 1 will be treated by the next one later on. At this time, it will treat it in this manner only. 1 plus 1 is 0 and carry is 1. Are you able to understand this point? Or shall I make the block diagram? I think I should make a block diagram only, otherwise you will not be able to understand this. So let's make a block diagram of 3 bits. Okay. So this will clear your concept of delay as well to some extent. This will generate some, this will also generate some, and the carry will be fed to the next stage. So carry I am making roughly only. So carry is being fed to the next stage. And final carry is generated here. So this will be your S0 I am calling, this is your S1 I am calling, this is your S2 I am calling, and this is your C2 I am calling. And what is applied? Look here, from left side we will start. 1 is added with 1, 1 is added with 1. 1 is added with 0, 1 is added with 0. 1 is added with 1, 1 is added with 1. So initially this is the scene. At t equals to 0, at t equals to 0 only all these are applied. At t equals to 0, all these are applied. So at t equals to 0, what this full adder will think? That here I am having 0, here I am having 0, and here also I am having 0. This is what this full adder will think. So it will give the result as per that. So it will give this sum as 0 and carry as 1, right? After that, what this guy will do? This will give this sum as 0, this sum as 1, sorry, and carry as 0, carry as 0. So this carry, which is this, carry as 0. And this guy will do sum as 0 and carry as 1. So this will change. But this will change after some time. This will change after some time, after TD time. Right? So this was the first state output, 0, 1, 0, and carry is 1 here. Carry is 1 here. This was the first state output. In the second state, this one came. This one came here. And this guy generated 0 only. This guy generated 0 only. So this 0 came here. So in the second state, this addition will be performed. That 1 plus 1 is 0. This did not change. 1 plus 1 is 0. And now 1 plus 1 is 0. And now carry will be generated 1. Now what this guy will do? 1 plus 0 plus 1. So it will generate sum equals to 0 and carry equals to 1, because 1 plus 1 is sum will be 0 and carry will be 1. So now this guy will do generate carry 1, but for the next cycle, for this particular cycle, this 1 1 will think that only 0 is applied. This 1 1 will think that 0 only applied. So 1 plus 1 is 0 and will generate carry 1. It will generate carry 1. So this is the output of the second state. In the third state, what will happen? This will be same. There is no change here. There is no change here. But here it will think that again 1 is applied. So 1. So in the next cycle, what will happen? This will be changing to 1. Because 1 plus 0 plus 1 was applied. So 1 came here, and after more TD time, this became 1. This guy became 1. So if this guy became 1, so 1 plus 1 plus 1, that is 1 only, and carry is 1. So 3 cycles it will take. In that manner it will go. Okay. So how many unstable states were there? 2 unstable states were there. 2 unstable state. We will see the deep analysis of this. Okay, very deep analysis we will see in the next lecture only. So wait for that. If you are not able to understand here, then also it is fine. So the point I wanted to make here, if you are doing the 3-bit calculation, then maximum unstable state you can get is 2. Here you got only 1 unstable state. Here you got 2 unstable state. So if I am doing n-bit calculation for n-bit binary parallel adder, n-bit binary parallel adder, maximum unstable state is equals to what? Maximum unstable state is n minus 1. Okay, so if I am doing 6-bit binary parallel addition, then I will have maximum 5 unstable state. So we will do the deep analysis of this. Just wait for that. All the conditions that can be there, all conditions we will pick and see what all delay would be there, how to analyze the delay. So in the next lecture only we will do the analysis. So wait for this. That will be very interesting. So as of now you just understand that there are 2 unstable states. So if n-bit calculation is there, then there would be n minus 1 unstable state. Okay. So what will be the block diagram of a 4-bit parallel binary addition? So here A0 and B0 will be added, and C0 could be anything. This C0 could be anything. Mostly it will be 0 only, but it could be anything. So it will generate some S0 and it will generate a carry. So this S0 will be there, and this carry C1 will be generated, which will be fed here. And here A1 B1 will be added. A1 and B1 will be added, right? A1 B1 will be added, and sum 1 will be generated, and carry will also be generated. So sum 1 it will generate, and C2 it will generate. Now A2 B2 will be added. All these are fed at t equals to 0 only. Okay, A2 B2 is not coming later on. All these are coming at t equals to 0. At t equals to 0. All these are coming at t equals to 0 only. So C2 is fed here. Then it will generate S2, and you will get S2 you will get, and C3 you will be fed here. So C3 you will fed here. So this will generate S3 and C4. Why did I make this? So this is your final output. This is your final output. At what time you will get, you don't know that. It will depend on the delays, but this is your final output. Okay, it will depend on the delay when you get that. This is your final output. Okay, so this is how the process happens. 2 bits come from here, the sum C1 goes here, come, wait here, go there, wait, generate, again do the calculation. So that's how it goes. So 4-bit binary parallel adder, and all bits are coming parallelly. All these A3, A2, A1, A0, B0, all these are available at t equals to 0 only. So all these are fed parallelly. It's not that one is fed then one is fed then other goes. All these are fed parallelly, but this C1 C1 changes in between. So their result also changes. So in between there are unstable state. Eventually all will have the correct carry and there will be stable state. Okay. Now for how 4-bit binary parallel adder can be implemented. Look, here you need to do the calculation of 3 bits. Here also you need to do the calculation of 3 bits, but this can be 0, right? This C0 can be 0. So I will say I need to do the addition of only 2 bits. Say yes or no? This C0, if C0 is 0, then I need to do the addition of only 2 bits. And addition of 2 bits can be done from half adder, right? So I can say 1 half adder and 3 full adders. See, yes or no? 1 half adder and 3 full adders. 1 half adder plus 3 full adders. Or what I could have said, or 4 full adders only. All 4 are full adders. Basically, this has to be full adder. Why is this has to be full adder? Because there will be carry. So it has to add 3 bits. It also has to add 3 bits. It also has to add 3 bits. So carry could be 1 here. This C naught will be 0 only. But what if this C naught is coming from some previous calculation? Let's just say some previous calculation I write alpha naught alpha 1. So if this C naught is coming from this particular calculation, then it could be 1 as well, right? C naught could be 1 as well. So here we can write, if C naught is 0, then you can use half adder. If C naught is 1, then you should use full adder. But if you are doing 4-bit parallel binary addition, that means you are considering initial carries are all 0. So that means C naught is 0 only. If C naught 0 you are considering, then you can use half adder. Okay. So this is the best design if you are doing 4-bit parallel binary addition and you are considering that there is no initial carry. C naught is 0. So this is how you will use, or you will use 4 full adder. How this can be written? 1 half adder plus 1 full adder can be made of 3 into 1 full adder can be made of 2 half adder plus 1 OR gate, right? So 1 half adder plus 6 half adder plus 3 OR gate. So this could also be the answer, or you can say 7 half adder plus 3 OR gate. Let's generalize it for n-bit addition. So for n-bit addition, you can use 1 half adder plus n minus 1 full adder. Say yes or no? Did you understand this point? 1 half adder plus n minus 1. For 4 bits, only 1 we used and 3 full adder were there. So n minus 1 full adder. What I can write this? 1 half adder plus n minus 1. 1 full adder can be equals to 2 half adder plus OR gate. I can write n minus 1 into 1 full adder. So 1 full adder is 2 half adder plus OR gate. So I can write this as 1 half adder plus 2 into n minus 1 half adder plus n minus 1 OR gate. Right? You don't need to remember this formula. Okay, you don't need to mug it up. So what you are getting? 2n minus 1 plus 1, 2n minus 2 plus 1. So 2n minus, just this is 2n minus 2 and this is plus 1. So 2n minus 1. No one will remember it actually. 2n minus 1 half adder. How to solve the problems of this concept, we will see that. And n minus 1 OR gate you will require. Okay. So if this kind of question is coming to implement 16-bit binary parallel adder, how much half adder and OR gate will be required? So what will you think? Okay, 16-bit binary parallel adder, that means 15 full adder will be there and 1 half adder will be there, and 1 full adder can be made of 15 full adder will be made of 30 half adder and 15 OR gate. Say yes or no? Plus 1 half adder. So that would be 31 half adder plus 15 OR gate. Did you understand how did I write this? 15 into 1 full adder will be made of 2 half adder and 1 OR gate. So 30 half adder plus OR gate. And if you had applied the formula, or if you had applied the formula that you are not going to do, that was 2n minus 1 half adder plus n minus 1 OR gate. So n is 32 minus 1, 31 half adder plus 15 OR gate. Okay, so this is a very basic question which can be asked. Okay, so from this particular lecture, there might be a scene that you might not be able to understand this unstable bit, but when we see the problem of delay, now we are going to study the problem of delay only. So we will see 4 type of problem, and those problems will be very interesting. So after that it will be all clear to you. Okay, how unstable state is coming, which one will be unstable, which one will be stable state. So that we are going to see in a very in-depth manner. For this lecture, you just need to know that what is the actual process, what is happening, and how much full adder and half adder you require. So till that, I hope everything is clear. Now let's see that delay based problem, which is very important and very intuitive, and you will love the explanation, that I can tell. Okay, so do not skip the next part. Just watch the next part, which will be of around 2 hours, and watch that part with full amount of concentration. Okay, then thank you very much. Hi everyone, so in this video we are going to see the problem based on binary parallel adder. So we have already seen the problems based on delay in full adders and half adders. So I hope you have seen that, then only you should come here. And just like the previous video, this also requires your high attention. So just pay your full attention, then only you will be able to understand. So here we will see 4 types of problem. This is type 1, we will see type 2, type 3 and type 4 with a lot of examples. So let's start with the first question. So 4-bit binary parallel adder is there, which is made using 4 full adders. For each full adder, the sum is produced after 10 nanosecond of delay and carry after 15 nanosecond of delay. You need to find the time when you receive the stable output. The complete output is stable. So in binary parallel adder, if you have studied it, there are unstable state as well, because these states A3, B3, A2, B2, A1, B1, A0, B0, all these bits will be applied at t equals to 0. All these bits will be applied at t equals to 0. So initially there is no carry here, there is 0. Initially 0, like before t less than 0. For t less than 0, there was no carry here, there was no carry here, there was no carry here. So now this guy will perform the calculation. This full adder will perform the calculation that one of my bit is this, one of my bit is this, and one of my bit is this. So it will perform the calculation considering A2 plus B2 plus 0. So here you will get the unstable output, because who knows, from the previous stage your carry could be 1. So after that output again can change. So in between there will be unstable states, right? So we need to find when your output is stable. So all these inputs are stable at t equals to 0. So if I write my stable output, this is what I am writing my stable output. Here I will write my stable output. So initial C0 I am taking as 0, because it is given initial C0 is 0. So this will generate some as 0 and will generate a carry. This is stable output. So now the output is given as A1 plus B1 plus C1. So it will generate S1 and carry. Now output is generated as C2 plus A2 plus B2, S2 and carry. Output is generated considering C3 plus A3 plus B3, S3 and carry. Okay, so this is the final output. So when we will receive this stable output, this is what they are asking. So now they are saying, now the operation will start at t equals to 0. Now they are saying that sum is produced after 10 nanosecond of delay. So this is showing my sum. Okay, this is my sum S0, S1, S2 and S3, and this is showing my carry C0, C1, C1, C2. Oh no, sorry. This is C1, C2, C3. Really sorry. C1, C2, C1, C2, C3, and this is your final carry C4. Okay. Now all these bits are applied at t equals to 0. The sum is produced after 10 nanosecond of delay. So these guys will produce the sum after 10 nanosecond of delay. So to travel from here to here, it will take 10 nanosecond of delay. So this will be stable after 10 nanosecond, right? This guy is stable at t equals to 0 nanosecond only. This guy is also stable at t equals to 0 nanosecond, and this guy is also stable at t equals to 0 nanosecond. What about this guy? Now the stability of this guy depends on this output, right? And now this output is generated after 15 nanosecond of delay. So when A and B were there ready, now this full adder was ready to give the output, because this input is stable, this input is stable, this input is stable. So this full adder is ready to give the output. So it will take 15 nanosecond of time and this will be stable. So now what about this full adder? So this full adder will say that A1 is stable, B1 is stable at t equals to 0 only, but my third input is not stable at t equals to 0. So I cannot produce the output at t equals to 0. So I will have to wait. So full adder will wait for this guy, because full adder will say that at my input A is stable, A1 is stable, B1 is stable at t equals to 0 only, but I cannot give the output because I have to wait for this guy, and this guy will be stable after 15 nanosecond. So after how much time it will generate the output? 15 nanosecond. For the sum it will take 10 nanosecond more, so 25, and for carry it will take 15 nanosecond more, so 30 nanosecond. Here it will generate the carry after 30 nanosecond. Now what this full adder will say, that my inputs are stable at t equals to 0 only, but this guy became stable after 30 nanosecond. So I can start working after 30 nanosecond. So 30 nanosecond plus 10 nanosecond it will take for reducing your sum, and 15 nanosecond, 13 plus 15, 30 plus 15. So at 45 nanosecond it will produce your what do we say, this carry. Now this guy will say that I was able to perform the addition at t equals to 0 nanosecond if this guy was stable, but this guy is stable at 45 nanosecond. So now I will take 55 10. Now I will start working at 45 nanosecond. To produce the sum I will take 10 nanosecond more, and to produce the carry I will take 15 nanosecond more. So your final carry is produced at 60 nanosecond and sum is produced at 55 nanosecond. So what will be that maximum delay? Maximum delay to receive the stable output. Stable output means my S3, S2, S1 and S0, this should be stable, and C4 should also be stable. This is what I mean by stable output. That my S0, S1, S2 and S3, these should be stable and C4 should also be stable. So this is what I mean by stable output. So my S3, S2, S1 and S0, they were stable latest by 55 nanosecond and my C4 was stable at 60 nanosecond. So what is my maximum delay? 60 nanosecond. Say yes or no. This is the first kind of problem that we have covered. So my sum was stable at 55 nanosecond, but final carry, I will say final carry, because there were in between there were many carries, but final carry we are talking about was stable at 60 nanosecond. So maximum delay in receiving stable output, what is that? 60 nanosecond. Okay, now let's solve this particular problem considering that there are n bit parallelly added. It is n bit parallelly added. Okay, they are n bit parallelly added. So how will I solve it? So look, all these are stable at t equals to 0. So we'll change the color. So this guy will be stable after ts time. I am calling the sum will be stable after ts time and carry will be stable after tc time. Okay. No, final, they are not final. So I am calling this delay as ts, this delay as ts and this delay as tc. Okay. So it is applied at t equals to 0. So at t equals to 0 it started working, it will give output at ts. This will give output at tc, right? Now this guy will start working at tc. This guy will start working at tc. So it will give this output after tc plus ts and will give this output at 2 tc, right? Now this guy will start working at 2 tc. So if this guy started working at 2 tc, now it will give output of sum. It will take ts time more. So sum output will be given as 2 tc plus ts, because to produce the sum it will take ts time more, and to produce the carry it will take tc time more. So it will give after 3 tc. So now 3 tc is fed here. Now this guy will start working at 3 tc. So it will give output of sum after 3 tc plus ts, right? And it will give the carry output at 4 tc. Say yes or no. Did you understand this point? Again I am repeating. At t equals to 0 it was stable. So ts will be this sum will be received after ts time, because this circuit started working at t equals to 0. So this will be received, but carry will be received after tc time. So this tc is going here. Now this guy will start working at tc. So it will give you sum after tc plus ts. Tc plus the time taken for the sum to get out. So that is tc plus ts. And for the carry, tc plus another tc, 2 tc, right? Because carry will take tc time. So tc plus tc 2 tc. Now this guy will start working at 2 tc. For carry it will take 2 tc plus ts time. For sum it will take 2 tc plus ts time. For carry it will take 2 tc plus tc time. So this guy will be starting working at 3 tc. For sum it will take 3 tc plus ts time. For carry it will take 4 tc. So what did you understand? For 4 bit binary parallel adder, your carry is being stable at 4 tc and your sum is being stable at 3 tc plus ts. 3 tc plus ts. Try visualizing this circuit in your mind. Close your eyes and try visualizing it. That sir, first tc, after tc it would come up, then sum will come up after ts and tc would go there. So this guy will start working at tc. So this will take tc plus ts and 2 tc. This guy will start working at 2 tc. So it will take 2 tc plus ts, and this guy will start working at 3 tc. So it will take 3 tc plus ts and 4 ts. So for n, how much it will take? So sum will be stable after n minus 1 tc plus ts, n minus 1 tc plus ts, and carry will be stable at n tc. Can I write this as n minus 1 tc plus TS. Look, if they are asking what is the maximum time to receive stable output, then you should pick the maximum value of this. Here I picked this value, 60 nanosecond. Why did I pick this 60 nanosecond? Because this was more. Here I don't know the value of TS and TC. I don't know these values. So I don't know which one will be more. So what I can do, I wrote NTC as n minus 1 TC plus TS. So these two are same, right? Let's just say n minus 1 TC is 5. Now TS is 3 and okay, n minus 1 TC plus, sorry, this would be TC only. N minus 1 TC plus TC. And TC can be written as n minus 1 TC plus TC. And this TC is 4. So which one is the maximum? 9. So this one will be your answer. So can I write it in this manner? That your delay will be n minus 1 TC plus maximum of TC plus TS. Sorry, TC comma TS. Maximum of TC comma TS. If this TS was 5, then you would have picked this answer, right? So your answer would be n minus 1 TC plus TS. Are you getting this point? How did I write it? N minus 1 TC plus TC. I just wrote n TC as n minus 1 TC plus TC. Then I got to know that these two are same. If I need to make a formula that what will be the maximum time taken to receive the stable output, so that would be n minus 1 TC plus maximum of TC plus TS. You don't need to remember it, but what if it is there in some of the option? Like in the option only they are framing the problem like this, that what will be the maximum. This direct question is coming and ABCD options are there. N minus 1 TS plus maximum of TC TS, n minus 1 TC plus maximum of. So there it will be used. Otherwise, if the questions are coming like this, the same question is there. A 16-bit binary parallel adder is made using 16 full adder. For each full adder, the sum and carry both are produced after 10 nanoseconds of delay. Then find the time taken to receive the stable output. So what about carry? So in the mind only I will think, wait a second. So in the mind only I will think, what I will think? That carry will be generated here after TC. Then this guy will start working after 2 TC. So this will receive, this guy will start working at TC. So this will be received after 2 TC. So second output is being received after 2 TC. That means 16th output will be received after 16 TC. That's it. And what about sum? So for sum I will think that first will be received at TS. But second guy, TC will go, it will generate at TC plus TS. Third guy, 2 TC will go, it will generate at 2 TC plus TS. So third guy is giving 2 TC plus TS. So nth guy will give, or 15th guy will, 16th guy will give at 15 TC plus TS. So that would be my answer. Now TC and TS both values are same only. So 160 nanosecond and here also 160 nanosecond you will get. So answer is maximum delay is 160 nanosecond. Okay, so the block diagram should be clear in your mind. Again I am repeating, again and again I will explain this concept very slowly because it is very important and it is not taught in that good manner. So we are going to see this. Okay, so first after 10 nanosecond data is received and 15 nanosecond and 10 nanosecond only the carry was received. So carry went here, this guy started working at 10 nanosecond. So 10 plus 10 after 20 nanosecond sum will be received and 10 plus 10 after 20 nanosecond carry will be received. So next guy will start working. So in that manner it will keep on going. So it will be added up. So you do not need to solve like each stage, but you will see a pattern there. The TC time is being added, right? You will see a pattern. Now I will frame the question more interesting. This kind of question is not asked and can be asked. Okay. Now it is 8-bit binary parallel adder is made, but all the full adders are different now. Full adder 1, 3, 5, 7. 1, 3, 5, 7. These have the sum delay of 30 nanosecond and carry delay of 10 nanosecond, and the rest of the guys will have 20 and 30. You can solve it on your own, then match your answer. Okay. So in the examination, I am not going to make this structure, okay, this beautiful structure, nothing like that. I know all input will be coming at t equals to 0. So why to make these arrows? It will just waste my time. And this will also come at t equals to 0. So I know that. I am just going to write the timings. So both input are coming at 0. So this guy will start working at t equals to 0 only. This guy will start working at t equals to 0. So if this guy has started working at t equals to 0, then it will, what about full adder 1? So it will give the sum after 20 nanosecond and carry delay after 30 nanosecond. So now this guy will start working at 30 nanosecond. This guy started working at 0 nanosecond. This guy started working at 30 nanosecond. So it will give the sum after 30 plus 30 60 nanosecond, because here sum is taking 30 seconds and carry is taking 10 nanosecond only. So here carry is 10, here carry is 30. So this will give output after 40 nanosecond. Now this carry is being fed to this. So here input was stable at t equals to 0 only, and this carry is being fed here. So that means this circuit will be in position to give output after 40 nanosecond only. It will not wait till 60 nanosecond. Are you getting this point? Here you received this output at 40 nanosecond, right? So and this is being fed here, that you know. So this guy will be in position to give output at 40 nanosecond only, because these are stable, these are already stable, and this guy became stable after 40 nanosecond. So now this guy will say that now I have the capability of giving the output. So this guy will start working at 40 nanosecond only. And what is the sum delay for this? That is 20. So this sum will be stable at 60 nanosecond. And what about the carry? Carry will be stable at 70 nanosecond. So this guy will start working at 70 nanosecond. So what about full adder 3? So full adder 3 will give the delay after 30 nanosecond, and carry delay it will give quickly 80 nanosecond. Now this 80 nanosecond is fed here. So this guy will be in position to give the output after 80 nanosecond. So 80 nanosecond, this is full adder 4. So sum will be given after 20 and the carry will be 110. So this guy will start working at 110 nano. So what about full adder 5? So full adder 5 will give the sum after some time, but carry it can give in only 10 nanosecond. So this guy will be in position to give the output at 120 nanosecond. So full adder 6, for full adder 6, the sum will be received at 140 nano, but carry will be received at 150 nano. So this 150 nano goes here, right? So if this 150 nano goes here, so this guy full adder 7 will be giving the sum after 30 nanosecond. That means 180, and it will give the full adder 7 and will give the carry after 10 nanosecond. So 160 nanosecond. So final carry is received at 160 nanosecond, and final sum. So these sum were stable. This was stable at 20, this was 60, 60, 100, 100, 140, 140, and then 180. So this guy was stable at 180 nanosecond. So final sum is stable at 180 nanosecond. So this is the answer, maximum delay. So these kind of questions are not asked every time they have framed the same kind of full adder. But what if they change the full adder? So no formula will work here. You need to know the concept. Like every time I have seen people solving these kind of questions with formula. n-1 Tc plus maximum of Tc plus Ts, maximum of Tc and Ts. But what is the meaning of that? This is the meaning of that these kind of questions can also come up. Okay. So this is done about our pattern 1, type 1 or pattern 1 you can say. Now we will take a pause and we will solve the questions of pattern 2. Okay. So I will take a pause and then we will solve the questions of pattern 2. So now this is our type 2. So a 4-bit binary parallel adder is made using 4 full adders. Okay. Each full adder is made using 2 half adder and 1 OR gate. Each half adder is made using XOR gate and AND gate. Delay of XOR gate is 30 nanosecond, AND gate is 20 nanosecond, OR gate is 10 nanosecond. Find the time for getting the stable output of binary parallel adder. Now 50% of the student will think that I can solve this question, right? Because full adder is made using half adder. I have studied the analysis of full adder already. So what I will do, I will generate the sum and carry. I will see the time in which sum and carry are stable, and then I can solve by the previous analysis, right? So this is what you guys are thinking. So let's solve by that. So 30, 20 and 10. So this is the internal structure, half adder and this OR gate. So when your sum will be generated, so sum will depend here. So this guy is stable at t equals to 0, but this guy will be stable at t equals to 30 nanosecond. So 30 plus 30, 60 nanosecond. So sum will be stable at 60 nanosecond. And what about this carry? So this carry will depend on here. So this guy is stable at 20 nanosecond, right? What about this guy? So in this guy is stable at 30 nanosecond, and this carry is stable at 0 nanosecond only. So 30 and 0, but this guy will have to wait for this guy. So 30 plus 20, here 50 nanosecond. So 50 nanosecond, this guy is stable at 50 nanosecond, this guy is stable at 20 nanosecond. So 50 plus 10, 60 nanosecond. So you are saying that my sum is also stable at 60 nanosecond and carry is also stable at 60 nanosecond. So it is 4-bit binary parallel adder. So what will be the time taken for the sum to be stable? That would be 4-bit binary parallel adder. So 60 nanosecond will go, 60 nanosecond will go. So 3 into 60 plus TS, that is 60 only. So answer would be 240 nanosecond here. Wait a minute, I am not saying this is the correct answer. This is how you would be solving it. Okay, and for here it would be NTC. The carry will be stable after NTC only. TC plus TC plus TC. For some TC plus TS, 2TC plus TS, 3TC plus TS, 4TC plus TS. So in that manner 3TC plus TS. For this it is 4TC. So you are getting 240 nanosecond. So this is the maximum delay you are thinking, and this will be there in the option, and this is wrong. Now why is that wrong? Your full adder is made using half adder. Okay. What will be the complete equivalent circuit? Try making it. You are not going to make it in the examination. I will tell you the method how to solve it, but try making it once. What will be the complete circuitry? I am asking you to make binary parallel adder using full adders, but there each full adder is made using half adders. So try making the circuit. You can make it. So this is how the circuit will look like, right? A node, B node is there, half adder is there. It will generate the carry. In between the carry, this carry I am talking about. This guy I am talking about. This is your question mark. So this will be your question mark. Sorry, this will be your question mark. Sorry, this guy. And now this will be A XOR B. This I am calling sum. This I am calling carry. Okay. So this will generate some carry. This will be fed here. And for this I am calling sum. This I am calling as carry. So both of the carries are being odd. Here you can see carry of this guy and carry of this guy. Both are being odd. Carry of this guy and carry of this guy. So carry of first half adder and carry of second half adder is being odd, and now this carry will be fed to the next stage. This is the final carry, right? This is Ci plus 1. This is Ci plus 1, or you can say for here it would be C1. So this C1 will be fed here now, and then operation will keep on going. This will be your C2, and this C2 will be fed here, right? This will be your S0. This will generate S1 here. For S1 XOR of this, and then again XOR, right? C2, and this will be your S2. This will generate next carry, that is C3. This C3 is being fed here, so it will generate S4 and final carry C4. This is what is happening. Okay. Now tell me one thing. If you analyze only a half adder, so only for half adder, both of the half adders are same only, no? So for half adder, what is your TS? 30 nanosecond. And what is your T carry? This will be your carry and this will be your sum, right? So for half adder, what will be your carry? 20 nanosecond. So if I start here, so all these inputs, why I have written A naught, B naught, it would be A1, B1, sorry, A2, B2, and A3, B3, A3, B3. Now all these guys are stable at t equals to 0. All these guys are stable at t equals to 0. Right? All these guys are stable at t equals to 0. Now, to generate the sum, how much time it will take? 30 nanoseconds. So here I am already writing that to generate the sum I am taking 30 nanosecond time to generate a carry out of half adder. For half adder, and to generate a carry I am taking 20 nanosecond. So these guys will start working. This will be generated after 30 nanosecond, and this will be generated after 20 nanosecond. But this guy is not stable yet. Now 30 plus this will take 30 more. So this guy will be stable at 60 nanosecond, and for carry it will take 20 more. So this guy will be stable at 50 nanosecond. Now both guys will go 20 and 50. So this guy will be waiting for this guy. So 20 plus OR gate is having 10 nanosecond delay. So this guy will be stable at 60 nanosecond. Now this guy will be stable at 60 nanosecond. Right? Now tell me one thing. These two guys were stable at t equals to 0 only, no? These two were stable at t equals to 0. So for half adder you need only two inputs, and both are stable at t equals to 0. That means this guy started working at t equals to 0 only. And if this guy started working at t equals to 0, so this input is already stable. This input TS, this will take 30 nanosecond time to be stable. What I mean to say is that this guy started working at t equals to 0. So this will be stable at 30 nanosecond. So this guy will be waiting for this guy to generate this final output. This guy will be waiting for this guy to generate this final output. So 60 plus 30, it will take 90 nanoseconds to come out. Say yes or no? 60 plus to generate the sum, it will take 30 nanoseconds more. So 60 plus 30, it will take 90 nanoseconds to come out. To here to generate carry, it will take 30 plus 20, 50 nanoseconds. What about this guy? When this guy was stable? Tell me when this guy was stable. So this guy started working at t equals to 0. So to generate the carry, you need 20 nanoseconds. So this guy was stable at 20 nanoseconds. This guy was waiting for him. So it came at 50 nanoseconds. So 50 nanoseconds plus 10. So this will be stable at 60 nanoseconds only. Yes or no? This carry was stable at 60 nanoseconds. This was also stable at 60 nanoseconds and this was also stable at 60 nanoseconds. Why that happened? Because this was already working. Why did not we consider this thing in the previous problem, in the previous pattern, in these patterns? Because here it was given as a black box. Full adder completely was given as a black box, and it meant to say that for each full adder, the sum and carry will be stable after 10 nanoseconds, or in the previous problem it was 10 and 15. So internal structure was not given. So here what we meant is that this full adder will be working, when all three input will be stable. This full adder would be working when all three input are stable. But when they are giving the internal structure, we know that one of the half adder in the internal structure itself will start working before waiting for this carry. So this guy was not waiting for this carry. This guy was waiting, but this guy was not even waiting, right? So it started working and gave the output. In the examination, we are not going to draw this circuit. I will tell you how to solve the problem in the examination. So this guy was waiting. So wait a second. This guy came at 16 nanoseconds. Wait a minute. There is an error. So this guy came at 60 nanoseconds. So this guy started working at 60 nanoseconds. So to produce the sum, it will take 30 nanoseconds, and to produce the carry, it will take 20 nanoseconds. So this will be 80 nanoseconds. So both 20 and 80, 10 nanoseconds more. So 90 nanoseconds. Now this guy will be stable at 90 nanoseconds. Okay, sorry for this blunder. This guy started working after 60 nanoseconds, not 30 nanoseconds, because this particular guy was waiting for both of the input to be stable, and input was stable at 60 nanoseconds. So this guy started working at 60 nanoseconds. So to produce the sum, it is taking 30 nanosecond time. To produce the carry, it is taking 20 nanosecond of time. So here 90 nanosecond. Now this input is stable at 90 nanosecond, right? This input is stable at 90 nanosecond. What about this input? This input will be already stable because this guy started working at t equals to 0 only. So this became stable at 30 nanosecond, and this became stable at 20 nanosecond. So these inputs were already stable. Now this input became stable at 90 nanosecond. So this guy will start working at 90 nanosecond. So 90 nanosecond plus 90 nanosecond. For some, it will take 30 nanosecond more. So 90 plus 30, 120 nano. So this will be stable at 120 nanosecond. And what about this? So 120 nano here, and this guy started working at 90 nanosecond. So I will mark it up. This guy started working at 90 nanosecond. This guy started working at 60 nanosecond. So 90 plus for to generate carry, it will take 20 more. So this will be stable at 110 nanosecond. So 110 and 20. So it will pick 110 only. So this will be stable at 120 nanosecond. Right? And what about sum? Sum was stable at 120 nanosecond. So better I should write here 90 plus 120. Now what about this? This is going here. So this guy will start working at 120 nanosecond, and this would have been already stable. So it was not waiting for him. So 120 plus 30, 120 to generate the sum, it will take 30 seconds more. So this will be stable at 150 nanosecond. 150 nanosecond. And what about this? This was already stable. This was already stable. Although the time was 30 nanosecond, this was also already stable. Now at 120 nanosecond, this half adder 3 or 4, sorry, 3, 2 and 1. So now this half adder started working at 120 nanosecond. So 120 nanosecond plus 20 nanosecond to generate here 140, and this has a delay of 10 nano. So this output will be stable at 150 nanosecond. So stable output you are getting at 150 nanoseconds. So maximum delay. What is your maximum delay in this particular problem? that is 150 nanosecond. Okay, so when the internal structure is given, you need to take care of that. Are you getting this point? Whenever internal structure is given, you need to take care of that. In the previous problem, no internal structure was given. Now, how to solve this question in your examination? So, one stage you will draw, okay, one stage you will draw, and the question is saying that XOR gate will take 30 nanosecond, AND gate will take 20 nanosecond, OR gate will take 10 nanosecond. So, on circuit level I am not drawing, on block level I am drawing. I know in the half adder internal structure is this is the internal structure. I know the internal structure of half adder, that my sum will take XOR delay and my carry will take AND delay. So, this I know, this I will write. Only one stage I am drawing, okay, only one stage I will draw. Now I will get to know that these two will be my input, these two will be stable at t equals to 0 only. So, this will be stable at 30 nanosecond, this is how I will write, and this will be stable at 20 nanosecond. Now I know one thing, 30 plus 30, this will be stable at 60 nanosecond, and 30 plus 20, this will be stable at 15 nanosecond. Now which guy is more? This guy is more, so this will be stable at 60 nanosecond. Now I know one thing, what is that? That this carry is being fed to the next stage. So this carry is being fed to the next stage here. So this next stage only here only I am drawing. So this input has become stable at 60 nanosecond. And now for the next stage, this guy also started working at t equals to 0. For the next stage I am telling, for this second stage. So in the second stage, this guy also started working at t equals to 0. Say yes or no? Say yes or no? So this guy would have been already stable for the second stage. This guy would have been already stable, 30 nanosecond, 20 nanosecond. And this guy also would have been already stable. So you do not need to change these guys. These guys will remain there as it is. Say yes or no? Not changing. So 30 nanosecond and 60 nanosecond. So this guy was waiting for this particular guy. So this guy came at 60 nanosecond. So they will produce the output after 30 nanosecond more. The sum output I am saying. So this will be stable at 90 nanosecond. And it will start working at 60 nanosecond. So 60 nanosecond plus 20 nanosecond, that would be 80 nanosecond. So this will be stable at 80 nanosecond. So this guy will be waiting for this guy. So 80 plus 10. So this will be stable at 90 nanosecond. So now this is again fed back. So this will be 90 nanosecond. No need to care about these guys. Start working at 90 nanosecond only. So sum will be given at 90 plus 30, 120 nanosecond. 120. Some bit is gone. What about this carry bit? So 90 plus 20, it will take, I will just mark them up that this is the time where my circuit is working. So it is working at 90 and this was 60. So what about the carry bit? 90 plus 20, it will be given at 110 nano. I will make it broad, okay, on a paper I will make it broad. In the examination I am telling. So 110, so this bit is stable at 110, so it will take 10 more. So this will be stable at 120 nanosecond. That means now, first stage I have drawn, this was the second stage, this is the third stage, now the fourth stage is coming, that is the final stage. So this is 120 nanosecond. So don't care about these guys, 120 nanosecond, 120 plus 30, this will generate final output at 150 nanosecond. So this is my sum output. What about the carry? 120 plus 20, so this will be working at 140. It is working at 120, it will take 20 times more, so this will, you will be getting at 140. And 140 plus 10, so this will be your final carry. So this is your final answer, maximum delay. So this is how I will be solving in the examination. There is no chance of blunder because I know that this is being fed to the next stage and I can analyze the next stage on one stage only. Because I have seen this. If I have seen this, picture is clear in my mind that what is happening. Half adder, producing sum being fed to the another half adder, produce the final sum. Here it is producing a carry and this second half adder is also producing a carry, that is being ORed and fed to the next stage. So one stage I will draw and based on that I will be able to solve all the problems. So this is how I will be solving in the examination. Okay, let's solve the next question which was asked in gate only. You solve it on your own, do not draw the full circuit. Okay, solve it on your own, write down your answer. I hope you must have solved it. The final answer is 12 nanosecond. So if you are getting 12 nanosecond, that is correct. So let's start. So they started working at t equals to 0. Now delay of my half adder will be equal to the XOR gate, that I know because picture is very clear, and OR gate, sorry, AND gate, that is 1.2 and this is having 1.2. So these two guys started working at 0, 0. So sum will be produced at 2.4 and carry will be produced at 1.2 nanosecond. This guy would be stable at 0 nanosecond only. So first circuit will start at, wait a second, sorry. So this guy would be stable at t equals to 0 only, but this guy is stable at 2.4 nanosecond. So first circuit will start at 2.4 nanosecond. So 2.4, some will take 2.4 more. So 2.4 plus 2.4, here I will be getting 4.8. And 2.4 plus 1.2, here I will be getting 2.4 plus 1.2, 3.6. And 3.6 plus 1.2, 4.8 nano. Right? Now I know that this will be fed back here. So now this 0 nano has become 4.8 nano. This 0 nano has become 4.8 nano. So this, in the next stage as well, this would have been already stable. So this guy would have been already stable and this guy would have been already stable. So this 2.4 nano is already there. So this guy will start working at 4.8 nanosecond. So 4.8 plus 2.4, because some will take 2.4 time more. So 7.2 nanosecond. At 7.2 nanosecond you are receiving your sum. And what about the carry? So 4.8 plus 1.2. So this will be stable at 6 nanosecond. 4.8 plus 1.2. 4.8 plus 1.2. So this will be stable at 6 nanosecond, and 6 plus 1.2, this will be stable at 7.2 nanosecond. Now it is again feedback. So 7.2 nanosecond. Now this guy started working at 7.2 nanosecond, right? This guy started working at 7.2 nanosecond. So 7.2 nanosecond it started working. So sum it will produce at 7.2 plus 2.4. That means 9.6 nanosecond. And what about the carry? 7.2 plus 1.2, that would be 8.4. So carry will be produced at 8.4 nanosecond. So wait, sorry. This carry will be produced here. This carry will be produced at 8.4 nanosecond, and 8.4 plus 1.2. So it will take 9 nanosecond. Are you getting this point? 8.4 plus 1.2, 8. This is 7.2, and 7.2 it will take 1.2 more time. So it would be generating the carry at 8.4. 8.4 plus 1.2 would be 9.6. So why I am writing 9? It would be 9.6 nano. Now this input will be stable at 9.6 nanosecond. So this guy will start working at 9.6 nanosecond, and 9.6 plus 2.4, what that would be? 9.6 plus 2.4, 12 nano. So this guy will be stable at 12 nano. And what about this? 9.6 plus 1.2, that would be 10.2. So this guy will be stable at 10.2. 9.6 plus 1.2, that would be 10.8, sorry. So this guy will be stable at 10.8. Now 10.8 plus 1.2, that will be 12 nano. So your final sum and carry both are being stable at 12 nano. Just don't do the calculation mistake that the way I am doing. 9.6 plus 1.2, that is 10.8. But 10.8, this is stable, and 10.8 plus 1.2, this will be stable at 12 nanosecond. So your sum is stable at 12 nanosecond, and carry is also stable at 12 nanosecond. So what is the final answer? Final answer, or you should say maximum delay. So what is the maximum delay? That is equals to 12 nanosecond only. So this was our type 2. So for this type, I will give you a homework. Here there are 16 bit. So 16 cycles will come. But do you think you will solve all the cycle like that? No, you will see a pattern here. Here also we are getting a pattern. Can't you see 4.8, 7.2, 9.6, 12? 4.8, 7.2, 9.6, 12. So solve for few cycles, you will see a pattern there. That's it. So if you see the pattern, that would be your final answer. So you are not going to solve for the 16 bit. These kind of questions haven't been like these kind of questions, they never asked. They are asking for 4 bits only, so that guy can do this analysis. Or if someone is solving by this analysis as well, then also he will be able to tell the answer. But what if there are 16 bits? So you solve it on your own. The hint is you do not need to solve it completely. You will get some pattern there. Okay. So I will send the solution in Telegram group. You can join the Telegram group. And if you are watching this video carefully, if I mean something to you, if this channel means something to you, then you need to type your answer. Just type your answer in the comment section, so that I could know how much guys are understanding. So please type your answer in the comment section after solving this particular problem. So now we will move to the type third. We will pause for a while now, and now we will move to type third. So we will be back in some time. Hi everyone. So now we will see the third type of problem, and this is very important and very high chance that if they are framing a question from full adder, then this kind of problems will come. So the problems I have written here, but before that I want to give you one very good concept that I have already given in our course, but let's see it here again. Okay, so this is the truth table of full adder, right? This is the carry and this is the sum. Mark that carry I have written first and then I have written sum. So if you talk about carry, then let's see these two lines. In these two lines, if my a and b are 0, if my a is equals to b is equals to 0, then without even caring about these two bits, I can directly say that my future carry would be 0 only. If my a and b are 0, then without even thinking of the previous carry, I can always say that my future carry will be 0. So if a and b are 0, then we will never care of the previous carry. We can directly give the output without even caring of the previous carry. If my a and b are 1, if my a and b are 1, then without even caring for the previous carry, I can always say that my carry will be 1 only. Forward carry will be 1 only. Say yes or no? If a and b are 1, so without even looking back that whether my ci will be 0 or 1, we can always say that my forward carry will be 1 only. So if a and b are 1, so without even thinking a bit, we will always give ci plus 1 will be 1. So here there is no wait, right? No wait for ci. We are not waiting for ci here. No wait for ci, right? Well and good. Do you agree to this point? But if a is equals to 0 and b is equals to 1, or b is equals to 1 and a is equals to 0, then your ci plus 1 will be equals to ci only. Basically, if a is 0 and b is 1, so let me take another color of pen, that is this. 0 or 1, 0, 1, 1, 0, 1, 0. So my ci plus 1 is equals to ci only. So here I will have to wait, because if a is 0 and b is 1, and if my ci is 0, then ci plus 1 will be 0. And if a is 0, b is 1, and if ci is 1, then ci plus 1 will be 1. So here my ci plus 1 is not fixed. Ci plus 1 is depending on ci, right? I can say that my ci plus 1 is not fixed here, but it is a function of ci, right? So here we will wait for ci, wait for ci to come. Is these 3 points are clear to you or not? See these carefully and see and tell me if these 3 points are clear to you or not. Clear? Because it will be very, very highly used. So if a is 0, b is 0, I am not waiting. A is 1, b is 1, I am not waiting. If a is 0 or b is 1, or if b is 1 or a is 0, I will wait for ci. Let's see what kind of questions we are going to see here. So the type 1 we have already seen, no? It is the same kind of problem. Full adder is given, no internal structure is given, full adder is given, you need to find the maximum delay. Carry delay is given, some delay is given. But this time input are mentioned. Input are mentioned, that is 0, 1, 0, 0, 1, 1, 0, 0. And for t less than 0, all inputs were 0. So for t less than 0, all inputs were 0. So this carry would have been 0, sum would have been 0, this 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 would have been 0. Although you do not need to write it, you will be remembering it only, no? Basically, if previous bits were 0, so 0 plus 0 plus 0 all were added 0, 0, 0, 0, and carry would also have been 0. So everything was 0 for t less than 0. Now for t greater than 0, that means for that means at t equals to 0 plus, this has been applied. So here what all will be added? 0 and 0 will be added, 0 plus 0. 0 and 0 will be added, 0 plus 0. 1 and 1 will be added, 0 and 1 will be added, 0 and 1 will be added, right? Previous things were, all these were 0. Now and C0 is updated to 1, okay? C0 is updated to 1, and this happened at t equals to 0 only. Now all these inputs that we see here, all these are stable at t equals to 0 only, no? All these are stable at t equals to 0. Now I will go to this guy. What do I see? I see 0, 0. What do I see? I see 0, 0. I will ask him, do you wait for C0? He will say, I don't wait for C0. Although C0 comes at t equals to 0 nanosecond only, but he does not wait for C0. He says that I do not wait for C0. if you are applying 0 0 here, I can give my carry equals to 0. First I am talking about carry only. So now my updated carry is 0, which did not change. Previously also it was 0 only, now updated carry is also 0 only. So it will take 0 nanosecond time. Although let's just say if carry generated was 1, if carry would have been updated from 0 to 1, then it would take TC time, which is 20 nanosecond. So to generate the carry, it is actually taking 20 nanosecond time, but after 20 nanosecond you get to know that the carry is 0 itself. So it is stable at t equals to 0 nanosecond only. Now I will go to this guy. I will ask him, do you carry? Do you care of your previous carry? He will say, no, I do not care of my previous carry. So I can generate this carry immediately. It will take 20 nanosecond of time. To update from 0 to 0, it will take 20 nanosecond of time, but it is not even updated. If it was going from 0 to 1, then you would have said that it has been updated from 0 to 1 at 20 nanosecond, but it is not even updated. That means this is also at steady state at t equals to 0 nanosecond only. Is that clear? Let's go to this guy. What this guy will say? I will ask him, do you care about your previous carry? He will also say, I do not care, right? He says, don't care. He says, I also don't care. He says, I also don't care. Why it doesn't care? Because previous carry is, because A and B are 1. If A and B are 1, then it will always give 1 only, irrespective of whatever the bit there is. Basically, if this is my circuit and I have applied 1 1 here, so if I apply 0, still I will get carry 1. If I apply 1, still I will get carry 1 only. So it doesn't care whether it is 0 or 1. So just as you applied it at t equals to 0, at that time he said that I am gonna give carry 1. And to give the carry, how much time it will take? 20 nanosecond. Because here it is changing, no. Here also it was taking 20 nanosecond, but it did not even change. So we will say that it was always stable. Here also it was taking 20 nanosecond, but it did not even change. So we will say it was always stable. But here it is changing, so it took 20 nanosecond. So after 20 nanosecond, this bit will become 1. Okay. So this point is clear, no? If 1 1 is there, it doesn't care about the previous carry. If 0 0 is there, it doesn't care about the previous carry. Now I will go to the other guy. I will go to this guy. I will ask him, do you care about the previous carry? He will say, yes, I care about the previous carry. He cares. If he cares, that means he will start working when this is updated. So this will start working at 20 nanosecond. So this guy started working at 20 nanosecond. Say yes or no? Because he cares. Because for 0 1 0, your carry will be 0. But for 0 1 1, your carry is different. So he cares whatever that is behind him. So he cares about this carry. So they were updated at t equals to 0 only, but this bit was updated at t equals to 20 nanosecond. So this guy started working at 20 nanosecond. So now what will be the carry bit? 0 plus 1 plus 1. What that would be? 1 only. So this carry bit will be updated to 1. And how much time it would take? So this guy started working at 20 nanosecond, and to generate the carry it will take 20 nanosecond more. So 20 nano plus 20 nano, 40 nano. So this bit was updated at 40 nanosecond. Did you understand this point or not? This guy said that I care about my previous output. I care about my previous carry. So if he is caring about previous carry, that means he will start working at 20 nanosecond. This we are talking about only carry. We will talk about some now. Wait a second, we will talk about some. So this guy said that I care about him. I care about the previous carry. So I will start working at 20 nanosecond only. When this guy comes, then only I will start working. So this guy came at 20 nanosecond and this guy started working. So to generate a carry, how much time it takes? 20 nanosecond more. So 20 plus 20, 40 nanosecond. So this bit is stable at 40 nanosecond. So this was about carry. Let's talk about sum now. So initially all the sum were 0, right? Now 0 plus 0 and this C0 is 1 here. So sum will be updated to 1. This guy came at 0 0. This guy also came at t equals to 0 nanosecond. So this complete adder started working at t equals to 0 nanosecond. If it started working at t equals to 0 nanosecond, that means it will give sum 1. And how much time it will take? What is the t sum? That is 10 nanosecond. So this will be stable at 10 nanosecond. Right? 0 0 0. Initially as well there was input was 0 and this carry was also 0. So initially sum was 0. After that as well, input is 0, carry is also 0. So this never got changed. So this was always stable. So this was stable at 0 nanosecond only. This never got changed. What about this guy? Initially 1 1 0 was there. Look, basically initial sum was 0. Then 1 1 was applied. Initial sum was 0. Then 1 1 was applied. If 1 1 was applied and this carry was 0, then what would have been the sum? When 1 1 applied, this was also there. This was at t equals to 0 nanosecond. This was at t equals to 0 nanosecond. This was at t equals to 0 nanosecond. This is the condition for t less than 0. Right? Now I am talking about t equals to 0 nanosecond because this was there at t equals to 0 nanosecond. So 1 1 0. What will be the sum? 1 only. Right? The sum will be 1. 1 1 0. Sorry. 1 1 0. Sum will be 0. Sum will be 0. Carry will be 1. So sum will be 0. After that as well, the carry never changed. Carry is always 0. So sum will also be always 0. So these are always 0 only. So it was always stable. The sum did not even change. Sum never changed. So it was always stable. What about this guy? When 0 1 0 was there, look, for t less than 0, what was the scene? For t less than 0, it was 0 only. At t equals to 0, what happened? At t equals to 0, this was 0, 1 and 0. Say yes or no? 0, 1 and 0 at t equals to 0. So at t equals to 0, the sum was 1. 0 plus 1 plus 0. The sum was 1. At t equals to 0, sum was 1. Sum was 1. Now after 20 nanosecond, this guy became 1. After 20 nanosecond, this guy became 1. So now the adder will say, I will add 0 plus 1 plus 1. So what is the sum of that? 0. So it will be updated to 0. When it will be updated, this guy started working at 20 nanosecond. And to get the sum, how much time you need? 20 plus 10. So t equals to 30 nanosecond. So it will be updated at t equals to 30 nanosecond. So this guy was updated at 0. This guy was updated at 0. This guy updated at 10 nanosecond. And this guy updated at 30 nanosecond. And this guy updated at 40 nanosecond. So your final sum came at 30 nano. And final carry came at 40 nano. So what is the maximum delay? 40 nano. And just wanted to add a point, like sometimes I have seen that people analyze some part wrong. Okay, they will analyze carry part correctly, but some part wrong. Like they do not even consider that initially there was 0. It might happen, like error may happen. Like from greatest of educators, the error may happen, but we need to analyze the carry as well. It's not that at that time it started working. So like I will show you a lot of example where the things will change in sum. So this was one of the example. I know you did not understand it 100%, but we will solve a lot of example. We will solve more examples. It will come to you again. Okay. So let's see the next example. The same question is there. 1 0 1 0 1 1 0 0 and C0 is 0. So C0 is 0. 0 will be added to 0 0 0. Sorry. 0 will be added to 0 0 0. 1 will be added to 0 1 0. Then 0 1 and then 1 1. So all the initial everything was 0. Initial everything was 0. Everything 0. Initial everything is 0. Now all these guys came at t equals to 0. All these guys came at t equals to 0. Right? This was also at t equals to 0. So this guy started working. For the first guy, you can directly see, okay, 0 0 0. I will ask him, do you care about the previous carry? He will say, no, I do not care about the previous carry. I will directly generate 0 here. So this guy did not even change. That means this was stable at 0 nanosecond. Now I will go to him and I will ask him, do you care about your previous carry? He will say, yes, I care about previous carry. So I will start working when my previous carry is stable. So my previous carry is stable at 0 nanosecond only. So this guy will start working at 0 nanosecond. 0 nanosecond, it will start working at 0 nanosecond. If it starts working at 0 nanosecond, what will be the carry it will generate? 1 plus 0 plus 0. It will generate 0 carry only. So if this carry is not even changing, that means it is stable at 0 nanosecond only. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, yes, I care about the previous carry. I will start working only when the previous carry is stable. So previous carry is stable at 0 nanosecond only. So he will start working. Now 0 1 0 is there. So how much carry he will produce? 0 carry only. He will produce 0 carry only. So this carry is stable at 0 nanosecond only. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, I don't care about the previous carry. I don't care about the previous carry. I will start working at t equals to 0 nanosecond. Even though if it is 1 or 0, I do not care about it. I will start working at t equals to 0 only. So I will generate output 1, carry output 1. Just as you apply the input, I will generate carry output 1 with the from here to here, coming from here to here. How much time it will take? 20 nanosecond. So it will take 20 nanosecond because my TC is 20 nano. TC is 20 nano. So this will be generated at 20 nanosecond. Let's talk about sum now. So initial bits were 0 0 0 0 only. After that also it is 0 0 0 only. So it got updated to 0 0 only. So it was stable at 0 nanosecond. What about this guy? Always 0 0 0. No bit change. Basically, sorry. So initially it was 0 0 0. So it was for t less than 0. It was 0. It was 0. It was also 0. So this was 0 only. For t greater than 0, at t equals to 0 nanosecond, it was applied 1. It was applied 0. And this was applied to 0 as well. So at 0 nanosecond, you got 1 0 0. So it will perform the summation. And what will be the summation? 1 plus 0 plus 0. That would be 1. And how much time it would take? It would take 10 nanosecond. Sum would take 10 nanosecond. Now you went here. So initial 0 0 was there, so sum was 0. At t equals to 0, you applied 0, 1, and at t equals to 0, your carry was 0 only. So it will perform the sum. And how it will perform the sum? It will make it 1. But how much time it will take? 10 nano. It started working at 0 nanosecond, so it will give the sum as 10 nano. What about this guy? When 0 0 was there, it was 0 only. But when 1 1 was applied, at that time as well, the sum was 0 only. Now 1 1 0 is applied, still the sum is 0 only. So sum never got changed. Sum never got changed. That means it was stable at 0 nanosecond only. So your carry was stable at 20 nanosecond and sum was stable at 10 nanosecond. So what is the maximum delay? 20 nanosecond. Well and good. Let's try solving the next question on your own. This is 0 written. In the back 0 is written. Okay, let's start now. So I will go to this guy 1 0. Do you care about the previous carry? He will say yes, I care about the previous carry, but previous carry is stable at t equals to 0 nanosecond only. And these guys are also, all these guys are stable at t equals to 0 nanosecond only. All these guys are stable at t equals to 0 nanosecond. So they will generate the sum. They will generate the sum, that is, forget about the sum. Sum we will see later on. And initial sum, all sum are 0. All bits are 0 0 0 0 0 0. Now I will, now this guy will say that I care about the previous carry. If my previous carry is 0, my next updated carry will also be 0. But it was already at 0, so it would take 0 nanosecond time. All these carries are already at 0. So it would take 0 nanosecond time. Now you go to this 0 0 guy, you ask him, do you care about the previous one? He will say, no, I do not care about the previous one. I will give my next carry equals to 0. So if it is updated from 0 to 0, that means at 0 nanosecond it is stable only, right? Now I will go to 1 1. I will ask him, do you care? He will also say, I do not care. That means I will update my carry to 1 because 1 1 is there. So if 1 1 is there, he will update the carry to 1, right? Because if A and B are 1, my carry will always be 1. If A and B are 0, my carry will always be 0. So he also doesn't care about the previous carry. So he will say, I will update it to 1. And to generate this carry, how much time I will take? 20 nanosecond. For TC is 20 nanosecond, right? TC we have assumed to be 20 nanosecond. So he will say, I will take 20 nanosecond. Say yes or no. Now I go to this guy. I will ask him, do you care? He will say, yes, I care. Yes, I care. So I will generate my carry only when this guy is stable. So when this guy is stable at 20 nanosecond. So I will start working at 20 nanosecond. So this guy starts working at 20 nanosecond. So if this guy starts working at 20 nanosecond, that means now it will generate the carry. So what carry it will generate? 1 0 1. The updated carry here is 1. At 20 nanosecond, you see 1 here. So 1 plus 0 plus 1. What will be the carry? Carry will be 1. Carry will be 1. And if it is being updated, carry is being updated here. If it is being updated, that means it would take 20 already was there and 20 more time it would take. So 40 nanosecond it would be updated. Now I will ask him, do you care about the previous condition? Do you care about your previous carry? He will say, I do not care about the previous carry. So what do you think? It will start working at 40 nanosecond or it will start working at 0 nanosecond? It will start working at 0 nanosecond only. Say yes or no? Because it doesn't care about the previous carry. It doesn't care about the previous carry. Just as you applied 0 0, the full adder will not care about the previous carry. It will generate the forward carry immediately. So this has been stable at t equals to 0 nanosecond. Now I will go to him, do you care about the previous one? He will say, I also do not care about the previous one. So here initial carry was 0. Now I do not care about the previous one and my carry would be 1. So this will be updated from 1 1. You started like this guy started working at t equals to 0 nanosecond. When this guy started working at t equals to 0 nanosecond, because it doesn't care about the previous carry. So if it is not caring about the previous carry, it started working at 0 0. So it generated carry equals to 1. So how much time it would take? 20 nanosecond, right? It would take 20 nanosecond. For carry, it would take 20 nanosecond. Now let's talk about sum. So initially 0 0 was there, so sum was 0. Now 1 0 1 1 0 0 is there, so sum has become 1 now. Sum has become 1. So to go from 0 to 1, how much time it would take? 20 nanosecond. Look, here it was the most important point in between, that this guy started working at t equals to 0 nanosecond only, because he knows that I do not care about the previous one. So even though this guy is being 1 at 14 nanosecond, but I don't care about that. Why I do not care? Because I am 0 0. So I will always give carry equals to 0 only, no matter what is my CI. So I do not care. So I will give my 0 at 0 nanosecond only. Although I should take time. I should take time of TC. To generate this carry, I should take time of TC. But this carry is not even being changed. So at 0 nanosecond only, you will get the same answer, right? So this you got at 20 nanosecond. What about this? Initial was 0 0. Updated carry is also 0. So nothing got changed. So this is stable at 0 nanosecond only. Here initial was 0 0, then 1 1 came. If 1 1 came, that means it will take the sum to 0. If 1 1 came, it will take the sum to 0 only. Initially 0 0 and 0 was there, all three were added, so you got 0 only. Now it has become 1 1 0. So 1 plus 0, the sum will be 0 only. Now after that, when carry came, it was again 1 plus 0 only. So this sum never got changed. This sum never got changed. What about this guy? So initial there was 0 0 0, so sum was 0. Then 1 0 0 was there, 1 0 0 was there, right? 1 was there, 0 was there, but this guy 1 came later on at t equals to 0. I am telling at t equals to 0, 1 was there, 0 was there, and this 0 was there. So at t equals to 0, this was 1 0 0, right? So it would give the 1, it would give the sum 1 at how much time? It will take 10 nanosecond time. It will take 10 nanosecond. 1 0 0, it will take 10 nanosecond time. Now after 20 nanosecond, what happened? 1 was there, 0 was there, but this guy became 1. So after 20 nanosecond, he realized that my input are changed now. If my input are changed, so I need to do the action now. So what action I will do? I will change 1 plus 1 is 0 only. So I will again change. So at 20 nanosecond, it started working. To get the sum, how much time you require? 10 more. So 20 plus 10, 30 nanosecond. So this sum will be stable at 30 nanoseconds. So this was a very important point. Are you getting this point? Like I can guarantee you, no one will teach you this thing. Okay, like they are changing, how they are changing. So like we cannot say that it will start working at 20 nanosecond and then after 10 nanosecond more, this will be 0. Like if I had analyzed it in this manner, that initially this was 0. Okay, initially this was 0. Then after 20 nanosecond, it was 101. So what would be the summation? 101. Again summation would be 0. So I would feel like that the summation did not even change. But there is an intermediate state. There is an intermediate state at t equals to 0. At t equals to 0, this was 1, this was 0, and this was 0. So at intermediate state, in between, the sum got changed. So this is the waveform of sum. 0, then it became 1, then it became 0. So there was a change in state. So this will be the steady state. This is not the steady state. So the state of sum got changed here. So we always have to see for t less than 0, at t equals to 0, and if your carry is changing, after that what happens? So these three states we need to analyze when we are talking about the sum. Are you getting this point? Okay. So yeah. Now let's go to the next one. This is the toughest question which can, no, this is not the toughest, another part will come. Okay, this is not the toughest. So yeah. So let's analyze for this guy, for this carry. For this sum, sorry. So initial 0 0 was there, so this was 0 only. When bits got updated, this was 0, this was 0, and this was 0 only. At t equals to 0, this was 0, this was 0, and this was 0. At t equals to 0. So nothing got changed, it was 0 only. Sum was 0 at t equals to 0 nanosecond. It was going fine. suddenly at 40 nanoseconds this guy became 1. At 40 nanoseconds this guy became 1. So now what you need to do, 0 plus 0 plus 1. So now addition will be 1. So now you need to perform new addition, that would be 1. So it started at 40 nanosecond. To get here I would need 10 nanosecond more. So my answer would be 50 nanosecond. Okay. So my answer would be 50 nanosecond. Now here initial was 0 0 0, so sum was 0. Then at t equals to 0 nanosecond only 1 1 came. At t equals to 0 nanosecond 1 1 came. So my sum got updated to 0. After that as well, this carry was always 0. So it did not even change. It never changed. This carry never changed. So it also did not ever change. So it was always 0. So this was stable at 0 nanosecond. So which one is the latest one? Look, we always do not need to look at the final one. We always need to look which guy got stability latest. So this guy got stability latest. This guy got stability at 50 nanosecond. This guy at 30. This guy at 20. And this guy at 0 nanosecond only. And this bit was stable at 1 nanosecond. This so what is the maximum time? This is the maximum time. So maximum delay is 50 nanosecond. And if they ask you this question, that delay in getting C4, this is C4 or C5. Okay, there are much more blocks. This will generate C1, C2, C3, C4, C5. This is C6. So C6 got stable at 20 nanosecond. But this is not the maximum delay. Your final stable output you will receive after 50 nanosecond. Say yes or no. So is that concept clear to you? We have seen 3 examples. You have to pause the video and think on your own what is actually happening. Then only you will be able to understand. Get back to the video, rewind it again. You will understand a lot of new things. Okay. Let's go to this question. This is very conceptual and I have framed it on my own only. And you are not going to find these kind of questions anywhere that I can write on paper. Okay. Yeah. So just like telling that it has required a lot of efforts. So for t less than 0, a binary parallel adder will perform this kind of operation. For t less than 0, this operation is there. So 1 plus 1 is 0. 1 plus 1, this would be 1. 0, 0 and 1. Let me check if this is correct or not. 1, 0, 0, 0. So these are my steady state bits. Say yes or no. Steady state bits. Steady state. And these are my steady state carry bits. 1 plus 1, 0, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1. So here I am having the output 1, 0, 0, 1, 0. This is my steady state bits. And steady state carry bits are 1, 1, 1. Look, this operation has been performed for t less than 0. Although it was binary, although it was parallel addition, but here I did serial addition. Why so? Because I need the steady state. Let's say that I am solving a question of transient. So will I say that for t less than 0, will I say that my capacitor voltage charged to 5 volt? I will say that at t equals to 0, I will get 5 volt. That's it. So similarly, at t equals to 0, you will get these outputs, these outputs, and these bits, these carry bits. So here there would be 1, 1, 1. Now let's see what gets updated. So now these bits are updated, and they are not talking about C0. So C0 I will take 0 only. So now bits are updated as 1, 0, 0, 1, 1, 1, 0, 1, 0, 1. Okay, ulta लिख दिया. Wait a second. So it would be 1 is added with 0, 1 is added with 0, then 0 is added with 1, 1 is added with 1, and 0 is added with 1. So now we will solve the problem. So here it was 0 initially. Okay, this guy came at t equals to 0. All these guys came at t equals to 0 nanosecond. All these guys came at t equals to 0 nanosecond. And this guy came at t equals to 0 nanosecond only. Okay, this should be given here. I forgot to write that that c naught is equals to 0 at t equals to 0 nanosecond. This should be given. Okay, now do you care about the previous guy? Yes, I care about the previous guy, but previous guy is 0 and it is starting at t equals to 0 nanosecond only. So if this guy is starting at t equals to 0, so now I can start my operation at t equals to 0 nanosecond only. So he will start the operation at t equals to 0 nanosecond and he will generate the carry bit equals to 0. Now the carry bit is changing. To generate this carry bit, how much time it took? TC time, which is 20 nanosecond. So this guy took 20 nanosecond time here to generate this particular carry. Although if 0 was here, so from 0 to 0 we would say that it is a steady state only, but here it got changed. So it was 1 1 1 1 1, then it got changed. So this would be the timing diagram of this bit. So it got changed at 20 nanosecond, right? From here it started working. To generate this carry, it would take 20 nanosecond of time. So it got updated at 20 nanosecond. Now I will go to this guy. Do you care? Yes, I care. So this guy got updated at 20 nanosecond. So I will start working at 20 nanosecond only. So this guy will start working at 20 nanosecond. So if this guy started working at 20 nanosecond, so now he will generate a carry. What that carry would be? Carry would be 0, right? 0 plus 1 plus 0. Carry would be 0. This guy started working at 20 nanosecond and it would take 20 nanosecond more time to update it. So how much time would be here? So this bit will be updated at 40 nanosecond. This bit will be updated at 40 nanosecond. Now I will go to this guy. I will ask him, do you care about the previous carry? He will say, I don't care about the previous carry. If you have applied 1 1, then I will start working at 0 nanosecond only. Because I don't care about the previous carry, I can generate my final output. I can generate my final C out, which will always be 1. So that I can generate. Now you will say that, sir, it would take 20 nanosecond of time. It would take, to update from 1 to 1, it would take 20 nanosecond of time, but it is always 1. So if it is always 1, that means it was always at steady state only. So I will call it, this is stable at 0 nanosecond only, because it never even changed. I will go to this guy. I will ask him, do you care about the previous one? He will say, yes, I care about the previous one. So now, what about the previous one? Previous one got stable at t equals to 0 nanosecond. So he will say that, yeah, now I can work at t equals to 0 nanosecond, because he is thinking for him. This guy is thinking here, but these guys do not care. These guys do not care about it. These guys do not care here. This guy is also caring, but this guy is not caring at all. Okay, this guy cares. It will start working at t equals to 0 nanosecond. If it started working at t equals to 0 nanosecond, what did he see? 0 1 1 1. So I will give my carry equals to 1. Now carry was already 1 only, so this did not even update. So the final carry you are getting at t equals to 0 nanosecond only. Final carry C4. This will be C1, C2, C3 and C4. C4 you got at t equals to 0 nanosecond. Final output means this is our final output. We have to look here. So this bit was always updated. Let's talk about sum now. So this guy started working at t equals to 0 nanosecond. Initially before that my sum was 0 by doing this calculation. Now if I do new calculation 1 0 0, my sum will be 1. So my sum got updated, and when this guy started working at t equals to 0 nanosecond, if this guy started working at t equals to 0 nanosecond, then how much time it would take to be 1? It would take 10 nanosecond more, because t sum is 10 nano, right? Now let's go here. Let's go to this guy. So initially it was 1, then it saw 0. When it was 0 1 1, then it was 1 only. Wait a second, where it was 1 1 1. Yeah, so at t equals to 0, what is the condition? At t equals to 0, for t less than 0, this is the scene. At t equals to 0, 0 1 1. So what will be the sum? 0. At t equals to 0, it shows 0 1 1. Sum will be 0. If sum is 0, then how much time it would take to come? 10 nanosecond, right? But at 20 nanosecond, it got to know that this carry has changed. At 20 nanosecond, it got to know that this guy has changed now. If this guy has changed at 20 nanosecond, then I have to give the changed output. What will be my changed output now? 0 plus 1 plus 0, and that would be 1. 0 plus 1 plus 0, that would be 1. So now my output will change. First it got changed here, now it got changed. Now it will change at how much time you will get it. At how much time you will get it. So it started working at 20 nanosecond, and how much time more it will take? 10 nanosecond more. So you will get it at 30 nanosecond. Let's see this again, okay? For t less than 0 or at t equals to 0 plus, you can say at t equals to 0 plus. At t equals to 0 plus, this was the condition, that it was 1. Then at t equals to 0, it got to know that 0 1 and 1 is applied. 0 1 and 1 is applied. Previously what was applied? Here you can say 1 1 1 was applied. If 1 1 1 was applied, it said that my some bit is 1. Now it got to know that 0 1 and 1 is applied. This happened at t equals to 0 nanosecond. This was there at t equals to 0 nanosecond, and this was also there at t equals to 0 nanosecond. now it got to know that 0 1 1 is applied. Now if 0 1 1 is applied, it will say that my sum bit should be 0, so it will update the sum bit. Now how much time it will take to come here? 10 nanosecond. Now after 20 nanosecond, it got to know that now 0 1 0 is applied, so something got changed. So now my sum is also getting changed, the sum is being updated to 1, so it will say that my sum is updated to 1. So how much time it will take? 20 nanosecond more. So basically 20, it started working at 20 nanoseconds, so it will take 10 nanosecond more. To generate the sum, you need 10 nanosecond more. So 20 plus 10, 30 nanosecond. So here you are getting the stable output at 30 nanosecond. What about this guy? So my initial here, this output 101 was there, so this was 0. At t equals to 0, what happened? This was 1, this is at t equals to 0. So at t equals to 0, this 1 came, this 1 came, and this was 1 only. So 1 plus 1 plus 1, it got to know that I have to update it. So it will be updated to 1. Now to update it, how much time it will take? It will take 10 nanosecond time. But at 40 nanosecond, it got to know that my input has changed. Input has become 110. So now if I perform the addition, what I will get? 0. So at 40 nanosecond, it got to know that. At 40 nanosecond, it got to know that my input has changed. So if input is changed and at 40 nanosecond, you got to know. So again, I will start working. Okay, at 40 nanosecond, it again started working, and how much time it will take more? 40 nanosecond it started working and 10 nanosecond delay. So it will take 50 nanosecond time. Okay, so this guy got updated at 50 nanosecond. Now here, previous bit was 110, so this was 0. At t equals to 0, what it got to know? At t equals to 0, it got to know that 0 1 1 is applied. At t equals to 0, it got to know that 0 1 1 is applied. If 0 0 1 is 0 1 1 is applied, that means I should update my bit to 0. I should update my bit to 0, which is already there, so it is at stable state. At 0, now this carry bit never got changed. Carry bit never changed. If carry bit never changed, that means 0 1 1 will always be there, and this sum will never change. So this sum never got changed. So what is the latest time where your stable output is there? That is 50 nanosecond. So my sum is stable at 50 nanosecond. Okay, so what is the final answer? That is 50 nanoseconds. Okay, so that's how we will solve these kind of problems. Now we are going to see the next concept, and for that you need to revise it completely. Spend more time, solve all the problems that I have solved again and again. See what is happening in the circuit. In the examination, if these kind of questions are coming, you need to perform it in this manner only. I have taken the toughest problem which can come, which is this. For t less than 0, they will make you analyze, and for t greater than 0, they will see what can happen. Okay then, thank you, not thank you very much. We will take another session. In this session only I will add that. So in that we will discuss the fourth type of problem, in which what we are going to do. What do you think? We will make this full adder using half adders and OR gate. So this is what we are going to do. Okay then, yeah. So let's go to the fourth type of problems. We will take a pause and then we will come back. So now we will see the fourth type of problem. So in these kind of problems, full adder will be made of half adder and OR gate, and half adder will be made of XOR gate and AND gate. So internal structure is given. In the previous problem, internal structure was not given, inputs were given. So here inputs are also given and internal structure is also given. So everything is there. Now whatever that we have studied from the initial chapter, like delay of half adders and full adders, so from there to here everything will be used. Okay, every single thing will be used. Now they are asking output will be stable at what time. So these are the initial bits were 0, these are the updated bits, and at what time output will be stable. And this C naught is also becoming 1 at t equals to 0. So this has become 1 at t equals to 0 nanosecond. Okay, so first I will draw this block diagram, and then I will draw this diagram in my paper. Okay, and then I will start solving the problem. So one thing I know, that to this full adder, 1 and 1 is being fed and another 1 is being fed, and all are being fed at t equals to 0 nanosecond. So all are changing from 0 to 1. All are changing from 0 to 1, right, at 0 nanosecond only. And this guy is also changing from 0 to 1 at 0 nanosecond. Sorry, 0 to 1 nanosecond I wrote, 0 nanosecond. Okay, so now 1 XOR 1 will be 0 nanosecond. This will be updated at 0 nanosecond, and this is also updated at 0 nanosecond only, right? This is 1, this guy is 1 here, which was updated at 0 nanosecond, and 1 XOR 1 is 0. But I will not say that 30 nanosecond time is taken. Why is that so? Because 0 did not even change. The 0 was constant. So this was updated at 0 nanosecond only. So now this guy is in action at 0 nanosecond only. This guy is in action at 0 nanosecond because both of the inputs are stable at 0 nanosecond itself. So this guy can give the output 1 after 30 nanosecond. So here output is changing. Output is going from 0 to 1. So after how much time? 30 nanosecond. Okay. Now one more thing I know. What do I know? That if my inputs are 1 1, then my Ci plus 1 will not depend on this Ci. So why do I need to look at this path? I will not even look at this path. Say yes or no. If my inputs are A and B are 1, then my Ci plus 1 doesn't depend on the Ci. So I will not even look at this path. I will go forward with this path only. Say yes or no. So 1 into 1, this was initially 0, this got updated to 1 at 20 nanosecond. So this got updated from 0 to 1 at 20 nanosecond. Now if it is becoming 1, then it doesn't need to wait for this guy. Say yes or no. Because this is a OR gate. This is a OR gate. So if this has become 1, that means this is 20 nanosecond. At 20 nanosecond this has become 1. No matter whenever it is coming, if the input of OR gate is 1, then it will give the output 1 only. So after this condition only, the OR gate has the capability of giving the output. So it will take 20 plus 10, 30 nanosecond time to give this output. So your carry is being generated at 30 nanosecond. And what will be the carry? Carry will be 1. I already know if 1 1 is applied, carry will be 1, or I can solve it as well, that carry will be 1. So at 30 nanosecond I am getting it. And what about this sum? Sum I am getting, that is 1 at 30 nanosecond. That also at 30 nanosecond. Okay. Now very interesting thing will come, like very interesting. All the shortcut method, everything fails here. That's the thing that will come here. So 1 0 1. So now this carry bit got updated from 0 to 1. For this adder we are talking now, 0 to 1 at 30 nanosecond, right? So 0 to 1 it got updated at 30 nanosecond. At 30 nanosecond. Okay. And now these bits are also different there. So everything I will clean up. In the examination you will have to cut it, right? There you cannot clean up. So this got updated from 0 to 1. One guy is from 0 to 0, one guy is from 0 to 1. This from 0 to 0 you can say, and this from 0 to 1. This from 0 to 0, this from 0 to 1. Why I am writing 0 to 0? That means initially it was 0 bit only, all bits was 0. So this transition happened at t equals to 0. So since this transition happened at t equals to 0, so these two guys will start working. Say yes or no? These two guys will start working at t equals to 0 only because they are stable at t equals to 0. So when it was 0 0, it was giving me 0 output, right? This was at 0 nanosecond. But when it is 0 1, it will give me 1 output. And this I will get at 30 nanosecond, right? So this input is becoming 1 at 30 nanosecond. And this input is becoming 1 at 30 nanosecond. What was your previous sum? That was 0. What is the new sum? Previous sum was 0. Why is that so? Why previous sum was 0? Because for t less than 30 nanosecond, this guy was 0 and this guy was also 0. Because it was becoming from 0 to 1 at 30 nanosecond. This guy became 1 at 30 nanosecond. So for t less than 0, this was also 0, this was also 0, sum was 0. Or you can say all the inputs were 0, so sum was 0 only. Now when it is updated 1 1, the sum is going to 0 only. Sum is already there. Are you getting this point? The best point of this particular program. The sum did not even change. So it feels like that delay should be 60 nanosecond, but nah, delay is 0 nanosecond. So here your final sum will be 0. So and that you will get at 0 nanosecond. Now one will have the doubt. What doubt some guy will have? That sir, for t less than 0, inputs were 0 0. So sum was 0. Okay, that I agree for t less than 0. But at t equals to 0 plus, what do I see? Sir, at t equals to 0 plus, I see that my inputs are 1 0 and here carry is 0. At t equals to 0, this was my carry is 0. So my sum should be 1. So sir, there is intermediate state. No, this would have been correct that there is intermediate state if this was a black box. But here there are two circuitry, no? So when these two guys changed, so it took 30 nanosecond time to become 1 here, and this guy also took 30 nanosecond time to become 1 here. So my sum did not even change. Let's just say if this delay was 20 nanosecond, if this delay was 20 nanosecond somehow, then in between this guy would have been 1 at 20 nanosecond and this guy would have been 0 at 20 nanosecond. So it would have changed its output. Then I could say that steady state, like in between there was another state, but there was no state in between. Are you getting this point or not? Both guys changed together. 0 0 was there, 0 0 was there for t less than 30 nanosecond, but both guys became 1 at 30 nanosecond. If this was 20 nanosecond, then there would be a scene that if this changed at 20 nanosecond and this guy is 0, so some would change its state, then at 30 nanosecond it will come back. Then you would say that 30 plus 30 at 60 nanosecond I have the steady state, but it is always remaining at 0. Say yes or no? So this intermediate state will not even come, because we are using two half adders there. Now this much depth will not come in the examination, okay? This much depth will not come. I just took blindly this particular example and this became very interesting. Okay, I blindly took it. And if the exam paper setter is also blindly setting, then it may happen that some good example may come up. So this guy became stable at t equals to 0 nanosecond. Okay. Now, so this guy is stable at 13 nanosecond, which is 1. And this guy is also stable at 13 nanosecond, which is 1. So now previously it was 0, but now it is changing its output. If it is changing its output, then it will wait for both of the guys, because it is an AND gate. So it will wait both of the guys. So from 0 to 1 it is going. At 30 nanosecond both are stable. So 30 plus 20, it will take 15 nanosecond of time. So this will become stable at 15 nanosecond. This became from 0 to 0 only. So this is 0 to 0. This goes from 0 to 0. So this was stable at 0 nanosecond only. But this became stable at 15 nanosecond. So this guy will have to wait for this guy. Why so? Because this is 0. And the output of OR gate is not defined with 0. For output of OR gate, you need 1. Or both 0 or both 1. But at least 1 you need if you want direct output. But direct output you are not getting. So this guy will have to wait for this guy. So this guy was waiting. After 15 nanosecond he came. So 50 plus 10. After 10 nanosecond you are getting this output. So 10 nanosecond this will be the output. And what will be the carry? You can do it, or you can directly know that it will be 1 only. Here also you can see 1 plus 0, it will be 1 only. So at 60 nanosecond it became 1. Say yes or no? Right? Now we will talk to the third guy. Okay, in the examination also, in gate examination also these kind of questions came, but that was pretty easy. That was pretty easy. Okay, and we will solve that particular problem, but there was not this much of concept involved. So you don't need to worry that sir, how we will solve in the examination. In the examination, how you will solve? When these kind of questions are coming, you will wait there that okay, something good is coming there. So you will get to know that this is a very good question. So I will wait there. I will not go blindly that let's solve this problem. So I will solve all other problems, then I will come back here. Okay. So these kind of problems just are there just to build your concept. Who knows what can be used anywhere? Let's just say they give only this circuit and they give the same input and they ask you at what time the output will be stable. Only this circuit. And the same thing, they can say that A and B are changing at t equals to 30 nanosecond, sorry, at t equals to 0, and Ci is changing at t equals to 30 nanosecond. What will be the time when output is stable? People will say 30 plus 30, 60 nanosecond. Output will be stable at 60 nanosecond. No, that is wrong. Output will be stable at 0 nanosecond only. Why is that so? Because output never changed. So these kind of concept can come up no in a short question. So that's why I deal a very big problem. I take all the cases so that you in the examination there is no need to worry about, right? So we are talking about the third one now. So one is changing to 0, another one is changing to. Now see this thing. Now do you think I need to solve this? No, carry is different, no. So yeah, I need to solve it. Otherwise, like if this was 30 nanosecond only, no. So I would not need to solve it. It was 60 or 50. 60 or 50. Here 30 plus 20, yeah, okay, 60 it was, okay. If it was 30 only, no, so I do not need to solve it because it would be the same, but here I need to solve it now. So this is 60 nanosecond. So this is changing from 0 to 1 at what time? 60 nanosecond. and one of the guys 0 to 1, same thing is there, 0 to 1, 0 to 1, no, 0 to 0, one guy is from 0 to 0 and one guy is from 0 to 1. Any guy could be anything, right? Because it doesn't matter. Now they will start their operation at t equals to 0 nanosecond only. So they would have started 1 XOR 0, this would become 1. This would become 1 at 30 nanosecond, right? So for t less than 30 nanosecond, what would be the scene? For t less than 30 nanosecond, this was 0, this was 0, sum was 0. At t equals to 30 nanosecond, what is the scene? T equals to 30 nanosecond. This has become 1. This is 0 only because it will take 60 nanosecond of time. This has already become 1. So 1 XOR with 0. This is 1 at 30 nanosecond. Say yes or no? This is 1 and this will take 60 nanosecond of time to become 1. So it is already 0. 1 XOR 0, 1 at 30 nanosecond. Say yes or no? At 60 nanosecond, this guy became 1 and this is already 1 only. So 1 XOR 1, again 0. So at 60, sorry, this was at 30 nanosecond, no? This was 1 at 30 nanosecond. So 30 and 30 time it will take, no? So this will be 60 nanosecond, really sorry. This will become 1 at 60 nanosecond. Why so? Because at 30 nanosecond, this was 1 and this was 0. So now it can start the operation, right? 1 XOR 0 will be 1, but to do the operation, it will take 30 nanosecond of time. So this will become 1 at 60 nanosecond. Now at 60 nanosecond, what is the scene? That this guy became 1 and this guy is already 1. So 1 XOR 1, it will again become 0. So this operation will start at 60 nanosecond. 1 XOR 1 will start at 60 nanosecond and you will get 0 after 60 plus 30, 90 nanosecond. So my sum is 0 only, but at 90 nanosecond. Say yes or no? What about carry? Carry will be 1, that I can directly see, right? Because 0, 1, 1, carry will be 1. But and why did I write 90 here? You go to know, because there is an intermediate state. In the previous case, there was no intermediate state. Now what is the scene? What we need to calculate? We need to see the path of carry. So carry. So for t less than 30 nanosecond, here there was 0, this was also 0, so this was 0 only, right? And then at 30 nanosecond, this was 1, but this was 0, this was 0 only. At 60 nanosecond, this is becoming 1 at 60 nanosecond. And this is also becoming 1 at 30 nanosecond. So at 60 nanosecond, both are 1. So now output will change. So after 60 nanosecond, output started getting changed. So how much time it will more take? 20 more. So it will be stable at 80 nanosecond. What about this? This will become, this was already 0 and already it is 0 only. So this will be stable at 0 nanosecond only. So after 80 nanosecond, this guy came here. That is 1. So 80 plus, so it will have to wait for this guy. So 80 plus 10, that is 1 you will get after 80 plus 10, 90 nanosecond. Right? So this carry you are getting after 90 nanosecond. Okay. Let's see the last condition, 1, 1. So in all other kind of problems, I gave you like some tips or tricks that there you can solve these kind of problems by that. But here I would want you to analyze it completely if these kind of questions are coming in the examination. I would not want you to do anything like make any random block diagram. In all the 3 cases, I told you how to do that in minimum time, right? But here, if these kind of questions are coming, I would want you to analyze there. Take your time. At least take 10 minutes. No one will like no need to worry about that. You need to draw the diagram, so you need to do everything there, right? So now our C was initially 0, it is changing to 1. C is changing to 1 at 90 nanosecond. Changing to 1 at 90 nanosecond. Okay. And I will write down these inputs. I'm just wasting your time. I will write down these inputs. So this is the scene of our circuit. 0 to 1, 0 to 1, 0 to 1, 0 to 1 at 0 nanosecond, 0 to 1 at 90 nanosecond. Okay. So these guys will start working at t equals to 0. One thing I know, carry will not care about this path now, right? Because carry says that I do not depend on the previous carry now. So carry will forward this path. So it was initially 0, it will become 1 now. After how much time? 20 nanosecond. 20 nanosecond. So it will become 1 at 20 nanosecond. And it will be in action to give the output because this has become 1. So no matter after how much delay it is coming, but it will not care about this. So 20 plus 10, 30 nanosecond. So this will be 1 at 30 nanosecond. So this about carry, I know that this will be 1 at 30 nanosecond only, because this guy started working at t equals to 0 only. And if this guy started working at t equals to 0, this got changed, this got changed. This is 30 nanosecond, that's it. Now what is the scene about the sum? So that we need to check. So initially it was 0 here. Now again it will become 0 only. So it will be always stable. So this is at 0 only always. And for t less than 0, t less than 90 nanoseconds, this was always 0. So sum was 0 only. But at 90 nanoseconds, this is becoming 1. At 90 nanoseconds, this is becoming 1. So 90 plus 30, 120 nanosecond. 90. So after 90 nanosecond, it will try to change. So 90 plus 30, at 120 nanosecond, it will change. So at 120 nanosecond, it will change. So this final carry you are getting at 30 nanosecond, this is you are getting, what is the maximum time? This is 90, this is 0 only, this is 30 only. So delay is 120 nanosecond. This question contains everything that can be there. Okay. This problem and this problem that is asked in GATE examination. These two you will solve, and every single case has been included. Whatever that can be a possibility, that has been included here. So look, these kind of information were given already. The circuit was also made. Okay. And input got changed 1 1 0 0 0 1 0 0, and this has become z not equals to 1. This has become 1, and these are the inputs. So initial condition were all 0 0 0 0. Everything was 0 0 0 0. Now if I go to the first one, I know that carry will not change, right? So now this guy can start working already. But like, let's solve it by the step only. Okay. Here I was just doing some smartness. What I was about to tell is that if 0 0 is there, this guy also did not change. So this will also give the sum 0. This will also give the sum 0. That means none of these changed. Only the sum here will change. So you just need to analyze this sum. Okay, just need to analyze this sum. If these guys are not even changing at 0 nanosecond, these are stable. No, this is also stable at 0 nanosecond itself. These guys did not even change. So just analyze this sum and then come here directly. That here you are having t equals 0 at 0 nanosecond. So these two blocks you do not even need to analyze. Only this block, for sum only you need to analyze. So for sum only I will analyze. So only C naught got changed. Everything is same, only C naught got changed. So here I will do it. So it is 0 only. It is also 0 only. This is also 0. This is also 0. So all are A XOR B. This is also 0. This is also 0 at 0 nanosecond. All these are at 0 nanosecond. But this guy got 1. This guy got 1 at 0 nanosecond. This guy got 1 at 0 nanosecond. This was already at 0. So before that it was 0. So your initial sum was 0. But now it will change to 1. So how much time it will take? 20 nanosecond. So it will take 20 nanosecond. Right? 20 is the delay, no? 20. Yeah. 20 is the delay. So this sum you will be getting at 20 nanosecond. These you are getting at 0 only because nothing got changed here. 0 0 0 was there, 0 0 is there. So everything is stable. So directly we are coming to the third stage. So this kind of easy question they asked. Okay. Here also I know that for carry I don't need to analyze much. Why so? Because I know carry will not see anything. Carry will go to 1. By which path? By the lower path. Because these are becoming 1 now. Na? These bits are becoming 1. So this is becoming 1 at t equals to 0. This is becoming 1 at t equals to 0. And this is also becoming 0 at, it will be at 0 only. So if I make the diagram for the third block, so how will I make it? Like it would be very easy to make in the examination. No? Like it is 0 to 0. 0 to 0 at 0 nanosecond. This is 0 to 1. All are becoming 1 at 0 nanosecond. So they will start their operation at 0 nanosecond itself. So if I talk about the carry, so carry will directly go here. That it will say that 1 1 is there, I will become 1 here. From 0 to 1 I will become at 15 nanosecond. And I do not care about this. I don't care about you. At 15 nanosecond I am there, so I have the capability of giving the output. So 15 plus 10 at 25 nanosecond I will give my carry 1 at 25 nanosecond. That's it. So directly this would become 0 to 1, 0 to 1, at 25 nanosecond. Okay, so last stage we will analyze, and for this we need to analyze the sum. So what will be the sum for this? 1 plus 1, it will be 0 only. So sum is also not changing na here. You can see, look, so this was there at 0 nanosecond, so this was stable at 0 nanosecond, right? And this will become 0 to 0 again. 0 0 was there, 1 1, 0 to 0 again 20 nanosecond, but it will not take 20 nanosecond, it will always be stable. So this guy was in action to give the output at 0 nanosecond itself, and what it will give? Initially it was 0, again it will give 0 only. There is no intermediate state. This guy was at 0 nanosecond, this guy was also at 0 nanosecond, this guy also at 0 nanosecond, so everything was 0. This guy got changed to 0 only. Okay, so nothing was, no change here, no change. These guys changed, so we expected that there would be a change, but the change is same. So this was the steady state, this is the steady state. Now 0 0 will give you 0 only, so this was already a steady state, right? So sum you are receiving after 0 nanosecond, this you are receiving at 0 nanosecond itself, already it is there. Now the final stage, what is the final stage? Now carry is becoming from 0 to 1, carry is becoming from 0 to 1, carry is becoming from 0 to 1, and inputs, one of the guy is 0 to 1 and one of the guy is 0 to 0, 0 to 1, 0 to 0, 0 to 1, 0 to 0. Okay, at 0 nanosecond, and this is becoming 0 to 1 at what time? This is becoming 0 to 1 at 25 nanosecond. So this is 25 nanosecond. Okay, so initially it was 0, now it will become 1 at 20 nanosecond, at 20 nanosecond. Now see the very interesting thing here. So for t equals to 0, this all was 0, sum was 0. Now at t equals to 20 nanosecond, this guy is 1, this guy is 0. At t equals to 20 nanosecond, this guy is 1 and this guy is 0. So now this guy will say that I will generate 1, but it will take 20 nanosecond more time. That means it will be, you will get 1 here after 40 nanosecond, right? Say yes or no. This guy was 0, this guy was 0 here. Okay, so already it was 0, but 1 XOR 0 you are getting now. So 1 XOR 0 will be 1 after 20 nanosecond. So at 20 nanosecond you are having 1 here, and here you are having 1 at 25 nanosecond. That means it was 0 before that, it was 0 before that, right? So here you are having at 20 nanosecond and it was 0 at 20 nanosecond. So 1 XOR 0, this will change. So at 40 nanosecond you will receive this. But what will happen is that at 25 nanosecond this guy will become 1, this guy will become 1 at 25 nanosecond, and this guy will be 1 at 20 nanosecond. So after 25 nanosecond, this guy will say that after 25 nanosecond, this XOR gate will say that 1 XOR 1 I will give 0. So after 25 nanosecond, it started the process of giving 0. Look, the thing is 1 was going, but behind that 0 also started coming. 1 was going, it said that it will take me 20 nanosecond more. So 20 plus 20 I will reach there at 40 nanosecond. And this guy is saying that I will be 0 after 20 like 25 nanosecond I started at 25 nanosecond and I will be 0 at 20 nanosecond more, after 20 nanosecond more. So I will be there at 45 nanosecond. So this will be there at 45 nanosecond. Are you getting this point? In between there is a state, so state is changing. So you will say that the output is going from 0 to 0, but it will take time. What is that? 45 nanosecond. Are you getting this point or not? Like I have seen this solution a lot at a lot of places, but nobody analyzed this condition. Luckily they got the correct answer. They are saying that this is being stable at 25, this is being stable at 20, so this will pick the maximum 25 plus 20, 45. But there is an intermediate state. If it is going from 0 to 0, then why are you saying that it is changing? You can say no, it is already at steady state. Why you are not saying that it is at steady state? It is changing there. Why it is changing? In between at 20 nanosecond the things are different, 1 and 0. So at 40, 1 and 0 is there, so at 40 nanosecond it will become 1 and then again it will become 0. Okay, so in the last only there was a twist. Okay, let's talk about this one. this carry. So our carry will care about everyone now because it is 1 0. So if it is 1 0, this will go from 0 to 0 only at 0 nanosecond itself. Now let's talk here. So this will become 0 to 1 at 20 nanosecond, and this will become 0 to 1 at 25 nanosecond, right? 20 and 25. Now for t equals to 20 nanosecond, this is 1, this is 0. So output is 0 only. When output will change? When both are 1. When both are 1, then only output will change. And when both are 1? At 25 nanosecond. So at 25 nanosecond, this guy will start working and it will say that I will change my output to 1. At what time? 40 nanosecond. So this guy is there at 40 nanosecond. So 40 plus 10, this guy will become 1 at 50 nanosecond. So this carry will be generated, that is go from 0 to 1 at 50 nanosecond. So that's the actual solution. You can send it to anyone, anywhere. That's the actual solution with all the analysis of intermediate state of this particular problem. And this is also a very good problem where things got changed, some was getting changed. No, but it was not taking any time. Here some was getting changed, still it is taking 19 nanosecond time. Okay, so this is the complete analysis. I hope you must have understood all kind of delay problems. Apart from this, nothing can be asked. They are not going to ask anything apart from this. So this was one of the topic that I wanted to deal in a very good manner. Always I wanted to deal it. So yeah, that's it from my side. I hope you enjoyed it. If you enjoyed it, just like I would need your comment here. At least I would need one of your comment. So that would make me feel good. Like if someone is writing something good about me, it makes me feel very good. If I am working 12 hours a day, I will work 14 hours a day. If you write something good. So that's the thing I would be expecting from you. Okay. So yeah, thank you very much. Happy learning. Hi everyone. So now we will see the limitations of binary parallel adder. So this was our binary parallel adder. A naught, B naught was there. Everything was available at t equals to 0. These bits were available at t equals to 0. And C naught was also available at t equals to 0. Right? Now, this would come after some time. This would take some delay. This would also introduce some delay. This will also come after some time. Now, in the worst case, this circuit will start working with the delay. Like let's just say if there is delay of 10 nanoseconds, so this circuit will start working at 10 nanoseconds. So now this will come after more delay. Then this will come after more delay. Then this will come after more delay. This will come after more delay. This will come after more delay. So here every stage have to wait for the previous carry. Each stage waits for the previous carry. So there is a lot of delay, na? So that's the problem with binary parallel adder. And this binary parallel adder is known as ripple carry adder as well, because each carry ripples to the next stage. Each carry output ripples to the next stage or propagates to the next stage. So that's why it is known as ripple carry adder as well. So that's the other name. We should remember this, okay? Because in the problem sometimes it can be written that a ripple carry adder is used. So you will consider that as a binary parallel adder only. So what is the issue? Issue is with the carry. So carry is being forwarded. So each stage will work. In the worst case, each stage will work after the carry has arrived, after the previous carry has arrived. So in that, if the number of bits increases, here only there were 4 bits. If let's just say if I need to do the addition of 10 bits, then delay will be more, right? So that's the issue with our binary parallel adder, and that we need to eradicate. So this is what I have written. So no need to worry about that, sir. What is what all these things are written? So you know everything. Next stage carry. This is what next stage carry. So what is that? That is AIBI plus A XOR B CI. You know that, and this is the previous stage carry, right? So basically, if this is our scene, this will be our AI. This is our BI. This is our CI. We will generate SI and CI plus 1. So this is what we do. And this term is known as carry generating term, and this is known as carry propagating term. This we have already seen. Carry propagates if 1 0 are there, and carry is always generated if 1 1 is there, right? So this we have already seen. So GI is the carry generating term and PI is the carry propagating term. And how can you write sum? Sum can be written like this, right? AI XOR BI XOR CI, and AI XOR BI is PI only. So this is how sum can be written, right? So this is current stage sum. So sum and carry both are depending on Ci, and Ci will come after some time. So that's the issue. So in worst case, each carry depends on the previous carry. If number of bits increases, then the delay will increase. So the main issue is with carry. Your sum and carry both are function of Ci. Both, this is different function and this is different function. Both are the function of Ci. So if I write, let's just say if I write S2 or C2, where I can write, let's just say if I am writing C3, so C3 will be function of C2 and S2 will be function of C2. So this guy will come after some time. So C3 and S2 will be affected by this guy. So what is our target? Which carry is available at t equals to 0? C0. C0 is available at t equals to 0. So my target is I will make these functions independent of C2 and C2. I will make all the functions depending on only C0, because what we have at t equals to 0? At t equals to 0 we have A0, B0, A1, B1, A2, B2, all these bits are there and C0 are there. So what if we make these function carry and sum function depending on only A0, B0, A1, B1, A2, B2 and C0? What do you say? Isn't that a good idea? That we make all these C2 and S2 depending on all these values which are available at t equals to 0 only, right? So what we have at t equals to 0? So what if I am able to generate all the carry at a time? So my target is to generate all the carry at a time. I don't want to wait for this carry. So I want to generate all the carry at a time. So how can I generate Pi? Pi is simply Ai XOR Bi. So let's just say my XOR gate is having TD delay. So that wouldn't be a issue. After TD delay I can generate Pi, and after TD delay only I can generate Gi. The issue is with Ci. So Ai and Bi will be available at t equals to 0 only, and after TD delay my Pi and Gi will be available, and C0 is also available at t equals to 0. The problem is with Ci. So what I want to do, that my Ci should be a function of A0 B0, A1 B1. It can go in this manner, A1 B1, A2 B2, and in that manner it can keep on going, and also it should be a function of C0. It can be a function of C0 as well, because this is also available at t equals to 0. So all these are available at t equals to 0. And if somehow I need this Pi term, that means if I need Ai XOR Bi, then it will be available after TD delay. That is not much of delay. And if I need to make Gi, that will be available after TD delay. So your function is depending on Pi, that can be available after TD delay. It is depending on Gi as well, which we can get after TD delay as well. The thing is with Ci. So now my only target I am left with is that I need to make Ci in this function. So this is what I have written. So now we will start. So this is our Si and this is our Ci. So if I put I equals to 0 for the first stage, so for the first stage this will be my C0, this will be my C1. So here my S0 is function of P0 and C0, right? And this is available at t equals to 0, and this you can get after TD. That is not much of delay, so that's not a problem for us. And this is the function of P0, G0 and C0. So this you can get after TD delay. This also you can get after TD delay, and this is available at t equals to 0 nanoseconds. So not an issue for us. Let's go to this one, P1, S1. So S1 is the function of P1, P1 and C1, So P1 can also be made at t equals to 0 only, because A1 is available and B1 is available. The thing is, A1 is already there, B1 is already there. So I can make P1 very easily at t equals to 0 only. So this I can get at t equals to 0 only, right? But this is an issue, because C1 will take some time. C1 will go through then from the full adder C1 will be out. So C1 will take some time. This is available after TD delay. I shouldn't say it is available at t equals to 0. Sorry. This will be available after TD delay. This delay is TD, no? So this will be available after TD delay. Okay. Now what do I do? Issue is with C1. So I replace C1 with G0 and P0 C0, because C1 is G0 plus P0 C0. So now this function is becoming, S1 is becoming new function I will write. The functions are different, no? So I have to change the function. I hope you are getting the point. All these functions are different. That's why I need to give different name. So now this is a function of P1, P naught, C naught and G naught. Now P1 will be available after Td time, P naught will be available after Td time, G naught will be available after Td time and C naught is available at 0 nanosecond. So now S1 can be available after Td time. Say yes or no. I wouldn't say after Td time because this is a function as well. We have to implement this function. But whatever that is required in S1, all these are available after Td time. Now we will implement that function. Some gates will come, some delay will come, but the delay will be less. Are you getting this point? Now eventually this C2 is also becoming a function of what? Because what is C2? G1 plus P1 C1. C1 was the issue, so I replaced C1 and I got this. So this C2 is becoming a function of G1 G naught, P1 P naught and C naught. All these are available after Td time and this guy is available at t equals to 0 nanosecond. So that's the thing, that we have implemented all these terms in terms of our known values which are available after a slight delay, right? And similarly we have done the same thing with C3 as well, right? Because C3 is function of G2, C3 is G2 plus P2 C2 and C2 is a function of P naught C naught. So now eventually C3 will become function of G2 P2, G1 P1, G naught P naught and C naught, right? So in this way we will make a circuit that is known as look ahead carry adder. In short form I will write it look ahead carry adder. Okay, so that we need to design. So in that thing your sum will depend on the propagating term and the carry term, right? And carry term will depend on these functions only which are available very easily. So let's see how we will implement. So this is how we will implement. You do not need to mug up the circuit but have a picture in your mind. So what we are implementing first, let's start from here. We are implementing P1 G1, right? What is our C2? What is our C2? If you see here, our C2 is G1 plus P1 G naught, P1 P2 C naught, P1 G naught plus P1 P2 C naught. This is our C2. C2 is P1 P naught C naught, actually not P1 P2 C naught, P1 P naught C naught. So first I have implemented G1, then this is my P1. So P1 into G naught is there, P1 into P naught into C naught is there, and this G2, why I have written G2 here, this would be G1, this would be G1, this would be G2, right? So this G1 is there. Now there will be OR gate. Now this will be fed and we get C2. And how do I generate S2? So S2 will be generated P2 XOR C2. Okay, right? So in that manner we can design everything. Now what is the important point that you need to remember here? Look, if you are generating C2, then G1 will come alone, right? And all these will be function, but G1 will come alone. How will you remember it? Let's just say I need to generate C2. So how will I write? What will be my C2? C2 will be, let's write in the full term, A1 B1 plus A XOR B, A1 XOR B1 into C1. Can you remember this, right? So what you can write, it would be carry generating term P1 and C1. Now this C1 will be replaced, some function will be there. Now it will be made some function that we can implement using AND gate. Those functions we can implement it using AND gate, and eventually they will be ORed, they will be added, but they will be added with G1. So G1 will come independently. If you are generating C3, then G2 will come independently. Independently means it will come alone. When we solve delay based problem, it will be used there. That's why I am telling it. When you are generating C1, then G0 will come alone. So you don't need to mug it up. You can just keep in mind, okay, what is your what will be my C2? My C2 will be G1 plus P1 C1. So G1 will come alone. That's it. Okay. Another thing is what? If you are generating C2, then G1 is as it is plus P1 will also be as it is. Now C1 will be replaced. So whatever that you write here, in all these terms P1 will be added. Whatever that you write here in C1, you will write, let's just say, some x plus y. So eventually you are going to get P1x plus P1y. So certainly P1 will be there in all the numbers. Here what will be there? C3 will be function of G2 and P2 and C2 as well. So C2 will be replaced, but in all the AND gate, somewhere P2 will be there. I don't know which all these terms will be. I don't care about those, but I know that certainly there will be P2 for sure. Say yes or no. So can you remember these two things? What is these two things? For C3, G2 will come alone, and if you are generating C3, that means certainly P2 will be there in all the AND gates. That's it. Nothing else you need to remember. This is my only ask. Well and good. Okay. So this is how our circuit will look like. You don't need to mug up the circuit. You just know the concepts, right? How it is coming. In the examination, there is 0.01% chance that they will ask an equation from here, from delay based problem. If they are asking delay based problem, then they will ask from half adder, full adder and binary parallel adder. Till today, never they asked any delay based problem from here. But still we will cover it, because if they ask, we will be in a very good position to answer that. Questions can be framed, but this is not that important. Okay. So just we know the concept that here, this is how we are implementing. So now the question will come, after how much time C1 you will get in the worst case. In the worst case, after how much time C1 you will get, C2 you will get, and C3 you will get. Tell me. So if I am saying that this is having TD delay, this is having TD delay, all are having TD delay. So this will take TD delay of time. If all are having TD delay, so they are all at level, all at the same level, right? All at the same level. So this will also take TD delay. Here also it will take TD delay only. This will also take TD delay. So at 3 TD delay, C1, C2 and C3 are available, and all are available at together. All are available together. So after 3 TD delay, all are available. What about P2? P2 is available after, this is available after TD delay only. So this guy is available after TD delay only, and this guy is available after 3 TD delay, and this is having TD delay. So your sum will be available after 4 TD delay, and it is same for all 4 TD. And if more bits were there, it would be same for all, because this circuit is symmetric, right? This stage, this stage, this stage, just the some stages are increasing, but the completely circuit is symmetric. So TD here, TD here, TD here, 3 TD, your C2 is available. After more TD, your S2 is available. But take care of one thing. What is your S naught? Really sorry, why I have written S2 here. This will be your S naught. What is your S naught? S naught is simply C naught, P naught. What is your S naught? S naught is P naught XOR C naught. Say yes or no? Right? C naught is available at t equals to 0 only, and P naught is available after TD time. P naught is available after TD time. This is available after TD time, and C naught is available at t equals to 0 nanosecond. So this guy is stable at 0 nanosecond only, and this guy is stable after TD time. That means it will take TD time more to generate S naught. So S naught you will get at 2 TD only. Are you getting this point or not? So only in S naught you will get very quickly. S1 also you will get after 4 TD only, because TD here, TD here, TD here and TD here. So S1 also you are getting after TD, S2 also, S3 also, all are you are getting after 4 TD only. But what about S naught? So P naught you generated at TD, this is at 0, so TD plus TD 2 TD. So S naught you are generating at 2 TD, rest all you are generating at 4 TD, carry you are generating at 3 TD, and after TD what you are getting? P1 G1, P naught G naught, P2 G2. So let's start from the beginning. At 0 nanosecond, what you are having? A2, B2, A1, B1, A naught, B naught and C naught at 0 nanosecond. After TD what you are having? P2 G2, P1 G1, P naught G naught. After 2 TD what you are having? After 2 TD you are having S naught. You are having these values as well, but they don't have any specific name. So I am not telling that after 2 TD we are having this, but you are certainly having S naught. After 3 TD what you are having? C1, C2, C3 C4 and till it will keep on going. And after 4 TD, what you are having? Your final sum. S1, S2, S3, S4, and it will keep on going. So these points I have written here. And yeah, one more thing, like this is simply your half adder only, no? This particular circuitry. This particular circuitry is half adder only. So this complete design can be replaced with half adder. Okay, the same design can be replaced with half adder. Nothing, just the same. This I replaced with half adder, nothing else. All things are pretty similar. Nothing new is there. Okay, and this is known as look ahead carry adder, and this particular structure is known as two level AND OR gate. AND OR gate, because there are two levels only, no? One level 1, this is your level 1, and level 2. So two level AND OR gate. So your look ahead carry generator is made of two level AND OR gate. Okay. So now those points I have written. A naught, B naught, A1 all are available at t equals to 0. P naught, G naught, P1, G1, P2, G2 will be generated at TD delay. They will come from the half adder, or you can say XOR and AND gate. So they will be available at TD delay. And S naught will be generated at 2 TD delay. We solved it, right? Because C naught is already there. P naught will come after TD. So TD plus TD, 2 TD. And C1, C3, Cn, they will generated at 3 TD. TD plus TD plus TD, 3 TD. And S naught 3 TD plus again plus TD. So S1, S2, S3 3 TD plus TD. That means at 4 TD all those will be available. Now in look ahead carry generator, this is what I am talking about. Okay, this is your look ahead carry generator. The whole circuit is known as look ahead carry adder, but this particular part is known as look ahead carry generator. So in look ahead carry generator I am talking about, not in the whole circuit. So in look ahead carry generator, so if we are performing the addition of two n-bit number using look ahead carry adder. So we are performing the addition using look ahead carry adder. So in look ahead carry generator, how many OR gates will be there? Tell me. Look, we are performing the addition using look ahead carry adder. So if you are using look ahead carry adder, then you need to use look ahead carry generator as well. Now in that look ahead carry generator, how many OR gates will be there? This is what we are asking. So this is how questions are asked. So in that look ahead carry generator, how many OR gates will be there? Tell me. For 3-bit, 1, 2, 3 OR gates will be there. For 4-bit, another OR gate will come. So just n OR gate will be there, right? N OR gates. So this is the only point which is important, which can come in your examination. And how many AND gates will be there? So here 1 was used, right? For 1 bit, 1 gate was used. For 2 bit, 1 plus 2 gate were used. For 3 bit, 1 plus 3 gates will be used. What do I mean to say? Here 1 is used, here 2 are used, and here 3 are used. So in 3, how much were used? In 3, 1 plus 2 plus 3 were used. So in n, how much will be used? 1 plus 2 plus 3 plus n. So how many they will be? N into n plus 1 by 2 AND gates. Right? 1 plus 2 plus 3. So 3 and then 4, 5, 6. So how many AND gates you require? N into n plus 1 by 2. So if the structure is clear in my mind, then I will not worry about that. OR gate, so everything is OR only. So n OR gates will be there. Number of OR gates will be n. And if they are asking about the number of AND gates, then I know 1 plus 2 plus 3. So number of AND gates will be n into n plus 1 by 2, right? And here propagation delay is independent of number of bits. So no matter how many bits are there, propagation delay is independent of that. Well and good. Now let's see some delay based problem. Easy problems only, not tough at all. So 2 5 bits number are added using look ahead carry adder. XOR AND and OR gates are available. These are the delay. Find the maximum delay in receiving the stable output. So no input are given, input are not given. So we need to calculate the worst possible delay. So without even drawing the circuit, can you think about it? Or here I will draw a rough circuit, but in the examination you can think about it without even drawing the circuit, right? But here I am drawing a rough circuit. Let's make it rough only then. So what will be happening? First there will be an XOR gate, and in the same stage there will be AND gate as well. Then it will be going towards a look ahead carry adder. There first some bits will be going from the AND gate, and this guy some carry generating term would be coming, and that will be going to your this gate, what do we call it, OR gate, and then you will generate a carry, and P term will be added to your XOR gate again. So this is what we get. Here we get some P term, here we get some G term, here some G term will be there, here some P term will be there. What else will be there, I don't know. This is your OR gate. Here I will get the C term, here P term will be there, and this is what I will get, some term. So this is what you need to remember. Only this thing you need to remember in your look ahead carry adder. You will never have to make the whole diagram. Only this is what I am asking you. Okay, you will be able to solve the problem now. 15 XOR gate will have 15, and this have AND gate have 10. Now this guy is function of G as well and P as well, right? So this guy will start working after P arrives. So P arriving here at 15 nanosecond, here G is arriving at 10 nanosecond, but P is arriving here at 15 nanosecond. Now 15 and this will take 10 more delay. So this will come at 25 nanosecond, right? This is having 10 delay as well. So P is arriving here at 15 nanosecond, 15 plus 10, 25. 25 plus this OR gate is 5. So 25 plus 5, here you will get at 30 nanosecond. And after that another XOR gate is there. So 15, 30 plus 5, so 15 you will get at 45 nanosecond. This was already stable, this P was stable at 15 nanosecond only, right? So is that clear to you, right? So how do we say this was the maximum delay? So here it went at 15. So 15 plus 10, this would be 25. 25 plus 5, 30. 30 plus 15, 45 nanos. This is the time when you are getting the stable output. Although carry was generated at 30 nanosecond, but we are finding the stable output. Stable output means all the sum should be generated. So when the sum are being generated at 45 nanosecond. So that's the final answer. Okay, let's wait for a second and then we will see the next question. I have some work to do. So we will see the next question after 1 minute. Yeah, so let's see this question. In this question, delays are mentioned. Okay, XOR delays are mentioned. Same problem is there, but inputs are also there. So what did I tell you? What we need to remember? Only this thing we need to remember, that first we will generate a propagating term, right? And we will generate a generating term. Then there will be carry generator, look ahead carry generator. In that look ahead carry generator, what will be there? This was your propagating term, this was your generating term. What would be there in this look ahead carry generator? So there will be an AND gate, could be any multiple number of gates would be there, anything could be there, and one generating term would be coming from here as well. Then there will be your OR gate, right? There will be a OR gate, and then this P would be coming here as well. This would be the carry, and they would be going to your sum. If you don't remember this, in the examination it might happen that you forget, but you can write down any expression. Like look what I will write, that my C would be, C2 would be equals to P2 plus, sorry, G2 plus P2 C1. So I know I need AND gate, I need G2, and this will be going to OR gate. So this is how I will generate it. And then how I generate P2 and C2? So P2 is my XOR gate and G2 is my AND gate. So this is how I can generate G. And what is the final one? Final, my sum will be P2 XOR C2. So I have C here and P is already generated. So this is how I get my sum. So in the examination, if you forget, just by using these formulas, you will know how will your circuit look like. So this is what you need to remember. This is what I told you, right? Now we will see when the final sum is generated. So bits are 1 1 1 1. So I am taking 1 1 1 here. All are 1 1 1 1. So taking 1 1 1 here. Okay. So this became this was initially 0. All bits were set to 0. So this became from 0 to 0 only. This became from 0 to 0. So this was already stable. 0 in a second. 1 XOR 1 is 0 only. 1 dot 1 1 and 1 would be 1. So this became 0 to 1. After how much delay? 10 nanosecond delay. So this guy became 0 to 1 at 10 nanosecond. So this input became 0 to 1 at 10 nanosecond. And this, what this will be? This will be our G. Here input will be P and here input will be G. So this will be our G. So wait a second, sorry, this input was P only, no? So P became 0 to 0 at 0 nanosecond only. Now if one of the input is 0, that means output is certainly 0. Say yes or no? If one of the input is 0, then certainly output is 0. So it will go from 0 to 0 at 0 nanosecond only. Okay. And what about this G? G become 0 to 1 at 10 nanosecond. Since this is an OR gate, so this guy will have to wait for this guy. So this guy is coming at 10 nanosecond. Now what is the delay of OR gate? That is 5 nanosecond. So at 15 nanosecond, this carry will go from 0 to 1 at what? 15 nanosecond. At 15 nanosecond, this carry will go from 0 to 1, and this was there at 0 nanosecond only. So initially sum was 0. In between, before 15 nanosecond, P was 0 and C was also 0. Before 15 nanosecond, because this is always 0. P is always 0, right? And C was 0 before 15 nanosecond. So 0 XOR 0, sum was already 0. Now at 15 nanosecond, this guy became 1. So what now XOR gate will say? XOR gate will say that now I will change my output, because 1 XOR 0 is 1. So now I will change my output. When do I start working? At 15 nanosecond. When do I start working? So sum will be generated. I start working at 15 nanosecond plus the delay of XOR gate. I will take 15 nanosecond more. So at 30 nanosecond, this will be stable. Do I need to check for other ones as well? No, because all bits are same. They will all be generated at a time. Although this bit S0, this bit might be generated before 30 nanosecond, but we need to take the maximum time. In S0, what are the inputs? In S0, these are the inputs, right? P0 and C0. This is your S0. Now, this is available at t equals to 0. This is also available at t equals to 0. P0 is available at t equals to 0. Why so? Because P0 is not even changing. So, this is also available at 0 nanosecond. This is also available at 0 nanosecond. And what is the delay of this? Delay of this is 15 nanosecond. So, S0 you will get, S0 will be 0 to 0 only. You see, S0 initially it was 0 and after that also it is 0, because P0 is 0 and S0 is 0. So, it is always 0 to 0. So, S0 is available at 0 nanosecond itself. So, S0 did not change. S0 was available at 0 nanosecond only. But this S change, that is available at 30 nanosecond. So, I will never see S0. Why so? Because if I need to calculate the maximum delay, then I know that my S0 will be certainly available before S1, S2, S3. So, I will only analyze for these guys. Say yes or no, right? Okay then. So, based on this, I got to know that all the sum will be coming at 30 nanosecond. And here I do not need to wait for this particular carry. No. I do not need to wait for the carry. I know these are my inputs. From here this will be generated, and here one of the bit will be this. So I know the output here, and this I have to wait 15. So till now these kind of questions are never solved anywhere in any test series or in any textbook as well. You will never find this. You will never find these kind of problems. It just came to my mind and I made this particular problem here. So it might happen that it can come to the mind of the examination setter as well. Examination setter guy who will be setting the question paper. So it might happen that these kind of concept can come to his mind as well. So he can frame the problem. But there is very rare chance that these kind of questions will be asked. And if it is asked, then you know what you need to do. Simply make this circuit and you will be good to go, right? Like those full adder problems we saw now, by binary parallel adder problems. So these were not that important before 2015. So only that NTC formula we studied, no, n-1 TC plus TS, n-1 TC plus TC. So only that formula used to be taught before 2015. But when that question came up, after that they started teaching that next concept using half adder and all those kind of concepts. So till now this is not introduced. If this is being introduced one day, then from the next year onwards this will be in the notes. Okay, so let's study it before. Easy concept only, you will be able to solve it. ये repeat क्यों हो गया? Oh, sorry for this slide. This will be deleted. Now, look ahead carry adder is made using only NAND gates. Okay. Find the maximum delay in receiving the sum and carry. No inputs are mentioned. So what do we have? This we have. Or I can directly say we have half adder here, right? Can I say we have a half adder? Half adder. We receive two outputs. Both goes to a block where we have this thing. If you make it 2-3 times, it will be fit in your mind. This thing and this particular thing is there, right? Now only NAND gates are available. What do you think what I need to do? Here what is there in between? Let's make it only. So you need to make this gate, these two gates using NAND gate. That means you need to make half adder using NAND gate. Half adder using NAND gate. Do you remember how do we do that? A B A B. What you get here? A XOR B. This is your sum, or better call it P here, because this is your P. And how do you get generating term? So AB bar you take from here, and you get your generating term AP. So delay of NAND gate should be given, no? Delay is equals to, that is given TD. I am considering TD delay is there. So to generate this P, how much delay will be there? TD plus TD plus TD. This will be available after 3TD, and this will be available after TD plus TD, 2TD. Now both are going here. You need P as well, you need G as well. So this guy is G, this guy is P, right? Now we need to make it using what? Using NAND gate. So tell me one thing. If I need to make this NAND, I need to add an inverter here. So another inverter I need. Here this important line is written that 2-level and or look ahead carry generator is not available. So in most of the question what they say is that look ahead carry generator is available. 2-level and or. So you do not need to change that. But here I am saying that look ahead carry generator also you need to make only. You only are making it. They will say that 2-level and or look ahead carry generator is available, and delay of that particular look ahead carry generator is this. This can say this can be said by the question paper setter. But here I am not telling that look ahead carry generator is available. You need to make the look ahead carry generator on your own. So how we will make it? So I need to use NAND gate only. Here I use NAND gate. So this circuit is done. For this one, if I use an inverter here, another inverter I will use here. If I use an inverter here, then another inverter I will have to use here. So how this can be seen? That this is an inverter. This inverter I have made. Now what is this? This is an AND gate only. Say yes or no? And what is this? This is also an AND gate. That's it. What is this? This is also 2-level. So how much delay it will provide? 2TD. Basically, this P will come here. P will come here. That came after 3TD. So this came after 3TD, and G will come here. This came after 2TD. So it will go through this delay. So this will be available at 3TD, and this will be available at 4TD, and this will be available, and these two will be available at what? 3TD and 4TD. So this guy will have to wait for this guy. So these two will be available at 5TD. So this guy will be available at 5TD, and this guy was what? This guy was P, which was already available at 3TD. So now 3TD plus this TD. Oh, sorry. Wait a minute. Yeah. So 3TD. Till this point we have got. Now we need to make this guy using what? NAND gate only. So how we will make this guy? This is how we will make this guy. The same circuitry, the two same circuitry. Right. So here 3TD, and this guy is available after 5TD. So this guy will be available after what? 6TD, right? This is available at 3TD only. This is available at 5TD only. So this, both of them will be waiting for this guy. So this guy will be available at 7TD. This guy also at 7TD, and this guy at 8TD. So when you are getting the final one, so maximum delay is 8TD. And if I talk about maximum, this is for some maximum carry delay. So this is your carry, no? This is your carry. This is your carry. This is your carry. So maximum carry delay is 5 TD. Well and good. So everything you made using NAND gate only. So maximum delay is 8 TD for some, and maximum carry delay is 5 TD. You do not need to make this circuit in the examination. You know that I can make my half adder using 5 NAND gates. So 1 level, 2 level, 3 level, 3 TD I will get here. These are 2 level more, 3 TD plus 2 TD, 5 TD. So at 5 TD I am getting carry, and these again 3 level more. So 5 plus 3, 8 TD I am getting my sum, and carry I am getting at 5 TD. Are you able to imagine it? Like you can imagine these circuits. Here if I need to analyze in terms of Boolean functions, no, then only I will make the circuit. If I need to analyze only the delay and inputs are not mentioned, and only delay I need to analyze, worst case delay I need to analyze, so I can think in my mind as well, TD, this way, right? You will be able to think. So that's it about look ahead carry adder. I don't have any other questions after that. Okay then, so yeah, that's it. So let's meet in the next video. There we will study about adders, but BCD adders. Okay, we need to do the BCD addition, BCD subtraction, then we will see the XS3 addition, binary addition also we will see. So all kind of different kind of circuits that could be there, we will see that. So now we are going to use your this 4-bit binary parallel adder. So this we have already studied 4-bit binary parallel adder, that we are going to use to do different kind of addition and subtractions. So that we will see in the next video. Okay then, thank you very much. Hi everyone. So in this video we are going to see some different kind of circuits. So first we are going to start with parallel binary subtractor. So parallel binary adder we have already studied. Now we are going to study subtractor. And before starting this video, I want to say one thing. You need to revise your number system. Okay, whatever that I have taught in number system, just quickly revise that. So that is very important. Otherwise you will not be able to understand this particular video. So please revise your number system. So what we need to do, if we need to do a minus b, where I am considering a is positive and b is also a positive number. B is also a positive number, but I need to do a minus b. So what I will write, a plus minus b, and I can perform this as a plus 2's complement of b. Why I did not write 2's complement of a here? Because I am saying that a is positive, and if a is positive, then sign magnitude form, 1's complement form and 2's complement form will be same. So now I need to perform 5 minus 2. Just a quick revision it is. So 5 minus 2, what I need to do? 5 plus minus 2, right? So what will be sign magnitude, what will be the 2's complement of 5? That will be 0 1 0 1, same. What will be 2's complement of minus 2? That will be first this is the sign bit, right? This is the sign bit, and then what you need to do? First now write 2. This is your sign magnitude representation. And what will be 2's complement? So 1 as it is, this as it is, this as it is. Since you get 1, then reciprocal. So 111 This is your 2's complement of 2. So this is what I have written. And if I have taken the 2's complement, then I just need to add it up. 5 plus minus 2. So 2's complement of 2 I have taken, that is this. So 1 plus 1 is 0 and 1 carry, and this will be 0, and here also 1 carry. So when we were studying number system, I told you one thing, that if carry is generated here, then your result is positive and in normal form. Say yes or no, do you remember it or not? If carry is generated, then your result is positive and in normal form. The same thing which I told for this carry, this can be applied to this carry as well. So here we will look at this carry. If here carry is generated, so result will be positive and normal form. Are you getting this point? The same thing of carry can be applied here as well. This is your magnitude bit. These are your magnitude bits. So after magnitude bits, if the carry is generated, that means result will be positive and in normal form. When we were studying number system, there I told about this one. For this also it is true. But after the magnitude bits, if carry is generated, then result will be positive and normal form. This is also true. So this I am telling here, because now we need to design the circuit. If we need to design the circuit, there we will drop this sign bit. We will see that we will not consider sign bit there. So that's why I am telling it here. Now let's see this particular question. So this is the 2's complement of 5, which will be the same. This is 2's complement of 6. So 6 can be written as this, What will be its 2's complement? So 1 as it is 0 1 0, right? Now we need to add it up. So 1 1 1 1. So 1 plus 0 1, 0 plus 0, 0 plus 1 1, 1 plus 0 1, 0 plus 1 is 0. So here there is no carry, and also after the sign bit as well there is no carry. So if no carry, what does that mean? That your result is negative, and result is negative and in 2's complement form. So now to get the correct answer, I again have to take the 2's complement. So what I will do, I will take 2's complement of this. What that would be? 1 as it is 1 0 0. So this is what I am getting. My answer is minus 1. So here there is a negative sign, and this is your magnitude 0 0 1. So my answer is minus 1. Are you getting this point? So again I need to take 2's complement. Well and good. Now this was one of the method of 2's complement, but I think you must have forgot this method. That is, first we can take 1's complement, and then we can add 1. Let's just say for this value only I need to calculate 2's complement. So what I will do, first I will take 1's complement. What will be 1's complement? Sign bit as it is, rest all complemented, and then I need to add 1. So this is how I can get 2's complement. Look, same I am getting, right? So this is also one of the ways that you should not forget, because while designing the circuit we will be using this thing. This is for solving the problems, but while designing the circuit we will see, first we will calculate 1's complement and then we will add up 1. Well and good. Let's go here. So a positive binary number b is written, you need to take its 2's complement. Positive binary number b is written, take 2's complement of that. How will you solve it? 1 0 1 0. If I need to take 2's complement, look, if they are saying you need to take 2's complement, then you need to consider that they want this number to be negative. Look, a positive and binary number is mentioned here. They should return that a binary number b is mentioned. You need to take 2's complement of that. A binary number b is mentioned. I know this number is 10, which is positive itself. But if they are asking me 2's complement, then they are considering that you will take this number to be negative. Why would they ask me 2's complement of a positive number? Because that is the same only, no? For positive number, 2's complement is same. If I need to take 2's complement, then I need to consider that this is my sign bit and this is my magnitude bit. And now I will take the 2's complement. So this is my sign magnitude representation. And if I take 2's complement here, so 0 1 1 0. So this represents my sign bit only. This represents sign bit. Again, this also represents sign bit only. And this is the magnitude. So I can write that 1 0 1 0 will have 2's complement of 0 1 1 0. If I am dropping the sign bit, because I know sign bit will be 1 only, no? So sign bit I am dropping. Sign bit I will drop. Are you getting this point? Okay. So 2's complement representation of this particular number will be this, right? Let's see next question. A binary number b3, b2, b1, b0 is given. Design a circuit to produce its 2's complement. What do you think what you will do? Binary numbers are given. So what I need to do? Binary numbers b3, b2, b1, b0 is given. So they are not considering the sign bit here. You need to consider by default it is 1. Because if they are asking the 2's complement, that means they are considering this number is negative. So by default it is 1. So first what I can do? I can take 1's complement. So what will be 1's complement? Forget about the sign bit, it will always be 1. And then I can add 1. Basically add 1. So this is how, this will be my answer. This answer will be 2's complement representation. So yes or no? So what I need to do? So these numbers are coming now, whatever the number that is coming. So I will take bar of all these numbers. B3 bar, B2 bar, B1 bar and B naught bar I will be getting here. Okay, and will add 1. This is a step I have done. Now I will add 1 here. That means I am keeping my C naught equals to 1. So this is what my 4-bit binary parallel adder. So these are the 4 bits, these are another 4 bits, which all I will keep grounded. Are you getting this point? 4-bit binary parallel adder, what it will do? A3, A2, A1, A naught plus B3, B2, B1, B naught. What I need to do? I need to get B3 bar, B2 bar, B1 bar and B naught bar plus 1 I need to do. So what I could have done? I could have put this as 0 and I could have put 0, 0 and 1. This also I could have done, right? Because I just need to take complement and then add here. Or what I could have done, that I put all these 0, all these are 0 and this is 1. So this will also be added 1 as well, right? Anything I could have done. So this is what I did. So both circuit I will draw, no need to worry, both circuit I will draw. So this is the way 1, right? So the final answer you will get, that will be 2's complement. This will be your 2's complement. Okay, now I will show the way 2. What could be the way 2? That you keep this as 0, C naught bit as 0 and keep all these 0, all these as 0 and keep this as 1, right? So 0, 0, 0, 1 will be added, this bit is also 0. So this is your way 2. This is your way 1. This is your way 2 and here you will get what? 2's complement representation. So that's it. This is how you will produce a 2's complement representation. Here we are ignoring the sign bit. We are not taking into action the sign bit. So we can ignore the sign bit. Now I am going to design of parallel binary subtractor. So parallel binary subtractor we are going to design. Okay. So what we need to perform? A minus B. So how I will perform? A plus 2's complement of B. If I am writing 2's complement of B, then by default I am saying that my B is already negative I am taking. So I will take bar of this and add 1 in that. So I am taking bar of this, adding 1, right? So what I am performing? A1, A3, A2, A1, A naught, taking bar here, plus 1. What this guy is doing? This is 2's complement of B. And it is being added with B. So now what will happen? You will have some sum S3, S2, S1, S0. So you will get some sum, that is S3, S2, S1, S0. And you will generate a carry here. This carry could also be there, no? If C4 is 1, that means result is positive and in normal form. So this I will accept. If C4 is 1, so this will become 0. If this becomes 0, so whatever the result that you are getting here, S3, S2, S1, S0, all will be XOR with 0. S3 XOR with 0. If C4 is 1, this is becoming 0 and S3 XOR 0 will be S3 only. S2 XOR 0 will be S2 only. So same thing is fed here. So here what you will be getting? S3, S2, S1 and S0, and that is being added with 0, 0, 0, 0. So nothing is changing, no? If C4 is equals to 1, here you are getting S3, S2, S1, S0, all are XOR with 0. That means here you are getting S3, S2, S1, S0, right? S3, S2, S1, S0, and all are added with 0, 0, 0, 0. So what you will get? S3, so I should call this as S3 dash. okay, because final answer I am writing S3, S2, S1, S0. So I will call this S3 dash, S2 dash, S1 dash. So all are added with 0, 0, 0, 0. So here you are getting S3, S2, S1 and S0. So that's the final answer that you are getting here. So this was the case for if C4 is equals to 1. Now if C4 is equals to 0, then here I am writing because there is no space. If C4 was 0, then what would have happened? Result is negative and in complemented form, in 2's complemented form. So what we need to do to get the final answer? To get answer in normal form, to get answer in normal form, take 2's complement again. Take 2's complement again. So this is you are getting if C4 is 0, if C4 is 0, if C4 is 0, then this would be 1, this would be 1, these bits will be 1. If C4 is 0, these bits will be 1 because there is an inverter. If these bits are 1, then S3 dash XOR with 1, what you will get? S3 dash bar. These bits are 1. If C4 is 0, these bits are 1. So here you will get S3 dash bar, S2 dash bar, S1 dash bar and S0 dash bar. Say yes or no? And now these bars are added with 0. S3 dash, S2 dash, S1 dash, S0 dash are added with 0 but with initial carry of 1. This is being fed here. If C4 is 0, this carry will be 1. So what you are taking actually? You are taking 2's complement only. So this will represent what? This is your final sum. Are you getting this point? How did we design this particular circuit? A3, A2, A1, A0. We took the complement, added 1. So this was your 2's complement. So A plus 2's complement of B. Then you generated sum. If your carry is 1, then there is no issue. So nothing should be done with that. You should keep that as it is. So S3, S2, S1, S0 should be kept as it is. That means from here I can take this one and take an inverter. So 0 should be XORed here. So if 0 are XORed, that means S3, S2, S1, S0 you are getting and nothing else should be done. Here also if C1 is 1, here also 0 is coming. So nothing is being added. But if C4 is 1, if C4 is 0, if C4 is 0, that means you need to take 2's complement again. So what is the circuit for 2's complement? This is the circuit for 2's complement. Inverter. This will act as an inverter only because if C4 is 1, if C4 is 0, this bit will be 1 and these will act as an inverter and I need to add 1 as well. So this one I am getting from here. So I added 1 as well. Here just the way I added 1 as well and here I am getting the final answer. So this is the circuit that we did. I hope you have understood it very clearly, right? So in the examination what can come? They will give this circuit and they will ask you what this circuit is performing. A plus B, A minus B, and if this circuit is correct or not, if it is not correct, then what correction should be made. So these kind of questions can be framed in MCQ and these are framed as well. So that we are going to see in assignment problem. So these kind of questions come. Okay, these are important. I would say these kind of block diagrams are important. Here we see everything on block level. We are not designing the inner part, but the block level, this calculation are important. Okay, then let's move to the next one. Now we are going to study BCD adder. So for that you need to know how to do BCD addition. So I hope you have revised it. So in BCD addition, when we get culprit, when do we get culprit in BCD addition? When your sum is greater than 9 or your carry is generated. So two examples I have taken, 5 plus 6, 11. So I will do it using BCD. So 5 in BCD will be 0, 1, 0, 1 and 6 in BCD will be 0, 1, 1, 0. So here what I am getting, this is the invalid case. Why this is invalid? Because 11 I cannot represent in BCD using 4 bits. So this is how 11 will be represented in BCD. So this is how you will represent 11. But here you are getting this answer which is sum greater than 9. This is 11. Sum is greater than 9. So what you will add? You will add 6. You will add 6. After adding 6 you will get the correct answer. So 1, 0, 1 1 0 0 and 1. So this bit and this is alone bit, so here you can add 3 0 from your side. So this is the correct answer, right? This was your invalid case. Invalid case. What about this 9 plus 9 18? So here you will generate a carry. 1 plus 1 is 0 1. This will be 0 0. Now carry is generated. If carry is generated, this carry is generated, that means this is also a culprit case, or you can say invalid case. So if this guy is culprit, that means I need to add 0 1 1 0, but we don't do anything with this particular carry. This carry comes as it is. What about this 0 0 0 and 1? So this comes as it is, this and this is your answer. So answer is 18. I hope you remember it. How do we solve it? So this is the correct answer, and this is correct answer, and this was 11. So this is what we studied in by BCD addition. Now we need to design the circuit. Okay, so let's see that, but before that let's make a combinational circuit. Let's make a combination circuit which will identify if it is an invalid case or not. What did I say? We are going to make a combinational circuit which will identify if that is an invalid case or not. So when do you get invalid case? Look, this was our 5 plus 6 calculation. This is the answer we got. I am calling this as S3, S2, S1, S0. Okay, and 9 plus 9 18 we did. This was our answer. This was our invalid case. So I am calling this as C4, S3, S2, S1, S0. So if carry is generated, if C4 is 1, then I don't need to care about anything else. Whatever that is there, if let's just say if I have generated a carry, then no matter whatever that is there, it will be an invalid case. So C4 and don't care, right? Then F will be 1. So this will be lit. This guy will be lit. F will be lit when there is an invalid case. So first condition is if C4 is 1, do not care about anything. It is an invalid case. Now next invalid case will be when you get 10. That means 1 0 1 0. Next invalid case will be when you get 11. That means 11 will be 1 0 1 1. Next invalid case will be when you get 12. When you get 13. When you get 14 and when you get 15. So these cases are there irrespective of the carry here. Irrespective of the carry. We do not care about carry. Even if carry is 0 or carry is 1. If these guys are occurring, that means that is an invalid case. So only these two invalid cases are there. And in all these invalid cases, your F will be 1. So can you write your F? Try writing it on your own. How will I write F? You can make the K-map and it will take a lot of time. But intuitively, by thinking it, how I can write F. So if my C4 is 1, then all over. If my C4 is 1, then certainly I do not need to think about anything else. If C4 is 1, then F will be lit. Invalid case is there. Or if S3 is 1 and 1 of S2 and S1 is 1 of S2 and S1 is 1. Basically S1 plus S2 is 1. Are you getting this point? If S3 is 1 or 1 of S2 or S1 is 1. S1 plus S2 1, 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 S1 plus S2 1. 1 of S1 or S2 1 or both could be also 1. What does this represent? That 1 of S1 S2 or both S1 and S2 are 1. If I said only 1 of S1 and S2 should be 1, then that would be XOR gate. But even if this is the condition, then also it will work. So this is the expression of F. If only C4 is on all over, plus if S3 is 1 and 1 of these guy should be 1. Now you will say that, sir, in all the cases S3 is 1, so why shouldn't I write only S3 there? 1 0 0 0. Here S3 is 1, but this is not the invalid case. This is valid case because this is 8. 1 0 0 1. Here S3 is 1, but this is not a valid case. This is not an invalid case. Both are valid. But here S1 plus S2 is 0. But I want my S1 plus S2 to be 1. So here S1 plus S2 was 0, but here I want it to be 1. So that's the thing, right? So here S1 plus S2 is, if S1 plus S2 is 1, that means 1, 1, 0, and this could be anything. This is our don't care. This could be 0 as well, this could be 1 as well. So if I am keeping it 0 only, then also it is invalid. If I am keeping it 1 only, then also it is invalid. So this is the expression of f. And how I can design it? Very easy. Even first year student can design it like, right? S3 plus S2 dot S3 plus C4. Very simple. So this is your f. So that I will be using. This I will be using as a black box in our final design. That my inputs are these. What all my inputs? And I will call this as CC star, combination circuit star. So inputs are S1, S2, S3. I do not need S0. I don't need S0, right? And C4. And my output is F. So our output F will be high. F will be high for invalid case. High means bit 1. Low for valid case. So let's see the design now. So first simple addition I am doing. What I am doing here? 4-bit addition I am doing. A3, A2, A1, A0, B3, B2, B1, B0. So 4-bit addition is there. I will generate S0, S1, S2, S3 and C4. Now this C4 could be 1 as well, this C4 could be 0 as well, right? So these are the sum that we have generated. C4 goes here, C4 goes here, and these inputs goes here. If F is 1, C4 goes here and these inputs goes here. If F is 1, so these guys go as the input of a log CC star. And F I will generate. Let's just say if F is 0, if F is 0, if F is 0, if F is 0, then you do not need to do anything. That's your final answer. If F is 0, then this is your final answer. Let's check if F is 0, then what our circuit will do. So if F is 0, this will go here. So this is 0, this is 0, this is 0, this is 0, all are 0. And these answers that we were getting, S3 plus S2 plus S1 plus S0, these will be added with 0, 0, 0. And with carry, I will put this to ground only. So basically, if F is 0, then S3, S2, S1 and S0 are added with 0, 0, 0, 0. So simply you will get S3, S2, S1, S0. So this is the answer you will get. This is I am calling as S3 dash, S2 dash, S1 dash and S1 bar. So this would be your final answer. Right? And in that case, certainly C4 dash would be 0. Right? Because if you are not even generating a carry. If you are generating a carry, then that means certainly there is an invalid case. So if you are generating a carry, that means this F will be 1. And if F is 1, that means these bits will be 1. So now S3, S2, S1, S0 will be added with 0, 1, 1, 0. 0, 1, 1, 0. So I should mark this. This should be your A0, A1, A2, A3. Or here I am taking these, so I will mark these as A dash. So basically this will be your MSB bit, this will be your LSB bit, this will be your MSB bit. So it will be added with 0, 1, 1, 0. So S3, S2, S1, S0 will be added with 0, 1, 1, 0. And these will be added. And there is an issue that if C4 is 1, okay, yeah, these will be added and from there you will generate a sum and carry. Right? S3, S2, S1, S0 are there. These will be added with 0, 0, 1, 1, 0. So you will generate a sum. So this sum you will be getting and carry as well. So this circuit doesn't sound that well, no? Because there is some issue. Let me check it. Yeah, so I thought about it. Now I will get to know. I can see there is an error. What is that error? Let's check. Okay. So let's just say I take this example. I am doing this calculation. So I will receive this 1011. Here I will receive 1011. Here I will receive 1011. Then I will get to know that this is an invalid case. I will send these things here. C4 will be 0 here. C4 will be 0 here. I will send this here. 1 0 1 1 I will send here. This 0 will also be fed here. 1 0 1 1 and this 0 will be fed here. This bit will be 1. This bit will become 1, right? If this bit becomes 1, this will be 1 1, and now 1 0 1 1 will be added with 0 1 1 0. So I will get 1 0 0 0 and 1. So yeah, that is correct. This answer is correct, that here I will get 0 0 1 0 0 1, and here I am getting C4 dash, I am getting 1 0 0. So this answer is correct. For this case it is correct. Let's take the second case. You understood, no? 1 0 1 1, this I sent here, this was 1 0 1 1 0 1 0 1 1 0 1 1 0. If I am adding, this sum I am getting and this carry I am getting. For this scene it was correct, there was no issue here. But where will be the issue? Issue will be there in the next case. So in the next case, here also there is an error, no? Here also there is an error. This is also invalid case. So 0 0 1 0 and 1. So 0 0 1 0. So after first adder we will get this, and this will be 1. So this one will be fed here, right? And these inputs will be fed here. So this f will be 1. So if this f is 1, so 0 0 1 0 is being added with 0 1 1 0. So what you will get? 0 0 0 1 0 and 1, and your carry will be 0. C4 dash will be 0. If this guy is performing the calculation, then 0 0 1 0 plus 0 1 1 0. So these will be the sum output and carry will be 0, right? Carry outputs will be 0. So there is an error. This is not giving me a correct answer. So what I need to do? I need to make some corrections here. So what I will do now, even in a lot of standard book as well, this kind of circuit is given, but today only, now only I noticed that it is incorrect, right? It just clicked to my mind. So this C4 dash, whatever that C4 dash I am getting now, I will ignore it. Okay, I will ignore it, and this F I will take as the carry. This F only I will take as not carry, it will be there in the final output. So this F will be my S4 dash, and my S5 dash, S6 dash, all these bits will be 0, 5, 6 and 7. So S5, S6, S7. So this will be your final output. This will be the ones place and this will be your tens place. Are you getting this point or not? Why is this correct? So we were having issue in the second one. So in the second one, what was the scene? 0 0 1 0 was added with 0 1 1 0. So we were getting 0 0 0 1. So this we are getting, and we were getting carry 0. So this I am ignoring, and we know that we will get carry 1 because of the previous one that was here. Because of the previous one, because C4 was 4, this C4 should be coming here, right? This particular C4 should be coming here. Let's see the example back. This C4 should be coming here, right? But that cannot come. But I know one thing, that if C4 is 1, then certainly this will give me output 1. So this guy I am directly taking here. And if C4 is 0, if C4 is 0, so what this guy will perform? Here, let's take this example, 1 0 1 1. So I will put 1 0 1 1. 1 0 1 1. And if C4 is 0, so this guy will be 1. Now what this guy will do? 1 0 1 1 and added with 0 1 1 0. So 1 0 0 0 and 1. This carry I am getting here, which I am ignoring. This I ignored. So 0 0 0 1 I will get here, and I know that my carry will be 1, and that carry is being fed here. That's it. Although it's not the carry that you got, but here I know that I should get F1 here. I should get F1 here, and that I am getting, because I know in this case, if my output is greater than 9, That means my output is 10, 11, 12. So certainly I will generate a carry which will be 1 only. I should not say carry, I will say that there will be another bits which will be here, this will be 1 only. For 15 as well, this will be 1, rest all will be different. So rest all whatever that is different that you are getting here, and you need only 1 here which is constant. So I just put 1 here, that's it. Are you getting this point or not? So I fixed it. Whenever there is an invalid case, certainly in the final answer you are getting 1 here. So if in case of invalid case, this bit will always be 1. So certainly just pick this bit and keep it there. In an invalid case, you will always get 4 bits and a 1. In all the invalid cases, you will get 4 bits and a 1. So better pick this one only, no? So this is fixed, that if invalid case is there, certainly this 1 will come here, the rest all bit will be 0. So this will be our tens place, and at 1's place what we will be having, whatever that you are getting after summation of 0, 0, 1, 1, 0. So this is what we are doing. Now I hope this is clear, and I also studied it now only that I also understood now only that it should be different. Okay, and in case of valid cases, f will be 0. So this bit will be 0, 0 only. So this will not change the answer. In case of valid cases, this f will be 0. So this will not change the answer. So now we have understood this is the right circuit of a BCD adder. Okay. So previously what we made, that was not correct. So let's see binary subtraction now. So in binary subtraction, not binary subtraction, that we have already seen, BCD subtraction. So in BCD you can represent number from 0 to 9 only, right? In 4 bits, in BCD using 4 bits, you can represent number from 0 to 9 only. If you do 9 minus 1, 8. If you do 1 minus 8, minus 7. Nowhere invalid case is there. Like invalid case will never occur. Invalid case will never occur. So why invalid case will never occur? Sum is never greater than 9, neither there is a carry. No carry is there, and sum is also less than 9. No carry, sum is also less than 9. So invalid case will never occur. If invalid case is never occurring, then never need to add 0, 1, 1, 0. If you never need to add 0, 1, 1, 0, then this subtraction will be same as 4-bit binary subtraction. Say yes or no? So what you are going to do? You will take the 1's complement, 2's complement of 1 or 2's complement of 8 and do the same thing. The circuit is ditto same. Nothing different is there. The design of BCD subtractor is same as binary subtractor. Now in the question, if I make this circuit and then in the option I ask you, what does this circuit represent? So what you will say? Binary parallel subtractor, right? And BCD subtractor as well. It is binary subtractor and BCD subtractor. So you took the 2's complement. If carry is 1, then there is no issue. If carry is 0, then this would become 1. We will take the complement of our output, which are S3 dash, S2 dash, S1 dash and S0 dash. We will take their complements, which will be again added with the carry 1. So here, if it is in 2's complement form, then 2's complement form, again we are taking 2's complement form. So you will get the final answer here. So that would be your final answer. So the same circuit I have explained before only. So this is your BCD subtractor. Well and good. Okay. Now see excess 3, addition and subtraction. So let's revise it. When we have carry 1, we add 3, and when we have carry 0, we subtract 3. You remember this? If carry is 1, we add 3, and carry is 0, we subtract 3. So 9 plus 9, let's do this. So 0, 0, 1, 1. But in this case, what we do? We add, now what we are going to do? If carry is 1, we are going to add 3. Now this will also be added with 3. Say yes or no? अरे यार 3 ऐड करना है, 6 क्यों ऐड कर रहा हूँ? This will also be added with 3. You do the same thing with 3 as well. You do the same thing with carry as well. So what you are getting? 1, 1, 0, 1, 0, 0, 0. So what is this? 4. And what is this? 1, 2, 4, 8. 1, 2, 4, 8. 1, 2, 4, 8. So 11. And this is what you expected? Say yes or no? Because 9 plus 9 is 18. 9 plus 9 is 18. So plus 3 will be 4 and plus 3 will be 11. So this is the correct answer. So this is what we do. Now can you tell me one thing? If carry is generated, then this will always be 0, 1, 0, 0. Say yes or no? If carry is generated, then certainly in our final answer we will get 4 only here, right? Here 2 bits are being added. You cannot generate a carry more than 1. Maximum carry is 1 only. So if carry is generated, then you will add 0, 1, 1 there. And this bit will always be 4 only. Say yes or no? If you are doing the 4-bit calculation. So this is fixed. Because I have taken the maximum example. In 4-bit, you can represent the maximum number, that is 9 only. In 4-bit. Because if I need to represent 10, then I will need to use 2 bits. Sorry, 8 bits, not 2 bits. 2 pack I would say. 1 pack and 2 pack. So I would need to use 8 bits. But in 4 bits, I can represent maximum number 9. So in maximum number also we saw that this is fixed to 4. Will always be 4. So this is an important point which we will be using in our circuit diagram. And what about 5? So 5 will be written as 8, right? So 8 will be written as 1, 1, 0, 0. And 1 will be written as 4. So carry is not generated here. So what we are going to do? Subtract this thing. So what we are subtracting? We are subtracting 12 minus 3. What we are going to add? 9. 1, 0, 0, 1. You could have solved it by the calculation as well. Like you take a carry here, 2 minus 1 will be 1. This will be 1 only. 1 minus 1 is 1. This will be 0. 0 minus 0 is 0. 1 minus 0 is 1. You take carry. This doesn't have anything. This will take from him. So this will be 2. Now if this is 2, you will take 1 from here. So this will be 2. 2 minus 1 is 1. This will be 0 only. If you whatever that you have taken here, that guy you have took. So this will be 1. So 1 minus 1 is 0. Basically 1, 1, 0, 0. 0, 0, 1, 1. This I need to do with the binary. So this guy will take, this guy will become 2. Plus 2 it will become basically. Plus 2 it will become. Now you will take from this guy. So you will become plus 2, but this will become 1. Because you have taken something from him. So this will become 1. So plus 2 minus 1, 1. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 0 is 1. That's it. And if you don't know this, then you can simply solve by this particular method. 12 minus 3. 12 minus 3 is 9. So what you expected? 5 plus 1 is 6. And what is excess 3 of that? 9 only. So here you are getting 9 only. Okay. So if no carry is generated, you need to subtract 0, 0, 1, 1. Right? Let's see the circuit now. This is the excess 3 addition circuit. Pause the video and try to understand it on your own. And tell me what we are going to do with this particular carry. So I will pause the video. You also pause the video and try to understand it on your own. Okay. So I hope you must have analyzed it. Let's see what we are going to do. So this is a very interesting circuit. And if this is coming in your examination, you would be able to tell this is a excess 3 addition circuit. So how we are going to do? So all these input bits are 0 only. Input carry bits are 0. So first it will perform the simple addition. This is the answer we are getting and we will get a carry. Now, if carry is 1, let's take the condition of if carry is 1. If carry is 1, that is this case. If carry is 1, you need to add 0, 0, 1, 1. 0, 0, 1, 1. So if carry is 1, so this guy will be 1 and these two guys will be 0, 0. So I need to add 0, 0, 1, 1. Whatever the answer I am getting here, what answer I was getting here? 1, 0, 0, 0. 1, 0, 0, 0. This will be added with, if carry is 1, this will be added with 1, 1, 0, 0. Right? This is added. Now, if that is added, then you will get this answer. And what about this? This 1 will be added with 0, 0, 1, 1. And always you will get 4. So if here you are getting 1, then you can pick it here and this you can give as your final answer. I just picked it here. This I was getting as 1. So I took this one and this I am getting here C4. So if that is 1, so you will get 0 1 0 0, which is 4 only. So this is your tens place, this is your tens place, and this is your ones place. This answer is, if I am calling S0 dash, S1 dash, or let's call it S0 S1. So if this is S0, this is S1, this is S2, this is S3, then this will be your S4, S5, S6 and S7, or we can write a C4 there as well. So did you understand this point? If a carry is 1, then I took it here and I added 0011. So this is the answer I am getting. For this guy I know 4 will be fixed, and for this guy I need to do the calculation. So I did the calculation, and when I did the calculation, this is what I am getting. So this is the final answer that I am getting in XS3 format only. So this is a XS3 addition circuit in XS3 format I am getting. And if this guy is generating some carry here, if this guy is generating some carry, this is of no use here. So I will ignore this carry, ignore this carry, ignore. So this I will not show at my output. This will not be my output. So I will ignore this particular carry. Okay. Now let's see for the second condition. What is that? When carry is 0. So if carry is 0, you need to subtract 3, right? If carry is 0. So if carry is 0, tell me what I am adding. If carry is 0, then I am adding 1101. If carry is 0, then I am adding this thing I am adding. If carry is 0. So in this case carry was 0, so I am adding 1100 and these two things I am adding. Let's see what we get. 1 0 0 0 and 1. So here I am getting 0001. Wait a second. 1101, right? So is there some error? Yeah, this would be 1 only, no? This would be 1, sorry. So this is what I am getting. Am I not getting the same thing? Why did that happen? Think about it. What do I do here? What did I do here? What is this? This is 2's complement of 0011. What will be 2's complement of 0011? Here you consider sign bit. This will come as it is. Ignore this sign bit. 1011. So this is your 2's complement of 0011. Okay, so let's write it in a better manner. 2's complement representation of 0011 will be what? 1101. I knew this thing, and smartly what did I do? If I am getting 0 here, I will make complement, I will get 11 here, right? And this will be 0 and this is 1. So here I am doing 2's complement addition. What I am doing? 2's complement addition. Here I am doing 2's complement addition. So I will generate the final sum, which was this, and I will ignore the carry here. I will ignore the carry here. Now what could be the doubt? That sir, you are ignoring the carry, but you are doing the 2's complement representation. What if this carry is 0? Then the answer will be in 2's complement form. Here our answer was, here when we did this calculation, we got carry 1, right? When I added in 100, in 1100, sorry. When in 1100, I added 1101. What did I get? 10011. So I get a carry here. If I get it in 2's complement addition, this I am doing 2's complement addition here, right? Because here I need to subtract. So I took the 2's complement of this and added. I took 2's complement of this and then added. This is what I did. But what is the scene here? If you are getting a carry, then your answer is positive, then it is fine. But if you are not getting a carry, then you need to do the 2's complement again and get the final answer. But the thing is, we will always generate a carry here. This answer will always be positive. What you are doing XS3 addition. Can your answer ever be negative? Can your final answer ever be negative? No. You are doing XS3 addition. Your final answer will always be positive. So this bit will always generate a carry which will be 1. In the second case, when C4 is 0, this will always generate a carry. So this answer will be always in 2's complement form, or you can say it will be in normal form only. So again, one more circuit I don't need to use. That you will say that, sir, design 2's complement circuit again, because this answer could be in 2's complement form. So one more circuit should be there. but the thing is this particular carry will always be 1. So my answer will always be 1, and if my answer is always 1, then I can ignore this carry because my answer is in normal form only. Understood this concept? So that's the thing. So I don't need to represent other circuit here. So here I can write that this answer will be in normal form or is equals to 2's complement representation. Okay, so this answer will, or better I should write, will always be positive. Will always be positive. This will always be positive. Well and good. So this circuit you have understood. So this was very interesting one. For C equals to 0 as well, for C equals to 1 as well. For C4 equals to 1, I know one thing. What is that? That this will be 1. So here I am always getting 4. So I directly picked it 1. I am getting 4 here. And what do I add? What do I add? 00 11. What I was adding, if C4 was 1, then I was adding 00 11. So if I am adding 00 11, this would be the final answer. 1's place I will be getting, and this will be my 10's place, right? And what about when C4 is 0? If there is no carry, that means I need to subtract 00 11. So if I am subtracting 00 11, that means I can do this calculation using 2's complement representation. So 00 11 01 will be the 2's complement of 00 11. Then I simply add, and one thing I get to know that my answer will always be positive, so I can ignore that particular carry. So this is the final circuit. Well and good. So this we have completed access 3 addition. Okay, access 3 subtractor circuit is not that important, that is very complex, so you can drop that, or if in the last if time permits I can deal that particular topic. So access 3 subtraction circuit you can ignore as of now. Access 3 subtraction, we have seen binary addition, binary subtraction, BCD addition, BCD subtraction, access 3 addition. We know how to do, no, we don't even know how to do access 3 subtraction as well. So we did not talk about access 3 subtraction at all. So later on we can talk about, but till now in the gate history or even in the interview anywhere, no questions has been asked on access 3 subtraction. I know how to do that, but that is a bit complex, you would say, like a bit complicated. So no one will ask you that, but if in the last time permits we can do it. Okay, so let's study about binary multipliers. So this question is given directly, let's solve it with problem only, very simple. For the multiplication of 2 bits number are given, let's just say 1 1 and 0 1 is given, you need to multiply that. Okay, so how much circuitry you would require? So if I multiply these two, I am taking the example of 1 1 0 1, or let's take an example of 1 1 1 1 only, this would be better. So 1 will be multiplied with 1, so A0 will be multiplied with 0, and B0 will be multiplied with A1, so A1 B0, B0 will be multiplied with A0, so A0 B1, and B1 will be multiplied with A1, so A1 B1. Now I need to add them up. So A0 B0, or better I should write S0 S1 S2 I will be getting. So A0 B0 will be directly coming. A1 B0 plus A0 B0 if I do, then this can generate a sum and a carry. This will be single bit, no? 1 into 1, this will be a single bit. So this will come as it is. But 1 into 1, 1 here, 1 into 1, 1 here, 1 into 1, 1 here. So this can 1 plus 1 is 0, and this can generate a carry, right? So this can generate a carry. This I am calling C1, and then it is added with this. So tell me one thing, no, I should not remove this. So 0, and another thing you can get here is that because if 1 1 is added, you can get another output that I am calling as C3. Okay, or should I call it C2? If I am getting S2, then I should call it C2. So this I can get. So to generate A0 B0, what do I need? For A0 B0, I need a AND gate. For A1 B0, because I need to generate these bits. Here you did the multiplication and you feel like that this is a single bit, sir. But we need to generate it, no? A1 into B0, that I need to generate. What I am given these bits. That you have 1, you have 1, you have 1, you have 1. So I need to do the multiplication of these two. So for that I need AND gate. This is your another AND gate I require. A naught B naught I require another AND gate, and A1 B1 I require another AND gate, right? Yes or no? Right? Now to add this up, 1 is added with 0 and coming as it is. So nothing you need to do. This will be A naught B naught only, no? So nothing you need here. But here you need to add these two bits, 1 plus 1. Tell me what you are going to use. OR gate. If OR gate is coming to your mind, that I will do 1 plus 1 using OR gate. No, no, no. OR gate do the logic operation, not the operation of binary numbers. There 1 and 0 were logic operations. That 1 plus 1 was 1 in OR gate. But in our binary, 1 plus 1 is 0 and carry is 1. Right? 1 plus 1, sum is 0, carry is 1. So you will do that using half adder. Okay. So this will be your half adder. So one half adder you require here, because only 2-bit operation is there. Another half adder you require here. So 2 half adders you require. So where you require 2 half adders? A naught B naught plus A naught B1. 2 half adders. Right? Sorry, A naught B naught, A naught B1. So this will take 1 half adder, and then it will generate a sum and a carry. So that will also require a half adder. Now A1 B1 are not 2 bits. A1 B1 is a single bit, right? A1 B1 is a single bit. A1 B1, this is a single bit. So all these after multiplication will become single bit only. It feels like that these are two bits, sir. So you should use a parallel binary parallel adder. No, no, no. These will become a single bit. No, this will be a single bits. All these are single bits. Single bits. This will also generate single bit. This will also generate single bit only. So for A1 plus B1 you will also need a half adder. This will also generate a single bit. So all these are single bit. No one is double bit. Okay. So they will generate these two things. So you need 4 AND gate, which you can directly see here. 1 multiplication, 2, 3 multiplication, 4 multiplication. 1, 2, 3, 4. 4 AND gate and 2 half adders. 2 half adders. So this is what is required. Let's do the next question on your own. So this is how you can implement it. A naught B naught. So A naught into B naught. This will be your S naught. Implementation you can see. And then A1 B naught I will get, and A naught B1 I will get, and that should be passed through A naught B naught, A naught B1. That should be passed through half adder. So I will generate sum 1 and carry 1. So this carry and A1 B2. Carry is C1. C1 and A1 B1 actually. C1 and A1 B1. Why B2? A1 B1. B2 is not even there. C1 and A1 B1. C1 and A1 B1 will be added. So they will generate S2 and C2. So what will be your answer? This being your MSB and this being your LSB. So this will be your answer. Right? Okay then. Let's do the next question on your own. What all circuitry will be required? Okay. 3 is multiplied with 2. So A naught B naught, A1 B naught, A2 B naught, B1 A naught, A1 B1, A2 B2. So how many AND gates you can see? 1, 2, 3, 4, 5, 6 AND gates. Now this will come as it is. So nothing is required for this. This will do the sum. This will do the sum. So here what is required? Half adder, right? There is no carry here. Initial carry is 0. So if carry is 0, this will take half adder. This will do the sum, let's just say S1, and generate a carry C1. So here you need to add 3 bits, right? Here you need to add 3 bits. And if you need to add 3 bits, that means you will require full adder here, right? So it will generate a sum and a carry. Here you need to add 2 bits only. So you require a half adder here. It will generate a sum and produce a carry. So here we needed half adder as well, right? So we need 2 half adder and 1 full adder. And one full adder can be made from 2 half adder plus OR gate. So anything could be possible here, okay? That option could be given that 6 AND gate plus 4 half adder and 1 OR gate, or it could be given as 6 AND gate plus 2 half adder plus 1 full adder, or it could be given as 6 AND gate plus 3 full adder, because whatever the operation that you can do with half adder, that you can certainly do with full adder as well. So here you can use full adder, here also you can use full adder, here also you can use full adder, and this is coming as it is. So 6 AND gate, half adder and full adder, so that you need to use. Okay then, so yeah, that's it about our combinational circuits. So our combinational circuit is completed now, nothing is left. We will solve an assignment, but a lot of questions we have already solved in our lecture itself. So I hope you enjoyed it a lot, and if you enjoyed it, I want you to share it to everyone. Just share this content to everyone, that this much depth has been covered in this particular lecture in such a low price. Or if you are watching it on YouTube, then you can say that it is being uploaded for free only, so they can watch it. Okay then, yeah, thank you very much. Let's solve an assignment. That would be an easy assignment only, because a lot of problems we have already solved. Okay then, thank you very much.